The main aim of compiler is to convert a high-level language into a low-level language. And what do I mean by parse tree, creators, code optimization, target code generator? I'll take a single example and I'll explain you all the phases in that example. The scope of this particular write will be only now. If you see this, the main responsibility of lexical analyzer is this is the only phase which actually reads the text. Parsers are also nothing but syntax analyzer. It also shows that we have seen everything of the start symbol. We started from the, then you need not change everything. What you should change is only the phases, the front end. We shall discuss compiler design now. The main aim of compiler is to convert a high-level language into a low-level language. Then the question is, if you have to convert the high-level language into low-level language, why don't we write a program in a low-level language? The reason is we are not comfortable writing programs in zeros and ones, the binary language. We are comfortable writing it in English language or some language similar to English, and then compiler is a software which is going to convert that high-level language to low-level language. Along with the compiler, we have many other software modules which will help us here. So if you look at this diagram, I'll tell you what are all the phases available. See, first the high-level language will be given to preprocessor. Then the preprocessor is going to convert that high-level language into pure high-level language. For example, what is a high-level language and pure high-level language is, if you write a C program, the starting lines are going to contain hash include, isn't it? Or it is going to contain hash define, right? So if a program contains such lines, then it is called high-level language, and preprocessor is going to remove these lines. Removing hash include by including the file. That is also called as file inclusion. File inclusion means whatever file you want to include, the preprocessor is going to substitute that entire file in your source program. Okay, and the second one is hash define. For example, sometimes you might have to define a constant and you don't want to write its name. Let me tell you an example. In some programs we might need the value interest provided by the bank, and the interest is variable, right? It is a constant, but then it is a variable. Therefore, if anywhere the interest has to be changed, you cannot go to the program and then mechanically manually change all the places where the interest is. Instead of doing that, you can just change in the define line, hash define something. Okay, so if you have hash define and hash includes, you can have hash define some constant. If you change the value of hash define constant, it is automatically going to be reflected. So it is called macro expansion. Sometimes we are going to write macros also. Macros are nothing but small functions for which we don't want to really call a function. Function calling is a overhead, macro calling is simple. That is why we go for macro expansion. So preprocessor is generally going to do these things, file inclusion and macro expansion. Now after the preprocessor phase, we are going to enter the compiler phase, and the input to compiler is pure high-level language, which means the program will not contain any hash lines, any hash tags, and these hash tags are also called as preprocessor directives. They direct the preprocessor about what to do. Okay, so the next phase is compiler. Compiler will take the pure high-level language and it will convert into assembly language. For every platform, by platform I mean the hardware that you are using. For example, Intel or AMD or Motorola, this is the hardware you are using. On top of it, the operating system, for example Linux, Windows, 64-bit, 32-bit. So depending on your hardware and the operating system, which is also called as platform, we are going to have some assemblers. A assembler for one platform will not work for other platform. For example, you can think of assembler as a manual which is using which we can only operate one instrument, we cannot operate other instrument. Therefore, the main purpose of compiler is to generate assembly level language, and assembly level language will be not entirely in zeros and ones and not entirely high level language. So it is somewhat intermediate. Previously, long back, people used to write programs in assembly language too, and later they came to high level language. Okay, before compiler they always used to have assembler. And once the assembler take this assembly language, it is going to convert the assembly language into machine code. So machine code is, you know what, it is zeros and ones. But then there are two types of machine codes. One is relocatable machine code and other is absolute machine code. Relocatable machine code means you can load that machine code at any point in the computer and you can run. In the sense, compiler assumes that it doesn't assume anything. Compiler doesn't assume that you are going to run a program only from particular memory. If you have the memory RAM, in that RAM, compiler assumes that you can either start from this point or this point or this point. Therefore, all the addresses within the program will be in such a way that they will cooperate for the program movement. While running the program, you can move it. Okay, and loader and linker will take the machine code which is relocatable and then convert it into absolute code. Okay. So let's see what, if you talk about any compiler like GCC or Turbo C compiler, all these phases are included. Okay, so but then actually compiler means only the part which converts pure high level language to assembly language. But if you look at GCC, you need not do pre-processing separately, assembly separately, loading, linking separately. Everything will be kept in a one tool. Now in this course compiler design, we are not interested in looking at all the tools together. We are only going to look at what a compiler is going to do. So let's see what are all the phases available in compiler. So first one is lexical analysis phase. Lexical analysis phase will take the program and read it and then convert the program into tokens. That is also called as stream of tokens. And next, this stream of tokens will be given to syntax analyzer. Syntax analyzer is also called as parser sometimes, and syntax analyzer is going to take the tokens and convert it into a parse tree. And now parse tree will be given to semantic analysis, and now semantic analyzer is going to again verify whether the parse tree is meaningful or not. That is called parse tree, which is semantically verified. And now this parse tree will be given to intermediate code generator. Intermediate code generator is going to generate 3 address code. There are various 3 address codes we have, and here there are various intermediate codes we have, and 3 address code is very popular. And now the output of this intermediate code generator will be given to code optimizer. The main purpose of code optimizer is to reduce the size of the program or is to reduce the number of lines, and then it will be given to target code generator, and target code generator is finally going to generate the assembly code. And during all the phases, all of the phases or the entire software modules are going to take support from something called as symbol table manager. So we shall see all of them in detail by taking an example. You will understand more when I take an example. And moreover, all of them are going to talk with a module called error handler. Okay. So we shall take an example and see what do I mean by stream of tokens, and what do I mean by parse tree, what do I mean by semantic verification, 3 address code, optimization, target code generator. I'll take a single example and I'll explain you all the phases in that example. Okay, fine, got it. Yeah, let's see an example about how all the phases are working. The example is x equal to a plus b into c. Let us say that is the source program we have given. Just for the assumption, the source program is just one line, x equal to a plus b into c. Nothing but you have to multiply b and c and then add a and then store the result in x. First, this one will be given to lexical analyzer. Once the lexical analyzer receives the input is converted into a stream of tokens. That is the main purpose of lexical analyzer, right? So other responsibilities of lexical analyzer is they are going to remove the white spaces if there are any white spaces opposite, after this, before it, and if there are any comments, if you might even write a comment, something like this. Whatever comment it is, this one will be deleted by lexical analyzer. So main responsibility is converting the program, the stream of lexemes means all these names, into stream of tokens, right? For example, id is x is an identifier, equal to is a operator, a is an identifier, plus is an operator, b is an identifier, c is an identifier, right? So how do you identify, how does the lexical analyzer identify that these are all identifiers and then these are all tokens is that is using some regular expression called patterns. So for example, an identifier can be like this. An identifier can be a letter followed by letter or digits, any number of them. A letter followed by letter or digits. This is called the pattern. If anything matches this pattern, then that will be automatically identified as an identifier. So the pattern will be known to the lexical analyzer before, which means you have to give it before you start everything. Now once you get the tokens, stream of tokens will be given to syntax analyzer. Now syntax analyzer is going to take all the tokens one by one, and then it is also going to take a grammar. No, it is generally called context free grammar. Why are grammars useful is, grammar's main use is this. The entire program, the rules of the programming language can be entirely represented in some few productions. Generally every programming language, it will have some few hundreds of productions. Using these hundreds of production means these rules. Using these rules, we can represent what a program actually is. For example, the meaning of these few productions is this. A statement can be identifier is equal to expression followed by semicolon. Okay, and now an expression can be expression plus term or term. A term can be term into factor or factor. A factor can be simply an identifier, right? So using these rules, your program has to be matched against them, which means the input has to be checked whether we have given it according to this format which we wanted. For this the syntax analyzer, it is also called as parser, it is going to construct a parse tree. Parse tree is going to start with the start symbol. Yes is the start symbol. A statement is identifier is equal to expression. An expression is expression plus term. A term is term into factor. Factor can be identifier, term can be factor, factor can be identifier. So finally what we get is a parse tree in which we can see the entire stream of tokens. In case if you don't see the stream of tokens, see the stream of tokens is this: id equal to id plus id into star followed by semicolon, right? Therefore you have to see that the yield of this parse tree and the input to the syntax analyzer both are same. If you get that, we can say that the input is according to the format we gave, otherwise there is a syntax error. Therefore syntax errors can be detected at syntax analyzer if the input is not according to the grammar given. Okay, now the output of syntax analyzer is a parse tree. This parse tree will be given to semantic analyzer, the next phase, right? So semantic analyzer is going to take the parse tree and verify it semantically in the sense whether it is meaningful or not. For example, it is identifier is equal to something, right? Now left hand side has to be a variable, it cannot be a constant, or it cannot be a function name, or it cannot be an array name. So left hand side has to be a variable which is compatible with the type of the right hand side. So all such type checkings have to be done at semantic analyzer. Okay, so output of semantic analyzer is going to be meaningfully verified parse tree. That is why it is called semantically verified parse tree. Now this semantically verified parse tree will be given to intermediate code generator. So intermediate code generator is going to generate intermediate code. There are various kinds of intermediate codes, but the most popular one in intermediate code is 3-address code. Why is it called 3-address code is, if you look at any line, there are only 3 addresses. For example, in this one, T1 BC, T2 AT1, X T2, which means maximum there can be 3 addresses. I mean, it can even be less. So the given statement is 4 addresses. Now we reduce the statement into 3 addresses. This is 3-address code. Why do you want to convert something into intermediate code generator is, if you can convert a program into intermediate code, then that intermediate code can be converted to machine language using the last 2 phases which are dependent on the platform. So till this part, whatever machine you are going to run the compiler on, this part is completely same. Which means if you want to design a new compiler for a new platform, you need not start it from the scratch. You can take all the phases till intermediate code generator, and you can change the last 2 phases so that the new compiler can be formed. Okay, therefore if you are having an existing compiler, what you could do is just take it and then change the last two phases so that you get a new compiler for a new platform. For example, if your existing compiler is writing some code which will run on a computer, maybe if you want to do a code or write a code which will run on a mobile phone, just you change the last two phases, these two phases. You need not change everything. Okay, and then by taking this intermediate code, the code optimizer is going to reduce the number of lines. How many lines were there? 3 lines were there. If you look at the lines, first what are they doing is, first they are trying to multiply B and C. First they are trying to multiply B and C and then put it in T1 and then add A to T1 and then put it in T2 and then write T2 into X. Now by using code optimizer, we are actually reducing the number of lines. We don't need actually 3 lines to do this job. Only 2 lines could do it. Okay, so that is why we are having code optimizer. Now the output of code optimizer will be given to target code generator. The main purpose of target code generator is to write the code which assembler can understand. You remember that, right? After the compiler there is a phase called assembler, and the assembler will be depending on the platform. Therefore, depending on what assembler you use, you have to write the this target code generator has to produce that kind of code. For example, now this is just an example I have taken. It need not be the same for all the compilers. So output could look something like this. I'm not saying that it is going to be always like this. No, we have how many variables? A, B, C. In case if you have moved A into R1, R0, B into R1, C into R2, then this code can be put in this way. First we are multiplying B and C. That is why multiply R1 and R2 and then storing it in R2 only. Therefore R2 will contain B into C, and then we are adding R0 to R2. Right? Why? Because T2 is nothing but adding R0 to R2, and then we are moving everything into X. Right? So this is actually X equal to A plus T1, and then we are moving everything into X. Right? So theoretically this is what all the phases are supposed to do, but then practically when you come to the practical implementation of compilers, we really don't have all these phases. Most of the phases or most of the jobs or the functions are done by syntax analyzer itself, which means the syntax analyzer is generally the heart of the compiler, which is even going to take lexical analysis. I mean, when you implement it, you are not going to implement it separately. In the same module, you are going to implement even the lexical analyzer and the semantic analyzer also, and even intermediate code generator. Therefore, this entire part will be implemented together, which is also called as front end. So till the phase intermediate code generator, it is also called as front end. Front end in the sense the starting part of the compiler, and after that whatever is remaining, that is called back end. Okay, so back end we have code optimizer and target code generator. So in all these phases there is front end and there is back end. Theoretically the entire front end is implemented together, and then the back end. If you give any program normally, so front end will act on it first and then the back end. If you are interested in implementing a compiler, there are various tools available. So first thing is, for lexical analyzer there is a tool called Lex available in Unix. So you can implement lexical analyzer using Lex. And for syntax analyzer there is a tool called YACC, yet another compiler. And if you want to do any project on this compiler, there is a tool called LANS, LANS. So LANS is nothing but implementation of the front end of the compiler, which will give you intermediate code, and then you can implement back end on your own depending on the platform. Okay, so what I mean to say is, theoretically there are all the phases, but practically we have front end and back end. All the phases till this intermediate code generator are implemented together, and mainly they are implemented in syntax analyzer. Okay. Now let's see some points on symbol table. So we are going now, since symbol table is a table, it is going to have the columns, right? And column names are also called as attributes. So let's see how does the symbol table look like, which means what are all the columns the symbol table is going to have. Now each entry in the symbol table is associated with attributes. So attributes means sometimes columns are also called as attributes, okay, that support that support the compiler in different phases. These attributes are, one is name, so what is the name of the entity that we are talking about, and the other one is size, so what is the size of it, right? What is the size of an int, what is the size of a character, in case if it is an array, what is the size of the array, right? And dimension, so the dimensions are used in case when it is an array, right? If it is not an array, the dimension is generally going to be 0. If it is a single one-dimensional array, the dimension is going to be 1. If it is a two-dimensional array, the dimension is going to be 2, right? And then the type. So type, as you know, it can be either integer or character or any type like that, boolean. And the next one is line of declaration. So this is going to give you the number at which that particular variable is declared. So why is this line of declaration is important is, in case if you have to generate an error saying that some error has occurred, then you should know where that line, where that error has occurred, right? So that is why you should always store the line of where it is declared as well as the line at which it is used, so that later when you are trying to report the errors, you can also give the line at which the error has occurred. So you are going to store the lines. And the next one is address, so address of that particular entity. Okay, so this is how your symbol table is going to look like. It is going to contain all these attributes, and depending on the implementation, there might be few more attributes added by some programming languages, and few more attributes may be deleted. But typically this is the information you are going to see in most of the symbol tables. Okay, so let's see some example. Let us say name of one variable is one array is Ravi, right? And it is of type character. Okay, and let's say it is a array of size 4, so size is 4, and it is a one-dimensional array, that is why dimension is given as 1, and then depending on the line at which it is declared, you are going to get the line number, and then depending on the line at which it is used, you are going to get the line of usage. Sometimes what happens is, you might use a variable or an entity in more than one place, right? Let us say in the program you are going to use a variable I at 10 places, right? And now if you see the line of usage, since it is given as a single field, while implementing it, it will be implemented as a linked list. So since we don't know how many times it is going to be used, it is better you maintain a linked list, and in that linked list, in each node you can save at each point at which, or each line at which it has occurred in the linked list. Okay, so you are going to maintain a pointer here, and that pointer is going to point to the linked list in case if a variable is actually declared at more than one place or used at more than one places, right? And address is going to give you what is the address at which this particular variable is stored. Okay, now all the attributes are not of fixed size, so the attributes may be of different sizes. For example, line of usage, it may vary, right? And now what about the size of the symbol table? Again, the symbol table is a kind of data structure. Now you are supposed to find out, or you are supposed to specify how much size you need. So the problem with this one is, just like the declaration of an array, you don't know the exact size that you might need. Now if you try declaring it too small, then it will be giving you advantage in terms of the space saving, but then the problem is you might not be able to store information about too many variables or all the variables. Now in case if you declare it too big, then you might be wasting some time, some space, because after storing the information about all the variables, some of the entries might be left over which will not be used anymore. So that is why it is better if you can use a dynamic allocation of this data structure, of this table, right? So see this limitations of fixing the size. Once you fix the size, there are two problems you might come across it with. So one is, if the chosen size is, if it is chosen small, then it cannot store more variables. It cannot store all the variables which are present in the program. If it is chosen large, a lot of space is wasted. Therefore, so the size of the symbol table should be dynamic to allow the increase in size at the compile time. So you should go to you should try to allocate this space dynamically. So whenever you need to add more variables, you should keep on increasing the size of the symbol table. So instead of using the static sizes, you better use dynamic sizes. Okay, fine. Now let's see the operations that we can define on a symbol table. So actually the operations depend on what is the language that you are working on, right? If your language happens to be structured, then the operations are going to be different, and if your language is going to be non-structured, then your operations are going to be different. See this? Depending on whether the language is block structured or non-block structured, the operations or the type of operations that you use will change, right? So what I mean by block structured and non-block structured is, if you look at block structured, you are going to have the entire program written in one single block. Okay, now here if you declare any variable, I'm just taking a random example. Let us say you have declared int I, right? Let us assume that there is a programming language which is non-block structured, which means there are no blocks in this. Now if you write int I, it means that this particular variable I is visible throughout the program and the scope is not going to change. Okay, so for every variable there will be exactly one declaration. Okay, you will not be able to declare it many times. Now if you have a block structured programming language like C, then in the same program you can have two blocks. Let us say you are having two blocks like this. Now in this block you can declare I once, okay, and in this block you can declare I again, right? Now when you are present in this block, the scope of this particular I will be only from here to here. Once you exit this block, then this variable is no way seen. Now if you see this, the scope of this I is from here to here, and once you exit it, this will not be seen, right? So depending on what type of language you are talking about, the operations are also going to change. Now in case of non-block structured, it contains only one instance of the variable declaration and its scope is throughout the program. So what we are trying to say here is, here we are going to declare every variable exactly once, right? And its scope is going to be throughout the program. So we are going to see this throughout the program. We are not going to declare it again and again. Therefore, once you insert an entry for I, you need not change it at all. That is the meaning of it. So that is why for non-block structured languages, the operations are insert an entry, and once you insert it, you just look up whenever it is needed. You just look at the entry whenever the information is required. In case of block structured, what happens is, since you are going to have various blocks and you are going to declare the same variable again and again in every block, now depending on which block you are in, you have to use different information about that variable. Therefore, whenever you enter a block, you create an entry for that variable, and whenever you exit the block, you just delete it. Therefore, we are going to insert as well as look up. Whenever we want, we are going to search for it, and set and reset. Set and reset means we need to clear that entry completely, and set means we need to start a new one, right? See this, here the variables may be redeclared and its scope is within that block. Therefore the operations are, we might try to insert and we might try to look up, and once you enter a new block, we might have to set the scope to a different value, and once you come out of the block, we might have to reset it, which means you might have to change the scope, right? So therefore, depending on the language, we might have to use these operations. So depending on the type of language, the operations are going to change. Okay, fine. Now let's see various methods by which we can implement a symbol table. I'm showing you all the various data structures available, and then if you implement it, the symbol table using these data structures, I'm telling you how much time is required for the insertion time, lookup time, and what are the disadvantages of it. Okay, now let's see this one first. If you are going to implement a symbol table using a linear list, so linear list means either it can be an array or a linked list, right? So let's see what happens with the times here. If you are going to implement it using an array, First thing is, it is difficult for us to implement it using an array because we don't know the exact size of the symbol table. Therefore, practically we don't go with arrays, but just for the theory sake, we have written it here. Now, in case if you are going to implement it using an array, and if that array is sorted, then if you have to insert an element, you might have to move all the elements to the right. So that is why, just like insertion sort, inserting an element into a sorted list or sorted array is going to take order of n time. And coming to the lookup time is nothing but the search time. If array is sorted, then in order to search for an element, you can use the binary search, and the binary search is going to take order of log n. Now if you implement the same thing using a linked list, right, in order to search for the position at which this particular element has to be inserted, time taken will be order of n, right? And after searching for its position, then only you are going to insert it. That is why time taken will be order of n. You have to search the entire list. And now if you are looking at the time taken to search for an element, again it is also going to be order of n, because you cannot apply binary search on a linked list, right? Why? Even if you try to apply binary search on a linked list, it is going to take a lot of time. It is better you don't go with that. It is going to take order of n time, right, if you go with linear search. Therefore, on a linked list, you are going to use linear search in order to insert an element as well as search for an element, right? But here, in order to insert an element, you can find out the element's location in order of log n time in the array, and after you find out the location, you might have to shift the elements. That is why it is order of n time, right? And for searching an element, it is order of log n. And coming to the unordered list, again in unordered list also you have two variations. One is array and the other one is linked list. In both the cases, if you are going to insert an element, it is going to be order of 1 time, right? Why? If you are going to insert an array into an unsorted list, in case of an array you can directly insert it at the end, and in case of a linked list you can insert it at the beginning, isn't it? Therefore the time taken is order of 1. See, I think you know how to insert an element at the beginning of the list in order of 1 time. If you don't have any restrictions like sorting, now let us say this is the list and this is the head, right? Now how you can insert a newly formed one node into this is, you can create a new node and you can make that node point to the head 1, and you can make this head point to this, right? Therefore, in order of 1 you can insert an element into a linked list if it is unsorted, right? And if it is unsorted array, you can place the element at the end. Again, it is also going to be order of 1 time. So it is order of 1 time. And what about the lookup time? Lookup time is the time taken to search for an element. If you are going to search for an element, right, so the time taken to search for an element here is going to be order of n, both in case of array as well as the linked list. So why is this so? Is you will have to search the entire list. In both the cases it is unsorted, that is why. Now one thing you should be careful about is, whatever method you are using, always you are going to search for an element before you insert it, right? And so insertion time might be affected. See, whatever insertion time I am telling you here is based on the assumption that there are no duplicate elements. Sometimes what happens is, if an element is declared 2 times, then before inserting an element into the symbol table, you should also check whether that element is already present in the list or not. In that case, every insertion will also need a search for the element, right? So I am not taking that into consideration. I am just assuming that we are not going to have duplicate elements. In case if we have duplicate elements, you will have to search before you insert, right? So removing this, I am telling you all the times. Just keep that in mind. Now in the exam, if they specify that no duplicate elements are allowed, then you are supposed to search before you insert, okay? And the next one is self-organizing list. So what is a self-organizing list is, it is a normal linked list only, but what we do is, whenever we search for an element, when we find it in the list, we just move it to the beginning of the list, so that most recently accessed element will always be close to the head. Head means the beginning of the list. Now what happens because of this one is, the frequently accessed data will be present at the beginning of the list, and so you will be able to find such elements with very less time. You need not search the entire list, it will be present at the beginning, right? So that is about self-organizing list. Now since a self-organizing list is generally an unsorted list, if you have to insert an element, the time taken will be order of 1 because you will be inserting it at the beginning, right? And what about the time taken to search? Since it is an unsorted list, you will have to search the entire list in the worst case, and so time taken will be order of n. But only thing is, after you search and find an element, you get that element and put it at the beginning, so that next time when you search for it, you will be able to find it easily, right? Okay, and the next one is search tree. So you can also implement it using search tree. So there are various types of search trees like binary search trees, B trees, B plus trees, all these trees are possible. Now coming to the search tree, if it is balanced, then it will give us the best performance. If you have n elements in the tree, and if the order of the tree is k, then the height of the tree will be in the order of log n base k, where k is the order of the tree. In case of binary tree, it is going to be log n base 2. In case of ternary tree, it is going to be log n base 3. In case of binary search tree, right? Okay, so in the binary search tree, it is going to be 2. Now if you are going to use a search tree in order to implement a symbol table, then the time taken to insert an element will be equal to the height of it, will be proportional to the height of it, and so it is going to be done in order of log n base k time. And if you are searching for an element, again it is also going to be log n base k time. And the next one is hash table. So hash tables are generally used in order to in order to have the constant time. So both for insertion and both for lookup searching, it is going to be order of 1 time, and in some cases, if your implementation is not very good, then sometimes what happens is there will be collisions, and again you will have to resolve the collisions using chaining and open hashing, all these techniques, and then the time complexity might increase. But if you look at it, on average the time taken should be order of 1. Now let's see the disadvantages of each method here. Now the disadvantage of the linear search is, if you are going to have if you look at the search time in the linear list, the search time is proportional to the size of the list in case if it is unordered list. In case of ordered list, you can do it in a log n time in case if it is an array. In case of a linked list, either it is ordered or unordered, you might have to search the entire list, and therefore the lookup time is directly proportional to the size of the table. And every insertion operation is preceded by a lookup operation. So if you are going to insert into a sorted list, right, then you have to search for the location where the element has to be placed. So that is why you might have to do a search operation before you insert it. So that is a disadvantage. And coming to the self-organizing list, so whenever you are going to search for elements which are less frequently used, then the search time is going to be worst. In case if you keep on searching an element frequently, then that element will appear at the beginning of the list and it is going to give you better time. Now if you are not going to always search for the frequent elements, if you are going to search elements randomly, then it is not going to give you better performance. Alright, therefore it is useful only when some elements are searched with higher frequency compared to the other elements. Okay, and next one is search trees, and in the search trees we have to always keep it balanced. If you are not going to keep it balanced, then there is a problem called as skewed trees. If the tree is going to grow only in one side, then the problem is the height of the tree will be proportional to the number of elements, which is nothing but n. Then instead of order of log n, we might get order of n. Therefore you have to always keep it balanced. And coming to this hash table, the disadvantage is if there are too many collisions, then the chain, we have discussed this thing in data structures in hash tables. So I told you that if there are too many collisions, then the time complexity is going to increase, and it is going to increase to order of n if the length of the chain is too long. So what is a chain and why are we using it? That everything will be discussed in the hash table topic. You can refer to it in data structures. Okay, so these are various implementations we have, and these are the various times they have, and these are the disadvantages. Okay, fine. Yeah, let's talk about lexical analyzer first. The main responsibility of lexical analyzer is, this is the only phase which actually reads the text character by character, which means once this phase is over, you will never see the letters I, N, T or M, A, X or X or Y instead of these every literal, this is called lexeme. In place of every lexeme, you are going to see a token. So for example, int is a token, max is a token, identifier xx. So only at this phase, lexical analyzer is going to read line by line, and its main responsibilities are, one thing is it will eliminate the comments and it will eliminate the white spaces. Even if you try it as interesting work, maybe even if you write the entire C program in one line, there will be no errors at all. You need not write the C program in many lines without giving any spaces in the sense after the line. Okay, between them, you have to between int and max you have to give a space, but then after this you need not give any space. So if you write a program completely without any spaces, then also it works fine, right? So here, coming to this, the main responsibility of lexical analyzer is, first is converting the lexemes into tokens, which means names into tokens. That is first one. Second one is removing the comments. Third one is removing the white spaces wherever you have given extra white spaces. And then only at this phase, since we are reading them character by character, we know what is the line number of each lexeme. For example, sometimes you will see that at some line number there is a syntax error, and this can be done only because the lexical analyzer is actually reading the program line by line. Otherwise, it would not be possible. Okay. So removing the errors, first thing is removing the comments, removing the white spaces, and third thing is, if you get any errors, it is going to show up. And how many tokens are there in this program? So if you count the number of tokens, so int is a token, max is a token, 1, 2, even open brace is a token, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So completely there are 25 tokens in this particular program. Okay, you are not going to count anything of comments as a token, that will be completely removed. So there are 25 tokens. And one more thing is this a valid declaration? Int max x comma y, and then later there is int x comma y outside it. They are not actually global variables. This declaration is perfectly valid, and I suggest that you read that book, the C Programming Language by Dennis Ritchie. That is the best book if you want to learn about programming more, especially C programming more. That is worth reading. Okay. And next one is, let us say there is a line like this. How many tokens are there in this particular line? So printf is a token, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You are supposed to get 11 tokens, right? But then there are this is wrong. The reason is there are no only 8 tokens in this. The reason is the entire string, literal, is considered as 1 token. The entire string constant is 1 token, and the remaining things are 1 token, which means 1 token is printf, second token is open brace, third token is the string, fourth token is comma, fifth token is ampersand, 6, 7, 8. Therefore only 8 tokens are there. So some questions in lexical analyzer is, what is how many tokens are there and what are the responsibilities. That is all about lexical analyzer. Okay. Let's see about syntax analyzer or parser. Before going to syntax analyzer, we have to think about grammars. So the input to syntax analyzer is a grammar, and therefore the syntax analyzer is going to take the grammar. See, if you have a syntax analyzer, you have to give the grammar first and then the input. Now the input will be checked according to the grammar. Therefore, before going to syntax analyzer, let's talk about grammars. And the grammars are like this. Generally, the way we represent grammar is VTPS. So if you are not good with the grammars, or if you have not done automata theory, it is better that you watch my automata videos of grammars, and then I can come back to this topic and watch it. Now there I will be discussing everything at depth. Here, I assume that you have already watched that video. So even then I just introduce the basics. Grammar is VTPS, where V is nothing but variables, T is terminals, P is productions, and S is the start symbol. Example, let's take this grammar. E derives E plus E E star E ID. If this is the grammar, I have three productions. Okay, so generally this is one of the way to represent three productions. You could even write it as E derives E plus E derives E plus E star E derives ID. This is one of the ways. Okay. Now here the main variables are nothing but the left hand side. In the left hand side we have only one symbol. Therefore, the set V contains only one symbol E. And the terminals are all the whatever is not there on the left hand side, that is generally a terminal. So in this grammar the terminal is plus, star and ID. Okay, so whatever these rules are called the productions, and the start symbol is one of the variable, and here we have only one variable, therefore start symbol is E itself. So next thing is, once we have considered this entire grammar, what is the output, what is the main purpose of the grammar is they will generate all these strings. For example, if I want to generate this string ID plus ID star ID, if I want to derive this string from this grammar, okay, so it will look like this: E derives E plus E, and then either you could use replace this E first or this E first with any of the variables. This is called derivation. I am going to do the derivation, and in this derivation you could derive the first variable in the expression or the second variable in the expression, or in any order. If I go in the leftmost variable first, then it is called leftmost derivation. Let me show you leftmost derivation. Okay, leftmost derivation means I have two variables and I am taking the leftmost one. Leftmost one is the first E. So how can I write it? This one is going to be replaced with ID plus E, and now the second variable E, this one has to be expanded using any of the productions. So the right production is E star E. Therefore I am going to expand ID plus E star E. This E is replaced with EE. Now again we have two E's. So which one do you want to replace? The leftmost one. Why? Because we are doing the leftmost derivation. Okay, now what do I get? ID plus ID star E, and finally the last one, ID plus ID star ID. Now for the same grammar, for the same string, this is leftmost derivation, what we did. Now if I want to do the rightmost derivation means at every point we are going to replace the rightmost variable first. So E derives E plus E, and now what is the rightmost variable? The rightmost E. What do you want to replace it with? You cannot replace with ID, you have to replace with E star E. Now how many variables are there? Three variables. Again you replace the rightmost one first, E plus E star ID. And what is the rightmost one? The second E, E plus ID star ID. And again the last one, ID plus ID star ID. Therefore this is the leftmost derivation and this is the rightmost derivation. Okay, now my question is this the only leftmost derivation possible, or is there any other leftmost derivation possible? Let's see this. Can I derive the same string using leftmost derivation using the same grammar in a different way? Let's just see this. E derives E. What if I take E star E first? Can I still derive this string? It turns out that we could. Okay, I'll take the leftmost one, E plus E star E. This leftmost one is replaced with E plus E, this production, leftmost one. And again the leftmost symbol is replaced with ID, and next again the leftmost variable is again replaced with ID, and again the leftmost one is replaced with ID. Okay, and next one is RMD. Is there one more RMD possible? It turns out that yes, we could do one more RMD also. E derives E star E, and now the E derives E star ID, and now first E derives E plus E star ID, and again the rightmost E is again going to be derived with ID, and again the rightmost one, which is only one, ID plus ID star ID. Therefore we have again derived it. Okay, so next question is, parse tree. Instead of deriving it using the derivation procedure, can we derive it using the parse tree procedure, which means parsing the grammar like this. E derives E plus E, and this E derives E star E, ID, ID and ID. This is one parse tree, and one more parse tree possible is E derives E star E, and then this first E derives E plus E, therefore this E derives ID, ID and ID. So if you observe this grammar, for a given grammar, for a given string, for a given grammar, for a given string, we got more than one leftmost derivation, and we got more than one rightmost derivation, and we got more than one parse tree, right? Either we get more than one LMD or more than one RMD, which means rightmost derivation, or more than one parse tree, then we can say that the grammar is ambiguous. Ambiguous in this sense, if we have two parse trees possible, generally parsers will get confused about which one to generate or which is right. Okay, so in these two parse trees, even though the output is showing it to be the required string, the evaluation is different. For example, if I have any input, let us say 2 3 4, which means if I have any input like 2 plus 3 into 4, the output is supposed to be 14, isn't it? Output is supposed to be 3 into 4 is 12, 12 plus 2 is 14. Now if I use this tree, what is the output that is resulting? And if I use this tree, what is the output that is resulting? Just see this. Now this ID is going to be 2, this ID is going to be 3, this ID is going to be 4. Then the first one, this E is nothing but the sum of this expression and the sum of the next expression. If I have to evaluate this expression first, I need the value of this expression, which means I have to evaluate this one first. Therefore, according to this parse tree, the first one which is going to be evaluated is multiplication, and then the next one is addition. Therefore, according to this parse tree, the right answer, this is the right answer, this is right, which will give the answer of 14. If you use the other parse tree instead, which means this is 2, this is 3, this is 4. In order to evaluate this expression, you have to evaluate this expression. In order to evaluate this expression, you have to evaluate this expression first. This is right, readily available. You need not evaluate anything. But this expression you have to evaluate first, which means 2 plus 3 is added and then multiplied with 4. So therefore, here it is going to be 20. This one is going to give you 20, and this one is going to give you 14. So which is right? Therefore, parser, the confusion with parser is when you have more than one parse tree, parser doesn't know which parse tree to use. So most of the parsers, almost every parser except one parser, we shall see it later, will not allow ambiguous grammars. If there is any ambiguity in the grammar, we have to convert it into unambiguous grammars. There are two questions here. How to find out a grammar is ambiguous? There are no algorithms. You have to do it hit and try way. Second question is how to convert a ambiguous grammar to unambiguous grammar. Again, there are no algorithms. Okay, so we cannot know whether a grammar is ambiguous or unambiguous using a direct procedure. You need practice, and then you have to do such methods. What? Take a string and then check whether we generate 2 or more parse trees. If you get 2 or more parse trees, or if you get more than one LMD, or if you get more than one RMD, then the grammar is ambiguous. In these lectures, I am going to follow the method of parse trees. So in order to find out whether a grammar is ambiguous or not, I'll take the grammar and I'll take a string, and then I'll see if I get more than one parse tree or not. Okay, let's see some examples to find out whether the grammars are ambiguous or not. Let's see 3 more examples whether the given grammar is ambiguous or not. The given grammar is S derives AS, SA or A. So in order to find out whether it is an ambiguous grammar or not, there are no algorithms, which means ambiguity problem is undecidable. We don't have any algorithm for that. So only one thing is you have to try and see all possible strings. A grammar is said to be ambiguous if for any string which is derived from this grammar, we get more than one parse tree. So for example, if given this grammar, tell me string which is generated by this. I'm guessing that this string AA might give me more than one parse tree. How do I know it? I'm just guessing it. There are no direct methods. Okay, so S derives, I'm just trying whether we get more than one parse tree or not. This is one parse tree, and sdrise SA, and this is one parse tree. Yes, we got two parse trees for the same string from the same grammar. Therefore, we can say that the grammar is ambiguous. The grammar is ambiguous. You can even try with two LMDs or two RMDs, but then maybe you might have to try with a different string. Yeah. So next one is whether this grammar is ambiguous or not. For that, you have to again do the same method. What is the method? Guess the string, some string, any string, and then see if you could find more than two parse trees. If you are lucky, you will find it for a small string. Otherwise, you have to keep on doing. That is why there are no algorithms. Okay. So the word is, let us say AB, AB. If this is the word which we want to generate from this grammar, let me see if you get more than one parse tree. So one is sdrise A, yes, B, yes, and now this one, this second, this sdrise B, yes, A, yes, and this one is epsilon, this one is epsilon, this one is epsilon. When you have such a big parse tree, sometimes you might get confused about what is the output of the parse tree. That is also called as yield of the parse tree. For that method, you have to traverse the tree top to down, left to right. While traversing the tree, whenever you come across any terminal, you write it down. Then you will find out what is the string generated by this. Traverse it top to down, left to right, which means like this. What is that you have encountered first? A, and then B, and then again A, and then epsilon. I am not writing it because epsilon is not going to be any value, and then again B. Okay, so therefore that is AB, AB, right? So let's see if we get one more parse tree. Just let's try sdrise A, yes, B, yes, and let us expand the second S first. Here I expanded the first S, here I am expanding the second S. I am expanding the second S with again AS, BS, and this S with epsilon, epsilon, and epsilon. Now just see the yield of this. Yield of this is, first you encounter A, therefore output of this is A, and then you encounter epsilon, so don't write it, and then you encounter B, B, and then you encounter A, yes, and then you encounter epsilon, leave it, and then you encounter B. Therefore output is AB, AB. So for the given grammar, for a given string, we got more than one parse tree. Therefore again this is ambiguous. Okay, so let's look at this example. So what is this example? R plus R, R star. It is nothing but a grammar which is representing all regular expressions. For example, this R derives R plus R is nothing but a regular expression can be union of two regular expressions, or concatenation of two regular expressions, or a clean closure of a regular expression. And a regular expression can be either A or B or C. They are primitive regular expressions, right? So how do I get more than one parse tree? It is same. Maybe if you want to generate A plus B into C, like how you generated it for A plus B into C there, A plus B concatenated with C, I get two parse trees. We have already seen such a model. RR, BC, and then A. Here this concatenation is getting higher precedence because it is at the lower level, right? And let us say one more, R, or let me say this is RR, and then this one is R plus R. Again it is A, B, C, which means one expression is computing B into C first, and the other expression is in the other parse tree is computing this first. However, we got two parse trees, therefore we can say that the grammar is ambiguous. Okay, so all the three grammars are ambiguous grammars. Let's see the types of errors that can be detected in lexical analysis, and then the actions that it could take. So what are the types of errors that a lexical analyzer can detect is when numerical literals are too long. So whenever you are going to give something like this, let us say int a equal to, let's say 1, 2, 3, 4, 5, 6, 7, 8. You have given a number which is too big to fit in an integer. Let us assume that integer is implemented as a 2 byte 2 byte number, which means using 16 bits we are trying to implement it, then the maximum possible number we can go with is 65535, isn't it? Now if I go even beyond it, even if it is unsigned int, then also the maximum possible is 65335, and if you are going to give even more than that number, then it is not possible to put there. So such things will be detected by this lexical analyzer. And the next one is long identifiers. So if you are going to use the name of a variable or a name of the function using a lot of characters than the required specified in the programming language, that also can be identified here, right? Why? Because lexical analyzer generally works with these regular expressions, and in regular expression you can specify what is the maximum length the identifier can take. So if you are going to go beyond that, it will find out that error. And the next one is ill-formed numerical literals. So ill-formed numerical literals means, again you can take this similar example. If you write int a equal to $123, if you are going to write like this, now dollar does not fall in an integer, so that is why it is a numerical literal which is not correctly formed. So ill-formed numerical literals can also be detected by this. And the next one is input characters that are not in the source language. Every language will allow certain characters and it will not allow certain characters. For example, if you are going to have a C compiler which is written for English language, and if you directly insert a Chinese character into it, it is not going to accept it. So that will also be detected. So these are all the types of errors that will be detected by the lexical analyzer, right? Apart from the the spelling mistakes, right? So as far as possible, some programming languages will try to correct the errors that occur in the lexical analyzer, so that your program will continue to the next stages and it will be compiled successfully, right? So instead of stopping the compilation whenever you get an error, sometimes our compiler will try to rectify it. So for example, if you see this error recovery, it will sometimes do deletion. So when is it possible is your compiler will automatically do that, and unknown characters are deleted, also known as panic mode recovery. So this is also known as panic mode recovery. If you are going to write CHARR instead of char, then some characters will be deleted and it will be corrected. If you are going to delete this R, then automatically it is going to be corrected, isn't it? And the next one is insert. And next one is sometimes we are going to insert in order to correct the mistake. So an extra or a missing character is inserted to form a meaningful token. For example, if you are supposed to write char and if you have missed out R, then your compiler will automatically insert it. And again, this is also done by the lexical analyzer only, okay? And the next one is transpose. So based on certain rules, we can transpose two characters. For example, if you are going to have while, right, and by mistake if you are written like this, then your lexical analyzer can find it out and it can replace it, so that while will be formed, and then replace based on the replacing one character by other. So if you are going to have CHRR written, then you are going to replace R with A, right, and you can get char. So these are the various recovery actions that our compiler can take. In case if it is not able to recover from the error even after doing all this, it will just stop the compilation and it will report to the user saying that there is some error at so and so line number. And also lexical analyzer is capable of giving you the line number at which an error has occurred. Then you can correct it. If these are not sufficient, then you are supposed to correct it. Okay, fine. So we have seen that given an ambiguous grammar, we are getting two parse trees. Therefore, what should we do about such grammars? Should we not use them in the compiler design completely? It turns out that some of the ambiguous grammars can be converted to unambiguous grammars. This is called disambiguating rules, which means we can use some rules and see what is the reason for the ambiguity, and if we can work on that root cause, maybe by converting the grammar we could do it. For example, this grammar E derives E plus E, we have seen this just now, right? E star E ID. This grammar, we have seen that it is ambiguous, right? And now if you see the reason for it being ambiguous, if I take a string ID plus ID plus ID, for this string we will get two parse trees. One parse tree is E derives E plus E, isn't it? And E derives E plus E, and ID, ID, and ID. And other pass tree is for the same string E derives, ID plus ID plus ID. Other pass tree is E derives E plus E, and then the second E derives E plus E. This one is ID, this one is ID, and this one is ID, right? So for the same string we got two pass trees. Maybe if we take one more string, then it will give us some more insight about it. We got some insight here. I want to see some more. ID plus ID star ID. If this is the string, let us see what are the two pass trees we get. One pass tree is E derives E plus E, and second E derives E star E. Okay, and now every terminal has to be even generated by the tree. So this is ID, and this is ID, and this is ID. So this is nothing but ID plus ID into ID. So one more pass tree is E derives E star E, and then this E derives E plus E. This is ID, this is ID, and this is ID. Okay, so we got two pass trees here, and we got two pass trees here. So even if we get more than one pass tree for a given string, we can stop there and say that the grammar is ambiguous, which means even here we can say that the grammar is ambiguous. But then I needed something more. So let's see the reason why for this string we got two pass trees, and why for that string we got two pass trees. Here we have ID plus ID, and whenever there are two operators on the either sides of an operand, for example, there are two operators on the other side of this ID, which operator should I associate this with? If I associate this with the left side operator like this, then it is called left associativity. If I associated this with right side operator, then it is called right associativity. In case of plus, the final output doesn't depend on what the actual associativity is in case of addition. But if you consider this to be a subtraction or some other operation like division, then definitely there will be a change. So in that case, I want plus to be left associative. See, only for plus associativity doesn't matter, but still plus is left associative, which means if I have two pluses, here plus and here plus, here plus and here plus, the leftmost should be evaluated first. Therefore this pass tree is right. Why? The leftmost plus is evaluated first, and this pass tree is wrong. The reason is the rightmost plus is getting evaluated first. So this grammar failed because the rules of associativity failed completely. And then let's look at this example. In this example we got two pass trees. The reason is, in this pass tree, star is getting higher precedence. When we have two different operators of different precedences, then the highest precedence one should be evaluated first, which means, see this has to be evaluated first, star has to be evaluated first, here it is evaluated first, therefore this is right. And what about this one? This is wrong. The reason is, in this one plus is evaluated first, therefore this is right and this is wrong. So here we got two pass trees because precedence is not taken care. Here we got two pass trees because associativity is not taken care. If we can take care of these two things, then the grammar can be unambiguous, right? So how can I modify the grammar so that we can take care of these two things? Let's talk about associativity first. So why are we getting both the associativities is, we are defining the grammar without any order. See this? Now according to that grammar, I can write expression to be expression plus expression, and if I want one more plus, I could either go this direction or I could go this direction. But then we found out that if we grow in this left direction, then it is going to be left associative, right? And if you grow in right direction, it is going to be right associative, right? So I want the left associativity, therefore I want to restrict the grammar to grow in only one direction, which means I want to apply the recursion only in one direction. For that reason, if I write E derives E plus id, if this is the grammar or id, let's see what happens. Here what happens is I am going to restrict the growth of the parse tree. So I am completely restricting the growth of the parse tree. See this? E derives, if I want id plus id plus id, id plus id plus id, then I am going to write it as E derives E plus id, and there is no other way I could grow. I could only grow it in the left hand side, which means again E plus id, and finally this E is id, which means I am growing in left direction because the grammar is defined as left recursive. That is the reason why I am growing like this. So is there any other possibility of getting one more parse tree for the same string? There is no way. This is the only parse tree. Therefore, if I have to see that the operator should always be left associative, I have to see that the grammar has to be left recursive. If the grammar is left recursive means the leftmost symbol in the RHS is equal to LHS. The leftmost symbol in the RHS is equal to LHS. Therefore, if the grammar is left recursive, then the operator will be left associative. You can take any operator and see. See, if you have even one more id plus id, one more plus id, then also it has to be evaluated this one first and this one first and then this one, which means it has to grow this way only, right? E plus id and then id. Therefore, in order to fix the first problem, what is the first problem? That we are not following the associativity. We have to define the grammar to be left recursive. Okay, and coming to the second problem, we want to see that when there are two different operators, the highest precedence operator should be at the least level, then only it will be evaluated first, because whatever is at the last level we are evaluating first and then coming up. Therefore, if we have to fix this problem of having different precedences, you define the grammar to be of different levels, which means if I have plus and star in the same grammar, I want to see that plus will be at the higher level and star will be at the next level, like this. If I have plus and star, if I write like this, E derives E plus T. E plus T means E is defined as left recursive, so that plus will be left associative, and then T derives T star F, which means star is nothing but left associative because T is, this production is defined as left recursive. And now so by having these two levels, what happens is if I have plus and star in expression, I don't have any other choice. I have to first derive the plus, then only go for star. Why? Because I have only this option, right? E derives E plus T and then T derives T star F. I don't have any other option here, isn't it? I cannot directly go to T without using this production. If I use this production, definitely I have kept plus. And once you have reached T, you can never reach plus. The reason is T can never generate a plus. Are we getting this? See, the reason is once you have reached T, this point, you can never reach any, you can never generate any star. Therefore, if we have many pluses in the expression additions, they will all be generated at the higher levels. Once you reach the level of star, you could again never generate plus. Now if I write like this, this grammar is right, but there is a small problem here. What if the grammar does not contain any plus at all? Therefore, to bypass the entire plus, if you directly want to go to star, I am going to write E plus T or T, and I am going to write T star F or F, and F derives ID. Why? Because a grammar might not contain any plus or a grammar might not contain any star. So understand this, I am writing every production to be left recursive because every operator here is left associative, and second thing is I am defining two levels in such a way that once I reach the second level, I will never generate plus. Or if I have to generate plus and star in the same expression, I will finish generating the pluses in the higher level and then go to the star in the next level. Okay, So in this particular example, if you have to generate id plus id star id, then what happens is e will derive e plus t, and then t will derive t star f. You will not get any other combination other than this. Therefore the grammar is unambiguous. So we have seen two rules. The grammar failed because it is not taking care of associativity and precedence. In order to define associativity, we are defining recursion. In order to define precedence, we are defining levels. Let us assume that we have one more operator, raised to the power of, which means 2 raised to the power 3 raised to the power 2, and this can be written as 2 raised to the power 3 raised to the power 2. If you are writing like this is actually right associative. The reason is, if I have such an expression, I have to evaluate 3 raised to the power 2 first and then 2 raised to the power 9 next. It is not like 2 raised to the power 3 and then this, which means it is right associative. If you want an operator to be right associative, then the tree should grow rightwards. That is the reason why for this, if I have to add one more operator, let us say f derives, I have to add raised to the power of. What is the recursion I should define here? The recursion we should define here is right recursion. Why? Because the operator is right associative. Therefore g raised to the power f or g. Yeah, see, if you see this grammar, if you have plus, star and raised to the power in the same expression, which one should get the highest precedence? Raised to the power of, which means which one should be generated last in the last level? It is raised to the power of, right? And then star and then plus. Therefore if I have plus, star and raised to the power of, first we'll generate all the pluses. The reason is, once we go to t and start generating star, there is no way we could go back to e and generate plus. Therefore this grammar ensures that all the plus will be generated first, and then all the stars will be generated first, and then all the raised to the power of. Therefore raised to the power of symbol will get the highest precedence, which means this symbol is going to be at the least level if you have an expression, and then star is going to be the second least and plus is going to be the closest. Therefore the operator which is closest to the start symbol will have the least precedence, and the operator which is farthest away from the start symbol will have the highest precedence, right? And if you observe this, I defined plus to be left recursive. Therefore plus is left associative and then star is left associative, but raised to the power is right associative. Exponentiation operation is right associative. So if I have more than one plus, the only way I could grow is to the left side. If I have more than one star, the only way I could grow is left side. If I have more than one raised to the power of, the only way I could grow is right side. Therefore all the operators have been set according to the associativity, one thing, and second thing is according to the precedence. So this grammar is perfect and it is unambiguous. We shall take some other grammars and see if we could apply the same thing or not. See the next example. If I have Boolean expressions, right? So a Boolean expression can be ORing of two Boolean expressions, a Boolean expression ORed with a Boolean expression, or a Boolean expression ANDed with a Boolean expression, or it is negation of a Boolean expression, which means whatever is the not, okay, or it can be simply true or false. Now see this, a Boolean expression can be ORing of two Boolean expressions, or ANDing of two Boolean expressions, or a not, negation of two Boolean expressions. Now there are three operators, OR, and not, and the terminals are true and false along with these operators, right? Now which one should get the highest precedence? Accordingly it should get, not should get the highest precedence, which means not should be defined at the least level. What is the next highest precedence? And what is next highest precedence? OR. What about the associativity of OR and they are left associative, right? Therefore the grammar has to be left recursive. What about this other one? There is no associativity because it is a unary operator, right? So For this grammar, if I have to disambiguate it, if I have to go for an ambiguous grammar for the same grammar, then I should write like this. A Boolean expression can be a Boolean expression or something f, and then f can be f and g or g, and g can be not g or true or false. By writing like this, first thing is we have followed the associativity rule, which is left associative. That is why we define it as left recursive. And second thing is we have followed the rule that the highest precedence operator should be farthest away from the start symbol. Since the start symbol is e, I am putting not at the farthest position, and then the lowest precedence should be closest to the start symbol. Therefore, this grammar is unambiguous. So let's see one more ambiguous grammar, and then try to convert it to unambiguous grammar. So the grammar is, we have just seen this. A regular expression can be sum of two regular expressions, or concatenation of two regular expressions, or clean closure of regular expressions, or A or B or C, right? So how are you going to convert it into unambiguous grammar is same rules. Which one should get highest precedence? Here highest precedence should be given to clean closure, next highest precedence should be given to concatenation, and next highest precedence should be given to union. Therefore, the least one is union. So I am going to write it like this: E derives E plus. So when I am changing the variables, the language doesn't change. Therefore, the variable names doesn't matter. Don't worry about it. Either R or E, nothing, no problem, right? And E derives E plus T or T. Why? Because the least precedence is union operation and it is left recursive because it is left associative. And then T derives TF or F, and then F derives F star or A or B or C. Okay, so that is how this grammar is again converted into unambiguous grammar. So let's see one more example. Now given a grammar, you can find out whether it is ambiguous or unambiguous, and if I give you any unambiguous grammar, you could even say the precedence rule. So let's say one example is this. It is one of the previous gate questions. One example is A derives $B, B derives B hash C, C derives C at the rate D or D, and then D derives small d. Okay, so in this what do you understand about the associativity and precedence of various operators? This dollar, star and at the rate are operators, and D is also a terminal. Okay, it is an operand. So small d is an operand, and dollar, hash and at the rate are operators. So if you look at this, the grammar is defined as left recursive. Therefore, dollar should be left associative, isn't it? And then again hash is defined as left recursive. Therefore, hash should be left associative. And at the rate is also defined as left recursive. Therefore, at the rate should be left associative, isn't it? Therefore, if I have in an expression $2 side by side in the sense there are some operands in middle. If I have $2 operators in an expression, which one should be evaluated first? According to this grammar, it is saying that if you have $2, left one should get highest precedence because it is left associative. Therefore, I am going to write like this. So this is just a notation to denote that left side star is having higher precedence than right side star. And if I have two hash symbols, then which is going to get the highest precedence? Since it is defined as the left recursive grammar, therefore it is left associative. Left one should get the higher precedence, right? And if I have 2 amp at the rates, which one should get the highest precedence? The left one, right? And now compare all the 3 operators once again. Which one is having the least precedence? Dollar is having the least precedence. Which one is having the next least precedence? Hash. Which one is having the next least precedence? At the rate. Therefore, in the order of precedence, the highest precedence will be given to at the rate, and the next highest precedence will be given to hash, and next highest precedence will be given to dollar. So this is how the operators are can be evaluated. Now one of the gate question is this. So given this grammar, given this grammar E derives E star F plus E, or F derives F minus F or ID. Tell me, what do you understand from this grammar, right? So from this grammar, one thing we could understand is the highest, the E plus and star are defined at the same level. See, this is not a different level unless you go to the next one, F. Plus and star at the same level. Therefore, according to the grammar, plus and star are having same precedence, and then minus is written at a further away level from the start symbol. Therefore, the highest precedence will be given to minus, right? So in this plus star and minus, the highest precedence is given to minus, and if you look at the associativity, E is defined as left associative, and then F is defined as left associative. Sorry, E is defined as star is defined as left associative, therefore it is left recursive. Okay, star is defined as left recursive, therefore it is left associative, and then here plus is defined as right associative, therefore it is right recursive, therefore it is right associative. And if you look at minus is defined in both left recursive as well as right recursive, therefore here the precedence is this associativity is undefined. The grammar is again ambiguous, but one thing you could note is star and plus both are having equal precedence, and then here star is defined as left recursive, therefore leftmost star will get the highest precedence, which means star is left associative, and plus is defined as right recursive, therefore plus is right associative, and minus is defined as both left recursive and right recursive, therefore we cannot say which one is higher. We can generate either in the right side or the left side, therefore it could either be left recursive or left associative or right associative. Okay. So in the previous grammars we have seen that in order to avoid ambiguity in some of the grammars, we introduced recursion. So recursion is like this. Recursion is of two types. Recursion can be left recursion, right recursion. Okay, left recursion is like this. If I have any production like this, A derives A alpha or beta, which means the leftmost symbol in the RHS is equal to LHS. The leftmost symbol in the RHS is equal to LHS. This is called recursion. Okay, and in fact it is called left recursion. If I have any symbol on the RHS which is equal to LHS, it is nothing but recursion. Why? A variable is calling itself. Therefore, that is also called as recursive calling. Now, if I have A derives alpha A or beta, it is also a recursion, but this recursion is right recursion. It is also a recursion, but the recursion is left recursion. So left recursion is if the leftmost symbol of the RHS is equal to LHS, then it is called left recursion. If the rightmost symbol of the RHS is equal to LHS, then it is called right recursion. Okay. So if I have left recursion, the problem is this: A derives A alpha, A alpha, A alpha. If you want to stop it anywhere, you are going to stop with beta, right? Or you can directly derive beta, right? Or you can derive 1 alpha, 1 A alpha, which means you can use it one time, 1 A alpha, and then alpha can derive beta, which means beta alpha. Only beta or beta alpha or beta followed by any number of alphas. Therefore, the language generated by this grammar is beta followed by alpha star, which means any number of alphas. Now the problem with this kind of left recursion is, if you see this, if you write it in terms of a function, A is going to call A without doing anything first, which means if you write it as a function, A is going to call A and then going to do some work alpha, isn't it? A is going to call A and then going to do some alpha. A is going to call A and then going to do some work alpha. If you consider that right recursion, it is different. A is going to do some work alpha and then call A. So if you consider these two, here it is going to fall in infinite loop. Left recursion is going to lead to infinite loop, but right recursion, this alpha is going to act as a condition checking, which means there is no way you can fall in infinite loop. The alpha is going to act as an anchor condition. It is going to stop you from following into it. Now if you consider this language, the language generated by this right recursive grammar is A is going to derive alpha A is going to derive alpha A, and whenever you want to stop it, you can stop it beta. Therefore the language is alpha star beta. You can either directly derive beta, which means directly beta, or it can be any number of alphas followed by a beta, which means alpha star followed by beta. If I use left recursive grammar, I am going to get this language, but then if I use a right recursive grammar, I am going to get a different language. Most of the compilers, most of them, compiler in the sense most of the parsers, they don't want, especially the top down parsers. There are two types of parsers, we shall see them later, but there is a class called top down parser. This top down parser, they don't allow a grammar, or they cannot work properly if the grammar is left recursive. Therefore we want to eliminate left recursion without changing the language. Let's eliminate the left recursion without changing the language generated by this. So this right recursion is not equal to this left recursive grammar. The reason is the language is changing. Now I want to have the same language, but I want to have a different grammar which is not left recursive and which is not this right recursive, right? So the language is, I want beta followed by alpha star. This is the language I want to generate. How can I generate this? Is S, or let us say A only. Variable A has to generate beta followed by alpha star. But if you see this, it is not left recursive, isn't it? Sorry, it is not a grammar at all. The reason is the grammar should not contain stars, right? Alpha star, anything like this. So I want to eliminate the this star and all. So what I do is, I want to generate this language. So A is going to generate beta followed by A dash, and now it is the responsibility of A dash to generate any number of alphas including 0 alpha. See, A is going to generate beta followed by A dash, and now it is the responsibility of A dash to generate any number of alphas including 0 number of alphas. Therefore A dash derives either 0 alphas, which means epsilon, or 1 alpha followed by any number of A dashes, isn't it? So it is a recursion. So which kind of recursion? Right recursion. So understand this. A derives beta followed by alpha star. That is what we wanted. So what I did is, A derives beta followed by A dash. Now A dash is going to derive either 0 number of alphas or any number of alphas. Therefore this is the right recursive grammar which is equivalent to left recursive grammar, this one. A derives alpha A or beta. This is the right recursive grammar which is equivalent to this left recursive grammar. Therefore in order to eliminate any left recursion, you have to follow these rules. Let's look at some examples where we have left recursion and we try to eliminate them. One example is this, we have already seen it. E derives E plus T or T, right? So if you look at it, the leftmost symbol of the RHS is equal to LHS, right? Now it is in the form of A derives A alpha or beta. A derives A alpha or beta. It is in the form of that. So what is A and what is alpha and what is beta? If you can identify it, you can directly substitute it here, isn't it? So in this one, A is nothing but E, and alpha is nothing but plus T, and beta is nothing but T, right? Therefore how can I convert it to this, eliminate the left recursion? See, A derives beta A dash, which means E derives beta, which is T E dash, right? And again A dash derives epsilon, which means E dash derives epsilon or alpha. What is alpha? Plus T E dash. Got it? So this is the equivalent grammar which is non-left recursive, which is right recursive, and which is equivalent to the original left recursive grammar. Whatever language is generated by this, the same language will be generated by this without getting into infinite loops. Therefore we have seen the left recursion and we eliminated it. Maybe we shall see 2-3 examples more. Just for the sake of practice, we shall see some examples. Eliminate left recursion from this grammar. Say the grammar is S derives S0, S1, yes or 0 1. I want to eliminate left recursion from that grammar. How could I eliminate it? Is there left recursion? Yes. What is left recursion? If the if the leftmost symbol in the RHS is equal to LHS, then it is called left recursion. Now you could imagine it this way. It is nothing but A is yes, A derives A, whatever is remaining is alpha, and the other production is beta, the other alternative, right? So you can substitute that in this formula. A is this, alpha, and then beta. Then if you want to convert it into eliminate the left recursion, you have to use this formula, right? You can remember it as a formula or you can derive it. My suggestion is don't by heart anything. So here if you substitute it, what you get is S derives beta A dash. What is beta? 0 1 S dash, right? And then S dash derives epsilon or alpha A dash. What is alpha? Alpha is 0 S 1 S dash. That is the elimination. Yes, let's eliminate some left recursion here. There is a left recursion in this grammar, right? So this is A. This production is fine. There is no left recursion. This production is fine. There is no left recursion. There is left recursion in this only this grammar. It is A derives A alpha or beta. Now what is alpha? Comma S. Beta is S dash. If I have the rule A derives A alpha or beta, in order to eliminate it, what is the conversion? A derives beta A dash, and then A dash derives alpha A dash or epsilon. This is the conversion, right? Now here alpha is comma S and then beta is S. Therefore I have to write L derives for this one beta is S L dash, and then L dash derives alpha is comma S L dash or epsilon. So these are the two productions which can be used to replace these two productions, and this is same. And coming to this grammar where you have more than one rule in the right hand side, right? More than one rule is having left recursion, and whatever is remaining after that I am naming it as alpha 1, alpha 2, alpha 3. So the main difference between this grammar and this grammar is we have only one left recursive rule. Here we have many left recursive productions. In this case, that is just extending the previous formula. This formula we are just extending. So we are going to write A derives beta 1 A dash for this production, or beta 2 A dash, or beta 3 A dash. How many ever betas we have, so on. And then A dash derives alpha 1 A dash for this one, alpha 2 A dash, alpha 3 A dash, so on. So that is how we can convert any grammar which is having more than one left recursive productions into right recursive grammars. Okay. So we have seen two classifications of grammars till now. One is ambiguous, unambiguous, and other is left recursive, right recursive. Yeah. So we have seen the grammars are of two types. One is ambiguous, unambiguous, and then we have seen the grammars are of two types. One is left recursive and then right recursive. See, we don't want ambiguous grammars because we are getting more than one parse tree. Therefore no parsers will really work for ambiguous grammars. So we want only unambiguous grammars. And then we don't want left recursive grammars because the top down parsers, they will fall in infinite loop. Why? The reason is, if I have A derives A alpha kind of production, A is going to call again A, right? Therefore it is going to follow infinite loop. So we are not going to use left recursive grammars. And one more classification of grammar is deterministic grammars and non-deterministic grammars. Okay. So what is deterministic and non-deterministic is, for example, if I have the grammar like this, A derives alpha beta 1, alpha beta 2, alpha beta 3. So A, capital A, on seeing alpha it might go to beta 1, on seeing beta it might go to beta 2. You can assume it that way. That is why it is called non-deterministic grammar. Non-deterministic grammar means we have many options on a single symbol. See, let us assume we have to derive alpha beta 3, right? And if you see the first symbol alpha, and if you see this production alpha beta 1, we might think that this is the right production in order to derive this word alpha beta 3. We might assume that this is the right production in order to derive this. So what we do is we use this alpha beta 1 and then we see beta 3. After seeing beta 3 and beta 1, we'll find out that it is not the right production. Therefore we have to backtrack again. So that is how the parser will fail. So if I have the second production, see, now I want to generate alpha and the second production is saying that I can generate alpha. Therefore if I use a derives alpha beta 2, then I'll be able to derive alpha, but later if I have to derive beta 3, it is deriving beta 2. Therefore at this point I'll know that I did a wrong thing, so I again go back. And again here also if I use the third production, A derives alpha beta 3, then also same thing happens. I'll see alpha first and then beta 3 first. Yes, now I'll accept it. Now the problem here is we are actually backtracking. This backtracking is happening because of the common prefixes. One or more productions on the right hand side are having something common in the prefixes. This is also called as common prefixes problem or non-deterministic grammars. The problem with non-deterministic grammars is there will be backtracking. If you observe this, why this backtracking has happened, the main reason is we are actually, the main reason is this. We are actually making a decision of which production to choose without seeing enough of the input. See, if the input is alpha beta 3, we are making the decision by only seeing alpha. We should have made the decision by seeing beta 3, right? So if you could see enough of the string which is beta 3 and then make a decision about which one to choose, then there would be no problem. Therefore I have to postpone the decision making process until I see beta 3. It is also called as left factoring procedure or eliminating non-determinism. So using left factoring is simple. Whatever is common prefix we have, we take it as common and write the remaining part as separately. So I can write it as like this: A derives alpha A dash and then A dash derives beta 1, beta 2, beta 3. If I write it this way, then what happens is, if I have to generate alpha beta 3, first I don't have any choice or I don't make any decision at this point by looking at alpha. By looking at alpha I have only one choice and I'll make it. A derives alpha A dash. I am not making any decision here. And then by looking at beta 3 at later point of time, I'll take the right decision, which is beta 3. So what has happened here is I postpone the decision making till the next part where I could see beta 3, right? So this is called non-deterministic grammar and this is the equivalent grammar which is deterministic. And the procedure whatever we used in order to convert a non-deterministic grammar to deterministic grammar is also called as left factoring. Okay, so what is the problem with non-deterministic grammar? Most of the top-down parsers will fail and will have to backtrack if we have non-deterministic grammar like this. So we don't want non-deterministic grammar, we don't want left recursive grammar, and we don't want ambiguous grammars. And we have seen how we could eliminate ambiguity by using disambiguating rules and how we could eliminate left recursion by converting it using that formula. And now we have seen how to convert a non-deterministic grammar to deterministic grammar using the procedure called left factoring. Okay, so let's see some examples on how to use this left factoring rule in order to convert deterministic to non-deterministic. Yeah, let's see this grammar. And is this grammar non-deterministic grammar? Yes, the reason is these two productions are having something in common, right? So at least you have I in common. In fact, this IETS and this IETS is entirely in common. So just see what this grammar is. This grammar is statement can be if expression then statement, or if expression then statement, else statement, or small a or small b. Which is nothing but if expression statement, right? So see, this small a is assignment statement Again, statement can be if expression then statement, or if expression then statement, else statement, or simply an assignment statement, and the expression can be any boolean expression. So that is the statement. Now if I have to generate the word, any word, you can take any word and then generate it, but before tell me whether it is deterministic or non-deterministic. It is definitely non-deterministic, right? So let us use left factoring and then convert it to deterministic grammar. If I use left factoring, S derives I, E, T, S, S dash, and then S dash derives, for this one it is epsilon, for the first rule it is epsilon, because whatever is there in the first rule we have written it, and S dash need not derive anything. And for the second one, IETS, the remaining part is ES, right? And since we are not doing anything with this A, leave A wherever it was with S, therefore we are leaving it at S. And then E derives small b. Small b is boolean expression, right? So now we have converted a deterministic grammar to non-deterministic grammar to deterministic grammar, and this method is called left factoring, right? Fine. And now my question is this: the original grammar, is it ambiguous or not? And then this grammar, is it ambiguous or not? How can you find out whether a grammar is ambiguous? Construct a string, take a string, and then see if you could get more than one parse tree. Let me take a string if expression then statement, else statement. So this is actually not a string, right? The reason is there are even variables here, right? If you look at it, there is a variable S, E, T, S. It is not actually string. There are variables also, which means it is a intermediate string which you get in the process of derivation. If I can show that for this intermediate string, if I can get more than one parse tree, we could just substitute in place of E and S some terminals, and we can see that for the resulting string we are getting two parse trees. Therefore no problem, we can even get two parse trees for this and prove that the grammar is ambiguous. Let's see whether the grammar is ambiguous or not. I am talking about the original grammar. S derives I, E, T, S. I am choosing the first one, and then this S derives I, E, T, S, E, S, right? So this is one parse tree, and let's see if you could get one more parse tree. S derives I, E, T, S, E, S, and then this S derives I, E, T, S. Yes, we got two parse trees, right? Therefore, for a given string, we got two parse trees from the original grammar. So we can say that the grammar is ambiguous. Now, after eliminating the non-determinism, which means after eliminating the common prefixes, we got a new grammar. Now my question is this: eliminating the non-determinism or left factoring procedure, will it eliminate ambiguity also? In the sense, is this grammar unambiguous? So if you have to find out, just take the same string and see how many parse trees we get. For this string, let me see how many parse trees I could get. S derives, one part is I, E, T, S, and S dash, and now this S derives I, E, T, S, S dash, and now this S can be ES and this S can be epsilon, right? Which means I got this one from here. And now I will use the same grammar and do one more parse tree. I'll just try. One more parse tree is I, E, T, S, S dash, and now this S dash, the second S dash is again I, E, T, S, S dash, and here I'll use ES here, and here I use epsilon, right? So we got again two parse trees. We got two parse trees for the original grammar for a given string, and we got two parse trees for the second grammar, which is non-deterministic grammar, for the same string. Therefore, what we can say is, from these two procedures, We can say that eliminating non-determinism or applying left factoring does not eliminate ambiguity. Therefore, ambiguity will always be there even if you convert a ambiguous grammar into deterministic grammar. So we know the reason for this ambiguity is not actually non-determinism. There is something else. If you observe why we got more than one parse tree here, it is nothing but this else is associated to this if, and this else is associated to this if, which means if I have more than one ifs in this statement, or if I have more ifs more than number of else's, then which if should I associate this else to? The general rule we follow is always else has to be associated to the closest if, which means this else has to be associated with this one. This else should not be associated to the farthest if. The reason why we failed here is, here we are getting two possibilities. One possibility is else is getting attached to the closest if, as well as else is getting attached to the farthest if. This is the problem. What is the root cause of the ambiguity? Ambiguity is not because of the non-determinism, right? So ambiguity is because of the inherent properties of the language. Now what we could do is we could change the grammar format using disambiguating rules, and then we could see that the grammar is again unambiguous. So this is a classic example which shows non-determinism actually cannot eliminate, determinism cannot eliminate ambiguity. Okay, let's eliminate non-determinism from these grammars. Is this grammar non-deterministic? Are there any common prefixes? Yes, the common prefix is like a minimum, and then you can even see that there are more common prefixes more than a. So my question is this: if I have some grammar like this, if I have some grammar like a derives a and then b derives ab, is this also a common prefix problem, or is this grammar a non-deterministic grammar? No, it is deterministic grammar. The reason is the non-determinism or common prefixes should be present for the same variable. They should not be present across various variables, right? So in this grammar, the problem we have is common prefixes. The reason is the common prefix is present for the same variable, which means more than one productions of the same variable are having a common prefix. Therefore the grammar is non-deterministic, right? So what is the maximum common prefix here? The maximum common prefix is as. So either you can take these two productions and then pull out as common, left factoring, or you could take these three productions and you can go pulling out a as common. Whatever you do, it is not a problem. You can follow any method, you are going to get the same answer, right? So let me say I want to pull the a first. So from the first three productions, from the first three productions I am pulling out a. You can go with any method. A followed by s dash. Now what should this s dash derive? S dash should derive ssbs or sasb or bb, and we are not doing anything with b, therefore leave b wherever it was, right? And what should s dash derive? S dash should derive ssbs or sasb or bb, right? Now is this grammar non-deterministic? No, we still have s as common prefix. Therefore do for one more step. If I eliminate s as common prefix, I could eliminate s as common prefix, which means s dash derives only in this place. S dash derives s followed by s double dash. Now what should s double dash do? Now s double dash should derive sbs or asb. Therefore if I replace these two productions with these two productions, right, then it is going to be fine. That is eliminating common prefixes. Let's see how to eliminate common prefix from this one, the next grammar. Is this grammar non-deterministic? Yes, it turns out that the grammar is non-deterministic. So what are the common prefixes here? Common prefix is either you can take b as the common prefix or bs as the common prefix in the three. So I am going to take bs as the common prefix in all three of them, or you could have even taken bss and bss as common prefix in the first two productions. I am going with taking bs as common prefix in all the three productions, right? So first I'll take out bs as common, then what do I get? S derives b s dash. Now what should s dash derive? S dash should derive for the first production the remaining part, second production remaining part, and the third production remaining part. Therefore s dash should derive for the first production what is the remaining part? S S. Or for the second production what is the remaining part? S B. Or for the third production what is the remaining part? B. Right? Then what about A? We didn't touch A. There is nothing to take out A as common. Therefore leave A wherever it was. Now I got this grammar. Is this grammar non-deterministic? No. It turns out that we still have, this is non-deterministic because it turns out that we still have common prefixes in these two productions. What are the common prefixes here? SA and SA, right? Therefore what I like to take out as common is SA in these two. So leave S production as it is, S derives BS S dash or A, leave it as it is, and in the second production S dash, take SA as common. If I take SA as common, then S double dash, and we are not doing anything with B, therefore leave B here. Now what should S double dash be? S double dash be, it should derive AS or it should derive SB. So therefore this grammar is the non-deterministic version, this grammar is the deterministic version for the given non-deterministic version. So you could have followed other method also. Instead of pulling out BS as common initially, you could have even pulled out BSS, and then again we could have done the second step, third step. However, the final grammar you are going to get is the same one, right? You could follow any method. Okay. Let us see the type of parsers. Parsers are also nothing but a syntax analyzer. So at the syntax analysis phase, we use the software parser. Parsers are basically of two types. One is top-down parser and other is bottom-up parser. And top-down parsers are again of two types. So coming to this point, various textbooks have various conventions and they follow various methods. And I am following this. Maybe in that book by Aho Ullman Ravisetti, the compiler's book, the Dragon book, they follow a different convention. You can follow anything, but I am following this. So top-down parsers are of two types. One is top-down parser with full backtracking and the top-down parser without full backtracking. So what do I mean by backtracking is we try to go and analyze all possibilities, and then if any of the possibility is wrong, again we go back and choose the next possibility. Okay. And top-down parsing without backtracking is we are going to generate the string exactly that is required. Okay. And bottom-up parsers. Bottom-up parsers are again of two types. One is operator precedence parser and other is LR parsers. Bottom-up parsers are also called as SR parsers. SR means shift reduce. What is shift is, if you use a stack, generally shift is pushing and reduce is popping. Okay. And there is operator precedence parser, which we'll talk about it, and there are LR parsers. And why it is called LR parsers is, L means we are scanning the string from left to right, and R means we are using the reverse of rightmost derivation. Okay. And LR parsers are of these four types. And coming to this top-down parsers without backtracking, one is called recursive descent. The name recursive descent is given because we are going to write recursive functions for every production, and the other is called non-recursive descent. Whatever it is, this LL1 is these two parsers. If you have to construct them, the mainly top-down parsers without backtracking, first of all, grammar should not have left recursion. So in order to construct this class of parsers, grammar should not have left recursion, and then the grammar should not have any kind of non-determinism, which means non-deterministic grammars are not allowed and left recursive grammars are not allowed. If you find any grammar which is having left recursion, you have to eliminate it, and if you find any grammar which is having non-determinism, you have to left factor it. Okay. So then any parser, if you have to construct it, you should not use any ambiguous grammars. Therefore ambiguous grammars are not allowed for any of these parsers except one parser, operator precedence parser. Operator precedence parser is the only parser which can even parse ambiguous grammars. Okay, so I'll tell you what is the basic difference between top down parser and bottom up parser by taking an example. Let's take this example of this grammar and then see what is the difference between top down parser and bottom up parser. Any parser, the main use of any parser is, given any string and given any grammar, it has to check whether this string can be generated from this grammar by using a parse tree. If we could construct a parse tree by using this grammar to generate this string, we can say that yes, this string is generated. And now there are two ways in which we could construct a parse tree. One way is I could start from the starting the start symbol and I could generate it like this. If I start from the start symbol and generate it, now the main decision is at every point what is the production I should choose. Let us say at this point there is no confusion, only way I have is use this production. Now at this point I could either use this production or this production, that is the choice I have to make. Okay, so I am making the choice of the first one. I am choosing the first production, and then A is going to B and B is going to D. Okay, so if you observe this, what we did is I started from the start symbol, and at every point I am making a decision about what is the next production I should be using, which means whether I should use this production or this production. Therefore the main decision coming to top down approach is starting from the start and going to the basic terminals. The main decisions that we have to make is at every point, at any point, if I have two productions, which one to choose. If I could make the decision, it is fine. Therefore the main decision making is what is the production I should choose for a variable, right? So that is why we need to be very deterministic in this. Next one is bottom up parsing. Bottom up parsing is I'll take the terminals and then I'll go to the root. For example, if the word is A, B, B, C, D, E, if this is the word, I'll start from the terminals and then I reach the top. So what is the terminal? A, B, B, C, D, right? So initially I'm going to convert this to B to A, and then I'm going to convert this to A, B, C to A. See, this is the production I'm using, right? And then I'm going to convert this D to B, and then I'm going to convert A, B, E, this entire thing to S. Therefore if you see the way I built it, I started from the terminals, the string, and then I reached the top, the start symbol. That is why it is called bottom up parser. Now coming to the bottom up parsers, the main decision I might have to make is, if I see any terminal, should I reduce it or not? When to reduce? Here what to use, which means if I have more than one alternative for a production, which alternative should I use? That is the main decision I have to take in top down parsing. And coming to bottom up parsing, if I have when I am just parsing it, when to reduce, right? So here the main task of bottom up parser is when to reduce, and the main problem with top down parser is what to use. If you have more than one production, what to use, right? And here if you have more than when to reduce and what is the production that I should use. So if we can solve these two problems, we can actually construct parsers. Then one more thing worth noting here is, if I look at the top down parsers, they work in such a way that they are following leftmost recursion, that leftmost derivation. The way which we used here is S will derive A, B, E, isn't it? The first production that I used is this, and in the parse tree the second production that I used is this A is replaced with ABC, which means A, capital A, small b, small c, capital B, small e. And again this A is replaced with B, A, B, B, C, B, E. And again this B is replaced with D. So if you look at this way, we did it exactly in the leftmost derivation manner, which means if I have more than one variable in the sentence, I am always going to expand the leftmost variable first and then going to the rightmost. Therefore top down parsers will also use leftmost derivation. Coming to bottom up parsers, let's see how this one is behaving. So first one I reduced is this B is reduced to A, and then ABC is reduced to this, and then D. So if you see this, it is a kind of bottom up parser is kind of as derives A, B, E. Okay, and now what is the right, let's see the rightmost derivation. In the rightmost derivation, what we get is A, this B is going to be expanded with D, DE, and again this A, B, C, D, and again this A, B, C, D. So this is nothing but rightmost derivation, right? So this is the leftmost derivation, this is the rightmost derivation, and now if you consider the way we have built this tree, the way which we have, using which we have parsed it, we are actually using a reverse of rightmost derivation, which means I have taken the string, in a reverse way. So reverse of rightmost derivation is like this. So I'll take the first thing that is reduced is this one, B is reduced to A, isn't it? And then ABC is reduced to B, A, B, C is reduced to A, and then D is reduced to D is reduced to B, D is reduced to B, and then A, B, C, E is reduced to S, right? So the way in which we build the bottom up parsers is in the reverse of rightmost derivation. The way in which we build the top down parsers is in the leftmost derivation. So top down parsers follow leftmost derivation, and the bottom up parsers follow rightmost derivation in a reverse order. It also called as reverse. The reason is we are not actually deriving the string from the start symbol, we are deriving the start symbol from the string. Therefore it is reverse process. Let's talk about LL1 parser first. So in LL1 parser, the name LL1 is given because the first L means we are scanning the input from left to right. That is the meaning of the first L, which means if I have input A, B, C, D, something like this, I'll scan it from here, from the leftmost symbol to the rightmost symbol. I will not scan it from the other side. And the second L means I am using leftmost derivation. So in the process of deriving the parse tree, we are going to use leftmost derivation. And this one means number of look aheads. Look ahead is nothing but how many symbols are you going to see when you want to make a decision. Generally in LL1 we are going to take only one symbol. So that is why the look ahead is 1. And if you look at any general parser, it is going to have all these components. First component is LL1 parser, which means the parsing algorithm, which will talk about what we should be doing, about what are the action that we should be taking, that is about the parser. And second is LL1 parsing table. Parsing table means it is a data structure which we shall construct using the given grammar. And then we shall use a stack. Stack is a data structure which is used for the procedure of parsing. And then there is input buffer. So inside the input buffer we'll have the input, and generally the bottom of the stack is having always $, and then the end of the string is always going to have $. These two dollars are used just to guess when we should stop. So the main thing is, if you have to construct a LL1 parser, you should construct the LL1 parsing table. How to construct the LL1 parsing table is, given a grammar, we should construct it. I'll just tell you how the procedure is. Before going to construct a LL1 parsing table, we should know two functions. One is first and other is follow. First is nothing but if I start with any symbol and generate all these strings from it. For example, if I have S derives, the production is A, B, C, D, something like this, a grammar, and then A derives small b, and then B derives small c, C derives small d, D derives small e. If I have a grammar like this, if I start from A and I try to derive all these strings, in all those strings what is the starting symbol, which means if I start with S and I start deriving all these symbols A, B, C, D, in all the strings that you get from this, what is the starting symbol? It is always going to be A. Therefore first of S is A. The reason is whatever strings you derive, always there is going to be A, and whatever happens after this, that is, you need not worry about it. The start symbol is always going to be A. If I start with capital A and derive all the possible strings, here I get only one possible string. What is the starting symbol in that? B. Therefore first of A is B. What about first of C, first of B? First of B is, if I start deriving everything, I am going to get only C. Therefore first of B is C, and first of C is D, first of D is E, right? So that is how you can find out the first. Let us say here, instead of this A, I don't have A and I have this production. S derives A, B, C, D. Now what is first of S? If I start deriving all the strings possible from S, I'll start like this. S derives A, B, C, D, right? And then now A is going to derive small b. So always whatever all the strings that are derived from this B, C, D, I don't care about it. Always S is going to derive the string starting with B. So in this example, first of S is B. In case if you don't have A, let us say I have epsilon here, B or epsilon. Now what is first of A? A can derive B or it can derive epsilon. Therefore first of A can be either B or epsilon. Now what is first of S? First of S is, if I start with S, I can derive A, B, C, D, and now A can derive either B. If that is the case, then first of S is B, or A can derive epsilon now. In case if A derives epsilon, which means this A will get vanished. Now S is going to start with B. Therefore first of S is C, right? So in case whenever you get any epsilon, you go and substitute in that position and then see what is the remaining string. From that string you have to find the first of it. So that is what is called first. So what is the definition of first is, if I have a variable or a string, from that variable if you try deriving all the strings, whatever is coming in the beginning, the first symbol, the first terminal is also called as first of that string. In this case, if I want to find out first of S, you have to derive all the strings from S, and whatever is in the beginning of those strings, that is called the first, right? And next one is follow. Follow means what is the terminal which could follow a variable in the process of derivation. Again, what is the terminal which can follow a variable in the process of derivation? For example, I am always going to start my derivation with S followed by $. The reason is, always input is followed by $. Always in the input, let us say if the input is A, B, C, D, always we are going to start with A, B, C, D, $. Input is always being followed by $. Therefore when we start the derivation, we always start it with $. At the end. So S is always followed by $. Follow of S is always $. And now let us say S is being derived with A, B, C, D. A, B, C, D. Now what is follow of D? Follow of D is $. Now let us assume that I am replacing B, capital B, or let us say capital C with D. If I replace capital C with D, then I am going to see B is followed by D. Therefore follow of B is D. So if you want to find out follow of a variable, you have to find out what are all the terminals that are following that variable in the process of derivation. But then it is going to be somewhat difficult in order to do this way. So one other way is, you need not actually derive the strings and see the follow. Instead of that, you could look at the productions. The reason is, every string is actually formed using the right hand side of the productions. Therefore you could see the right hand side of the productions and then guess what could be follow of what. Let us say the grammar is S derives A, B, C, D. Now what is the follow of S? Always remember, follow of start symbol is going to contain $. Yes, so follow of S is, one thing is we have $, follow of S is $, as well as if you see S in the right hand side of any production, then you have to consider that also. But then S is not present in the right hand side of any production, therefore you need not worry about it. For now, follow of S is $. What is follow of A? Follow of A is, see wherever the A is in the right hand side, A is here. Therefore there is a chance that when you are deriving a string, you are going to get A here and then followed by B, C, D. Therefore follow of A is nothing but first of BCD. Whatever this BCD derives, in that whatever is in the beginning, that is going to follow A. So what is first of BCD? First of BCD is nothing but first of B. What is first of B? First of B is C. Therefore follow of A is C. What about follow of B? Follow of B is first of CD. What is first of CD? First of CD is first of C. What is first of C? C derives D. Therefore follow of B is D. Right? And what about follow of C? Follow of C is whatever is first of D. Now what is first of D? First of D is E itself. Therefore follow of C is E. Now what about follow of D? There is nothing following D, right? If there is nothing following D, should I write epsilon? Remember this, follow will never contain epsilon. The reason is, if nothing is following a variable, obviously there will be a dollar, because we are always going to start the derivation with S dollar, isn't it? Since we are starting the derivation with this S dollar, if nothing is following a symbol, then definitely there will be dollar at the end. It doesn't mean that if there is nothing in the end, there will always be dollar, right? So there are some cases. If I have a production like this, see this, if I have production like A derives BC, right? Then what is follow of C? Follow of C need not be dollar. Follow of C is follow of A. The reason is, in the derivation process, let us say somewhere I got capital A, small a, BC, dollar. This is the string I got in the derivation procedure. Now we are going to replace A with this BC, right? If I replace this A with this BC, then what happens is, whatever was previously following A will now follow C. That is why if there is nothing at the right side of a variable in the right hand side, then always follow of that variable is follow of left hand side. The reason is, in the process of this expansion, we are going to expand it in such a way that the left hand side is going to be replaced with right hand side. Therefore whatever was following left hand side will now follow the rightmost symbol of the right hand side, right? So there are two exceptions. First thing is, in the first we get epsilon, and in follow we never get epsilon. If there is nothing to the right of a variable, it doesn't mean that we have to always write dollar. You have to check the left hand side, right? So I'll take some examples and then I'll explain you what is first and follow. Okay. Well, these are some of the grammars for which I would like to construct first and follow. Okay. So let us say this is the grammar, entire grammar. So this grammar is going to start like this. From the S and then this part. So there are 1, 2, 3, 4, 5, 6 productions. Now I want to find out what is first of S. Okay, I want to find out first, and then I want to even find out follow. Before finding follow, you have to always find the first. That way it will be easy. So now what is first of S? So first of S is nothing but anything that will start with A, isn't it? So in order to find out the first of S, I have to find out first of A. What is first of A? First of A is small, see, A is going to derive small a or epsilon. Therefore first of A is A or epsilon. What about first of B? B or epsilon. Why? Because it is generating B or epsilon. What about first of C? It is only generating small c, therefore it is simply C. What about first of D? First of D is D or epsilon. First of E is E or epsilon. Why? Because they are generating directly epsilon. So we are going to include epsilon only when it is being generated. Okay. Next, what about first of S? First of S is whatever is first of the right hand side. Now if I start generating something from S, the first one that is going to be useful is A. Therefore first of S is first of A. What is first of A? First of A is small a. Now epsilon, I don't write it here, epsilon I substitute it here. If I substitute epsilon over here, it is nothing but A is going to get vanished. If I substitute epsilon here, A is going to get vanished, right? So you are not going to see A. Then what is remaining? BCD. Then what is first of S? First of BCD, which is nothing but first of B. What is first of B? B comma epsilon. Therefore I write B here, and epsilon I don't write it here directly, I'll substitute epsilon here. Then B is going to be vanished. Then what is first of S? First of S is first of CDE. What is first of C? First of C is C. Therefore first of S is ABC, isn't it? I cannot pass through C because C is not generating epsilon. If C would have generated epsilon, we could have passed it. Next one is follow. What is follow of S? Always follow of start symbol is dollar. Dollar we are going to write it, and if you see dollar, S anywhere on the right hand side, then also we are going to write it. But then there is no dollar in the right hand side, so we need not worry about it. No S in the right hand side, we need not worry about it. Next one is what is first of A? Look at all the right hand sides and see if you find A anywhere. Yes, we find A in this first production here. Therefore follow of A is BCDE. Whatever is first of BCDE, that is nothing but follow of A. Therefore follow of A is first of B. What is first of B? Small b and epsilon. Write small b here and substitute epsilon here. If I substitute epsilon here, B is going to be vanished, and what is remaining? CDE. Therefore follow of A is first of CDE. What is first of CDE? C. Got it? Next, what about follow of B? Look at it. The follow of B is follow of CDE. First of CDE. Follow of B is first of CDE. Now what is first of CDE? First of CDE is first of C. Therefore we have to write C here. Next, what is follow of D? What is follow of C? Follow of C is first of DE. What is first of D? First of D is first of D, which means small d or epsilon. Now I am going to substitute epsilon here. If I substitute epsilon here, D is going to vanish, and what is remaining? E. Therefore follow of C is first of E. What is first of E? Small e, and epsilon I will again write it here, which means C is coming at the right end. Whenever any variable comes in the right end, and if you want to find the follow of it, you have to find the follow of left hand side. So follow of C is nothing but follow of S. The reason being D and E are generating epsilon, which means D and E are getting vanished. Therefore whatever is following S will now follow C. Therefore follow of C will even contain follow of S, which is dollar. What about follow of D? Follow of D is first of E. What is first of E? First of E is small e, and you take epsilon and write it here. Now follow of D is follow of S. What is follow of S? Dollar. What about follow of E? Follow of E is occurring at the right end. Therefore whatever is follow of S, that will be follow of E, which means dollar. See, we are not writing dollar directly. We are writing dollar because follow of E is equal to follow of S. Okay, so there are 2 points worth noting. Whenever a variable is at the right end of a production, at the right end, and if there is nothing after it, like this, if a variable is at the right end and if there is nothing after it, then follow of E is nothing but follow of left hand side. That is one thing. And second thing is, whenever a variable after which everything goes to epsilon, for example in follow of C, D and D are going to epsilon, right? In this case, this is what case? This case, in this case, D and E are both going to epsilon. Therefore C is coming to the right end. Either it is directly present at the right end, or somehow it comes to the right end because all these symbols are going to epsilon. Always follow of that symbol is equal to the follow of left hand side. Okay, so that is one grammar. Next, see this grammar. What about first of S? Instead of talking about first of S, let's talk about first of B. It is simple. What is first of B? First of B is, because of this production I get small a. Why? Because all these strings starting with this production are going to start with small a, and because of this production B can definitely derive epsilon. And what is first of epsilon? Epsilon. Therefore because of these two productions I got this. And coming to this, what about first symbol of C? Because of this production all the symbols are going to start with small c, all the strings. Therefore first of C is C, and since it is directly generating epsilon, first is also going to contain epsilon, right? And what about first of S? First of S is, because of this production we get first of S as first of B, which means A, and epsilon I am not going to write. Epsilon I am going to substitute it here. Whenever you get epsilon, you substitute there, which means B will get eliminated. Then what will be remaining? Small b. Therefore because of the first production BB, I got A comma B. And because of the second production, what about the first of S? If I would have chosen this production, then first of S is nothing but first of C. First of C is small c, and epsilon is substituted here. If you substitute epsilon here, we are going to get D. This is first symbol. And next, follow. What about follow of S? Follow of S is always, remember, start symbol is always dollar. Follow of start symbol is dollar. And see if S is occurring anywhere in the right hand side. I don't think that S is occurring anywhere in the right hand side, therefore only dollar. Now what about first of follow of B? Just see in the right hand side wherever B is occurring. It is occurring here. Therefore, what is follow of B? Follow of B is first of small b, which is nothing but small b. Why? Wherever capital B goes, small b follows, because it is going to come together as a package, right? Capital B, small b. And what about what about this symbol? Follow of B is nothing but follow of B, which is nothing but small b, so we don't get anything else. What about follow of C? Follow of C is first of this. See, only this is the point, and now C is being followed by D, therefore follow of C is D, and here also we are getting C again, and follow of C is again C. Got it? So this is how we calculate the first and follows. Let's look at this grammar. This grammar is very interesting. I mean, since it is very popular and it is being used as a running example in many of the textbooks. This grammar is nothing but T derives E plus T, or T derives T star F or F, from which left recursion is eliminated, right? So let's take first off, I want to find out what is the first of E. E is the start symbol, right? First of E is nothing but first of T, therefore I have to go to T. First of T is nothing but first of F, therefore I will go to F. So let me find out what are the easy productions, and I will find first of them first. So what is first of F? First of F is ID and open brace. What is first of T dash? First of T dash is one is star and other is epsilon. And what is first of E dash? First of E dash is one is plus and other is epsilon. Now what is first of T? First of T is first of F. What is first of F? First of F is ID comma epsilon. Therefore I am going to write ID and open brace. Now what is first of T? First of T is first of F. First of F is ID and open brace. Understood that? First of E is first of T. First of T is first of F. First of F is first of T is first of E is first of T, and then F, and then F. Because of F I got this. What about follow? Follow of E. Since E is the start symbol, we are always going to get dollar as the follow, and moreover, look at the occurrences of E in the right hand side. It is occurring here. Therefore, follow of E is going to contain close brace also. What about follow of E dash? Follow of E dash is, look at the occurrences of E dash. E dash is occurring here. Follow of, therefore, since it is occurring at the right end, therefore follow of E dash is nothing but follow of E. What is follow of E? Follow of E is dollar and close brace, and see if there is E dash anywhere. Nowhere, therefore leave it. And next one is, what is follow of T? Follow of T is, look at all the occurrences of T. It is occurring here. Follow of T is first of E dash. What is first of E dash? First of E dash is plus and epsilon. In place of epsilon, you don't write epsilon here because follow is never going to contain epsilon. Just substitute epsilon in this production. Then follow of T is follow of E, because it is completely at the right end. Whenever a variable comes to the right end of a production, always follow of that variable is follow of left hand side. Now what is follow of left hand side? Dollar and close brace. Okay, and see anywhere if it is occurring. Yes, here also it is coming. Follow of T is follow of E dash, first of E dash, and I know again we get the same thing. See anywhere if there is E dash, there is nowhere, so we can close it here. What about follow of T dash? Follow of T dash is follow of T, isn't it? Follow of T dash is follow of T. Where is it? Follow of T. Follow of T is plus dollar close brace. Follow of T dash is follow of T. Therefore, I got plus dollar T dash, and again T dash is here, and follow of T dash is follow of T dash again. Right? So this is we get only these three. And what about follow of F? See anywhere there is F. Yes, F is here. Follow of tf is first of t dash. What is first of t dash? First of t dash is star and epsilon. Don't write epsilon in the follow, substitute epsilon here. If I substitute epsilon here, follow of f is follow of t. What is follow of t? Follow of t is plus. So next one, let's see what is first and follow of this first. So what is first of s? Since s is the start symbol, first of s will always contain this is first, right? So let's see about all these reproductions. Let us see the easier ones first. It is directly easy to find out what is first of b. What is first of b? First of b is it is generating g as well as epsilon, therefore g comma epsilon, and first of c is it is generating h and then epsilon, therefore h and epsilon. What about first of a? First of a, because of this production I get first of a to be d because of the first production dA, and then first of a is first of bc, right? And what about first of bc? First of bc is first of b. First of b means g here, and write epsilon here, which means first of a is now first of c. Now what is first of c? H, and then write epsilon here, epsilon here. So therefore finally we are getting completely epsilon. Now a is able to generate epsilon also. How? When b and c go to epsilon, a is generating epsilon, therefore first is going to contain epsilon also. Now what about first of s? Because of this production a, c, b, I get first of s to be first of a. What is first of a? First of a is d, g, h and epsilon. Epsilon I substitute here. If I substitute epsilon here, I am going to get c. Now what is first of c? H comma epsilon. H is already there. Now if I substitute epsilon here, it is also going to vanish. Then what is that I am getting? B. Now follow of first of s is first of b. What is first of b? G. G is already there, and epsilon. See, a can go to epsilon, c can go to epsilon, b can go to epsilon. Therefore s can derive epsilon. That is why I am going to write epsilon in the first. Now because of this second production, what is first of s? First of s is first of c. What is first of c? H comma epsilon. Write h, which is already there, and epsilon you don't write it here, you substitute here. Then what do I get? Small b. Therefore first of s is small b because of this production. And what about this one? First of s is first of b. What is first of b? It is g comma epsilon. G is already there, and now you write, put epsilon here. If I put epsilon here, then it is going to be eliminated. Then what is remaining? Small a. I get small a. Okay. Now follow of yes. Always remember, follow of start symbol is dollar, and see if anywhere you can see s in the right hand side. There is no s in the right hand side, therefore dollar is the only symbol. Next one, follow of a. Follow of a is, see in the right hand side wherever a is occurring here. Therefore follow of a is first of cb. Now what is first of cb? First of cb is first of c, which is h, and substitute epsilon there. If I substitute epsilon there, first of b, therefore first of b is g, and again you substitute epsilon there. Now follow of a is nothing but follow of s. What is follow of s? Dollar. And that is the only occurrence of a, therefore you need not worry about other productions. Next one, what is follow of b? Follow of b is follow of s, isn't it? Because of this it is occurring at the end. Follow of b is follow of s. Then what is follow of s? Dollar. And follow of b is follow of s, and follow of b is small a. And here also there is b. Follow of b is first of c, and first of c is h, therefore h. And if I put epsilon here, follow of b is follow of a. What is follow of a? H, g and dollar. So g is not there, so therefore I am writing g. Now what about follow of c? Follow of c is, wherever c is there you have to just check it. Now c is here, therefore follow of c is first of b. What is first of b? Follow of c is first of b. What is first of b? Is g. First of b is g, and if I substitute epsilon here, follow of c is follow of s, which means it is dollar. And because of this c, follow of c is first of bb, which is nothing but b, and follow of C is here. Because of this, follow of C is follow of A. So whatever is there in the A, you can write it. H is missing, therefore H, and dollar is there, G is there, right? And then follow of C, they are the only things. Okay, in this grammar it is worth noting that, it is important that you note this is variable C, there is no terminal C, which means wherever you see C, that is capital C, which is a variable, and in this grammar this is variable C and this is terminal C, variable C and terminal C, this is also variable C. Okay, so depending on that we have seen all this. We shall see two more examples. Yeah, let's see this. Now I want to find out the first and follow for these symbols. Okay, so what is first of S? First of S is, because of this production we get small a. What is first of A? First of A is, because of this production I get small c, this is small c, not a variable, and then because of the second production, capital A is able to derive epsilon, which means empty string, so first is also going to get epsilon. Now what about first of B? Because of this production I get D, and because of this production I get epsilon, right? Fine. What is follow of S? Follow of S is nothing but, since it is a start symbol, it is always being followed by dollar. Now what is follow of capital A? Follow of capital A is first of BB. What is first of B? First of B is D, and even there is epsilon, you substitute epsilon here. If I substitute epsilon here, then what is follow of A? Follow of A is small b. Okay. Now what is follow of B? Follow of B is, in the right hand side you see B only at this point, therefore follow of B is small b. Coming to this grammar, what is follow first of S? First of S is A here, and what is, because of this production, right, A, and what is first of B? See, this is capital C, which is a variable, and this is small c, which is a terminal. What is follow first of capital B? It is small c. What is first of small capital C? It is small b or epsilon. Now what is first of D? First of D is first of E. What is first of E? First of E is G, and if I substitute epsilon here, first of D is first of F, first of F is F, and if I substitute epsilon here, then it is, both are going to be epsilon and epsilon, therefore I get even epsilon in D, therefore epsilon is added. Epsilon is added only in the worst case. What is the worst case? When the variable is actually deriving the epsilon, right? And what is first of what is follow of this one? What is first of E? First of E is G, and because of this I get epsilon. And what is first of F? First of F is F, and because of the second production I get epsilon 2. Fine. What is follow of S? Follow of S is dollar, and you don't see anywhere S occurring in the right hand side, therefore we don't get any more symbols. Now what about follow of capital B? Follow of capital B is first of DH. What is first of D? First of D is G, F, G, F, as well as epsilon. Epsilon I am going to put it here, therefore epsilon D is going to get eliminated and vanished, and what is remaining? H. Therefore follow of B is even H. Now what about follow of C? Follow of C is follow of B. So what is follow of B? G, F and H. Follow of C is follow of B. Yes, that is why I got 3, and there is nowhere else where C is occurring. What about follow of D? Follow of D is first of H, therefore H, and there is nowhere in the right hand side where D is occurring, therefore only that. What about follow of E? Follow of E is first of F. What is first of F? First of F is small f, and in place of F, if you substitute this epsilon, then this F is going to vanish, then follow of F is follow of D, then follow of D is again follow of D is only H. Alright, and there is nowhere in the right hand side where E is occurring. Next one is follow of F. Follow of F is follow of D, follow of D is H. Follow of F is follow of D, follow of D is H. So only one place F is occurring, therefore only we get this. In case if variable is not at all occurring in the right hand side, then what is follow? Nothing, because it will never in fact occur in the strings, therefore there will be nothing. So this is all about the first and follow examples. So we shall see an example of this grammar. Just now we have seen this grammar already, how to find out the first and follow for the same grammar. Now what is important is, why are we doing this first and follow? So previously we have seen that in order to construct LL1 parsing table, we need something called as LL1 parsing table itself for the LL1 parser, right? So if we have to construct the LL1 parsing table for the grammar, why are we constructing it? It is a top-down parser. The main purpose of top-down parser is, whenever I have two alternatives for a variable, I have to find out, I have to be sure about which production I should use. It depends. See, if I have this production plus TE dash, this production is used whenever I want to derive plus. That is why I want to find the first of it, isn't it? And this production is used whenever we don't want to use E dash at all. Whatever is following E, that can generate E. And whenever I have two alternatives, which one should I use? That depends on the first. See, if I have ID and E, whenever I see ID, I am going to use this production, and whenever I see open brace, I am going to use this production. Therefore, the main use of the top-down parsers is to find out what is the first generated by a symbol. So in this case, the table is going to look like this. What are the variables? Variables are going to be in the rows E, E dash, T, T dash, and F. These are all the variables. And what are the terminals? Terminals in this grammar are, one is ID, and one is plus, other is star, open brace, close brace, and I am also going to write dollar. Why am I writing dollar here is, there is a chance that we might see dollar in the string, because always the string, the input is going to be ending with dollar. Therefore, I am even going to see dollar in the input, and I might have to take some actions there. So now what does it mean is, if I am seeing at E in the derivation process, and if the symbol that I have to get is ID, what is the production that is apt? That is what I am going to write here. Whenever I see any variable, and if I have to generate a terminal, which production I should use? That depends on if the first of that production contains this variable, this terminal or not. For example, let us say this production E derives TE dash. Where should I place this one? In the E row. Why? Because we will use that production only when we see capital E in the derivation, isn't it? That is why we have to place this production in the E row. Under which column? That is nothing but first of TE dash. Why? Because whenever we want to generate first of TE dash, then only I am going to use this production. Now what is first of TE dash? First of TE dash is nothing but first of T. What is first of T? ID and open brace. Therefore, under ID and open brace, I am going to write this. E derives T, E dash, and then E derives T, E dash. What is the meaning of this? Whenever you are looking at E, if you have to derive ID, you go and use this symbol. Why? The first of T, E dash is generating this. See, I am not placing it in the first of E. I am not placing it in the first of E. I am placing it in the first of right hand side, because first of right hand side is going to generate the strings actually. The right hand side is going to generate the strings. So I am not going to see the first of left hand side, I am going to see the first of right hand side. Now let's look at this production, this one. Where are we going to place this? In the E dash row. Why? Because whenever we see E dash, I am going to choose this production. Under which column? See this? Now these are the columns. Okay. So where should I place this one is, whenever I am in E dash, I am seeing E dash, and whenever I want to generate first of this entire right hand side. What is first of this right hand side? It is plus. Therefore under plus I am going to place it, which means E dash derives plus T, E dash. So why did I write this? Because whenever you are seeing E dash, and if you have to generate plus, then go with this production. This is going to generate plus. Now what about the next one? E dash derives epsilon. Whenever you have epsilon, what is first of epsilon? Epsilon. Therefore you should place it under epsilon, but then we are not going to place it. The reason is, we are never going to see epsilon in the input. Always there is going to be dollar. So whenever you get epsilon productions, or if the first of right hand side is containing epsilon, then you are going to place this production even in the follow of left hand side. So what is follow of left hand side? What is follow of E dash? Follow of E dash is dollar and close brace, which means here E dash derives epsilon, and then E dash derives epsilon. So why are we placing it at the this follow is, let us say in the derivation procedure I got something like this. I got something like id e open brace and dollar E dash. Okay, now I want to see what I should use for E dash, whether I could use epsilon or not. I could use epsilon here, epsilon production, provided that the next symbol is in follow of E dash. If the next symbol is in follow of E dash, then I can use epsilon. It is nothing but can you vanish, can you make that variable vanish? You can make it vanish only if the right hand side, if the next symbol in the production is not, if the derivation is nothing but follow of that symbol, that variable. Okay, next one is T. Where are you going to place this next production? It has to be placed under T row because left hand side is T and in the first of ft dash. So we are going to place it under the T row and in the first of ft dash. What is first of ft dash? First of f. What is first of f? id and open brace. Therefore under id and open brace I am going to write T derives ft dash. Under id and open brace, T derives ft dash. Next, what about first of T dash? Sorry, this one. Where are you going to place this one? Under T dash row, because left hand side is T dash, and under the column star, which means I am going to place it as T dash derives star f T dash here. And what about this one? It has to be placed under follow of T dash because it is epsilon. All the epsilon productions have to be placed under follow of left hand side. What is follow of T dash? Follow of T dash is plus close brace and dollar. Follow of T dash is plus close brace and dollar, which means T dash derives epsilon plus close brace is T dash derives epsilon and dollar is T dash derives epsilon. What about this production? This production has to be placed under first of id, which is nothing but id. So here I have to place it f derives id. What about this production? Its production has to be placed in the f row and first of that, which is open brace, which means f derives open brace e. So this is called LL1 parsing table. So how did we construct it? Given a grammar, first find out the first and follow and take every production and place it in the left side row. So row should be the left hand side and the column should be first of right hand side. So take each production, place it in the left hand side row and the column always should be first of right hand side. And whenever you see epsilon in the first of right hand side, you place the production in the follow also. In case if I would have got epsilon in the this one first of T dash, I will have to place it in the follow of E also. So where should we place a production? That depends on what is the first of right hand side. If the first of right hand side is only terminals, directly place them there. If the first of right hand side contains epsilon, then place it even in the follow of left hand side. If the right hand side is simply epsilon, then place it only in the follow of left hand side. These are the rules. Now why did we do this all? What is the use of this entire table is in order to construct the parse tree. I'll tell you how the LL1 parser works. Till now we have seen the first, the follow and the construction of LL1 parsing table given a grammar. Now I am going to show you how we are going to use this parsing table in order to construct a parse tree. Okay. Yeah, let's see the next grammar. Next grammar is S derives S or epsilon. So this is a simple grammar. Using this I'll show you how to construct the table and then the parsing procedure. Maybe the previous example would have been too big that you wouldn't be able to follow. Let's see what are the variables here. Yes, what is the terminals? Open brace, close brace, and the one more terminal is dollar. Always you are going to write dollar. Now where are you going to place the first production? The first production. So what is this grammar? This grammar is going to generate all balanced parentheses, which means like this, all nested balanced parentheses. Okay. So if I had to place the first production, it has to be kept in the left side. So what is the left side? Yes, and it has to be placed in the first of right hand side. What is first of right hand side? Open brace. Therefore the first production has to be placed under this cell. What about the second production, epsilon? It has to be placed under follow of S. What is follow of S? Dollar and close brace according to this grammar. Therefore under close brace you are going to place this as well as under dollar. Okay, yes. So my doubt is every grammar ready to be used for LL1 parsing? Every grammar may not be able to be used. No, we may not be able to use every grammar for the LL1 parser. The reason is sometimes we might get multiple entries in a single cell. In this grammar we are getting only one entry in one cell, but then in some other cases we might get more than one entry in a single cell. In such cases the grammar is not feasible. So we shall see the example here. Let us say I want to generate this one. Okay, how does LL1 parser work is simply we are going to have a pointer which is going to see one symbol because it is LL1, and always bottom of the stack is dollar and top of the stack is the start symbol. What is the start symbol here? S. Now S on seeing open brace, S on seeing open brace, what is the production? The first production, which means the tree is going to start with open brace, S, and then close brace. So we are going to use this production. Therefore replace S with this right hand side so that the leftmost symbol will appear on the top, which means I am going to write it as close S open brace. Now top of the stack is open brace and input is open brace, therefore there is a match. Whatever you wanted to generate, you generated it. That is why pop of the stack and increment the input pointer, right? And now what is that we want close brace, and what is the symbol we are looking at? Yes, open brace, and what is the symbol we are looking at? Yes. Now S on open brace is again the same production, open brace, S, and close brace, which means S has to be open brace, S, and close brace, which means this S has to be open brace and then S and then close brace, so that open brace will appear on the top of the stack. Therefore close brace, S, and open brace will appear on the top of the stack. Now see this, open brace and open brace, there is a match. Therefore pop off the input symbol, pop off this open brace and increment the input pointer. I incremented it. Now S on close brace. What is S on close brace? See that production, S on close brace is simply epsilon. Therefore S on close brace is epsilon, which means pop it off. Close brace on close brace, there is a match, therefore pop it off and increment it. And again close brace on close brace, there is a match, pop it and increment it. Dollar on dollar, therefore it is accepted. You understood it? Or if you want to see one more example, you can trace it out. You can start with this. Always remember that LL1 parsing algorithm is going to start with dollar in the bottom of the stack and dollar at the end of the input. Whenever we see dollar, we can say that it is successful matching. Otherwise we are going to consult the table. Now the next question is every grammar, using every grammar we can construct LL1 parsing table? It turns out that for some of the grammars we will not be able to construct LL1 parsing table. The reason is we might get multiple entries. So what is the meaning of each entry here? When you see a variable and when you see a terminal, which production to use? If you can predict it so well, then only it is called predictive parser or top-down parser. But then if you have more than one entry here, there is a confusion about which one to use. Therefore such kind of grammars we may not be able to use it. Okay. Let's construct the LL1 parsing table for this grammar. You can look at, you can pause the video and have a look at it. The grammar is S derives A, B, 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 A, and then A derives epsilon and B derives epsilon. So for this grammar, if you look at it, the terminals, the variables are going to be S, A, B. Therefore rows in the LL1 parsing table are S, A, B, and the columns are terminals. What are the terminals? A, B, and dollar, right? So where should we place the first production? S derives A, B. It has to be placed under S row, this row. Under what column? Under first of the entire thing. So what is first of this entire thing? First of this entire thing is first of A. First of A is epsilon. If I put epsilon, I get small a. Therefore that production has to be placed under small a. Why? First of right hand side is simply small a. Then what about the second production? This one, where should I place it? In the first of right hand side. The first of this entire thing is first of B, and the first of B is small b. Therefore I am going to place it here. S derives B, 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 A. And what about this A derives epsilon? It has to be placed under follow of A. What is follow of A? Small b, which means A derives epsilon and A derives epsilon. And where should I place the next one? Third production in the left hand side is B, and in the follow of B. What is follow of B? Small a and small b. B derives epsilon and B derives epsilon. Therefore, in every entry we got only one production. In every cell we got only one production. Therefore, this grammar is LL1 and it could be constructed. But then there are some grammars for which LL1 parser cannot be constructed. The reason is the parsing table might contain more than 2 entries. So it is worth noting that any grammar which is left recursive cannot be used for LL1, and any grammar which is non-deterministic cannot be used for LL1. So you have to eliminate the left recursion if you want to use it for LL1, as well as you have to eliminate the non-determinism by using left factoring. And there are some other grammars which are not left recursive and which are deterministic, still they cannot be used for LL1 parsing table. The reason is we might get more than one entries. For example, if I have an entry like this, if I have a grammar like this, A derives alpha 1, A derive alpha 2, A derive alpha 3, so on, alpha n. Now all these productions have to be kept in the same row. What is the row? A, right? And let us say we have terminals A, B, C, D, so on. Now, if where should I place this alpha 1, A derives alpha 1? In this row only, in A row only, under one of these terminals, whichever is first of alpha 1. If whatever is first of alpha 1 happen to be first of alpha 2 also, then these two productions have to be placed in the same cell. That is the reason why we might not get LL1 parsing table for all the grammars. The reason is sometimes we might have to place two productions in the same cell if they are having the first same. If this grammar has to be LL1, then alpha 1, first of alpha 1, first of alpha 2, first of alpha 3, so on, first of alpha n, all of them have to be mutually exclusive. Mutually exclusive means there should not be any common part in the first of all this. Or are there any possibilities for which we might get more than one entry? Is if I have a grammar like this, A derives alpha or epsilon. These two productions have to be placed in the A row only. This production is going to be placed under first of alpha, and this production is going to be placed under follow of A. If in this case first of alpha and follow of A, they are having intersection, then both of them ought to be placed in the same row. Therefore, we might get non-LL1 grammars whenever we have whenever first of alpha 1, first of alpha 2, so on contains something in intersection, or if I have any grammar of this kind whenever first of alpha and follow of A are having intersection. Let us take some examples and see whether they are LL1 or not. Okay, now we shall test that. Let's see some more examples and check out whether they are LL1 or not, whether each grammar is LL1 or not. So when a grammar is not LL1 is if a left hand side, if a variable is having more than one alternative and more than one alternative wants to get into the same entry. So in this case I have three alternatives, right? So in case if any of the alternative wants to get into the same one, then it is not going to be the LL1, right? So what is this row in which you want to place this production? Under S row only. What is the column in which you want to place this one? Under first of this one. What is first of this? Small a. And what about this one? First of this entire thing is small b. And what about this one? We are going to place it under follow of S. What is follow of S? Both small a and small b and dollar. Therefore, already I am placing one production in A and one production in B, and the third production is going to be placed both in A and B. That is why this grammar is not LL1, and even the reason is it is ambiguous. Yes, it is not LL1, and moreover it is not ambiguous. Now let's see the next one. So whenever we have only one production in the right hand side, you need not check about it, because you can, even if you place this production in the entire row, no one is going to compete with this. Therefore, this has to be actually placed under S row and in the column of small a, but don't worry about it at all, because there is only one alternative, so there is not going to be more than one alternative because of this row. And in this row there could be a problem. See this, where are you going to place the first production? First production has to be placed under C column, A row. And where are you going to place the second production? Second production has to be placed under follow of A. What is follow of A? Follow of A is first of BB. What is first of BB? First of BB is D, because of this, and if I place epsilon here, B. Okay, so the first production has to be kept under C column, and the second production has to be kept under B and D columns. Fine. What about this one? This first production has to be kept under D column, and the second production has to be kept under follow of B. What is follow of B? Small b. Therefore, even though we have more than one alternative for a variable, all of them are going to be placed in a different cells. So this is LL1. This grammar is LL1. This grammar is not LL1. Let's see about this. Whenever we have more than one alternative, we have to think about it. When there is only one alternative, we need not think about it at all. Here we have more than one alternative, right? So where are you going to place the first alternative? In S row. And what is the column? Under small a. Therefore, first one has to be placed under S row and small a column. What about the second one? Under S row only, and the column is small a. Therefore, intersection is there. So it is not LL1. The reason is both of them are going into the same cell, right? And in fact, this grammar is also ambiguous. This grammar is also ambiguous. So you should understand that no ambiguous grammar is LL1. That is what you should understand. And coming to this one, there are two alternatives. Therefore, you have to check the first. Where are you going to place the first one? Under small a. Where are you going to place the second one? Under follow of S. What is follow of S? Dollar. Follow of S is 1 because of dollar, because it is the start symbol, and then follow of S is follow of C. Follow of C is follow of B, and follow of B is again follow of S, which is nothing but dollar, right? So there is no problem with these two productions, because one is going into A and other is going into dollar. What about the next one? This is going to be under B, because first of this one is B, and this one is follow of B. Follow of B is follow of S. Follow of S is dollar. And what about the third one? This one has to be placed under C, and this one has to be placed under follow of C. Follow of C is follow of B. Follow of B is follow of S. Follow of S is dollar. So there are no intersections at all. And one more thing you should understand it, you should never compare two productions which are having different left hand sides. You have to compare only two productions which are having same left hand side, because they are the ones which are going to go into the same row. If the productions are getting into the same row, then there is a chance that they might even get into the same column and there is a conflict. But here, when these left hand sides are different, you need not worry about it at all. Okay, there is only one production, so you need not. So this grammar is LL1, and in this case there is only one production. Don't worry about it. And here there are two productions, and this production is going to be placed under first of right hand side, which is A, and this production has to be placed under follow of A. What is follow of A? Follow of A is small b, and follow of A is follow of S. Follow of S is dollar. And what about this one? The first production has to be placed under small b, and second production has to be placed under follow of B. What is follow of B? Follow of B is follow of S. What is follow of S? Follow of S is dollar. So if you see them, they have arranged themselves beautifully without any conflict. Therefore, this grammar is LL1. And next one, coming to this grammar, the first production has to be placed under first of this right hand side, which is nothing but small a, and the second production has to be placed under follow of S. What is follow of S? First of A. What is first of A? It is C, as well as it is C and even more. First of C, follow of S is first of A, which is C, and then if you place epsilon here, follow of S is follow of S. Already follow of S is dollar, right? And what about the second one? This has to be placed under C, and this has to be placed under follow of S. What is follow of S? This has to be placed under follow of A. Follow of A is follow of S. What is follow of S? Follow of S is first of A. First of A is C. Okay, again slowly, see this. Where are you going to place this production? This production has to be placed under C. Yes, that is why I placed under C. And then it has to be even placed under, this second production has to be placed under follow of A. What is follow of A? Follow of A is follow of S. What is follow of S? Follow of S is first of A. What is first of A? It is going to be C. Therefore, I have to place it under C and C. The first production also in the S row and C column, and the second production is also under A row and C column. Therefore, there are multiple entries. This grammar is not LL1. Okay. And now this one, there is only one alternative. Don't worry about it. There are two alternatives. Just see. What about this one? We have to place it under first of BB. What is first of BB? One is small a because of this one, and if I place epsilon here, I get small b. And what about this one? It has to be first of CD. What is first of CD? One is small c, and if I place epsilon here I get D. Okay, so there is no problem with these two productions, both are being placed in different columns. Now what about this one? Where should I place this one? This one has to be placed under first of A, which means this one, and this one has to be placed under fall of B. What is fall of B? Fall of B is small b. Therefore there is no problem with these two productions, they are going into different cells. What about this one? This one has to be placed under first of C, which is nothing but C, and this one has to be placed under fall of C. What is fall of C? Small d. Got it? What about this one? This one has to be placed under small a, and this one has to be placed under fall of S. What is fall of S? Dollar. And what is fall of S? Fall of S is fall of A. Fall of A is small a. Check this. First one has to be, this production has to be placed under A, and this production also has to be placed under A. Therefore, there are multiple entries. This grammar is not LL1. Now check this one. Where are we going to place this first production? This first production has to be placed under I. What about the second production? Under A. Therefore, there is no intersection. There is no problem with the first two productions. Now, what about this production? This one has to be placed under E. The first production has to be placed under E, and the second production has to be placed under fall of S dash. What is fall of S dash? Fall of S dash is fall of S. What is fall of S? Fall of S is first of S dash. First of S dash is again E. Therefore, there are multiple entries, which means both of them are going into the same entry E. Again, listen to this. Where are we going to place this one? For first of E, that is why I am writing E. And where are we going to place the second one? It has to be placed under fall of S dash. What is fall of S dash? Fall of S dash is fall of S. What is fall of S? Fall of S is first of S dash. What is first of S dash? Again E. Therefore, this grammar is also not LL1. So we have seen that a grammar is not LL1 whenever we get multiple entries. We might get multiple entries in two cases. One case is if I have A derives alpha 1, alpha 2, alpha 3, and if any one of them are having same first, alpha 1 or alpha 2 or alpha 3, then it is not LL1. And the other case is if I have A derives alpha or epsilon, I find the first of alpha, and for this one fall of A. If first of alpha intersection fall of A is not 5, then also it is not LL1. Okay. Now let's talk about recursive descent parser. I have taken a small grammar, and the grammar is only three productions: E derives IE dash, E dash derives plus IE dash or epsilon. Only three productions are there. Just for the sake of simplicity, I have taken a small grammar. Now the problem is, how can I write a recursive descent parser? If you see, if you have remember that classification, recursive descent function is one of the top-down parsers. So it is a top-down parser, and the name recursive descent came from the fact that for every variable we are going to write a function. For example, for the variable E, I am going to write this function like this. Variable is E, and if look ahead equal to I, then I am going to match I and then call E dash, which means for this production E derives IE dash, this is the function, right? So how is this function written? Check this. E is the function name, and if look ahead equal to I, then I am going to match I and then call E dash. Okay, and L is nothing but look ahead. It is a global variable. L is look ahead, and it is actually L equal to get char, which means at every point L is going to take the next character. And for E dash, for this second production, E dash derives plus I E dash. The function is like this. First one is you have to check if the look ahead is plus and match with plus and then match with I and then again call E dash, which means this one. Okay, else return is for the third production. I am just simply returning nothing, right? So for these three productions I have written three functions, and writing the functions is called recursive descent parser. And next one is, there is a function called match. Match will do just this. If the input is equal to the required, if the input is equal to I, it is going to match, and if input is equal to plus and the input is equal to I, it is going to match. See this? Match is nothing but whenever the input matches with whatever I wanted, I am going to increment the look ahead. How can I increment the look ahead? Is by using the function get char. If I use the function get char, we are just incrementing the look ahead pointer. Otherwise, it is going to print error. I'll take an example and explain you. And main function is supposed to call everything. So main function is going to start with the initial variable e, and finally if the look ahead is dollar, then we are going to say successful. So you have to just remember one thing. Whatever the number of productions we have, we are going to write one function for every variable. For example, for the variable e, I have one function, and if for the variable e dash, I have one function. And if any variable is having more than one production, then I am going to have more than one if else cases, or I can even have switch cases. Here I have written if L equal to plus means I am taking the first production, else it is just returning means the second production. And then look at the function match. Now match char t, how am I matching t is, whenever the input is equal to whatever symbol I wanted, I am just matching it and then incrementing the pointer. I'll just take an example and see. So according to that grammar, I plus I dollar has to be generated, right? So let's see what happens. If you call main is the function in the recursion stack. See, here we don't use any special stack. The stack provided by operating system, which is recursion stack, is going to use, is going to be useful for passing the entire example. Now I am going to be in main, and main is going to call the first line. First line is what? There are three lines in this. First line is what? E. Therefore, one more stack record is going to be created, and that record is going to be for the function called e, which means we are starting the tree with e. Okay. Now we go to the function e, but then remember that after coming back we have to again start with line number 2. So in main I am again going to start with line number 2. So now I am in function e, this one, right? There are first line, second line, and then third line. Now what happens is we are going to see what if L equal to I, what is the look ahead here? Look ahead is going to start with first symbol. This is L here. L equal to I. If L equal to I, then match I and then call E dash, which means if whatever we wanted to see that is equal to whatever their I is, just match it. What is match going to do? Match is simply going to check this and increment the pointer, which means look ahead is going to be incremented, which means here I have taken the production I E dash, that is the meaning of it. Okay. And next one is it is going to call the function E dash. So E is going to call the function E dash, and after the function E dash returns, we are going to come to the fourth line. Fourth line means it is all over. Fourth line. Okay. Now we have to go to the function E dash. Yes, we are in the function E dash. Now check if L equal to plus. Yes, L equal to plus. Now we are looking at plus. Therefore we have to match plus and then I and then call E dash, which means I am taking this function plus I and E dash, which means this E dash is expanded to plus I and E dash. Okay. So in E dash, these are the lines 1, 2, 3, 4, 5, 6. Okay. So now we have seen that we are at line number plus and I have been matched, and now we are at line number 4 and it is again calling E dash. So after returning I have to come out, let us say line number 6, let us say line number 7, this E dash has to return, and now I am at the next E dash and I am looking at dollar, isn't it? So plus and I have been matched, the next look at symbol is dollar. Now I am looking at dollar and E dash. Therefore the calling is E dash. Is look ahead equal to plus? No, it has to go to else part. Therefore simply it is going to return. Everything is going to return, everything is going to be over. So finally in main, look ahead equal to dollar and it is successfully passed. So what has happened is we have written the functions for every variable, and then we are able to call the functions using the stack provided by operating system. It is also called as recursion stack. Therefore it is also a kind of mimicking the construction of parse tree. Even this particular parser, recursive descent parser, is also a top-down parser. That is why it started from the top and then it generated the entire string. Okay. Yeah, we shall talk about one of the bottom-up parsers. The first type is operator precedence parser. The reason why it is called operator precedence parser is it is mainly used to define the mathematical operators in the for the compiler. For example, before going for operator precedence parser, I want to talk about operator grammar. Okay, so operator grammar is this. A grammar which is used to generally define the mathematical operations is called operator grammar, with some restrictions on the grammar. For example, any two variables, see if I have E is a variable, expression can be sum of two expressions or product of two expressions or identifier. Now this grammar is operator grammar. The reason is no two variables are adjacent. So no two variables are adjacent and there are no epsilon productions. In case if I had this grammar, E derives E, A, E, and A derives plus and star. Both are actually same grammars, but then this is not operator grammar. The reason is two variables are adjacent to each other, right? So why do you think that this rule is given is that two variables should not be adjacent to each other is, in general, when you are writing any mathematical expression in C compiler, for example, I take the C language, we are never going to have two identifiers side by side, which means I don't have A into AB is not equal to A into B, isn't it? Always two variables are separated by a terminal. That is why we should see that no two variables will ever be side by side. So if you have to convert this grammar into operator grammar, then it is going to be E derives E plus E, which means I am just expanding A here, or E star E or ID. Okay, so this is operator grammar. And let's see one more example of whether the grammar is operator grammar or not. Let's see this example. S derives S, A, S or small a. A derives B, S, B or small b. This grammar is not operator grammar. The reason is two variables are adjacent. So if you have to make it to operator grammar, you just expand out what is A. If I expand out what A is, then I am going to get S derives, in place of capital A I am going to put this S, B, S, B, S, or I am going to put this small b, S, B, S, or small a. And what about capital A? Capital A is B, S, B, or small b. Therefore, in the resulting grammar, no two variables are adjacent to each other. So this is operator grammar. Okay. So taking the operator grammar, we are going to consider or construct a operator precedence parser. And one thing you have to note here is, even this grammar is operator grammar, but it is ambiguous, right? And there is no problem with this ambiguity also. Even though the grammar is ambiguous, operator precedence parser is the only parser which can parse some of the ambiguous grammars, and it can parse this ambiguous grammar. How it could parse is, it is going to construct something called as operator relation table. So using the operator relation table for this grammar, it is going to construct the operator, this is going to construct the parsing. So I'll show you how to construct the operator relation table for this grammar. So let's see this grammar. This is ambiguous grammar. Even though the grammar is ambiguous, operator precedence parser can construct the parsing, can do the parsing using something called as operator relation table. So for this grammar, the operation relation table is going to look like this. So what are the various operators? One is ID we have, and other is plus. I'm just writing the terminals, plus, and other is star and dollar. Dollar is always included. Okay, and I'm going to construct the table like this: ID plus star and dollar. So this is the table. Now in this table I am going to compare each operator, ID and ID, which means what if two IDs have to be compared? In general they will never be compared, right? The reason is two variables will never come side by side, therefore you need not compare them at all. What is ID and plus? So always ID will be given highest precedence. See, this entry is nothing but comparing ID with plus. If I have ID and if I have plus, what is the precedence among them? ID will be given highest precedence. Always remember this, identifier will be given the highest precedence compared to any other operator. Okay. And now what about this row? This row is plus is compared with ID, then plus is having less precedence. Star is compared with ID, star is having less precedence. Dollar is compared with ID, dollar is having less precedence. What about this entry? Plus is compared with plus. What does it mean is, if I have plus and plus, actually we don't have plus and plus side by side in the input, but it means that if you have two plus in the expression, what is the first plus that you will execute? Since plus is left associative, we are going to take the highest precedence for the left one. Therefore plus is greater than plus. It is worth noting, plus is greater than plus doesn't mean that one plus is having higher precedence than the other plus. It means that it is left associative. That is why we are going to give higher precedence to the left side plus. And this entry is plus is compared with star. If I compare plus with star, which one will have higher precedence? Star. And this entry is plus is compared with dollar. Always remember, dollar will have least precedence compared to any other operator. ID will have highest precedence compared to any other operator. Dollar will have least precedence compared to any other operator. Therefore dollar will have least precedence compared to plus. So plus is getting higher precedence. Now star and plus. See, these rows are in the left side and columns are in the right side. Now if I compare star and plus, star is going to get higher precedence. Next, star and star. If I compare star and star, star is having left associative, therefore leftmost star is getting higher precedence. And then star and dollar, star is getting higher precedence. Dollar and plus, dollar is always going to get lower precedence, and dollar is completely successful. So this is called operator relation table. Even though the grammar is ambiguous, we are able to construct the operator relation table in which we are able to define the precedence rules. That is why it is called operator precedence parser. The reason is, in the given grammar it doesn't talk about any precedence, but the table talks about precedence clearly. If you want to see the precedence in this table, star is getting the highest precedence compared to plus, and both plus and star are defined as left associative, which means left side plus and left side star are getting higher precedences. Okay. So this is also called as operator precedence table. Now using this operator precedence table, operator precedence parser will parse the input. Example, let us assume we want to parse ID plus ID star ID. We want to parse this, and the input is ending with dollar. So it is worth noting that this parser is bottom up parser, which means we start with the terminals and we go till the root. So first step is, there will be a stack. In the stack, bottom of the stack will be dollar, and there will be look ahead. So algorithm goes like this: whenever top of the stack is less than or equal to the look ahead, whenever the top of the stack and look ahead in the table is less than or equal to, then we are going to push it, and whenever we get greater than or equal to, we are going to pop it. That is the algorithm, right? It is also infix to postfix algorithm, the same one. So what is it? Whenever top of the stack is less than or equal to ID, we are going to push, and whenever it is greater, we are going to pop. Now see this, dollar and ID has to be compared. Dollar and ID, this row, this entry, right? When I compare dollar and ID, it is saying less than, which means I have to push. It is also called as shifting, right? Shifting means pushing, and then increment the input pointer. Now ID and E are compared. What about ID and E? ID and plus. ID and plus, when I compare, it is greater. So whenever you see greater, you have to pop. I am going to pop ID. whenever I pop it, it actually means we reduced it. We reduced id to e. We reduced id to e. That is what is happening in the parse tree. Next one is plus and dollar. If you see dollar and plus, it is again less than. Therefore, you have to push plus. Whenever it is less than, you have to push and increment the input pointer. Now id and plus, actually plus and id. Plus and id, it is again less, which means you have to push. I am going to push it and increment it. Now id and star. id and star, it is greater. Whenever the entry is greater, we have to pop, which means I am popping the next id, which is nothing but in the tree we are reducing id to e. Okay. Now plus and star, check it. Plus and star, it is greater. Okay, plus and star, it is lesser. Lesser means we have to push, which means I am pushing star and increment the input pointer. And next id and star and id. See this? Star on id, which means less. Less means we have to push id and increment the pointer. Now dollar and id. What is dollar and id? Dollar and id is less. Okay. Okay, you have to see id and dollar, not dollar and id, because we have to always see this top of the stack first and then the input, which means id and dollar, which is greater. Therefore, I have to pop id and dollar. See, this input, the top of the stack is equal to the row and input is equal to the column, which means if I have id on top of the stack and dollar in the input, I have to go to the table for the entry id comma dollar, not dollar comma id. Okay, so now since I am looking at id and dollar, now it is showing greater. So whenever it is greater, I have to pop. Popping means this is the reduction. So see what are getting popped first. First thing they are getting popped is IDs, because ID has the highest precedence, right? And next one is star and dollar. So what about star and dollar? Star and dollar greater than, which means it has to be popped, which means the first one which is getting popped is star. So star is having higher precedence, or it is getting evaluated first. And next one, plus and dollar. So what is plus and dollar? Again greater than, therefore it has to be popped. So this is how the parse tree is constructed. And now dollar and dollar, we are going to stop it. So if you look at the way we constructed the parse tree, it is also kind of bottom-up parsing, right? Isn't it? It is also kind of bottom-up parsing, because we started from the terminals and we went to the root. So what is the algorithm? So we are going to start with dollar on the bottom of the stack, and we are going to see some input symbols. Whenever input and dollar, whenever input and the top of the stack are compared, if top of the stack is less than or equal to the input, then we are going to push, and if top of the stack is greater than the input, we are going to pop. They are the rules we are going to use for this parsing. That is how the parsing algorithm is going to work. Maybe we shall take one more example and explain. Let us say what happens with id plus id plus id. Let's see what happens with id plus id plus id. If the input is id plus id plus id followed by dollar, and this is the stack, and the stack is containing dollar in the bottom. Now top of the stack is dollar and the input is id. Now dollar is compared with id. What is it? Dollar comma id is less, therefore I am going to push it. Whenever it is less, I am going to push, right? Which means id is being considered. Next, plus and id. So id and plus is greater. So if you see that id and plus, it is greater, therefore it is going to be popped, which means I am looking this, which means this is reduced to e. And now plus and dollar. So dollar and plus is less, therefore I am going to push it and increment it. Next is id and plus. So plus is less than id, therefore it is going to be pushed and incremented. Next one is id and plus. id is greater than plus, therefore it is going to be popped. So it is going to be popped. And next one, plus and plus. So leftmost plus is greater than rightmost plus. If you see this, plus and plus, the leftmost plus is greater than rightmost plus, therefore it is going to be popped off, which means this is going to be reduced to E before considering the next plus. Okay, next plus and dollar and plus, it is less, therefore I am going to push it and increment it. And now plus and ID is less, therefore I am going to push it and increment the pointer. Now dollar and ID, or ID and dollar. Now what is ID and dollar? ID and dollar is greater, ID is greater than dollar, therefore it is going to be popped off, which means it is reduced to E. Now plus and dollar, plus is greater than dollar, therefore it is again going to be popped off, therefore it is reduced to E. Dollar and dollar, we are going to accept it. Now if you look at the parse tree we got, the leftmost plus is evaluated first because of the rule that leftmost plus is having higher precedence than rightmost plus, and then the parse tree is constructed in this way. Only we get one parse tree. So even though the grammar is ambiguous, we are getting only one parse tree because of the precedence rules we defined here, right? So that is how we could that the parsing algorithm is going to work. So one disadvantage of using this operator relation table is, if I have 4 operators, then I got 16 cells, or the size of the table is 16. If I would have had 5 operators, the size of the table will be 25. If I have n operators, then the size of the table is order of n square, which means if I have n operators in the row and n operators in the column, so total size of the table is going to be order of. So the disadvantage of this operator relation table is number of entries. If I have 4 operators, we are getting 16. If I have 5 operators, we are going to get the size of the table as 25. And in general, if I have n operators, the size of the table is order of n square. Therefore this is the disadvantage. Now this operator relation table is having the disadvantage that the size of the table is going to be order of n square. So in order to decrease the size of the table, we go for operator function table. Okay, so operator function table is we are going to do something like this. For the rows I take the function f, and for the columns I take the function g. Okay, and now I'll try to construct a graph. So for every entry, for every operator, there is GID and there is FID. There is G plus and there is F plus. There is G star, F star, like this. So I'm going to construct a graph. Graph is going to look like this. So FID, GID, F star, G star, F plus, G plus, F dollar, G dollar. So for every symbol there, I am going to construct a node here. Okay. Now in this graph, using this graph, I am just going to see if there is a transition like this. If there is a greater than transition, then it is nothing but, you can think of it like this, it is a kind of arrow. So this arrow is going from FID to G plus. Where is it starting from? FID, and where is it going to G plus? Because of this value, I am going to write FID to G plus. Okay, and now look at this arrow, the second one. Because of this, it is going from FID to G star, FID to G star. And because of this entry, I am going from FID to G dollar. And because of this entry, I am going from, see, this value is, this is pointing that side, therefore you have to write it from GID to F plus, GID to F plus. Okay, why? Because the arrow is that side, so you can think of them as arrows which are starting from GID to F plus here. Now what about this one? This one is going from F plus to G plus, F plus to G plus. And what about this one? This one is going from G star to F plus, G star to F plus. And this one, if you look at this one is going from F plus to G dollar, F plus to G dollar. and this one is going from f gid to f star, gid to, where is f star, and this arrow is going from f star to g plus, and this entry is going from f star to g star, and this entry is going from f star to g dollar, okay, and this entry is from gid to f dollar, and this is from g plus to f dollar, right, and this is from g star to f dollar. So how did I fill out the entire graph? I have taken every entry here, and if there is a greater than symbol, then I am going to take it as this arrow, and if it is less than symbol, I am going to take it as this arrow, okay. If it is greater than symbol, always left side is f and right side is g, and left side is f and right side is g. So that is how I constructed it. Now after constructing the graph, I have to see in this graph that there are no cycles. If there is any cycle in the graph, you can stop the procedure and say that it is not possible to construct the function table. See, what is that I am trying to do is convert the relation table into function table. For that I have constructed the graph. Now the entire graph is going to contain few entries, right? So if I have to construct the relation table, the function table, I have to find out for every node what is the length of the longest path starting from that node. For example, I have to see what is the length of the longest path that is starting from FID. So if you see FID, length of the longest path is going to be like this. So FID, if the graph is containing any cycle, we cannot go further, we have to stop it there. Since the graph is not containing any cycle, which I have already checked, you too please check it, I am going to construct the longest path starting from FID. From FID, I can go to G star. From G star, I can go to, I think, F plus. From F plus, I can go to G plus. From G plus, I can go to F dollar. So you can find out all the possible paths from FID. Then I think you are going to get this as the longest one. 1, 2, 3, 4. 4 is the longest one. And GID. For GID, the longest path is from GID, I can go to F star. From F star, I can go to G star. From G star, I can go to F plus, and from F plus, I can go to G plus, and from G plus, I can go to F dollar, right? So after finding out for each of these, the longest paths, then you can construct the table, function table like this. Function table will look like this. F and G, what are the operators we have? ID, plus, star and dollar. Okay. Now what is the value for FID? FID is 1, 2, 3, 4. Is this the longest path? You can check. There are various paths possible, but then you can find out that this is the longest path we get. So the length of the longest path is 1, 2, 3, 4. I am going to write 4 here. And what about F plus? F plus is already there on the path. If this is the longest path, then definitely from F plus this would have been the longest path. Therefore it will be 2. And what about F star? F star is here. So longest path is 1, 2, 3, 4. What about F dollar? F dollar is there is nothing going out of it. There is no path going out of F dollar or G dollar. Therefore there will be simply zeros. What about GID? 1, 2, 3, 4, 5. Therefore I have to write 5. What about G plus? G plus is 1. What about G dollar? G star? 1, 2, 3. What about G plus? G dollar is 0. Now this is the function table for this relation table. Now what is the main advantage of this function table is it is it is representing the same information, but only difference is that the information here It is having the same information. If you can see it, the same information is being represented, but then the size of the function table is less compared to the size of the relation table. Okay, so what is the size of it? It is 2n. So relation table size is order of n square and the function table size is 2n. And now you can find the same information there. If I have to compare plus and plus, then how can I compare it? Then left side is always given f and right side is always given g. Now go and take the value of f plus and take the value of g plus. What is the value of f plus here? F plus is 2. And what is the value of g plus here? G plus is 1. Therefore, if you compare it, you can find out that f plus is greater than g plus, which means left side plus is having higher precedence. If I want to compare, let us say star and plus. If I have to compare this, left side you give f and right side you give g. So if I have to compare star and plus using the function table, left side you give f and right side you give g. And now go to the function table and see. It is f star is 4 and it is g plus is 1. So it is greater. Therefore star is greater than plus. If I have to compare star and star, then left side you give f and right side you give g, and go to the table and take the values. So what is left side? F is 4, f star is 4 and g plus is 1, right? Therefore left side is greater, which means left side plus is greater than right side plus. That is why star is left associative. So what is the main advantage of using this table is function table is lesser size compared to relation table, but it comes with a cost. In this one, if you see, even we are able to compare ID and ID. If I get ID and ID, I get that ID is having higher precedence than ID. But then if you look at the original table, there are blank entries. That is the disadvantage. One disadvantage of using the function table is, even though we have blank entries in the relation table, we get non-blank entries in function table. So what are blank entries generally? They are errors. Therefore error detecting capability of function table is less than error detecting capability of relation table. Anyway, generally we are using function table only. The reason is the size is going to be small. So if you take any C compiler, the number of operators we are going to have are nearly close to 100. Then 100 operators, 100 into 100 is nothing but 10,000. But then if you go for this table, it is just going to be 200 entries. That is why it is always better that you use function table, even though it is having some disadvantages. Okay, so we shall see one more example of how to convert it. Let's see this example, this grammar, and first tell me whether it is operator grammar or not. It turns out that the grammar is not operator grammar. The reason is S and R both are adjacent. So whenever two variables are adjacent to each other, definitely the grammar is not operator grammar. Now I have to convert the grammar into operator grammar. Before going to that, can you tell me what this grammar is? Can you just guess what the grammar is? What the grammar is saying? P is deriving SR or S, R is deriving BSR or BS, S is deriving WSBS or W. Just have a look at it. You can pause the video and look at it and tell me what does this grammar actually do. This grammar is, a paragraph can be a sentence, a paragraph can be only a single sentence or a sentence followed by any recursive number of sentences. And recursive number of sentences are blank followed by a sentence, or again recursive number of sentences, or simply a blank followed by a sentence, which means if you have one sentence, you can directly go with paragraph is sentence. If you have two sentences, you can go with paragraph is sentence followed by a recursive number of sentences, and this recursive number of sentences can be a blank followed by a sentence. And next one is, a sentence is word followed by a blank followed by a sentence or simply a word, which means a sentence can be simply one word or it can be a word followed by many number of sentences. And then a word is a letter followed by a word or simply a letter, and then the letter is simply an identifier. So that is what it is. The entire grammar is nothing but it is defining a paragraph. Now if you look at this, two variables are adjacent to each other. What does it mean? When two variables are adjacent to each other, it means that it is not a operator grammar, right? So let us convert this into operator grammar. The reason is, this is the problem, right? So let me call the first two productions as 1 and second two productions as 2. I want to substitute in place of R the second two productions and see if it is going to convert it into operator grammar. If I do that, then P is, yes, in place of R I am going to write this entire thing, B, S, R, yes, B, yes, or simply yes. Now again, even after substituting, I am getting SR. But then you can make an observation that a sentence followed by recursive number of sentences is nothing but a paragraph. That is why I could replace SR with P. So understand this. Even after substituting R into the first production, we are not going to get the entire operator grammar. Therefore, what I am doing is, I am just seeing the meaning of the SR. SR is nothing but sentence followed by recursive number of sentences, which is nothing but a paragraph. Therefore, in place of SR, even if I write it as P, then it is not going to be any problem. So, by writing this way, I have eliminated R completely, which means if you want one sentence, yes. If you want two sentences, yes. If you want more than two sentences, you can use P only. Therefore, P is recursively defining paragraph. You need not have one more variable R. Therefore, this production is not required now. Then what is the resulting grammar? Resulting grammar is, for the first two productions, I got three productions. And next one is, S derives W, sentence can be word followed by blank followed by sentence or words. And word can be letter followed by a word or simply a word, and letter has to be an ID. Okay, so I didn't do anything much. I just eliminated the two variables side by side and converted the grammar into operator grammar. Now this is the operator grammar. For this grammar, operator grammar, if I have to construct the operator relation table, so what does operator relation table contains? It will contain the operators only. What are the operators in this grammar? If you see the operators, one operator is ID, and other operator is star, and other operator is blank, and other operator is dollar. Similarly, one operator is ID, star, blank, and dollar. And we are going to write like this. Okay. Now, ID and ID, they are never compared. Now look at this, ID is defined at the last level, which means it must be having the highest precedence. So how do you know the precedence and associativity rules from a grammar? From the meaning of it, you can guess it, right? So generally there are two ways. If the grammar is ambiguous, you define it. If the grammar is not ambiguous, it is already defined, you just you have to get it out of it. Now ID is at the last level, therefore it is at the highest precedence. So ID is having highest precedence, then star, then blank, and obviously dollar is having the least precedence. And now see star and ID, again ID is having highest precedence. And now see star and star, see where star is. Star is in this production, and it is defined as right recursive. Since it is defined as right recursive, we can say that it is right associative. Therefore, if it is right associative, if I have two stars, then the rightmost star will get higher precedence. What is the meaning of right associative? If I have two stars, then the rightmost star will get highest precedence, which means star and star, right star has higher precedence. Next, star and blank. Look at the level at which star and blank are defined. Star is defined at the least level, therefore star has to get the highest precedence. Star and dollar. Look at the, obviously we know that dollar is least than anything else. Next one, B. B and ID. So ID is having highest precedence, and B and star, we have seen that star is having highest precedence compared to B, and B and B. What about blank and blank? It is defined here as well as it is defined here, right? So this is not a recursion. Wherever there is recursion, I am seeing it. It doesn't say anything. These two are going to say something. See this? Here it is defined as right recursive. Here also it is defined as right recursive. Therefore, it is nothing but right associative. Since it is right associative, rightmost B will get highest precedence than leftmost B. Obviously, we know that dollar is having least precedence. Dollar is having least, dollar is having least, dollar is having least, and dollar dollar we are not going to compare. So this is the operator relation table for the given grammar. What did we do? For the given grammar, we eliminated the converted the grammar into operator grammar, and for the operator grammar we have formed the operator relation table. In this grammar, it is clear about which one is having highest precedence and which one is having least precedence. That is why we are able to do it very easily. Okay. Yes, now let us see this table. This is the operator relation table, which is having 1, 2, 3, 4, 5 operators including dollar, and therefore the size of it is going to be 25. So what I want you to do is just do it as a practice. Convert this operator relation table into operator function table. You are supposed to get this one as answer. If this is the table, then the function table is this, relation table is that, function table is this. Now we can see directly, so there are some disadvantages here. Some operators are never compared in the relation table, which means whenever you end up in these empty cells, that is an error entry. But then if you look at the function table, it is showing that they are always compared, isn't it? So whatever operators are not compared, just see this entry. This entry says that A and no, close brace and A are never compared, which means if I have close brace and if I have A, according to relation table they are never compared. But then according to function table, what happens is we give F here and we give G here, and now we are going to see that F open brace is 2 and GA is 3. So because of this, both are compared, and it is even saying that the precedence is less. So that is the disadvantage of this function table. We have to take extra measures to see that whatever were not being compared there, we have to compare here, which means whatever were the empty cells here, we have to maintain a separate data structure which contains all the empty cells. We have to go into that data structure first, and if it is not empty, then only you have to use the table. Therefore there has to be one more level of error checking involved when you try to implement it. Okay, and one more thing you have to note here is there are two operators with the equal priority. Till now we didn't get anything like this. This is important. Okay, so open brace and close brace, if I get, both are having equal precedence, right? So in the graph, when you are talking about open brace and close brace which are having equal priority, when this priority, then even in the function table both are getting equal numbers. See, open brace and close brace, F and then G, which means F open brace and G close brace should get the same one. F open brace is 0 and G close brace is 0. Both are getting the same precedence, right? So how can I ensure that both will get the same precedence is, in the graph, generally we are going to have F open brace as a node and G close brace as a node. But then what you should do is you merge these two, and then you get F open brace and then G close brace in one node, in one single node. By doing something like this, you can say that both are, you can ensure that both will get the same values. So that is what you should do when you are trying to construct the graph. For all the other nodes, keep the F and G separately. For this one only, F open brace and G close brace should be in a single node. Therefore they will get the same values in the table. So you please construct this, convert the relation table into function table as an exercise, and you should get this one as the answer. Okay. Yes, now let's see the LR parsers. LR parsers are of 4 types here. So one is, LR parser is also one type of bottom-up parsing, right? So we have seen various parsers, top-down as over, LL1 and recursive descent are top-down parsers, and then we are seeing this bottom-up parsers. In bottom-up parser, operator precedence parser is a bottom-up parser, and then the other class of bottom-up parsers are LR parsers, and there are 4 types: LR0, SLR1, LALR1 and CLR1. So this is in the ascending order of their pass. So least powerful is LR0 and the most powerful is CLR1. And now how does this LR parser work is, LR parser is a algorithm, okay, and now this algorithm requires, one is input stack and other is LR passing table and other is input buffer. So it is same as the bottom up parser LL1. In LL1 what was the passing table? It was LL1 passing table, right? In LR what is the passing table? It is LR passing table. So for all the 4 parsers this is same, the parsing algorithm is same, input will be given in buffer and everything is going to have stack, and only difference among all these parsers is how you construct the parsing table. Only change in all the parsers is the passing table. Other than this, everything is same. The construction of parsing table is going to vary. In order to construct the parsing table of LR0 and SLR1, we use something called as canonical collection of LR0 items. LR0 items will be used in order to construct the LR0 and SLR1 parsers. And in order to construct LALR1 and CLR1 parsing tables, we are going to use canonical collection of LR1 items. Okay, so this is what, try to understand it. First thing is, in order to construct all of the parsers, we need parsing table, but the parsing algorithm is same and everything else is same. Only difference is the construction of parsing table, and that too, in construction of parsing table we are going to use LR0 items here and LR1 items here. Now let's see what is an item and what is LR0 item and what is LR1 item. I'll construct the simplest parser, which is LR0 parser first, and then I show you how to use the LR0 items to construct it, and then I'll even show you what is the parsing algorithm and how is it implemented. Just for this example, I'll show you what is the parsing algorithm, and it is going to be same. Only thing that is going to vary is parsing table. Okay, let's see one example now. I'll take this example, S derives A derives A or B, simple example, and I'll show you how to construct the LR0 parsing table, the simplest one, right? So like LL1 parsing table, in LL1 parsing table we have seen first and follow, right? Similarly, in LR0 parsing table or any LR parsing table, we have closure and go to. Like first and follow, we use closure and go to. As with this example, and I'll explain you. So first one is, whenever any given grammar is given, you add one more production to the grammar. This is actual grammar. To this grammar I am going to add one more production, S dash derives S. This is called augmented grammar. This is called augmented grammar because one more production is added, right? So first step is, you take S dash derives S. So before that I'll tell you what an item is. So I told you that we are going to use something called as items, and in this case we are going to use LR0 items. Item is any production, let us say any production like this, with a dot in the right hand side is called item or LR0 item. So which means, this means that in the right hand side we have not seen anything, and this means that in the right hand side I have seen A, and this means that in the right hand side I have seen everything. So why do we need it, or what is the importance of it is, the main decision we should make in terms of this bottom up parsers is, when should we reduce a string to the left hand side. So when are we going to reduce a string to the left hand side, we perform a reduction operation. Reduce is nothing but A is reduced to S. If I see AA in the input, it has to be reduced to S. This is reduction, right? So when do we reduce it? Whenever we have seen the entire thing of the right hand side. Therefore, whenever you see completely the right hand side, then we should reduce it. In order to remember that we have seen everything in the right hand side, I am going to use this production, right? So S derives AA is the production. The reason is I have seen everything in the right hand side. Now these LR0 items are going to be helpful whenever you want to know that till what part we have seen the input and whether it is the right time to reduce it or not. So now first thing is, S dash derives dot S. This is the starting point. Now I have taken the LR0 item for the first production. Now I apply the closure. This is called the starting production, and with dot I am going to apply the closure. Closure is nothing but whenever there is a dot to the left of a variable, you have to add all the productions of that variable with dot in the beginning. See, there is a dot to the left of the variable, so closure includes S derives dot AA, and again there is a dot to the left of A. Therefore I have to again add the remaining productions, A derives dot AA or dot B. It means that whenever you see a dot to the left of a variable, you are going to add all the productions with dot in the beginning. Can I add any more productions? No, because there is a dot to the left of the terminals. Therefore you can stop here. This is the closure of S derives dot S. This is the closure of it. Now after that we have to do go to. Go to means it is simply like a DFA. So on this state, if there is any dot somewhere, if I move the dot over the next symbol, which means if I move this dot over the next symbol, what do I get? I get S dash derives S dot. I am just moving the dot right of it, isn't it? Now if I look at this one, if I move the dot to left of A, to the right of A, the dot is to the left of A, I am moving it to the right of A. It is also called as goto. This is a canonical collection of LR0 items, and now I am just moving it. S derives A dot A. Now you have to apply closure whenever you apply goto. Now this goto is over, now you apply the closure. If I apply the closure, I get all the A productions with dot in the beginning. So what are all the A productions? A derives dot AA or dot B. Why did I add these two productions? Because there is a dot to the beginning of A. Okay, that is why I got this. I don't get any more productions. Now what are the other transitions or what are the other go-to items I have? On small a, you can again go to one more state. On small a, where do you go? A derives small a dot A, which is nothing but I am moving a dot from the left of small a to the right of small a. Okay, and now we have to apply the closure. If I apply the closure to this, what I get is A derives, if I am applying the closure, A derives dot AA or dot B. Why did I get these two productions? Because of this dot B before capital A, right? And then B. On B I get A derives B dot. So what is the importance of this production is? It is also called as final item. Whenever dot is to the right hand side, rightmost side, it is also called as final item. Okay, now this one is complete. On S we have shown what happens. On capital A, on small b, everything is complete. This one is complete. The reason is dot is at the right end, we cannot move it further, and this one is not complete. The reason is dot is here, we can move it still. So on capital A, what happens is S derives A dot. This is a final item. And here on small a, what happens is, if you see it on small a, we are going to get the same state. Capital A derives small a dot capital A, and then capital A derives A dot B, which means on small a we are going to get the same one, right? And on small b we are going to get the same one, isn't it? So now see if everything is over or not. So what about this particular state? In this particular state, we have seen what happens on capital A, we have shown what happens on small a, we have shown what happens on small b, and on this one we have seen what happens on small a. Oh, we didn't see this, right? So on small a it is going to produce the same state, and on capital A it is going to produce a different state. What is it? A derives A dot, and on small b it is going to the same state, this one. Got it? So now we have shown what happens on capital A, and we have shown what happens on small a, and we have shown what happens on small b, right? Now I'll show you after this. This is called canonical collection of LR0 items. What did I do? I taken the grammar and then I added a new production, and then I started with that augmented production with dot in the beginning, and I applied the closure, and then I found out the transitions, which are also called as go to moves, and then again closure. Go to and closure, go to and closure, go to and closure. From every state again go to and closure, right? So I have found out that I got all these states, and some of these states are containing final items. What is the final item? Any item with dot at the ending is called final item. What is the importance of final item is, it specifies that we have seen everything in the right hand side, and therefore you can reduce AA to S now. We are scanning the input, and now with some part we have seen the entire thing of right hand side, and it is the time that you reduce it, right? So now this is called canonical collection of LR0 items. Using this I am going to construct the LR0 parsing table. Okay, so just name the states once. This state can be, for the sake of identification, I am just naming it. You can name any names here. I am calling it as I0, I1, I2, I3, I4, I5, I6. So there are totally 7 states, I0 to I6. Therefore now I am going to construct the parsing table for this. Let's construct the LR0 parsing table for this canonical collection of LR0 items. Okay, this is also called as canonical collection of LR0 items. LR0 item is nothing but any production with dot in the beginning. Okay, so now first thing is you have to see the number of states there, number of states in the canonical collection. So we have I0 to I6, which means 7 states. Therefore I am writing 0, 1, 2, 3, 4, 5, 6. So they are all total 7 states. Okay, and now the table will have two parts. One is called action part, another is called go to part. The LR parsing table will always contain two parts. Either it is LR0, SLR1, LLR1 or CLR1. They will all contain two parts. Now action part will contain only terminals. What are the terminals in the grammar? Terminals are A, B and $. These are the only terminals. And what are the go to part is? In go to part we have all the variables. What are the variables in the grammar? We have a variables as A and S. These are the two variables. Okay, now I have to fill all the entries of all the states. Now go to the state I0. In I0 on capital S it is going to 1. So whenever you have a transition on variables you have to go to part. So I0 on S is going to I1. Therefore I am going to write it as 1. I0 on S is going to 1 and on capital A it is going to 2. Therefore I0 on capital A is going to 2 and I0 on small a is going to I3. So whenever there is a move on terminals, I am going to write it as I0 on small a is going to I3. Therefore I am going to write it as S3, which is nothing but shift 3. I'll tell you what the meaning of it is. These are the conventions. Next one is I0 on small b is going to 4, I4. Therefore I am going to write it as S4. So we have 4 transitions and we have 4 entries here. 2 entries are in action part and 2 entries are in go to part. Next one, let's see I2. I2 on capital A is going to 5. I2 on capital A is going to 5 and I2 on small a is going to 3, which means S3, and I2 on small b is going to 4, which means S4, and that is it. We have only 3 transitions on capital A, small a and small b. Next I3. I3 on small a is going to itself, which means S3, and I3 on small b is going to I4, which means S4, and I3 on capital A is going to 6. I3 on capital A is going to 6. Okay, and now we have 4, 5, 6. So this is common for all the parsers. For all the parsing tables, action part and go to part is common. Only thing which is different is whenever any state is having final item, then the entries are going to be different. Now just see the state I1. The state I1 has final item which is corresponding to the augmented production. Therefore only this is the exception which is used for accepting. Remember it, whenever you get the final production or the final item of the production which is augmented, we have to understand that is a special production which is added because we want to accept it, so we are going to accept it, right? Or the meaning of this is, it also shows that we have seen everything of the start symbol. We started from the terminals and then we reached the start symbol, therefore we have seen everything. Maybe that is also a valid explanation why we had to write accept there. Next one is, let's see I4, I5, I6. All the I4, I5, I6, I5, I4 and I6, all these states are containing the final items. Final item is any production with a dot in the right hand side, with the dot in the right end, rightmost part. Now all these final items are corresponding to some productions, right? So let us number the productions. Let us say this production number is 1, this production number is 2, and this production number is 3. Therefore first production is S derives AA, second production is S derives small, capital A derives small aa, and capital A derives small b is third production. Now see the state I4. If you see the state I4, it is containing a final item A derives B dot, and what is the production corresponding to this? The production is third production, production number 3. Therefore for this one, the third production, I am going to write it as R3. So in the construction of LR0 parsing table, whenever any state is having a final item, in that particular row I am going to write reduce move completely, which means here I am going to write reduce move as R3. R3, R3, R3. Why should we reduce this? Because we have seen everything in the right hand side of a state, right hand side of a production. Now we could reduce B to capital A, that is the meaning. And next one is, if you see I5, it is also a final item and it corresponds to a reduced move. What is the reduced move? AA is reduced to S. Therefore what is the production number? Production number is 1. So I am going to write R1 in the entire fifth row. And next one is sixth. In the sixth state, what is the production? A derives AA. It is R2. I am going to write R2. So understand this. How we did it is, we have constructed the canonical collection of LR0 items, and after constructing the canonical collection of LR0 items, we actually considered all the states, and we have constructed the table in which the number of rows is equal to number of states in this diagram. And then every shift move is nothing but whenever there is a state, and if that state is going to some other state on a terminal, that corresponds to a shift move. And if a state goes to some other state on a variable, that corresponds to go to move. Okay, and whenever you come across this production, the production is augmented production, and you have to remember that production is being added by us, therefore that corresponds to the accept move. And whenever you come to any state in which there is a final item, you have to write reduce moves of the corresponding production. For example, the production number of AA is 2, therefore in I6 I am going to write R2. So remember this, whenever a state is containing a final item, you have to write the corresponding reduce move in the entire row, in case of LR0 parsing table. This is also called as LR0 parsing table. Now I'll take an example and then I'll show you how we shall use this parsing table in order to parse an example. Okay. Let's take an example. For this grammar, if the input is given as AABB, which can be generated from this grammar, let us see how this parser, that parsing table, is going to be used in order to generate or in order to verify whether this string is generated by this grammar or not. Always the input is followed by $, and first symbol I am looking at is small a. Okay, so we are going to have a stack. Let's say this is the stack, and you have to follow this example very carefully. First thing is, always top of the stack will contain a state, and the first state I am considering is 0 because that is the starting state. Now I'll be in 0 and I'll see A. So 0 on small a is shift 3, which means shift the A and then 3. Shift means this, whatever input you are looking at, you shift it onto the stack, as well as you shift the state number onto the top of the stack and increment the input pointer. Now top of the stack is 3 and you are looking at small a. Now whenever you see again small a on 3, so 3 on small a is again shift 3, which means shift a and then 3. Whenever you shift it, you have to increment it. What is happening is, here we are just remembering that we have seen a and we have seen one more a, and I didn't get any chance to reduce it, therefore you just remember them. That is why I am just remembering them in the stack. And now top of the stack is 3 and the input is B. So 3 on B. 3 on B is S4. S4 means shift 4. Shift whatever is the symbol B and then you shift 4. Okay. And now next I am at 4, which means the state is 4 and I am looking at B. Now the state is 4 and I am looking at B. Then it is saying that reduce with production number 3. What is production number 3? Production number 3 is A derives B. So I had to use the production number 3 in order to reduce whatever I have seen now. So how to do that is, they are saying that you are seeing this B and now you have seen reduce 3. It is actually reducing the previous B. One thing you have to note is, whenever you see a reduce move, actually we are not reducing the current look ahead or the current symbol, we are actually reducing the previous symbol. And in this stack, how could you apply reduce is, see the number of symbols in the right hand side, number of symbols, the length of it, length of the symbols which you have to reduce is 1. Therefore, you have to actually pop off 2 symbols from the top of the stack. If the size of the right hand side is, let us say x, then you have to pop off 2x number of symbols from the stack. The reason is, if you have to pop off B, you have to pop a stack also. If you have to pop off A, then you have to stack, you have to pop off 2 state numbers, that is why. So now how does the reduce move act is, first you pop off twice the number of symbols in the right hand side and then you push left hand side onto the stack. Which means we are remembering that we have replaced this small b with capital A, and then you should always fill the top of the stack with a state number. That is the reason. Just see what is below 3. What is below A? Below A there is 3. Therefore see what is the state that 3 on A should go. 3 on capital A should go to state 6. That is why fill it up here. Okay, one more time listen to this. What happened is, so I was looking at small b and I was in state 4. Now it said that R3. R3 means reduce the b with capital A. Reduce the b, use the production number 3 to do the reduction. Then how are we doing that reduction is, I'll just pop off twice the number of symbols in the RHS. Here I have only 1 symbol, therefore I am going to pop off 2 symbols and then push the left hand side of the production, which means A, and always fill the top of the stack with a state number. So which state number? Just see what is below A. Below A there is 3. Therefore 3 on capital A it is 6. That is why I am filling with 6. Okay, so whatever has happened is, we just reduced B to capital A. That is what has happened. Now again we are seeing B. Whenever we see reduce, we are not going to increment the look ahead. We are still seeing B. Now B on 6. B on 6 is saying R2. B on 6 is saying R2, which means take the production number 2. Production number 2 is what? Capital A derives AA and then reduce it. How many symbols are there in the right hand side of production number 2? In the right hand side of production number 2, there are actually 2 symbols. Therefore we have to pop off 4 symbols. So what do they mean is, reduce this A and this capital A into capital A. That is what we mean to do. Now if we have to reduce small a and capital A to capital A, we have to delete capital A and small a and replace with capital A, which is left hand side. Now if I have to delete 2 symbols from top of the stack, I have to pop off 4 symbols. The reason is, if I have to delete 2 grammar symbols, there will be 2 states associated with this. Therefore pop off twice the number of right hand side, which means AA and then 3A, and then push the left hand side. What is left hand side? Capital A, and fill the top of the stack with the state number. Now you have to fill the top of the stack with state number. How can I fill it? See what is the state below capital A. The state below capital A is 3. 3 on capital A is 6, which means I have to write 6 here. Okay. Now 6 on capital A. See this? 6 on capital A is again saying 6 on small a. 6 on small b. 6 on small b is again saying reduce with production number 2. Which means we have to again use this production to reduce it. A has to be reduced to A. So how can I reduce it? Just we have to pop off all these 4 symbols on top of the stack and then push the left hand side. So pop off the 4 symbols. 1, 2, 3, 4. I have popped off 4 symbols and then replace them with left hand side. What is left hand side? Capital A. And now fill the top of the stack with the state number. What is 0 on A? 0 on capital A is 2. Now you are in 2. Okay. Now see what happens for 2 on small b. For 2 on small b, it is S4, which means shift B and then 4. That is the meaning of S4, and increment the input pointer. Now we are seeing dollar and we are seeing 4. 4 on dollar is R3. What is R3? Reduce it with the production 3. So what is third production? A derives B. So how can I reduce it? Pop off 2 symbols from the RHS and then push the LHS and fill the top of the stack with the state number. What is the state number? 2 on A. 2 on A is 5. Okay, and what has happened here is this B has been reduced to A. Okay, that is what has happened. Now we are seeing capital 5 on dollar. What is 5 on dollar? 5 on dollar is R1, which means reduce with production number 1. So what is production number 1? SD derives AA, which means you have to pop off 4 symbols from top of the stack and then push left hand side, which means finally we are getting this AA is reduced to S. Therefore we got the entire pass tree, right? So we have to pop off 4 symbols, 1, 2, 3, 4, and then push the left hand side. What is left hand side of the first production? R1. Left hand side is S, and then fill it with the a state number. What is below S now? Below S there is 0. What is 0 on S? 0 on S it is 1. We have reached state number 1 and the top of and the input is dollar. Now what is 1 on dollar? Accept it. Therefore we are going to accept it. Now let us examine why it is called LR0. What does 0 mean? We are looking at, we are having 0 look aheads. It doesn't mean that we are not looking at any symbol. Actually it means that when we are parsing this input string, we did it A, B, B. We have seen A, we pushed it on the stack. Next A, we pushed it onto the stack. Next B, we pushed it onto the stack. And next B, we are actually standing at this B, and then we reduce this B to A. Okay, which means whenever I do any reduce move, I am not actually reducing it by looking at that symbol. Whenever I pass to the next symbol, then I am actually performing the reduce. But then if you look at this parsing table, the entire table, right? So it says that if you are in a state, let us say 4th state, don't worry what the next symbol is, whether it is A. See, whether this one is A or B or C or D, don't worry. Whenever you reach that state, you have to reduce it, which means I don't care what the next symbol is. That is why it is LR0. It is called LR0 because we don't care what the look ahead is, what the next symbol is. We are simply reducing it. Because of this, there could be some errors. See, now we have reduced A, B. Now what is the string we get is A, B. Now again we have to reduce some part of it later into some other variable. What if this B is not in follow of A? Then it cannot be reduced, right? So that is why LR0 is LR0 will allow us to find that error later. We should have looked at the next symbol, which should be follow of A, and then we should have reduced it. But then LR0 says that don't look at the next symbol. Whatever the next symbol is, you can reduce always. But then which is wrong. So because of that, we might get some errors which will be detected later. And second thing you should note is, whenever we get into any of these blank entries, let us say if you are in state 2 and if you see dollar, or let us say if you are in state 1 or leave state 1 or state 3 and if you have seen dollar, it means that they are errors. So whatever are the blank entries in the table, they always correspond to the errors. So LR0 says that whenever you have a final item in a state, you have to put the entire reduce moves in the entire row. Now there is a small difference between LR0 and LR1. Now what does LR1 say is, whenever you have a final item in a state, don't put the reduce moves. The main difference between LR0 and SLR1 is in terms of reduce moves. Both are using canonical collection of LR0 items only, but coming to the placement of reduce moves, both are different. So observe this. Just understand this. Now I'm talking about SLR1. So SLR1 says that don't blindly reduce whenever possible. Don't blindly reduce whatever is the next symbol. You reduce this symbol to capital A only if the next symbol is in the follow of A. Otherwise what happens is, if the next symbol is not in follow of A, you could not reduce it further to the start state. Therefore SLR1 is bit more powerful because it is taking wise decision in terms of if it is not a symbol which is not in follow of A. So that is why we are going to apply reduce moves, but reduce moves will be done only when the left hand side is being followed. For example, let us say state number 4. State number 4 is having actually R3. See, state number 4 was having, in the previous diagram, state number 4 was having A derives B dot. This is the final item, right? So since the state number 3 is having this final item, state number 4 is having this final item, don't place R3 in the entire row. You just place whatever is the follow of left hand side. What is follow of A there? Follow of A is follow of A. So what is follow of A? Follow of A is first of A as well as follow of S. What is follow of S? Dollar. What is first of A and B? Therefore we are going to place this in R3, R3, R3. So we found out that we have to place this one in follow of A, and follow of A is containing A, B and dollar. That is why I placed it here. And next one is, let us say the next state 5. State 5 is containing like this: S derives A dot, which means state 5 is containing the production R1. We should not place R1 in the entire row in SLR1 parsing table. We have to place it only in the follow of left hand side. Now what is follow of left hand side? Follow of dollar. What is follow of S? Follow of S is dollar. Therefore you have to write R1 here. Okay. And 6 is containing this second production. So what is second production? Capital A derives small a, capital A dot. This is the second production. Where should I place it? I should place it in the 6th row under what? Follow of A. What is follow of A? B and dollar. Therefore I have to write R2, R2, R2. So in terms of shift moves and in terms of go to moves, both SLR1 and LR0 both are same. Only difference between these two parsers is where you are going to place the reduce moves, and it turns out that reduce moves have to be placed in the entire row in LR0, which means we need not care what the next symbol is. We have to place the reduce moves in the entire row, right? And in coming to the SLR1, don't place the reduce move in the entire row. Just see that the next symbol that you get after reducing is in the follow of left hand side or not, which means don't place the reduce move in the entire row, just place it in the follow of left hand side. The reason is simple: even if you reduce it later, it has to be reduced. See, in this case, let's take this example. In this case, what is this production? R1 is S derives AA, which means whenever you want to reduce AA to S, see that S will be reduced to S dash later. So if I reduce AA to S in this string, if I have AA and if it has to be reduced to S, which means it is end of the string, then it has to be followed by dollar. That is where I got this, isn't it? This entry says that you can reduce AA to S provided that next symbol is dollar. That is why we have to see that the next symbol, the look ahead, is always in the follow of left hand side. That is why it is also called as SLR1. 1 means number of look aheads are 1. Okay. So we are looking at one look ahead and then taking the decision. So which one is powerful? SLR1 is powerful. The reason is SLR1 is having less number of reduce moves. Therefore, if there is any error, SLR1 will detect the error faster, very fast. But LR0 will actually detect the error slower, which means it will not be able to find out that there is an error because all the entries are full. So number of error entries depend on number of blank moves, and number of blank moves are more in SLR1. Therefore SLR1 is powerful because it can detect the errors earlier. Okay. And how to implement the errors is, in place of blank entries, you can have pointers to functions. So whenever you hit that entry, we can call a function, and that function will take the move. Sometimes what we would like to do is, we don't want to stop the parsing, we want to continue it. In that case, the function will take some action, like it will assume that whatever symbol is missing, it will put it there, or whatever is the symbol, it will just assume that it is there, and then it will go continue, or something like this. Or it can even print some error message saying that something is expected, A is expected, B is expected, or here A is not expected, B is not expected, something like this. Okay. Now we have seen two parsers, two types of parsers. One is LR0 and other is SLR1. And we observed that if I have a state, let us say this state is, let us assume that I5, then whatever are the transitions going out of it, for all those transitions we have to fill the state number or the row number 5, right? And we have seen that if there is a terminal, then this corresponds to the move. If it is going to, let us say, I6, then it corresponds to the move S6, right? And we have seen that if there is a production which is final item, A derives alpha dot, then it corresponds to reduce move. Now I am talking about LR0. Is every grammar LR0? Every grammar may not be LR0. The reason is, there could be a chance that it is, if I have something like this, which means in a row number 5 I am going to some state on S3. Therefore in the action part, forget about go to part, in the action part under A in the 5th row I am going to write S6, which means we are going to 6, right? And along with this S6, I might have to put the reduce move in the end. Let us say AB are the terminals. Now what happens is, because of this final item, I might have to put the reduce move in the entire row, which means I might have to put something like R1 because of this production number 1. So now this is called a shift reduce conflict. Therefore all the grammars are not suitable for LR0 parsing. The reason is, there could be SR conflict, or there could be one more chance of getting like this. Let us say this is the grammar, this is a state I5, some state, and now there are two productions, A derives alpha dot and B derives beta dot. If I have two productions like this, alpha dot and beta dot, and let us assume that this is production number 1 and this is production number 2, then what happens is, in the state number 5 in the table, if I have terminals A, B, C, then I have to place R1 for this first production, as well as I have to place R2 for the second production. Therefore if there are more than one final items, the grammar cannot be LR0 because of RR conflicts. We cannot have two entries in a cell. This is called RR conflict and this is called SR conflict. So understand this, a grammar cannot be LR0 if I have RR conflict or SR conflict. And what is the chance of getting a SR conflict in LR0? Whenever there is a shift move as well as a final item, then I might get a SR conflict in LR0. And whenever there is a two reduce moves, then I might get RR conflicts. Whenever there are two final items in the same state, then I get RR conflicts in the LR0. Now what about SLR1 then? SLR1 is a bit different, right? In SLR1 we get a SR conflict in this state. Let us say this is the case, and in this case it might not be a SR conflict. The reason is, we are going to small a, on small a we are going to 6, therefore definitely here I am going to write S6. But then reduce move may not be present under small a. The reason is, we are going to place reduce moves in SLR1 under the follow of left hand side, and if the follow of left hand side doesn't contain small a, then it could be SLR1. So in case if this grammar should is not a SLR1, or if you have to get a SR conflict in SLR1, let us say SLR1 grammar parsing table. Now if I have to get SR conflicts in SLR1 parsing table, then the possibility is, one thing is, you have to see the follow of left hand side. What is follow of left hand side? Follow of A. If follow of A contains small a, then only this reduce move will be placed under small a, and already there is shift move, then only we are going to get SR conflict. And in this case there will be RR conflict in SLR1 parsing table if there is any intersection between follow of A and follow of B, because R1 will be placed under follow of A and R2 will be placed under follow of B. Therefore if there has to be any let us say a conflict, RR conflict, then follow of A and follow of B, they have to intersect. In case follow of A intersection follow of B, if this is not equal to phi, then only the grammar is having RR conflicts. So in LR0 the grammar is having SR conflicts. In case if we have any problem with follow of A and shift A, and in case if there is any intersection between follow of A and follow of B, then only we get the RR conflicts, otherwise we don't get it. Now I'll take some grammars and we have to check whether they are LR0, SLR1 or not. Okay. Have a look at this grammar, this particular grammar. S0 is this one. No? So my question is whether this grammar is LR0 or not, SLR1 or not. So I want to find out whether the given grammar, this one, is this grammar 1, LL1 or not, 2, LR0 or not, 3, SLR1 or not. I want to find out these three things. Okay. So first thing is I want to find out whether it is LL1 or not. So how can you find out whether it is LL1 or not? When a production is having, a variable is having two alternatives, find the first of this. So this one is going to be placed under D, this one is going to be placed under A, no problem. This one is going to be placed under B, C, no problem. B, C, no problem. Therefore this grammar is definitely LL1. You please refer to the video where I discussed about LL1. Okay. And next one is, coming to the next one, I want to find out whether the grammar is LR0 or not, SLR1 or not. So you have to note one thing, you need not actually construct the parsing table in order to see whether there is shift reduce conflict or reduce reduce conflict. You can construct the canonical collection of LR0 items, and in this canonical collection itself you can find out whether there are conflicts or not. So there are two types of conflicts. One is SR conflict and other is RR conflict. So whatever the conflict is, reduce move is definitely a must, which means we get the conflicts only in the states which are having reduce moves. So after constructing the canonical collection or while constructing it, whenever you get a reduce move, which means a final item, you have to stop it and check whether there is a conflict or not before going ahead, right? So you need not construct the entire parsing table, you can construct the canonical collection of LR0 items and then go into the states where there are final items. See this? Actually this is not a final item, I1. The reason is this is augmented production which we added. And coming to this one, I9, there is a final item. There is only one final item, which means there are no RR conflicts. And second thing is, there is no shift move, therefore there is no SR conflict. Therefore there is no SR or RR conflict in this production. Now coming to this I4, there is a final item. This is a final item, and this final item is only one final item, therefore there are no RR conflicts. And second thing is, there is no shift move in this, therefore there is no SR conflict, no SR conflict and RR conflict. And coming to state I6, again there is only one reduce move and there is no shift move, therefore there are no conflicts. I7, only one reduce move and there are no shift moves, no conflict. And then I11, only one reduce move, I10, only one reduce move. Therefore in these states, wherever you have seen the final items, we don't have actually conflicts, right? Therefore the grammar is definitely LR0. Yes, the grammar is LR0, and if the grammar is LR0, it will definitely be SLR1. The reason is, if there are no conflicts in LR0, and by reducing the number of reduce moves, you will not add any more conflicts, right? So if a grammar is LR0, it is definitely SLR1. So what I did is, for this grammar, I constructed the canonical collection of LR0 items. How? We discussed it already. You start with s-derives.s and then you keep on adding them. And in this example, one point worth noting is s-derives.s. If I apply closure to this, I got only two productions, two LR0 items. I didn't get A and B. The reason is, we don't have dot in the beginning of A. So these two productions are not going to give me either A production or B production. So many people generally they write all the productions here. They write all the productions here and then try to expand it. That is wrong. You have to see that whether it is needed to add A production and B production. They are needed only when you get them in the closure. Okay. So this grammar is actually both LR and LR0, SLR1 as well as LL1. So let's see some other example. Let's see one more example. Let us see whether this grammar is LL1 or not. I want to find out whether this grammar is suitable for LL1 parser or LR0 parser or SLR1 parser. So we have already seen that this grammar is not suitable for LL1. The reason is, if I see first of this, it is going to be A, which means it has to be placed under A, and this one also has to be placed under A. So both two productions are going into the same cell. Therefore we have already seen that it is not LL1, and in fact the grammar is ambiguous grammar, and ambiguous grammar is not suitable for any of the parsers. So even it will not be LR0 or SLR1. Just see the example. Now construct the canonical collection of LR0 items, starting with augmented production s dash derives dot s. Then we have to add all the s productions, which means s derives dot a or dot small a, and then a derives dot small a. Okay, and now we have to find out transitions on s. On capital S, transition is s dash derives capital S dot and on small a, s derives a dot, a derives a dot, and on capital A, s derives capital A dot. Okay, now if you see this is not a reduce move, it is a final item which is augmented, and this is a reduce move. But then in this state we have got two reduce moves. Whenever we got two reduce moves in the same state, two final items in the same state, definitely the grammar is not LR0. Now check whether the grammar is SLR1 or not. How can I check whether the grammar is SLR1 or not? Where are we going to place this production, this reduce move, under follow of S? So what is follow of S? Follow of S is $. And where are you going to place the second production? This one under follow of A. What is follow of A? Follow of A is nothing but follow of S, which is $. Therefore, under the same entry, I might have to put two reduce moves. Therefore, it is not SLR1. So the given grammar is not SLR1 as well as the given grammar is not LR0. Okay, but the given grammar is not LL1 also. In fact, this grammar cannot be parsed by any of the parsers. The reason is it is ambiguous grammar. Okay, let's see the next example. Let us see one more grammar. This grammar, whether this grammar is LL1 or not, you can have a look at it. You can pause the video and have a look at it. And this grammar is whether I want to find out whether it is LL1 or not, first thing, and then whether it is LR0 or not, and then whether it is SLR1 or not. I want to find out these three. So first of all, I want to find out whether it is LL1 or not. If you look at the grammar is left recursive. Any left recursive grammar cannot be LL1. Therefore, this grammar is definitely not LL1. And next one is I have to find out whether the grammar is LR0 or not. In order to find out whether the grammar is LR0 or not, we have to find out canonical collection of LR0 items. This is the canonical collection of LR0 items, right? And how to start with, we have to add a production which is called augmented production, and then take the closure of the LR0 item. Okay, so I'm going to add the production s dash derives dot s, and with a dot in the beginning of s. Therefore, I got the closure as this. And if you observe it, we are not going to get all the productions here. Same as the previous example. We are not going to get all the productions in the state I0 or in the starting state. The reason is there is dot to the beginning of S. That is why I added all the S productions. And now there is no dot to the beginning of L, which means we have to add only S productions. No L productions are added. And once you see the transitions, what are the transitions out of this state? There is a dot to the beginning of S, therefore there will be a transition on S. There is a dot to the beginning of open brace, therefore there will be a transition on open brace. So on open brace, I have to apply the transition. That is why I got S derives open brace dot L close brace, and again you have to apply the closure. After the transition, I have to apply the closure. What is closure? Since dot is to the beginning of L, I have to add all L productions with a dot in the beginning. That is why I added this production and this production, because of this L, right? So because of this L, I added these two productions, right? And now if you see one more production, there is one more production with the dot before s. Therefore, because of this s, I have to add s productions. That is why I added all these s productions, right? And now if you look at the dot, there is a dot to the beginning of L, therefore there is a transition on L. There is a dot to the beginning of L, therefore there is a transition on L. Both these two transitions on L will go to the same state. The reason is this is always a DFA. Okay, so on L we get two transitions, not just one transition. That is important in this example. Till now we haven't seen any example in which there are two transitions on a single symbol. So on L we have two transitions, right? So we got two transitions. Okay, and on S there is one transition, and on open brace again there is one transition, and we get the same state. That is why on open brace I am writing this. Okay, now if you look at this, on L dot will be moved to the right of L here, I got this one, and dot will be moved to the right of L here, I got this one. Even if I apply closure, I get only two transitions. Okay, now this one on close brace, I got this one on comma, you can fill it up. Okay, so it is all straightforward from now on. Now I have to find out whether the grammar is LR0 or not. When will a grammar be not LR0 or when will a grammar be not SLR1 is whenever there are conflicts. What are conflicts? SR conflict and RR conflict, which means if there has to be any conflict, there has to be reduce move. What is a reduce move? Final item. Therefore, go to the states where there are final items. This is not a final item, this we added it, therefore this is used for accepting, actually not final item. Are there any final items in this state? No final item. Are there any final items in this state? No final item. Any final items in this state? No final item. Final item is dot in the rightmost. Yes, this is a final item because dot is in the rightmost. Now in this state, are there any shift moves? No. Are there any other reduce moves? No. There is only one reduce move, therefore no conflict. Are there any final items here? No. Yes, this is a final item, and in this state, are there any other reduce moves? No. Or are there any other shift? No. Therefore, no problem. This is a final item and there are no other reduce moves, no other shift moves, no problem. Final item, final item. So wherever there are final items, there is no shift or reduce in that state. Therefore, the grammar is LR0. And any grammar which is LR0 is by extension SLR1. So this grammar is both LR0 and SLR1. Okay, we shall see one more example. Let's see a simple grammar. E derives E plus T or T derives I. This grammar is nothing but the expression grammar, which which derives all the sum, which means I plus I plus I plus I, something like this. Okay, so this is the simplest grammar. And let's see what happens with this. Let us add the augmented production. S dash derives dot E. Then because there is a dot in the beginning of E, I am going to add all the E productions. And now because there is a dot in the beginning of T, I am going to add all T productions, right? And see what happens on capital E. The transition, there are two transitions on capital E. So one transition is S dash derives E dot, and other transition is E derives E plus T. Now if you look at this transition, the first one looks like the final item, which means a reduce move, and the second one looks like the shift move, right? It is a reduce move and this is the shift move. Therefore, you might think that this is SR conflict, but one point here you have to note is this augmented production is the production which you added, right? Therefore, this cannot be a reduce move, this is actually accepting move. If you think that you get confused because of such states, it is always suggested that you add dollar at the end of the first augmented production. The reason is always the starting symbol will be followed by dollar, therefore input can be generated by E and then dollar will be generating the dollar. So even since we are going to give the input as input followed by dollar, this E followed by dollar is going to generate input followed by dollar. That is why it is suggested, right? It is just a recommendation. If you want to follow it, you can follow it, because you might get confused otherwise. So in all the previous examples, you can add a dollar. Now what happens is, this is now not a final item, isn't it? This is not a final item and this is not a shift. Now there is no conflict here. Therefore, on dollar only, it is going to be S dash derives E dollar dot. We got this. So there is no problem with this state. This is not a SR conflict. right? And on plus, if you see, we are going to a next state, and here also there is no final item, therefore there are no conflicts. On T we got this, there is a final item, therefore it is a reduce move, but then it is a single reduce move, therefore there is no conflict. No conflict, no conflict. This is a simple grammar where there are no conflict. Now let's see what if the grammar is right associative. Right associative means instead of this simple grammar, I'll just change the associativity, and then let's see what happens with that. Okay, we shall see it next. Let's see a simple grammar. This is the same grammar as previous one, but then instead of this left recursion, we have used the right recursion. Okay, so first one, what is this grammar? This grammar generates all I plus I plus I expressions like this, right? Simply I or I plus I or I plus I plus I or something like this. Now since E is defined as right recursive, here plus is defined as right associative. Previous grammar E is defined as left recursive, therefore plus is left associative. I didn't do anything, just I changed the recursiveness, that's it. Okay, and now my question is whether this grammar is LL1 or not. It is not left recursive, therefore let me check whether it is LL1 or not. Where are we going to place this production? In the E row in first of T. What about this production? This is also in the E row in first of T, therefore both of them are going to the same symbol, which is I. Therefore this grammar is not LL1. You can check it. I know if you remember LL1, you can check it. Since both the productions are going to the same cell, why? Because this one has to go into E row into first of T, and this one has to go into E row and first of T, and since first of T and first of T are I, both the productions are going into the same cell, therefore this is not LL1. And now next thing is whether it is L or 0 or not. In order to find out whether it is L or 0 or not, we have to construct the canonical collection of L or 0 items, right? So this is the canonical collection of L or 0 items. E dash derives dot E is the augmented production. Because of dot at the beginning of E, I am going to add all the E productions. And now because of dot at the beginning of T, I am going to add all the T productions, right? And now one interesting thing is here on capital T, the transition is E derives T dot plus E, and then E derives T dot. This is a final item and there is a shift move, right? And because of this state, there is a conflict. There is a shift move on plus, therefore this is shift, and there is a final item, therefore it is reduced. Therefore in this state we have SR conflict. If you want to see that in the table, in this table, you can see that in the second state I2, in the second state I2, under the cell plus, under the plus, there is a SR conflict, and the reduce move is R2. Okay, how do you place reduce moves? Let us say we have numbered the productions. Production number is 1, production number 2, production number 3, and if you see this I2 state here, the final item corresponds to the production E derives T, which is 2. That is why I am going to write R2 in that row. So according to LR0 parsing table, I have to place the reduce moves in the entire row. That is why, see this, in the I2, in the state 2, since there is a final item, I am going to place the reduce moves in the entire row, right? And in the I3, since there is a final item, I am going to place the reduce move in the entire row. In I5, again there is a final item, therefore I am going to put the reduce move in the complete row. Now where did the conflict arise? The conflict arises here, and this table is LR0 parsing table. You need not actually construct the parsing table to show that the grammar is not LR0. Here itself we can stop and say that since there is SR conflict, the grammar is not LR0. Now my question is, yes, this grammar is definitely not LR0. Now my question is whether this grammar is SLR1 or not. How to find out whether the grammar is SLR1 or not? What is the main difference between LR0 and SLR1 is, in LR0 reduce item is placed, reduce move is placed in the entire row. In SLR1, reduce item is placed, reduce move is placed only in the follow of left hand side, which means this R2 corresponds to second production. What is the second production? E derives T dot. This is what is R2, right? R2 corresponds to this production. Where should you place it is only in the follow of left hand side. What is follow of left hand side? E. Therefore in SLR1 parsing table, we are not going to place the reduce move in the entire row, we are going to place it only in the follow of left hand side. Now tell me what is follow of E. Follow of E is, according to the grammar, follow of E is, since it is the start symbol, it is dollar. Okay, and follow of T is since it is the here T is followed by plus and dollar. How to find it out? We know that, right? Now the production E derives T dot, where the left hand side is E, has to be placed only in the follow of left hand side, which is nothing but dollar. Therefore R2 is not placed all over, R2 is placed only under dollar. And next one is, look at the third production is T derives I. So T derives I has to be placed only under plus and dollar, which means you need not place it here. And next one is fifth production is E derives T plus E. Where should this be placed? Only in the follow of E. What is follow of E? Follow of E is dollar. So this is nothing but SLR1 parsing table. So what is the difference between SLR1 and parsing table and LR0 parsing table? In SLR1 parsing table, we are going to place the reduce moves only in the follow of left hand side. In LR0, we are going to place the reduce moves throughout. So that is the main difference. Now, if you look at this, the grammar is now SLR1. The reason is there is no conflict. The grammar is definitely SLR1 but not LR0. Okay. So we shall see the next example. Let's see the next example, this one. E derives E plus T or T derives TF for F and F star AB. Oh, what is this grammar? This grammar is nothing but it derives set of all regular expressions, right? Regular expression can be union of two regular expressions or concatenation of two regular expressions or a clean closure of a regular expression or simply primitive regular expressions, right? And now the question is whether this is LL1 or not. The grammar is not LL1 because top-down parsers, they don't want left recursion and the grammar is left recursive. Therefore, the grammar is not LL1. Now, my next question is the grammar LR0 or not? You can pause the video and see how I constructed this canonical collection of LR0 items. It is very easy and straightforward. No, you can make it out. So I am going to start with E dash derives dot E and then add all the productions because of this E, and then add T productions because of the T, F productions because of the F. So the construction of this canonical collection, you know it. And now my question is whether this is LR0 or not. In order to find out whether this is LR0 or not, we need not actually construct the parsing table. Just by looking at this entire canonical collection, you can examine the states. So whenever a state is having final item, there could be a possibility of a reduce move and there could be a possibility of a conflict. Therefore just watch the states and then see wherever there are final items. Okay, now if I look at this first state, I0, in I0 there are no final items, isn't it? And in I1, are there any final items? Actually there is a final item, but then this is augmented production, therefore you need not consider it as a reduce move. This is actually accepting move. You need not think about I1. Now look at I2. In I2, yes, there is a final item. What is the final item? E derives T dot. There is a final item and then see if there is any conflict because of this. Because of this final item, in the entire row in LR0 parsing table, I am going to put the reduce move. What is the reduce move? E derives T dot is nothing but second production. Therefore, R2 is placed in the entire row of I2. And now, what about this move? Capital T derives T dot F, which means there is a transition on capital F. Is there any conflict because of these two? Actually, there is no conflict because T derives dot F is actually T dot F is actually go to. It is not an action part. Therefore, this is in the reduce, which is nothing but action part, and this is in go to part. These two are not leading to conflict. And what about this one? This is also not leading to conflict. What about this one? Small a and small b? Yes, they are leading to conflict. There is a reduce move and then there is A and B, there is shift move. Therefore, there is a conflict in this state. So, this grammar is not LR0. In the exam, if they ask you whether the grammar is LR0 or not, you need not construct the entire table, canonical collection. Once you reach state I0, I2, you can stop there and say that the grammar is not LR0 or not. You need not proceed forward. But then if the question is, if the grammar is SLR1 or not, then you have to check it. Then you have to check whether these conflicts could be resolved by SLR1 or not. For that I need to construct the parsing table, SLR1 parsing table, and then see it. But then there are few observations you have to make. You need not construct the entire parsing table. You have to construct only the part of the parsing table where there could be conflicts. Where could be conflicts? Only in the action part. Therefore, you need not talk about go to part at all, because we are just interested in finding out whether there are conflicts or not. So I need not construct the entire parsing table. I'll just construct a part of it, only some part of it. Okay, look at this. So I'm not going to construct the entire parsing table. I'm going to construct only a part of it, which means what are the terminals here? I am talking about state 2. Why state 2? Because state 2 is having conflicts. It is also called as inadequate state. Any state which is having SR conflicts or RR conflict is also called as inadequate state. Therefore, I am constructing SLR1 parsing table only for state 2. In state 2, what are all the terminals? You tell me. Terminals are A, B, plus, star, and dollar. Isn't it? Now, what is the reduce move? E derives T dot. What is E derives T? It is second production. Therefore, I had to write R2. In SLR1 parsing table, where should I place the reduce move? Only in the follow of left hand side. What is follow of left hand side? Follow of E. Therefore, only under follow of E, I am going to place the reduce move, which means under plus and under dollar, I am going to write R2 and R2. Why these two? Because the production number is 2. Okay. And now what about the shift moves? Shift moves are on A it is going to 4 and on B it is going to 5, which means under A I have to write S4 and under B I have to write S5. Okay. And this is one conflicting state. Now we have seen that even though there are conflicts in the canonical collection of LR0 items, which means even though the grammar is not LR0, but the grammar could be SLR1, because the conflicts could be reduced easily, right? This way. So SLR1 is actually able to resolve the conflicts present in I2. But then you should not stop just here and say that the grammar is SLR1. Why? There could be some other states in which there could be conflicts which may not be resolved by SLR1. Therefore, you have to complete the entire diagram and then see every inadequate state and then check whether it is resolved or not. Now, if I finish the entire diagram, I am going to the next state. Yes, next state is I3. Is there any final item in I3? Yes. Is there any shift move? Yes. Therefore, there is a SR conflict, right? So now let me go to I3 and see the state number 3. What is the production? T derives F dot. What is the number of it? 4. Therefore, I have to place R4 in SLR1 parsing table under the follow of T. What is follow of T? Follow of T is plus $AB. Therefore, under plus $AB, I have to write A, B, plus and dollar. What is the number I have to write? I have to write T derives F production, which is nothing but 4th. Therefore, I have to write R4, 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 R4. And now on star I3 is going to I8. Therefore, I have to write it as S8. Okay. And now next one is this is about third production. Now the whatever were the conflicts in I3, they have been resolved in the SLR1 parsing table. But then you should not say that the grammar is SLR1, because you have to check all the other states. Now let us see one more state. There is no final item in I6, therefore no problem. Yes, there is a final item in I7, which means again I7 there is a final item as well as a shift item. Right, there is a shift move as well as reduce move. Therefore, in LR0 parsing table, it was a conflict. Now, let's see whether this conflict could be resolved by SLR1 or not. So, what is the state? 7. 7 is the state. And where should I place the reduce move? Reduce move should be placed in the follow of T, y left hand side. Right, in SLR1, it has to be placed in the follow of left hand side. What is follow of T? Follow of T is plus $AB. Therefore, under A, B, plus and dollar, I am going to place reduce. So, what is the reduce move corresponding to this? T derives TF. T derives TF reduce move is the third production, which means I have to write R3, R3, R3 and R3. Right. Then what about the shift move? Shift move is under star, on star it is going to 8. Therefore I have to write S8. Yes. Now see how beautifully they are getting arranged themselves. In case of SLR1 parsing table, in case of LR0 parsing table, reduce move has to be placed in the entire row. Therefore they are going to conflict with shift. Here also reduce move has to be placed in the entire row. Therefore they are going to conflict with shifts. But then when we look at this SLR1, the reduce moves are placed only in the fall of left hand side, and therefore shift moves are getting the chance to be placed independently. Therefore these conflicts are getting resolved. Let's see if there is any more inadequate state. Yes, this state there is only one final item, no problem. One final item, no problem. One final item, no problem. And no final item. Look at this state I9. Yes, there is a final item, and now there is a final item as well as there are shift moves. Shift moves are on small a and small b, and these two are go to moves, right? So 9 again is inadequate. What is the final item? E derives E plus T dot. Where should I place this reduce move? This final item's reduce move in the follow of left hand side. What is follow of E? Plus and dollar, right? Therefore for this production E derives E plus T, which is 1, which is the first production. I have to write R1 under plus and dollar, R1 under plus and R1 under dollar. Okay. And what about the shift move? Shift move has to be placed under small a and small b. On small a it is going to I4, therefore it is S4, and on small b it is going to I5, therefore it is S5. So even all the conflicts, there are actually four rows or 4 states which are having conflicts in LR0 parser, and all the conflicts have been resolved by SLR1. Therefore in this example the grammar is not LR0 but the grammar is SLR1. So this is a classic example in which we can find out the power of SLR1. So according to this example you can say that even if a grammar is not LL1 or a grammar is not LR0, it could still be SLR1. The reason is the conflicts could be resolved by SLR1, right? So we shall see some more examples. Let's see this example. It is a simple example, right? It is a simple question where what is the grammar? Grammar is simply AA, AB, BA, BB, BA. And what are the strings generated by this? I think there are only 2 strings generated by this grammar. One is AB, other is BA. Such a small simple grammar. And now I want to find out whether this grammar is, first one, LL1 or not, and I want to find out whether the grammar is LR0 or not, and I want to find out whether the grammar is SLR1 or not. Okay, so let's see whether the grammar is LL1 or not. How can I find out whether a grammar is LL1 or not? Where are you going to place this one? Under S row and in first of this, which is nothing but this one is going into A and this one is going into B. Therefore there is no problem, the grammar is LL1, right? And let us see whether the grammar is LR0 or not. So how can we find out whether a grammar is LR0 or not? A canonical collection of LR0 items as before, but one point you have to note here is, if I have anything like this, A derives dot epsilon or A derives epsilon dot, you can write it as A derives dot, right? Which means if I take the first production, augmented production, and apply the closure, S dash derives dot S, then apply the closure, I get, since there is a dot to the beginning of S, I get all the S productions. Yes, I got all the S productions with the dot at the beginning. And now because of this dot before A and because of this dot before B, I have to add A production and B production with dot at the beginning. Now it is nothing but A derives dot epsilon. I can even write it as A derives dot, B derives dot. Now if you look at these two are final items, and 2 final items are present in this state I0. You can stop here and you can simply say that the grammar is not LR0. The grammar is definitely not LR0. The reason is there are 2 reduce moves in the same state, therefore it is not LR0. Now I want to find out whether this grammar could be SLR1 or not. Before going further and then filling up the entire canonical collection of LR0 items, just see whether this state, these 2 conflicts can be resolved by SLR1 or not. If I write the SLR1 parsing table for the 0 row, for this I0, 0th row, what are the terminals? A, B and dollar, right? Now look at this production. This is production number 1, production number 2, production number 3 and production number 4. Now look at the production number, this one, A derives epsilon. What is the production number? 3. Therefore I have to place R3. In SLR1, this production has to be placed under follow of A. What is follow of A? Under A and B. Therefore under A and B I have to write R3 and R3. Okay. And now what about shift move? And okay, let's see about this reduce, second reduce. This second reduce has to be placed under follow of B. What about follow of B? A and B only, right? Which means even R4, this B derives epsilon is fourth production. Even R4 have to be placed under A and B. Therefore there is reduce conflict. So the grammar is not SLR1, the grammar is not LR0, but the grammar is LL1. That is interesting, right? So where are we going to place the first production? Under S row and small a column. Under S row and small b column. And what about these two productions? They can be placed anywhere, no problem. Even if you place it the entire row, no problem, right? So the grammar is LL1, but the grammar is not LR0 or SLR1. This is a very good example. We shall see more examples. Let's see next example. The example is this grammar. Okay, have a look at this. This is the grammar and I want to find out whether the grammar is, first one is LL1 or not, and next one is LR0 or not, and next one is SLR1 or not. Okay, so where are you going to place each production? See this. Now in LL1, where are you going to place the first production? This production has to be placed under first of A. What is first of A? First of A is small a as well as first of S. What is first of S? Is small b. Therefore this production has to be placed under A and B, and again this production also has to be placed under B. See, in the S row, this production has to be placed under A column and B column, and this production has to be placed under B column. Therefore the production, one production is going into in one cell there are two productions coming in, right? Therefore the grammar is not LL1. You can say it there. Now I want to find out whether the grammar is LR0 or not. In order to find out the grammar is LR0 or not, I am going to construct the canonical collection of LR0 items. So this is the canonical collection of LR0 items. You can pause the video and see how I constructed it. Actually I didn't complete the entire diagram. Even there are some transitions on small a and small b. This diagram is enough for me to say whether it is LR0 or not. So coming to this state, see, in this state there is no problem because there is no final item, so you need not check about it. And in this state there is no final item. You might think that this is the final item, but actually this is the accepting item, right? Or the augmented production, which means there will be dollar. So don't worry about it. And there is no final item, don't worry about it. Yes, in this state there is final item. And what is the final item? A derives SA dot. Now because of this final item there is a reduce move, and then because of this dot B dot B dot A, these three productions, there is shift move. Therefore the grammar is not LR0 because there are SR conflicts because of this state. Here itself we can stop. You need not complete the entire diagram. Now let us see whether this grammar can be SLR1 or not. In SLR1, this production will be placed, this final item will be placed in the follow of left hand side. What is follow of left hand side? Follow of A. Now what is follow of A? See this, follow of A is first of S. What is first of S? First of S is first of A as well as B, which means this production has to be placed under follow of A, and follow of A is small a comma small b, and this shift has to be placed under B. Therefore under B there is reduce as well as shift. So this grammar is not SLR1 also. So this grammar is not LL1, this grammar is not LR0, as well as this grammar is not SLR1. And in fact no parser could actually parse this grammar. The reason is the given grammar is ambiguous. So what is ambiguous grammar? For a given string or for any string, if we get more than one parse tree, then it is ambiguous grammar. For that example, just see, I have given here, for this string AB, the given grammar is giving us two parse trees. The given grammar is giving us 2 parse trees. Therefore, this grammar is ambiguous, and because of the ambiguity, it cannot be either LL1 or LR0 or SLR1, right? So actually you need not construct the entire diagram. You can construct it till the state where you get conflicts. You can stop there and check whether these conflicts could be resolved by SLR1 or not. You need not actually construct the entire diagram. I did it just for the sake of information. You can pause the video and note it down. Okay. Now let's see the next example. Next example is this one. So I want to find out whether this grammar is LL1 or not, and LR0 or not, and SLR1 or not. Okay. So if you look at the grammar, the first production has to be placed under first of A. What is first of A? This one has to be placed under D. The first one has to be placed under D. The second one has to be placed under B. The third one has to be placed under again D. So 2 productions have to be placed under S row and D column. Therefore the grammar is not LL1. Now I want to find out whether the grammar is LR0 or not. How could I find out whether the grammar is LR0 or not is, I have to construct the canonical collection of LR0 items. So I am starting with augmented production S dash derives dot S, and because of this dot before S, I have to add all S productions. So I am adding all S productions with dot in the beginning, and because of this dot before A, I am adding A productions. Now check if there are any conflicts in this state. Actually there are no conflicts because there are no final items. So for this state it is fine. Now on D, see what is happening. On small d, I am going to the state where, see, I am just moving the dot over D. So here S derives dot DC is there, was there, therefore it is S derives D dot C, and then A derives dot D is there, therefore A derives D dot. Now this is a conflicting state, or in this state there are conflicts, therefore it is called inadequate state. You can stop here and you can say that since there is reduce and shift is on C and reduce is for this final item, this is not LR0. So here itself we can say that it is not LR0. Now before going ahead and then checking whether it is SLR1 or not, just see whether this conflict could be resolved by SLR1 or not. How could I check whether this conflict be resolved by SLR1 or not? See, where are we going to place this final items, this reduce move and shift move. So in this state, let us say I1, if you construct the table, let us say this is state I1 and the terminals are A, B, C, D and $. Okay, so where are we going to place this shift move? Shift move is placed under C. And what about the reduce move? This reduce move has to be placed under follow of A. What is follow of A? Follow of A is small a, small c. So under small a and small c we have to place the reduce move. Therefore there is SR conflict even in SLR1 parsing table. Therefore the given grammar is not SLR1 also. So we have seen many examples in which grammars are either SLR1 or not, or LR0 or not. Now let's see the next class of parsers, which are LALR1 and CLR1. Okay. Now let's see the next class of parsers. The next class of parsers are this: LALR1 and CLR1. So these are the two parsers I wanted to construct. And as we have seen, for all the parsers, the parsing procedure is same, the parsing algorithm is same. Only thing that is going to vary is the construction of parsing tables. So if you have seen this LR0 in the construction of parsing table, we are going to place the reduce move in the entire row. And if you see this SLR1, we have placed the reduce move only in the follow of left hand side. And similarly here, in order to construct LALR1 and CLR1, we are not going to use canonical collection of LR0 items, we are going to use canonical collection of LR1 items. So in case if we have seen SLR1 and then LR0, we have used canonical collection of LR0 item. What is LR0 item? Any item with dot in the right hand side is LR0 item. LR1 item is nothing but LR0 item plus a look ahead. So if we add look aheads to LR0 items, then we are going to get LR1 items. For example, if I have any production, let us say, what is LR0 item? Any production with dot on left hand side, on right hand side, right? So let us say a production is like this: dot A. This is nothing but LR0 item, right? Now to this LR0 item, I even add some symbols which are called lookaheads. So what is the importance of these lookaheads is, whenever we reach the final item, for example, if the final item is sdrise AA dot, and at that place if the lookahead is like this C comma D, it means that don't place the reduce move in the entire row or in the follow up left hand side, just place it in the lookahead symbols. Therefore these lookaheads are going to be useful in order to determine where we are going to place the final item. So I'll take an example and I'll show you how does this canonical collection of LR1 items are formed. Let's see the example where, even we have seen one example in the beginning. This example is sdrise AA, A derives small aa or b. So for the same example, we have constructed LR0 and SLR1 parsing tables also. Now for the same example, I want to show you how to construct the canonical collection of LR0 items. So always remember, we have to start with the augmented production. So augmented production is s dash derives dot s. It is nothing but LR0 item. You have to make it LR1 item. So for the initial production, always start with this, with dollar. Dollar is the look ahead. So for the augmented production, this is LR0 item. In order to make it LR1, I am going to add a look ahead, and the look ahead is always dollar for the augmented production. Now since there is a dot to the beginning of S, you have to add all the S productions. See, since there is a dot in the beginning of S here, I am going to add all S productions. What are S productions? S derives AA with dot in the beginning, and now you have to add the look ahead symbol. Now why did I add this production? I have added this production because of this dot before the S. Whatever is remaining after it, what is remaining after it? Dollar. You have to find first of that and add it here. So I'll tell you the rule. In case if you are going to do the closure for A derives alpha dot B beta comma, let us say A or B. If this is the production, and because of this LR1 item, if you are applying the closure, then you have to add all the B productions with dot in the beginning, and now you have to add the look ahead. Look ahead is going to be, we have added this B production because of this B. Whatever is remaining after that, what is remaining after that? Beta followed by A or B. Find first of beta followed by A or B and then add it. So let us say first of beta is C or D, then I am going to add C comma D here. Okay. Or in case if there is no beta, then we have added this B production because of this B. Now whatever is remaining after that, what is remaining after that? A or B. Therefore we have to add A or B here. Okay, so remember this. Now how did I do it? There is a dot to the beginning. Whenever you add any production, just see the production because of which we added it, and then in that production, whatever is remaining after that variable, you have to add all the find first of it and then add it as a look ahead. Okay. Now see this. Why did I add this production? I added this production because of this S. Now what is remaining after that S? Only dollar. So what is first of dollar? First of dollar is dollar. Okay. Now I have to add A productions because of dot before this A. Therefore I am going to add A productions. A derives dot AA or dot B. Now why did I add these A productions? Because of this A. Now what is remaining after that A and dollar. So what is first of A dollar? Are you getting this? See, what is remaining after this? The next remaining symbols are A dollar. I added this production because of this A, and whatever is remaining after this, which is nothing but A dollar, I have to find first of that. So what is first of A dollar? First of A dollar is nothing but first of A, which is nothing but A or B. So here the look aheads are going to be AB, and here also look aheads are going to be AB. Got it? So this is nothing but I naught. I naught is nothing but canonical collection of all collection of all LR1 items starting with S dash derives dot S. So I have taken the first production and I applied the closure. Now remember that whenever we apply the transition, which is nothing but if I apply transition on capital S or on any symbol, the look ahead doesn't change, which means S dash derives S dot, and whatever was the look ahead, you had to write it there. Okay, and let us say what happens on capital A. On capital A, if you see this, then S derives capital A dot capital A, because I am moving this dot to right of first A, comma dollar. Why? Because the look ahead was dollar, and now because of this dot before this A, there is a dot before capital A, I am applying the closure. So when I am applying closure, I have to add all A productions. What are A productions? A derives dot AA or dot B. Now why did I add this A production? I have added this A production because of the second A. These A productions are added because of the second A. Now whatever is remaining after second A, what is remaining? Dollar. So what is first of dollar? Dollar and dollar. They are the look aheads here. Got it? And no more symbols will be added, no more productions will be added, because we didn't get any dot to the left of a variable. Okay, now let's say on small a. On small a, what happens? This dot has to be moved to the right of small a. A derives small a dot capital A, and whenever we are applying the transition, whenever we are moving the dot, we need not change the look ahead. So look ahead is going to be A or B, and now because of dot to the beginning of this A, I have to add all the A productions with dot in the beginning. So I am going to add A productions. A derives dot AA or dot B. Observe this. Now I am just adding this A productions, which is already added, right? So this production AA is already there. Again I am adding AA, but then these two productions are different in terms of LR0 items. Even though the productions are same, LR0 items are different. This LR0 item says that we have seen till small a. This LR0 item says that we have not seen anything, right? So both are different. Now what should be the look ahead? Look ahead is, see this. Why did I add this second A production? I added this second A because of the dot before this A. Now whatever is remaining after it, what is remaining? A or B? Find first of it. What is first of A or B? It is simply A or B. Okay. And now this one on small b. On small b, it is going to give A derives small b dot or look ahead is going to be A or B. While applying the transition, don't change the look ahead. While applying the closure, look ahead might change, right? And now what about this on capital A? On capital A, S derives AA dot comma dollar. We are not changing the look ahead, and this is the final item. And what about this on small a? On small a, it is going to give us, see, on small a it is going to give A derives small a dot capital A comma dollar. Why? I have moved this dot to the right of small a, and you might observe that this state and this production both are same, but then in terms of look aheads they are different, therefore they are different states. Okay. So even though in LR0 items they are same in terms of LR0 items, but in terms of look aheads they are different, therefore they have to be split into different states. Now see this, on small a I am moving capital A dot small a comma dollar, and now I have to add all A productions, right? What are all A productions? A derives dot AA or dot B. Now why did I add these A productions? Because of this dot before this A. Now whatever is remaining after that, what is remaining after that? Dollar. You have to find first of it. Now what is first of dollar? Dollar and dollar. Alright. So you have to make an observation here. These two states are actually having the same LR0 items but different look aheads. Here the look ahead is AB, AB, AB. Here the look ahead is dollar, dollar, dollar. Therefore they have to be in different states. Okay. And now let's finish this. Now what about this one on small b? This one on small b is going to give A derives B dot comma dollar. What about this one on capital A? On capital A we are going to get a final item. A derives A capital A dot, look ahead is A or B, and this one on small b is going to give us A. This one we have already seen it. On small b we are going to get the same production, right? So what about on small a? On small a we loop to the same state, and this one also on small a we loop to the same state, and this one on small b is going to be A derives B dot. On small b it is going to be A derives B dot comma dollar, right? On small a it is that, and on capital A it is going to be A derives A dot comma dollar. See, look here, doesn't change when I am applying the transition. Okay, so on small a it is over, on capital A it is over, on small b it is over, right? And capital A, small b, right? So yes, so all these states are done. Now you just open the page where we have discussed the same grammar for canonical collection of LR0 items. Here I am discussing the grammar for canonical collection of LR1 items. You will observe one point. The number of states in this canonical collection of LR1 items will have increased. The reason is, previously these two states were not there, these two states were not there, these two states were in one state. The reason is, whenever I consider the look ahead, because of the changes in the look ahead, I got these two states. If you look at LR0 items, in terms of LR0 items, both these states are same, isn't it? Both these states are same in terms of LR0 items, but when I consider the LR1 items, in terms of look aheads, both these states are different, right? And moreover, you can even observe this state and this state, both these states are same in terms of LR0 items, but they are different in terms of look aheads, even these two states, right? So there are some states which are having same look aheads, which are having same LR0 items, but which are having different look aheads. Therefore, the number of states when I consider canonical collection of LR1 items might increase in general. Okay, and one more thing is, while constructing this, I can use this canonical collection of LR1 items, and I can construct, first one is CLR1 parsing table. So in CLR1 parsing table, the number of states will be equal to the number of states in this canonical collection, and always the go to part and the shift part is same as previous. So previously, however, you have constructed this go to part and shift part, that is going to be same. So only difference coming to this CLR1, using this canonical collection of LR1 items is, where are you going to place the final items? Whenever there is a state which contains final items, whenever there is a state which contains final items like this, we are not going to place them in the entire row or on the follow-up left hand side. In case of CLR1 parsing table, we are going to place the reduce moves only in the look ahead symbols, which means for this, in this state, for this reduce move, for this final item, a reduce move will be placed under small a and small b. That is the advantage of using this look ahead symbols. So previously, if you see this, in LR1, in LR0 parsing table, we are placing the look aheads in the entire row. And in SLR1, we are not placing it in the entire row, we are placing it only in the follow-up left hand side. Now in CLR1, we are not placing it in the follow-up left hand side, we are placing only in the look ahead symbols. Therefore, the number of reduce entries compared to LR0 or SLR1 is less in CLR1. Therefore, there will be less number of conflicts. Whenever I reduce the number of reduce moves, obviously the conflicts are going to be reduced. But then and moreover, whenever I reduce the reduce moves, the blank spaces are going to increase. So since the blank spaces are going to increase, the error detecting capability is going to increase. What is a blank space in any parsing table? It is nothing but the error. So whenever I have more number of blank spaces, it means that we are even increasing the error detecting capability of the parser. So the overall thing is, I'm increasing the number of states because of having look aheads, and I'm decreasing the number of these reduce moves because of having the look aheads. Now for the same canonical collection of LR1 items, I want to construct the parsing table. In order to construct the parsing table, instead of I could not, I may not be able to construct the parsing table side by side on the same board. Let us number the states. You also number the states in the same way I am numbering it. Later you can refer to this diagram when I am constructing the parse table. So let's just number them the same way so that our diagrams will be consistent. This, let us call that one as I0, and this one as I1, and this one as I2, and this one as I3, this one as I4, and this one as I5, and this one as I6, I7, and A.I8, and this one as I9. Oh, I7 is already written. I7 and I9. Okay, these two states are already written. Now according to these numbers, you can observe one thing. So please number them according to this. So because the table is going to be, I'm going to construct the table according to these numbers. And before going ahead and then erasing it, I just want you to observe two things. One thing is, in this example, I3 and I6. Yes, I3 and I6 both are having the same LR0 items but different look aheads. That is one point. And then I4 and I7. I4 and I7, if you observe it, where is I4? I4 and I7, yes, I4 and I7 both are having same LR0 items but different look ahead. And then I8 and I9. So I8 and I9 both are having same LR0 items but different look aheads. So you just keep that in mind, because when I'm constructing LA-LR1 parsing table, I'm going to merge these states. Okay. So let me now show you how to construct the CLR1 parsing table from this canonical collection. Okay. This is the CLR1 parsing table for the previous example. So please refer to the state numbers that I have shown you, previously. If you write the state numbers accordingly, you are going to get this parse table. So in this parsing table, one thing you have to observe is the shift moves and go to moves, they are same as LR0 and SLR1 parsing table. Only difference is whenever you have reduce moves. So if you look at the fourth state, so what is R3 is this. See this? Now let us say the first production is SD rise AA is production number 1, and second production is AD rise small a capital A is second production, and then AD rise small b is third production. R3 means it corresponds to this. Now if you look at the fourth state I4, you will see that there is a production like this with dot at the ending, AD rise b dot, which means a final item, and then the look aheads will be a comma b. That is why only under A and B I am placing the reduce move. Okay, and if you look at I5, the production will be SD rise AA dot, this is the final item, and the look ahead symbol will be $. That is why only under $, I am going to place this R1, right? So, and even the same thing is true with I7 and I8. So only difference between LR0, SLR1 and CLR1 is the placement of reduce moves. And one thing you have to observe is, for the same grammar, if you construct canonical collection of LR0 items, and if you try to construct the LR0 or SLR1 parsing table, you will get only 7 states. But in CLR1 parsing table, we got 10 states. The reason is we got few states which are same in terms of LR0 items but different in terms of look aheads. Since we are having look aheads, the number of states may increase. So here the number of states have increased and number of reduce moves have decreased. Therefore obviously conflicts are going to be less. Now this is CLR1 parsing table, and we have seen that the size of CLR1 parsing table is very big. So if you observe this, the states I3 and I6 in the previous diagram, the states I3 and I6, they have the same LR0 items but different look ahead, and then I4 and I7 they have the same LR0 items but different look ahead. Similarly I8 and I9. So what you could do is we could merge these states into one state, which means if I merge I3 and I6 and if I make a new state I36, and if I merge I4 and I7 and if I make a new state I47, and if I merge I8 and I9 and if I make a new state I89. Okay. Now by merging these states into single state, what we could do is we could actually reduce the size of the CLR1 parsing table. How I could reduce the size of CLR1 parsing table is wherever there is 3 or 6, I am going to replace it with 3, 6. And now by doing this, what we are actually achieving is, even though because of look ahead aheads, two states are going to be in different states, or a single state is going to produce two different states because of look aheads. By merging them back, I am actually making the look aheads irrelevant. Therefore, if I merge these states, I'll again get the 7 states, right? So you should understand one thing. Now coming to the number of states in LR0, the number of states in LR0 is equal to number of states in SLR1. This one we are very sure. And now because of adding look aheads, the number of states in CLR1 actually have increased. The number of states in CLR1 might increase sometimes, or they may not increase. And when I merge these states which are differing only in the look aheads, I am actually combining the states. See what is happening is I am merging these states which are different in look aheads. Therefore, I am merging some of these states, and again I am achieving the same number of states in LLR1 parsing table as they were in LR0 or SLR1. Therefore, number of states in LLR1 is also equal to LR0, SLR and LLR. All the states, the number of states in all these 3 parsers will be same, but then there is a slight increase. There might be an increase coming to CLR1. So let's see how to convert this CLR1 table into LLR1 table. So in order to construct CLR1 table, we considered the canonical collection of LR1 items, and then we have constructed the table, and then I have seen that there are some states which are differing only in the look ahead. So I am going to combine only those states. So wherever there is 3 or 6, I am going to write it as 3, 6. Now 3, 6 is a new state. See, here there is shift 3. Now I am going to write it as shift to 3, 6. Shift 6, 3, 6, 3, 6. I should not write R3 as 3, 6, because this reduce move is nothing but the production number, and the shift move is nothing but the state number, right? And then S 3, 6. Okay. So wherever there is 3 or 6, I am going to write it as 3, 6. So we don't need 3 or 6, I am writing it as 3, 6. Okay. Now wherever there is 4 or 7, I am going to write it as 4, 7. So here there is 4, 7, and here there is 4, 7, 4, 7, and again this is also going to be 4, 7. Okay. And wherever there is 8 or 9, I am going to write it as 8, 9. So there is no S8 or S9, so you could write it as, yes, here there is 8, 9, and here there is 8, 9, right? So now change it even in the row numbers, 4, 7, 4, 7, 8, 9, 8, 9. So we have converted, we have combined 2 states into one state. Now we don't need 2 3 6s. So see this, I am going to see this 3 6 state and then this 3 6 state, they represent the same state. Therefore I am erasing it. I am erasing one of it. Okay. And now I don't want 2 8 9s. So I am going to erase it, but then once if you have to erase this 8 9, you see that the effect is is being replicated here. So that is the reason before erasing this I have to union them, merge them. Merging them is nothing but R2. Then you can delete it. And see this 4 7 also. In 4 7 again there are 2 4 7s, merge both of them, then you are going to get R3 here. Got it? So that is how this is again CLR, this is again LLR1 parsing table. So from CLR1 parsing table I converted it to LALR1 parsing table. So how did I do it? Whenever there are two states which are having same LR0 items but different look aheads, I am going to merge those two states into a single state. Therefore the final number of states are again 7. So LALR1 parsing table, LR0 and SLR1, all of them will have the same number of states, and number of states will be equal to the number of states in canonical collection of LR0 items. In CLR1 parsing table, the number of states could be more because of adding look aheads. Okay. So let's see some more examples and you will understand it better. Now let's see the possibility of conflicts in LR1 items. In case of LR0 items, we have seen this. So in case of, if I have LR0 items, right, if I have any production like this, any final item, A derives alpha dot, and if I have a B derives small a or something like this, there is reduce and there is shift, therefore there is a conflict. But then in case of LR1 items, the conflicts are not so frequent. The reason is, even though there is a final item here, if there is a shift move, this final item will be placed only under A and S, let us say $, right? So if you look at this final item is going to be placed, or the reduce move is going to be placed only on the look ahead, under look aheads. What are the look aheads? A and $. And now if you look at this production, there is a shift move, right? And in this shift move will be placed only under A. Therefore in this case, under A there is shift and under A there is reduce, therefore there is a chance of getting SR conflict. If there would not have been this A, if there is no A here, then there is no conflict here, right? And coming to this RR conflict, whenever I have to place two reduce moves, this is a final item, this is a final item, if these two reduce moves have to be placed under the same row, and they have to be placed under the look aheads. If they have the common look ahead, or there is any intersection in the look ahead, then only there is a chance of RR conflict. Therefore SR conflicts or RR conflicts will depend even on look aheads here. Previously in LR0 we don't have these look aheads, therefore we didn't consider much about the look aheads, right? So now, given a grammar, if you see any such state in canonical collection of LR1 items or any such state in canonical collection of LR1 items, we can stop and say that the grammar is not CLR1. We can stop it and say that it is not CLR1. If a grammar is not CLR1, definitely it is not LALR1. The reason is, if the table is having the conflicts, even if you reduce the number of states, then again it will contain the conflicts. Okay. And one more thing is, if a grammar is CLR1, it may not be LALR1 always. The reason is, even if there are no SR or RR conflicts in CLR1, there could be a chance of getting RR conflicts in LALR1. Consider this. In CLR1, let us say we have two states. A derives A dot, let us say A derives alpha dot, and again B derives beta dot. These are the final items, and this final item has to be placed under the look ahead A and this one under look ahead B. And let me say I have one more state. I am talking about CLR1. In CLR1 parsing table or canonical collection of LALR1 items, I have one more state. A derives alpha dot and the look ahead is small b, and B derives beta dot and the look ahead is small a. Now if I merge these two, I'll be getting one more state, and in this state A derives alpha. What will be the look aheads? Because of this one I get A, and because of this one I get B, which means under A and B I have to put the final item A derives alpha dot, and now I'll get one more final item B derives beta dot, and because of this one I get B, and because of this one I get A, again A or B. So what do you understand from this? From this one we can understand that we are going to place the final items under A and B, therefore there is a conflict. So even though there are no conflicts in the original CLR1 parsing table, by merging them there could be a chance of getting a conflict in LALR1. Therefore every CLR1 is not LALR1. If a grammar is not CLR1, definitely it is not LALR1. But if a grammar is CLR1, it does not mean that it could be LALR1. The reason is because of this. right? And one more thing is, if there are no SR conflicts in CLR1, there will be no SR conflicts in LALR1. If there are no RR conflicts in CLR1, there could be RR conflicts in LALR1. Okay, it is better that I'll take some examples and I'll show you how this is happening. So let me take the examples for some grammars which were not LR0, SLR1, and let us see whether those grammars could be this LALR1, CLR1. Okay, let's see some more examples. Yes, let's see this grammar. S derives AA, AB, BB. We have already seen this grammar, and I want to find out whether this grammar is any of these parsers. So first of all, we have found out that this grammar is LL1 because this production has to be placed under small a and this production has to be placed under small b. Therefore, two productions are not going into the same cell. Definitely it is LL1. Now I have to, and again we have even seen that the grammar is not LR0 or SLR1. The reason is, if I construct the canonical collection of LR0 items, if I consider this state S dash derives dot S, because of this S I have to add all S productions with dot in the beginning, AB dot BB BA, and because of A in the dot of A, because of dot in the beginning of A and beginning of B, I have to write A derives dot and then B derives dot. Now there is RR conflict, therefore it is not LR0. Now coming to this SLR1, where are you going to place this final item is in the follow of A. What is follow of A? Follow of A is A comma B. Therefore this one has to be placed under A comma B, this reduce move, and again this one has to be placed under follow of B. What is follow of B? Follow of B is again A comma B. Therefore two reduce moves have to be placed under AB and AB. So this grammar cannot be SLR1 also. Now I want to check whether the grammar is CLR1 or not. For that I have to construct the canonical collection of LR1 items. So let's see how to construct the canonical collection of LR1 items. This is an important example. So I am going to start with the augmented production with dot in the beginning. Augmented production is S dash derives dot S, and always the look ahead is going to be dollar for the start symbol. The reason is the start symbol will be always followed by dollar. Okay. And now because there is dot here, I am going to add all S productions. S derives dot AA, AB or dot BB, BA. Now why did I add these two productions? Because of this S. Now whatever is remaining after that S, what is remaining? Dollar. You find first of it. If I find first of dollar, I get dollar and dollar. Therefore dollar is the look ahead. Now because there is dot to the beginning of A, I have to add all A productions. I am adding A production with dot here. And now why did I add this A production? Because of this A. Whatever is remaining after that, small a, capital A, small b, dollar, whatever is remaining after that, find first of it. If I find first of this, I get small a, right? Which means this reduce move has to be placed under small a. Now what about this one? Because of this dot in the beginning of B, I am going to add B production. B derives dot epsilon, which is nothing but dot. Epsilon dot or dot epsilon or dot, everything is same. Okay. Now why did I add this production? Because of this B. Now whatever is remaining after that, what is remaining? BB, B, small b, capital B, small a, dollar. You find first of it. So what do I get? B. Therefore this reduce move, yes, there are two final items, but then there is no conflict. The reason is this reduce move will be placed under small a and this reduce move will be placed under small b. So this conflict, there was a conflict coming to LR0 items, but there is no conflict coming to LR1 items because both the reduce moves are placed under different look aheads, right? And now just can I stop here and say that the grammar is CLR1 since one conflict is resolved? In order to say that the grammar is CLR1, you have to finish the entire canonical collection of LR1 items and see that there are no conflicts in any of these states. So let's just finish it. On capital S it is going to be S dot comma dollar. So there is only one final item. In fact, it is not a final item because we added it, right? And on capital A, it is going to be S derives capital A dot small a, capital A B, comma dollar. The look ahead doesn't change, right? And on small a, it is going to be SD rise capital A small a dot capital A B comma dollar. Look at doesn't change when I'm applying the transition. And now I have to add A production, A derives dot. Now why did I add this A production? Because of this A. Now what is remaining? B dollar. What is first of B dollar? B, right? There is a final item, which means there is a reduce move, but then there is no shift item. It is go to, on capital A it is go to item, not a shift item, right? So SD rise capital A small a capital A dot B comma dollar. Look at doesn't change. And on small b it is going to be SD rise capital A small a capital A B dot comma dollar. So you might think that this is a conflict, but actually this is final item and this is a go to move. Only in the action part of the table we get a conflict, not in the go to move, which means only on terminals there will be shift, on variables there will be go to, so there is no conflict there. And finally we got only one final item in this state, therefore there is no conflict. Let's see what happens with capital B, SD rise capital B dot B A comma dollar, which means on I'm just moving the B, the dot over B. So because of that there is no change in the look ahead. So whatever was the look ahead previously, the look ahead will be same. Now on small b I get SD rise B small b dot capital B small a comma dollar, and because of this dot before B, if I apply the closure, I am going to get B derives dot comma. What is the look ahead? I added this because of this B, therefore I am going to get look ahead as small a, which means this final item will be placed under small a, but then there is no shift or reduce move, there is only one reduce move. This is actually go to. On capital B it is going to give us SD rise B capital B dot small a comma dollar. If you see this, whenever I am applying transition, look ahead doesn't change. Whenever I am applying this closure, look ahead is changing. On small a, SD rise B A dot dollar. Now one thing you have to note here is there are no states except the first state which are having two final items. Therefore, there could be a possibility of conflict here, but since both the final items are placed under different look aheads, there is no conflict. And in the remaining states, whenever there is a final item, there is no other final item or there is no other shift move. Whenever there is a final item, there is no other final item or there is no other shift move. Therefore, the grammar does not have any conflicts coming to LR1 items. Therefore, the grammar is CLR1. Now, my question is whether the grammar is LALR1 or not. What is the difference between CLR1 and LALR1 table? Whenever there are two states which differ only in terms of LR0 items and which have same look aheads, you are going to merge them. That is the difference. Now, if you look at this canonical collection of LR1 items, you don't find any two states which are having same LR0 items with different look aheads. Therefore, we need not consider LALR1 at all, because CLR1 parsing table is equal to LALR1 parsing table here. There cannot be any merging. Therefore, the same table applies both for CLR1 and LALR1. So, the grammar is both CLR1 and LALR1. Now, if you see this, the number of states are not increased because of this LR1 items. The reason is there are no two states with same LR0 and with different look aheads. So, coming to the number of states, all the parsers will contain same number of states. Of course, you cannot construct LR0 or SLR1 parsing tables, but in case if you consider constructing them, then the number of states in all the tables are going to be the same. Okay, so let's see one more example. Let's see this example. For this example, we have already seen that the grammar is not LR is not LL1 definitely, because these two productions, where is it? Yeah, these two productions B and B, they have to be placed in the same cell. Therefore, it is definitely not LL1. Now we have even seen that it is not LR0 because we got conflicts, and those conflicts were not resolved by even SLR1. Now I want to check whether the grammar is CLR1 or not, LLR1 or not. So I want to construct canonical collection of LR1 items. So starting step is S dash derives S dot, and what will be the look ahead for the first one, augmented production, dollar. S dash derives dot S. Okay. Now because of this dot before S, I am going to add all S productions. S derives dot AA dot BAC dot DC dot BDA. And now what will be the look ahead for all these productions? Why did I add these productions? Because of this S. Whatever is remaining after that S, what is remaining? Dollar. You have to add first of first. So first of dollar is dollar, 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 and dollar. Now I am going to add A production. A derives dot D because of this A. Now because of this A, I have added A production. Whatever is remaining after that, what is remaining after that? A followed by dollar. Find first of it. If I find first of it, I get A. Therefore look ahead is A. Now in LR0 items, we got a conflict because of this transition small d. Now on small d, what is the transition you might be getting is, one is S derives small d dot C comma dollar, because I am just moving the dot to the after d, and the look ahead doesn't change, which is dollar. And now A derives d dot comma A. A derives d dot comma A. This was a conflict in LR0 items. Now let's see if this is a conflict in CLR1 item or not. Now what is this shift move? Shift move is on C. And what about this reduce move? Reduce move is on A. This reduce move will be placed under A, and this shift move will be placed under C. Therefore, even though it was a conflict in LR0 items, this is not a conflict in LR1 items. So the grammar looks like it is CLR1, but then in order to say that, you should not stop here. You have to complete the entire canonical collection and then check it. Let's complete it. S derives DC dot comma dollar, right, final item. And now on capital A, S derives A dot small a comma dollar. On small a, S derives A dot comma dollar. On, let us say D is over, what is remaining? B. On small b, S derives B dot AC comma dollar, and again S derives B dot DA comma dollar, and because of this A, I had to add A productions. A derives dot D, and I added this A production because of this A. Therefore whatever is remaining after that, what is remaining after that? C dollar. You have to find first of it. What is first of C dollar? First of C, which is nothing but C. Okay. And now on small d, on small d, it is nothing but S derives B D dot small a comma dollar, this production, and then A derives small d dot a final item comma C. Now check this. Again there is a final item, and again there is a shift move. Now the final item here is, if you check it, the final item here is placed under, the reduce move is placed under C, and the shift move is placed under A. Therefore there is no problem, right? So since the shift and reduce are going to be placed under different entries, reduce is placed under C and shift is placed under A, therefore there is no problem at all here, right? And on small a, it is S derives B D A dot comma dollar, and on capital A, it is S derives B A dot C comma dollar, and on C, S derives B A C dot comma dollar. So we have finished it, and on small d it is over, d and a it is over, a over, c over. Yes. So now we have seen that there were some conflicts in LR0 items, but coming to LR1 items there are no conflicts, and moreover we have seen that there are no two states which are different in LR0 and same in which are different in LR1 items and same in LR0. Therefore this is the same table even for CLR1 and LLR1. So when the table is same, when there are no conflicts in CLR1 table, there will be no conflicts in LLR1 table, given that there are no mergings. Whenever there are mergings, there could be a chance that the grammar might not be LLR1. But for this example, the number of states are same both for CLR1 and LLR1. We shall see the next example. Let's take the next example, and in this example I want to find out whether the grammar is LL1 or not, LR0, everything. Now straight away we can say that the grammar is not LL1. The reason is this production and this production both are going into S row and under B column. Therefore two productions are going into the same cell. Therefore definitely it is not LL1. And next one is I have to find out whether the grammar is LR0 or not. For LR0 and SLR1 I have to find out the canonical collection of LR0 items. So I am starting with S dash derives dot S derives. Because of this, yes, I am going to add all. I am constructing canonical collection of LR0 items. No need of look aheads. Okay. I am adding all S productions, BAC, BC, BBA, and because of this dot before A, I am going to add A production. A production is dot D, and because of this dot before B, I am going to add B production. B derives dot D. Now this is I naught. Since we are actually finding, trying to find out whether the grammar is LR0 or SLR1 or not, we need not go with all the transitions. Just go with the transitions which will quickly lead you to some conflicts. So I want to see what are the final items. If I go on D, then I get definitely final items. A derives D dot and B derives D dot. So I got two productions with D dot and B dot. Now these two are final items, therefore there is RR conflict in LR0. The grammar is not LR0. Let us see whether this conflict can be resolved by SLR1 or not. In SLR1, where should we place this reduce move? Under follow of left hand side. What is follow of left hand side? Follow of A. What is follow of A? A and C. So this reduce move has to be placed under A comma C. And what about this one? This one has to be placed under follow of B. What is follow of B? B, A and C. So both of them have to be placed under A and C. So there is RR conflict here too in SLR1 too. The reason is both the productions have to be placed under the same one, right? So A and C, it is not SLR1. Now I have to check whether the grammar is CLR1 or not. In order to find out whether the grammar is CLR1 and LLR1, we have to construct the canonical collection of LR1 items. Okay. Now I am going to construct canonical collection of LR1 items. For that, the augmented production is S derives dot S and the look ahead is dollar. And because of this dot in the beginning of S, I have to add all S productions. I am adding them. S derives dot AA dot BAC dot BC dot BBA. Now why did I add these productions? Because of this S. What is following that S? Dollar. So what is first of dollar? Dollar, dollar, dollar and dollar. Now because of this dot I am going to add A production. Now A production is going to be A derives D dot. Why did I add this production? Because of this A. What is following that A? A dollar. Therefore what is first of A dollar? A. So look ahead here is small a. And now I am going to add B productions. So why did I add this B production? Because of this B. What is following that B? C. C is a terminal here, not a variable. And B is followed by C dollar. What is first of C dollar? It is C. Okay. So this is I naught. Now we have to find out the transitions. Previously we have seen that on small d we got conflicts. Let's see what happens to this on small d. On D it is going to be A derives D dot and look ahead is A, and again B derives D dot, and look ahead is C. Now if you see this, this is a reduce move and this is a reduce move because of final items, but then this reduce move has to be placed under A and this reduce move has to be placed under C. Therefore there is no RR conflict. Even though there is a conflict according to LR0 items, according to LR1 items there is no conflict because reduce moves are placed differently. Let's see. So we should not stop here and say that it is CLR1. The reason is there could be some other states which might have conflicts which might not be resolved by again LR1 items. Therefore complete the diagram. On capital A, S derives A dot small a comma dollar, and on small a, S derives A dot comma dollar. No problem with this one. Now let us see with small b. With small b, S derives B dot AC comma dollar, and because of this dot, and one more production is B dot BA comma dollar. Because of these two dots I have to add A production. A production is A derives dot D. And why did I add this production? Because of this A followed by CS. Now what is following A? CS. What is first of CS? C. Therefore I am writing it as C. Now because of this B I am going to add B productions. B derives dot D. Why did I add this production? Because of this B. What is following this B? A dollar. Therefore what is first of it? Small a. Right? Okay, and all the productions are added. Now this one on capital A, there will be no problem, you can fill it up. A B A dot C comma dollar, and on C A derives B A C dot comma dollar. Sorry, S derives. Okay, this one also no problem on B. S derives B B dot A comma dollar, and this one on small a, S derives B B A dot comma dollar. No problem. And this one on small d is going to give A derives D dot, a final item, and it has to be placed under C, and then B derives D dot, a final item, it has to be placed under A. Now check this. Again we got two final items, which means RR conflict might be there, but then in terms of LR1 items there is no RR conflict because the first reduce move is placed under C and the second reduce move is placed under A. Okay, so the grammar, even though there are RR conflicts in LR0, there are no RR conflicts in LR1. So let's see if everything is done. This one on capital B, yes, S derives capital B comma C dollar, and on C S derives BC dot comma dollar. Final item, no problem. Right, and we have seen that we have reached all the final items, and one thing is there are no conflicts in terms of LR1 items, therefore the grammar is CLR1. Now whether we have to find out whether the grammar is LA-LR1 or not. Are there any states in this which are differing only in the look aheads? Yes, we got two states, this state and this state. These two states are actually having the same LR0 items, but different look aheads. Therefore coming to LA-LR1 we have to merge these two states into one state. When I merge these two states into one state, what happens is A derives D dot, and then B derives D dot, and now because of this A I have to write A here, and because of this C I have to write C here, and again because of this C I have to write C here, and because of this C I have to write A here. Now see this, in LA-LR1 parsing table, even though in CLR1 parsing table there are no conflicts, because of this LA-LR1, because of merging, in LA-LR1 parsing table we got conflicts. The reason is this reduce move has to be placed under A and C, and again this reduce move has to be placed under A and C, right? Therefore the grammar is not LA-LR1. Okay, so this is a classic example in which because of merging there could be conflicts. Even though there are no RR conflicts in CLR1 parsing table, there is a chance of getting RR conflicts in LA-LR1 parsing table, and this is the example. Okay, so this example is only CLR1 parsing. This grammar is only CLR1 and it is not any of the other parsers. Okay, we shall see the next example. There are some class of examples like this one, and in these examples what we should do is, it is not just enough that we add we add closure once. I'll show you, you'll understand this. See, now I want to find out closure of this. So what is closure of this? Always we have to add whatever is there into the closure, which means dot a comma dollar. Now since there is a dot to the beginning of a, you have to add all the a productions. So I am adding all the a productions. A derives dot ab, or a derives dot epsilon is nothing but dot. Now why did I add these productions? Because of this a. So what is following that a? Dollar. What is first of dollar? Dollar and dollar. That is why I got look ahead as dollar. Now there, should I stop it here or should I add even more? That is the main difference. You might think that we could stop it here because since there is a dot to the beginning of a, we have added all the a productions. Yes, this is true, you could stop it here, but that is in the case of LR0 items. Coming to LR1 items, you might have to add a one more time. The reason is look aheads might change. So since there is a dot to the beginning of a, I am going to add a productions again one more time with dot in the beginning, ab or dot. Now why did I add this second set of a productions? Because of dot here, because of this a. Now what is following that a? B dollar. Therefore find first of b. What is first of b? A comma b. What is first of b? A comma b. Right? Now if you see this, we have added a productions two times. The reason is we are getting different look aheads. Therefore you could even write it like this. Instead of adding it two times, you could even write it like this: s derives dot a comma dollar, and merging these two you can write a derives dot ab dot, and here the look aheads are dollar and ab, dollar a b, and here the look aheads are again dollar ab. Alright, so this is same. So based on this example, I'll show you one more grammar where we might have to add the productions more than one time. So instead of adding the productions more than one time, I'll just add the look aheads. Okay, so let's see the next example. Yeah, let's see this grammar. Like in previous example, construction of LR1 items, canonical collection of LR1 items is not very straightforward. The reason is we might have to add same productions again and again because there will be changes in look ahead. With this example I'll explain you. See this. Now e dash derives dot e comma dollar. This is the augmented production, and because of this e, I have to add all e productions. So I'm adding e productions. E derives dot e plus t or dot t. Okay. Now why did I add these e productions? Because of this e, right? So after this e, what is remaining? Dollar. You have to find first of dollar. What is first of dollar? I get dollar and dollar. And again, because of this e, if I add e productions again, then because of this plus t dollar, I have to find first of plus t dollar. Then I am going to get look ahead as plus. See this. Because of this e, I am adding again e production. So what do I get? E derives plus or dot t. Now why did I add this again? Because of this e. Now what is following that? Plus t e dash. Therefore we have to even add plus again, which means I have to add look ahead as plus and plus. Got it? Now because of if you look at these two productions, they are having same LR0 items, but they are having different look aheads. Therefore instead of having these two, I can strike it off and then I can write plus here and plus here. Okay, so it doesn't make any difference, which means you can remove this and then have the same LR0 items and add the look aheads here itself. Okay, dollar and plus. Now because of this dot before t, I have to add all t productions. So I am adding t productions. T derives dot t star f or dot f. What will be look ahead is I have added it because of this t. So whatever is following that, what is following that? Dollar and plus. So here the look ahead will be dollar and plus. dollar and plus, right? And now because of this t, I have to again add all t productions, right? Therefore I am going to add again t productions. T derives dot t star f or dot f. Now why did I add these t productions? Because of this t. What is following the t? Star f dollar plus. So what is first of it? Star, which means I get again star and star. So if you see this, these two are same in terms of LR0 items, only in terms of look ahead they changed. Therefore it is as good as writing here as star. You need not have this copy and you need not have this copy, because we are adding the look ahead to the LR0 items themselves. Now because of this dot before f, I have to add all f productions. F derives dot I. Now why did I add these f productions? Because of this one. Now what is following it? Dollar plus and star. Therefore look aheads for this will be dollar plus and star. Got it? So this is I naught. So one thing you have to observe is we are not going to have these two. Instead of these two, I have added look aheads already there. Now what about this one? The transition of this on capital E. On capital E, this dot is going to be moved wherever there is capital E before the after the dot, which means E dash derives E dot comma dollar. And what about this? E derives E dot plus T comma dollar or plus. I just moved dot to the right of E. Okay. And now what about T? On T we get E derives T dot, this one, and because of this T derives T dot star f, right? So what will be look ahead here? Here the look ahead will be dollar and plus, and here the look ahead will be dollar plus and star, right? So one thing you have to observe is this is a final item and this is a shift move, but then this final item will be placed under dollar and plus, and this shift move will be placed under star. Therefore there is no problem. So even though it might look like a SR conflict, it is not. The reason is this final item is the reduced move corresponding to this final item will be placed under dollar and plus, and this shift will be placed under star. So there is no conflict. Okay. And on capital F, I get a final item. T derives F dot dollar plus and star. And on I, F derives I dot dollar plus star on the lookout, which means this final item will be placed under dollar plus and star. Okay. Now let's finish this. If I go on plus it is going to give E derives E plus dot T comma dollar and plus. The reason is when I am applying the transition, look ahead doesn't change, right? And now because of this T, I have to add all T productions. What are all T productions? T derives dot T star f or dot f. Now why did I add this one? I added this production because of this one. So what is following it? Dollar and plus. Therefore dollar and plus will be look ahead for these two. And now again because of this dot, I have to again add T productions. If I add T productions, then what will be look aheads for them? Look aheads will be this one, right? So I'll be getting star star because of this production. Now I have to add all F productions. If I add F productions, what do I get? F derives dot I, and what will be look ahead? I added it because of this F. What are the look aheads? Dollar plus and star. Okay. And now this one on T. On capital T it is going to be E plus T dot, E derives E plus T dot, comma, dollar R plus, this is the final item, and again T derives T dot star F, comma, dollar plus and star. Okay, so you can fill it up. So it is looking like as if there is a conflict. It is looking like a reduce move and it is looking like a shift move, but then this reduce move is placed under dollar and plus and the shift move is under star, therefore there will be no problem, no conflict. Okay, and you can fill it up. So only one thing that I want you to observe is whenever I am adding a production, again if I have to add one more time the same production, then you need not add it 2 times, you can just add the look aheads there. So that is one thing you have to keep in mind. Okay, we shall see more examples. We have already seen lots of parsers, all the types of parsers, LL1, LR0, SLR1, LLR1 and CLR1. Now let's see which one is powerful among all this. So if you can look at this diagram, I want to explain the power of all the parsers using this diagram. Okay, now grammars are of 2 types, unambiguous grammars and ambiguous grammars. So first thing is, if a grammar is ambiguous, no parser could ever parse it, not even the most powerful parser, which is CLR1 parser, right? So only one type of parser can parse even some of the ambiguous grammars, and that parser is operator precedence parser. Therefore operator precedence parser can parse some ambiguous as well as unambiguous grammars. Now in coming to this unambiguous grammars, we have various types of parsers which can parse some of the unambiguous grammars. Now the least powerful parser is LL1 and LR0. Now if a grammar is LR0, it will definitely be SLR1. What is the main difference between LR0 and SLR1? In LR0, the reduced moves will be placed in the entire row. And what about SLR1? The reduced moves will be placed only in the follow of left hand side, which means we are reducing the number of reduced moves, therefore we are reducing the number of conflicts, therefore SLR1 must be really powerful. And now what about LALR1 and CLR1? So in coming to CLR1 and LALR1, we are not placing the reduced moves in the complete row or in the follow of left hand side. We will be placing the reduced move only in the look aheads. Therefore we are still reducing the reduced moves and the possibilities of conflicts. So if you look at this, the table size is might increase in CLR1 as well as reduced moves might reduce, and LALR1 and SLR1 the table sizes are same. So this is the order of power. If a grammar is LR0, it is SLR1, LALR1 and CLR1. If a grammar is SLR1, it is LALR1 as well as CLR1. If a grammar is LALR1, it is definitely CLR1. Now one thing you should observe is LL1 is not included completely in LR0 or it is not included completely in SLR1, but then it is completely included in LALR1. So from this you must understand that every LL1 grammar is LALR1 grammar. The reason is it is completely included in LALR1, right? So if you take a grammar, if you find out that it is LL1, definitely that grammar will be LALR1. So questions on this in the relationship will be, one thing is what are the relationship among the table sizes, and second thing is what about shift moves, reduce moves and error entries. And given a grammar, they'll ask you what type of grammar it is it LL1 or LR0, SLR1. Okay, and some theoretical questions is, they'll say let a grammar is LR0, then what are the following statements are true? It is definitely SLR1, it is definitely LALR1, it is definitely CLR1. So some questions will be like this. Or if a grammar is LL1, then which of the following is true? It is definitely LR0, it is definitely SLR1, it is definitely LALR1. What is the answer? It is definitely LALR1. If a grammar is LL1, it is definitely LALR1 because it is completely included. Okay, we shall see some of the questions which are asked in previous examinations, and we shall discuss about this. Consider a question, this one. They are asking about SLR1 and LALR1 table for a grammar. So for a given grammar, we know that SLR1 and LALR1 tables will have the same number of states. only in case of CLR1 table the number of states could be more, but in terms of SLR1 and LLR1 the number of states will be same. Now they are asking whether go-to of both the tables may be different. So actually if you consider that canonical collection of LR0 items or canonical collection of LR1 items, now in case of LLR1, even though we are looking at LR1 items, we are combining two LR0 items which are different only in look aheads, which means in case of SLR1 and LLR1, the number of states and the number of transitions will be exactly identical. Therefore, go-to moves will not be different, they will be same. So this is false. Go-to moves are definitely going to be same in both the tables. You can take an example and you can check it. Next one is shift entries are identical in both the tables. Yes, shift entries are definitely identical in both the tables. And next one is reduce entries in the table may be different. Yes, reduce entries are obviously different. In SLR1, where are you going to place reduce entries? In the follow-up left hand side. And what about LLR1? We are going to place the reduce entries in the look aheads. Therefore, unless the follow-up left hand side and the look aheads both are same, the reduce will be placed in a different entries. Therefore, they may be different. In case if both are equal, if the follow-up left hand side and the look aheads both are equal, in that case we get the same table, same reduce entries. Otherwise, we don't get the same reduce entries. So reduce entries in both the tables may be different. And next one is error entries in the tables may be different. Yes, the reason why error entries in the tables will be different is whenever the reduce entries are changing, see, shift is same, go to is same, but only reduce entries is changing, which means if there is a change in reduce entries, then there will be change in blank entries. And what is a blank entry? Blank entry is definitely reduce entry, error entry. Therefore, error entries in the tables are definitely going to be changing. And one more question they might ask you is, one is, let us say N1 is the number of states in SLR1 table for a given grammar, okay, and N2 is number of states in LLR1 table, and N3 is number of states in CLR1 table. Now they didn't give you any grammar, they are saying that these are the number of states for some grammar. What can you say about the relationship among N1, N2 and N3? Whatever the grammar is, always number of states in SLR1 and LLR1 are same. The reason is, even if the lookaheads are different, we are merging the states, therefore we get, as you know, same number of states in SLR1 and LLR1. So N1 is definitely equal to N2, right? And for some grammars there is a chance that we might get more states because of some states having more different lookaheads, which means some states will be having the same LR0 items but the lookaheads will be different. Therefore, some states will be having some grammars will be having more number of states in CLR1, or they might be equal also. So less than or equal to N3. Whether it is less than or it is equal to, that depends on the grammar. Given a grammar, we can resolve this issue. So in general, this is the relationship, which means in general the number of states in CLR1 could be either greater or equal to number of states in SLR1 and LLR1. But if you have to find out whether it is actually greater than or equal to, then we should take a grammar and we should see it. So if the grammar contains more than one state which is having same LR0 items but different lookaheads, then we can say that the number of states in CLR1 is greater than number of states in LLR1 and SLR1. We shall see some examples where we can resolve this. So in this grammar they are asking whether this grammar is LL1 or these are the options given. So what is this grammar? Now if you look at this grammar, we have already seen this grammar as a running example with a different name, isn't it? So this grammar is nothing but S derives A derives small a capital A or small b. The same grammar they have asked, right? So actually this grammar is everything, which means this grammar is LL1, LR0, SLR1 and LLR1. So this grammar is definitely LL1, this is SLR1 as well as LL1, this is LLR1 as well as CLR. So that is why the first option is right. If you have any doubt, you can see this. Where are you going to place this production? This production is going to be placed in the S row, and in the first of CC, which means under C and D. Since there is only one production, there is no chance that we get one more production in LL1 parsing table. And where are you going to place this second production? This production is going to be placed under C row and under the column of small c, and this one is going to be placed under C row and under the column of small d. Therefore, this grammar is definitely LL1. Now let's see. We want to find out the number of conflicts in SR, the number of SR conflicts and RR conflicts in this grammar in the DFA with LR0 items. DFA with LR0 items is nothing but canonical collection of LR0 items. Okay. Now, they are not actually asking whether this grammar is LR0 or not, SLR1 or not. They are asking what is the number of conflicts. Therefore, you have to construct the complete canonical collection of LR0 items, and in every state you have to examine whether there is SR conflict or RR conflict. Let's see. The starting point is S dash derives dot S, and this is LR0 item, therefore you need not write any look ahead. And because of this S, I am going to add all the S productions. What are all the S productions? S derives dot SS or dot A or dot. That's it. Because of this dot, even if you add one more time S, you get the same thing, because these are just LR0 items. Okay. And now this dot is because dot epsilon or epsilon dot is simply a dot. Now if you look at this production, it is nothing but a reduce move, and this is nothing but a shift move. So therefore there is SR conflict. In this state there is one SR conflict. There is reduce move and there is shift move. Let us see what happens on capital S. On capital S, S dash derives S dot, and let's write dollar here, so that you will not get confused between reduce move and then accepting move. And what about this? S derives S dot S. Because of this S, I have to add all S productions. What are they? S derives dot SS or dot A or dot. Again, in this state there is a final item, therefore reduce move, and there is a shift item, therefore this is also shift reduce conflict. One shift reduce conflict we got. Now let's see what happens on S one more time. It is nothing but S derives SS dot, and again see, because of this one I am getting S derives SS dot, and again because of this S derives S dot S or small a or dot. Now see this, because of this final item we got reduce move, and because of this there is a shift move. So there is shift reduce conflict, and moreover there is a final item here also. So between these two there is reduce conflict, and between these two there is shift reduce conflict. So here there is one shift reduce and one reduce conflict is also there, right? Now what about on small a? This one on small a is going to give S derives small a dot, and this one on small a is also going to give the same, and this one on small a is also going to give the same. So this is the canonical collection of LR0 items or DFA with LR0 items, and we found out that in this state I got one SR conflict, and in this state I got one SR conflict, and in this state I got one SR conflict as well as one RR conflict. Therefore in total we have 3 SR conflicts and 1 RR conflict in 3 states. Okay, so that is the answer for it. We shall see more. Yeah, look at this grammar. They have given this grammar E derives E plus N, E star N, and then N, and they have given a string N plus N into N. Now the question is, for this string, for the given grammar, what are the handles in the right sequential form of reduction? Right sequential form of reduction is nothing but bottom up parsing, and handle is nothing but whenever we find a part in the string, what is that part we are going to reduce to the left hand side. For this example, see this, if I have N plus N star N, now I will be reducing the first N to E, isn't it? Therefore this N is called a handle. Why? Because it is reduced to E. And now what is remaining is E plus N into N. Then I will be reducing this E plus N into E. Now what is the handle is E plus N. Now what is remaining is E star n. Next I will be reducing E star n to E. Therefore what is the handle is E star n. See, maybe you can understand it in the other way. E derives, I am just writing the derivation. E derives E star n, and then E derives E in place of first E plus E star n, and then this derives, C derives n plus n into n, right? So if you look at this, what are the handles is, you go in the reverse order and you can find out. So initially n has been reduced to E, therefore n is a handle, and then E plus n has been reduced to E, therefore E plus n is a handle, and then E star n is reduced to E, therefore E star n is a handle. So we have three handles. One handle is n, other handle is E plus n, other handle is E star n. Therefore D is the option. Okay. Now in this question, a grammar is given, and now the question they are asking is whether the grammar is, what is the relationship between the number of states in SLR1, CLR1, LALR1 for the given grammar, which means they are saying that in case if number of states in SL, I just I have just condensed the question, I simplified it so that it will be easier for me to write and for you to understand it. So the question what they are asking is, they are given a grammar and they are saying that if I construct SLR1 parsing table, then the number of states will be n1. If I construct CLR1, LR1 parsing table is also nothing but CLR1. CLR1 is also sometimes called as LR1. Okay. Now they are saying that for this grammar, CLR1 contains n2 states and LALR1 contains n3 states. Then they are asking you what is the relationship between n1, n2 and n3. So one thing you know that n1 is definitely equal to n3. This one is for sure. Why? Number of states in SLR1 and LLR1 both are same. And then second thing, we know that this n2 can be greater than or equal to both of them, isn't it? Which means for some grammars number of states in CLR1 can be larger, and for some grammars number of states in CLR1 can be smaller. So that one we have to find out. First thing is for sure n1 is equal to n2, and the second thing is we are not sure whether there is a difference in the number of states here. So in order to just resolve that issue, we have to construct the canonical collection of LR1 items, and in case if you get two states with same LR0 items and different look aheads, then we can say that number of states are larger. So you need not finish the entire canonical collection of LR1 items. You have to start with canonical collection of LR1 items. Why? Because I want to see the size of CLR1 and compare it with SLR1 and LALR1. Definitely I need canonical collection of LR1 items, and then I should know where to stop it. I am going to stop the solution if I get at least two states which are same in look aheads, which are same in LR0 items but different in look aheads. Because of those two states only we might get extra number of states. If we don't find any such states, we can say that the states are same in CLR1 and LLR1. Now let me construct canonical collection of LR1 items. So first one is s dash derives dot s comma dollar. This is the augmented production, and because of this s I am going to add all s productions. S derives dot and dot a. And why did I add this s? Because of this dot before s. What is following that? Dollar. What is first of dollar? Dollar and dollar. This is the first one. And now on small s, on open brace. On open brace it is going to be s derives open brace dot s close brace comma dollar. So because of this dot before s, I have to add all s productions, right? What are all s productions? S derives open brace s. And why did I add this second s? Because of this s. What is remaining after that? Close brace and dollar. Therefore what is first of close brace and dollar? It is simply close brace, right? And then s derives dot a, and this is also added because of this production, therefore look ahead is going to be close brace. Now if I get two states which have same LR0 items but different look aheads, I can stop and say that number of states in CLR1 are greater. Why? Because we could merge these two states later to find LALR1. Okay. Now on small a we are going to get s derives small a dot comma dollar, and here also on small a we are going to get one more state s derives small a dot comma close brace. Now if you observe these two states, both these states are having same LR0 item, but a different look ahead, which means coming to the CLR1 table, both the parsers are different. Coming to the CLR1 table, these are two different states, therefore number of states are more, and when we go for the construction of LILR1, we actually merge these two, therefore number of states will reduce. So the actual relationship is, for this grammar, for this example, n1 is equal to n3. It is always true for any grammar, but for this example they are less than n2. The reason is number of states in CLR1 is more, there are more states, right? So what is the option? The option is B. Okay. So we have seen that many of the parsers cannot work for ambiguous grammars, right? But then there are some advantages if you go for ambiguous grammars. The advantages are, one thing is ambiguous grammars are simpler to see. I'll just give you an example and show you what is the difference between ambiguous grammar and unambiguous grammar. We already know what is an ambiguous grammar. So if for any string, if I get more than one parse tree, then the grammar is ambiguous. Let us say this is the grammar, e derives e plus e star e or id. This is a grammar, and we have seen that this is an ambiguous grammar. The reason is, for any string we are getting, for some string we are getting more than one parse tree, and we have seen that the unambiguous version of the same grammar which generate the same language but with the unambiguous grammar is this one, e derives e plus t, t derives t star f derives id. So this is an ambiguous grammar and this is the unambiguous version of the same grammar. Now we have seen that all the parsers will fail to parse this grammar. The reason is, okay, except that operator precedence parser, remaining all parsers fail to parse this grammar. The reason is the grammar is ambiguous, and if you have to use any parser like LR0, SLR1, LALR1, CLR1, we are supposed to use this grammar, right? But then even though there are some conflicts using ambiguous grammars, sometimes we still go for ambiguous grammars because there are some advantages. One advantage is, if you look at the number of productions are less here, which means the grammar is shorter and easier to represent. And second thing is, this is very natural and meaningful. If you see this, expression is nothing but expression plus expression or expression into expression or id. It is natural to read and it is simple to understand. It is easier to understand. And the third advantage is, see this. Now coming to this grammar, the associativity and precedence are fixed, which means if you take this grammar, you need not specify the associativity and precedence, or you cannot change the associativity and precedence later. So by looking at this grammar, you can find out that star is having higher precedence than plus, and plus is left associative, therefore, and star is left associative. This is fixed. But coming to this grammar, the rules are not fixed, which means star and plus, the precedence is not fixed, and moreover associativity is also not fixed. Therefore there is flexibility in this grammar. The reason is, later at some point of time we can specify what about the associativity and what is about the precedence. We can change the associativity and precedence. And next one is, let us say I have to derive id. Directly e will derive id, but if you take this grammar, e will derive t and t will derive f will derive id. So coming to bottom of parsers, if I have to reduce id to e, I have to reduce it to f and then f to t and then t to e. So it is going to take 3 steps. But here using this grammar, it is simply one step. So you can understand that from this explanation you can understand that there are some advantages of using ambiguous grammars. So even though ambiguous grammars are not useful for parsing, there are some advantages if you go for it. Now let us see why this ambiguous grammar is not useful for parsing. One reason is, we get lot of conflicts in the parsing tables. If you go and if you try to construct LR0 parsing table for this grammar, we end up in states where we get conflicts. Now if you could resolve those conflicts somehow meaningfully, then yes, we can use this grammar. We can use this grammar in which there will be less number of productions, therefore there will be less number of states and the parsing table will be smaller. Only thing you have to consider is there will be some conflicts which you have to resolve. For example, you might enter one state where you might get this production like this. The conflicts will be e derives dot here and then e derives e plus e dot. Along with some other productions, you might get this production. If you go for canonical collection of LR0 items for this grammar, you might end up in this state. So there could be some other productions too, right? But what is the meaning of this is, we have reached a state in which I am looking at plus and I have already seen 1 plus. I am looking at 1 plus and I have already seen 1 plus. Where do you get this is id. If I have the input id plus id, then if you are standing at this point, if you have scanned till this point, it means that you have already seen 1 plus and you are about to see 1 plus. You have already seen 1 plus and you are about to see 1 plus, right? Now there are two choices, whether either you could reduce this to e, which means you could perform this one first, or you could shift. Shift means you could reduce this one. If I go for shift, then plus is becoming right associative. If I go for reduce, then plus is becoming left associative. Why? Because if I reduce it here itself, then leftmost plus is getting evaluated first. So if I reduce it here, I will get this and then get this, which means this one is getting evaluated. If I go for shift, this one is getting evaluated. So if you can resolve this conflict meaningfully and manually, yes, we could use that grammar. For example, in this case, if you want plus to be left associative, even if there is SR conflict, you have to go for reduce so that you will get this, right? So one more example is, maybe you will get one more state like this. One more state is e derives e dot plus e and then e derives e star e dot. Now see what should be done here. So in this state, when do you get such a state is, if the input is id plus id star id plus id, and if we have scanned till this point, which means we have seen e star e and then we are going to see a plus. So whether should you reduce this to e or should you shift it to plus, right? Which means should you go for a reduce move or should you go for a shift move? So in this case, if you want to give more precedence to star, then you should go for reduce move. Therefore, even though there is SR conflict here, in this case if you go for reduce, this can be resolved successfully. And let us say there could be one more example like this. One more state you might get, and in that state you might get something like this. E derives, we have seen e plus e and we are about to see a star. E derives e dot star e. Now when do you get this state is, if the example is, if the input string is id plus id star id, which means you have seen one id plus id and you are about to see a star. What do you want to do? Do you want to reduce this or do you want to go for star and then come back to plus? So there is SR conflict here. So if you go for reduce, we are actually giving higher precedence to plus. If you go for shift, we are giving higher precedence to star. Therefore in this example, in this state, if you want to resolve it meaningfully, you should go for shift, which is nothing but giving higher precedence to star. So even though some grammars are ambiguous, we could still go and use them for parsers, bottom up parsers, if you can resolve the conflicts meaningfully. And there is one more parser generator tool. There is a tool called Yak. In Unix there is a software called Yak, yet another compiler, which is a software which will automatically generate a parser for the given grammar, and this is actually using LALR1 parsing tables. So whatever grammar you give it as input, it is going to produce LALR1 parsing tables as output. And in this case, whenever Yak comes across a grammar which is having conflicts, it might not, it need not be any ambiguous grammar. Even for unambiguous grammars also, whenever React comes across any conflicts, if there is a SR conflict, it is going to go for shift, and if there is RR conflict, it is going to go for first reduce. So SR conflicts are always resolved in favor of shift, and RR conflicts are always resolved in favor of first reduce. What do I mean by first reduce is, if I have R1 and R2, these two are the two productions, first production and second production, then it is going to take the first production itself, automatically it is going to include. So if you give any grammar to act as input, if the grammar is containing conflicts in LLR1 parsing table, then the conflicts are automatically resolved by ACK. If there is a SR conflict, it is going to go for shift, and if there is a RR conflict, it is going to go for first reduce. First reduce means if I have productions R1, R2, R3, so on, it is always going to take R1 as the first, R1 as the main choice. Okay. So till now we have seen some grammars, and for the grammars we have given some parsers. Now, but in practice, whenever we go for any compiler design, which we practically implement, along with the grammars, we are even going to associate some informal notations. For example, let us say this is the grammar, this one this is the grammar, and along with this I'll have even some informal notations associated. These are also called as semantic rules. So a grammar plus semantic rules is going to be SDT. So in the compiler design, we are not just going to use plain grammars. Along with the grammars, we give some meaningful rules, so that syntax analysis as well as many other things like code generation and storing of some values in the symbol table, intermediate code generation or expression evaluation, many things can be done in parallel at the time when the parsing is being done. Therefore, parsers are even capable of doing more when we give along with the grammar some other actions also. These are called semantic actions. Now this is an example which is used to evaluate a expression. For example, I'll take a string, let us say 2 plus 3 into 4. This is the expression and I want to evaluate it. What will be the answer for this? The answer will be 20, right? So the answer will be 14. 3 into 4 is 12, plus 2 is 14. So I have to get 14 as the output if I carry out this SDT on this input. So first thing is, as usual, we have to derive the parse tree. So the procedure is like this. How to carry out a SDT on an input is, first you have to carry out the parse tree. So let me construct the parse tree. E derives, E plus T, T derives, T star F. Let me write it in a, because E derives, E plus T, E to T, T to F, F to number, and then T derives, T star F, and then T to F, F to number, F to number. Okay, so this number is nothing but 2, this number is nothing but 3, this number is nothing but 4. So number is nothing but the token, and 2, 3, 4 are lexical values. Lexical value means what does this number actually mean. So lexical value means whatever is the actual value, we are going to call it as lexical value, right? So after generating the parse tree, we are going to traverse it top down, left to right. That is the method. So I am going to traverse it top down, left to right, top down, left to right. And whenever there is a reduction, this is a reduction. What is the reduction? Number is reduced to F. Whenever there is a reduction, we go to the production and carry out the action. So what is the reduction that we are using? Number is reduced to F. Whenever there is a reduction, number is reduced to F, we go to the production and perform the action. What is the action? F is associated with a variable called value. This is also called as attribute. Here every variable is going to get an attribute. Variable is nothing but non-terminal, every non-terminal is going to get a attribute in this SDT. It is not necessary in that in all the SDTs we should get it, but in this SDT every variable is going to get a attribute. Now what is the attribute associated with f? It is VAL, value. So f dot value is equal to num dot lexical value. So what is num dot lexical value? 2, which means this information of 2 has passed to f. And now again there is a reduction. What is the reduction? F is reduced to t. Now when f is reduced to t, this is the production, right? F is reduced to t. T to f is the production. And what is the action? Action is t dot value equal to f dot value, which means here I should substitute t dot value equal to whatever was f dot value. What was f dot value? 2, right? And again there is a reduction. What is the reduction? T is reduced to e. Then what is the production? E derives t. What is the action? E dot value equal to t dot value, which means here I should get E dot value equal to t dot value, which is 2. Therefore 2 has reached the expression, this one E, and then it is waiting there. Okay, again this is not reduction. Why? Because E has seen E plus E. E plus E you cannot reduce to E. Again there is a reduction, right? So what is the reduction? Number is reduced to f. What is the action there? F dot value equal to number dot lexical value. Therefore f dot value equal to number dot lexical value, which is 3. And again there is a reduction. What is the reduction? F is reduced to t. When f is reduced to t, the production is t to f, right? So what is the value? T dot, what is the action? T dot value equal to f dot value. Therefore t dot value equal to f dot value, which is 3. This is not a reduction. This is a reduction. What is the action? F dot value equal to num dot value, which is 4. This is a reduction. What is the production? This is the reduction, and the production is t derives t star f, which means this one. Production is t derives t star f, which means t dot value is equal to t dot value into f dot value. See, here I am writing t dot value and t dot value. So you might get confused which one is left side t and which one is right side t. Just to avoid confusion, for the right side t I am writing 1, and here also I am writing 1. So it doesn't mean that t1 is a different variable. It is the same variable, just to have that marker, in the sense just to distinguish between left side plus and right side plus, I am going to use it. So t dot value equal to t1 dot value into f dot value. There is nothing much different. The only difference is this t1 is nothing but the t in the right hand side. Okay. Now what is the action with this? T dot value, which means left hand side variable will get the value whatever was right hand side t dot value into f dot value, which means 3 into 4 t dot value into f dot value will be given to this t value. Therefore this t value equal to 3 into 4, which is 12. And again there is a reduction. What is the reduction? E plus t is reduced to E, which means the production is E derives E plus t, right? Then what is the action associated with this? E dot value equal to E dot value plus t dot value. Therefore the action is E dot value. Here also we have two E's, right? So left side we have one E and right side we have one E. Just to distinguish between left side E and right side E, I am going to write one here and one here. That is just to distinguish the right hand side E from the left hand side E. Therefore E dot value equal to E dot value plus t dot value, which is nothing but 14. So if you observe this, how I did it is SDT is nothing but grammar plus semantic rules. And whenever after generating the parse tree, I am going to traverse the parse tree top down, left to right, and whenever I am traversing, I am going to perform, whenever there is a reduction, I am going to take the production and perform the action, right? So one thing you have to observe is, in SDTs every variable is going to get a attribute, one or more attributes, or sometimes it might get even 0 attributes also. That depends on the type of SDT we are talking about. Okay, so we shall see more examples and understand what is the advantage of SDTs. This is an SDT, this is the grammar and this is the SDT. and this SDT is used to convert infix expression to postfix expression. And in the previous example, I have shown you how to evaluate a expression, like what is the final value of the expression, but here I want to convert the expression into postfix expression. So there are two ways actually. So this SDT, whenever we say syntax directed translation, this SDT will be carried out along with the syntax analyzer or parser, which means while doing the parsing itself, the parser will carry out all the actions associated with the productions. And we know that there are two types of parsers, one is bottom up and other is top down, right? So if you have, if you remember that bottom up and top down, in top down parsers we start from the root and we go to the children, and in bottom up parsers we go to the terminals and we go, from terminals we try to reach to the top. So in the previous method, what we have seen is whenever we perform a reduction, we are performing the action. So that is nothing but the way how a bottom up parser will do. Now let me show you how the top down parser will work with this SDT as well as bottom up parser will work with this SDT. Let me take an example, 2 plus 3 into 4. So I want to find out what is the postfix expression for this infix expression. Okay, so first thing is, as usual, you have to construct the parse tree. So while constructing the parse tree, you just think about this one also. While constructing the parse tree, let us say this is the entire right hand side of the production, which means the E production is not just E plus T, it is E plus T followed by a semantic action. And let us name this semantic action as semantic action number 1. This is semantic action number 2, semantic action number 3, semantic action number 4, semantic action number 5. So which means along with the productions, I am even going to write the semantic action. So in order to derive this, we know that I have to use this tree. E derives, one is E plus T, and this production is followed by the semantic action number 1. Therefore I am writing semantic action number 1. And then T derives T star F, and it is followed by the production number 3. So I am writing production number 3. And now E derives T, but then it is followed by production number, the semantic action number 2. And then T derives F, but then F is followed by semantic action number 4. And then F2 number, and then semantic action number 5. And again same thing, T to F followed by semantic action number 4, and then here F2 number is followed by semantic action number 5, and again F is derived as number followed by semantic number 5. Okay, so what are these three numbers is, this number is nothing but 2, this number is 3, and this number is 4. Therefore it is 2 plus 3 into 4. So we got the entire expression. Now how does the top down parser work for this grammar is, top down parser will take this SDT and try to construct this parse tree, and after constructing the parse tree, the way it will evaluate it is, we are going to traverse the parse tree top down, left to right, and whenever we come across any semantic action, we are going to perform the action. For example, top down parser will traverse the parse tree top down, left to right, top down, left to right, and whenever it comes across any semantic action, it will perform it. So now it is coming across the semantic action number 5. What is semantic action number 5? Printf number dot lexical value. So what is number dot lexical value? Here it is nothing but 2. Therefore 2 will be printed. And now next one is semantic action number 4. What is semantic action number 4? Nothing. Therefore leave it. Next one is semantic action number 2. What is semantic action number 2? Nothing. Therefore leave it. And next one is, I am just traversing it. I didn't come across any semantic action. Yes, again I came across semantic action number 5. What is semantic action number 5? Printf number dot lexical value. And what is the lexical value for this number? It is 3. Therefore 3 will be printed. and then again semantic action number 4. What is semantic action number 4? Nothing. Therefore we need not print anything. And then again semantic action number 5. What is semantic action number 5? Printf number dot lexical value. What is the number dot lexical value here? 4. So 4 is printed. And then now again semantic action number 3. What is semantic action number 3? Printf star. So star is printed. And now semantic action number 1. What is semantic action number 1? Printf plus. So plus is printed. Therefore this is how the top down parsers will act. So how did I do this? I was trying to just derive the parse tree from the start symbol, and I am using the all the productions as it is. In place of semantic actions I am just writing numbers representing the semantic action. And then after doing this I am just traversing the parse tree, and whenever I encounter any semantic action I am just performing the semantic action. So that is how top down parsers will work, and even they are able to produce the same output, the postfix expression. Let me show you how the bottom up parsers will work for the same example. For the same example, bottom up parsers. So if you remember, bottom up parsers are mainly focused on reductions. Therefore they will try to reduce the terminals to the variables. Terminals means these terminals or the right hand side to left hand side, and whenever they reduce they perform the action. So whenever they go for a reduction they'll take the production and then perform the action. So how does it look like is E derives E plus T, T derives T star F, F derives number, T to F, F derives number, E derives T, T derives F, F derives number. Okay. Now we are just traversing it, and then there is a reduction. So what is the reduction? Number is reduced to F. Number is reduced to F. What is the production? Printf the number value. So what is the number value here? 2, 3 and 4. Therefore for this production, the reduction, for this reduction the production is number is reduced to F, and what is the action? Printf 2. Therefore 2 is printed. And now next one is F is reduced to T. What is the action? F is reduced to T? Nothing. So don't do anything. And again T is reduced to E. What is the action? T is reduced to D? Nothing. Therefore don't do anything. And now number is reduced to F. What is the action? Printf number dot lexical value, which means printf 3. And F is reduced to T. What is the action? Nothing. And again number is reduced to F. What is the action? For this number is reduced to F. Printf lexical value, which means 4. And again T star F is reduced to T. What is the action? Printf star. Isn't it? T star F is reduced to T. T star F is reduced to T. Therefore what is the action? Printf star. I printed star. And next production is E plus T is reduced to E. E plus T is reduced to E. What is the action? Printf plus. So even by using the bottom up parsing method we got the same output, and by using the top down parsing method we got the same output. So SDTs can be used both by bottom up parsers as well as top down parsers, and just the difference is when are you going to carry out the actions. Okay. So we shall see the next example. Now let's see this grammar. The SDT is this is the SDT given, and now the question is what is the output printed if we carry out this SDT on this input string. So you could use any method either by top down parser or the bottom up parser, but let us say what happens if we use LR parsers, the bottom up parsers. If I use LR parsers in order to generate this particular string from this SDT, how will it react is, first thing is you have to generate the entire string. I'm just generating this string S derives X, X, W, and W derives S, Z, and S derives X, X, W, and W derives S, Z, and finally S derives Y. So that is why we get X, 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 Y, Z, Z. Okay. Now how does the LR parser work is, whenever there is a reduction we go to the production and perform the action. So see this, is this a reduction? No, not a reduction, because we know XXW will be reduced to S, right? Is this the reduction? No. It is a reduction? No. Yes, this is a reduction. What is reduction? Y is reduced to S. Now what is the production? Y is reduced to S. What is the production? This one. What is the action? Printf2. Therefore for this reduction the action means 2 will be printed. And now SZ is reduced to W. SZ is reduced to W. What is the action? Printf3. Therefore 3 will be printed. And now XXW is reduced to S. XXW is reduced to S. What is the action? Printf1. 1 will be printed. And then SZ is reduced to W. SZ is reduced to W. What is the action? Printf3. So 3 will be printed. And next one is XXW is reduced to S. XXW is reduced to S. Therefore what is the action? Printf1. Right? So this is the output printed if we perform this particular SDT in order to generate this particular string, or if we take this string and do the bottom up parsing and carry out that SDT, we are going to see this output. Okay, so we shall see one more example. Now for this example, consider this example where we have this SDT and that is the word that has to be generated. And just examine the grammar given. See, E derives E star F for F. So where star is nothing but multiplication, and then T derives F minus T or T, F minus T or F, where minus is nothing but subtraction, that is fine. And now F derives 2 and F derives 4. So if you observe this, there is nothing called a token here. Generally, what does if you see other grammars, we generally see that F derives number or F derives ID, but then here directly they are deriving the numbers, which means lexemes are directly used in this grammar as the numbers itself. Okay, so lexemes are the tokens itself. So that is one thing you have to observe. And second thing is, given this grammar and given these actions are nothing but expression value equal to expression value into terminal value, t dot value. So in order to differentiate between left side and right side E, I am just marking it as E1. It is not a special variable, it is E itself, but just to differentiate between left side variable and right side variable. Now in order to differentiate between these two, I am writing it as 1 here. Okay. So what they wanted is, what will be the value of this string, if I carry out this SDT on that particular string. So as usual, one method is you have to construct the entire parse tree, and then whenever you reduce, you can perform the actions and find out the value like in bottom up parsing. But then if you can understand this grammar, you could do it in a much better way. See this grammar, try to understand it. What is this grammar? This grammar contains two operators. One is multiplication and other is subtraction. And multiplication is defined as left recursive. Therefore, multiplication is left associative. And minus is defined as right recursive. Therefore, minus is right associative. And moreover, star is defined at a higher level than minus, which means minus has higher precedence compared to star. So we have to understand two things. One is minus is having higher precedence than star here, that is first thing, and then minus is right associative, that is second thing, and then star is left associative. Using these rules, you can directly evaluate it. You need not actually construct the parse tree and then find out the actual value. So using these rules, try to do it. So I have minus and star in the expression. So which one should I evaluate first? According to the grammar, minus has higher precedence, which means I should evaluate minus first. And even coming to minus is defined as right recursive, which means it is right associative. Therefore, rightmost minus has to be evaluated first, this one first, and then the next minus, and then star. So this is the way you have to evaluate it. Without drawing the parse tree, you can directly say the answer. That is just a cheat, right? So what is it? 2 minus 2. 2 minus 4 is minus 2, and 4 minus of minus 2 is 6, and 6 into 2 is 12. Therefore the answer is 12. in case if they want to force you to even do the bottom up parsing, let us assume that they want to see whether how the SDT will be carried out in bottom up parsing or not. They could ask you to even count the number of reductions. If you have to count the number of reductions that are carried out during this SDT, you should actually see the parse tree and then traverse it, and you have to see the number of reductions. So just for the practice, for the sake of practice, let's see how a bottom up parser will work on this. In order to see that, I have to construct the entire parse tree first. Let me construct the parse tree first. So parse tree for this input will be this one. E derives E star t and then E to t, t derives f minus t, t derives f minus t, t to f, f to 4, f to 2, f to 4, t to f, f to 2. Okay, so now this is the parse tree, and even if you traverse it from top down, left to right, and then perform the actions whenever I do the reduction, you will get the same answer as 12. So that is I am not interested in this. Now let us say the question is how many number of reductions are there. Even for the counting the number of reductions also, you could observe one point. Every non-leaf is nothing but a reduction. See, this is a reduction. Why? 4 is reduced to f. This is a reduction. This is a reduction. This is a reduction. F is reduced to t. F is reduced to t. 4 is reduced to f. This is a reduction. 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 Right? So all the non-leaves are reductions. So if you count the number of non-leaves, I think there are 10. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yes. So 10 reductions have taken place during this parsing. So either you could understand the grammar, the kind of grammar, and then you could evaluate it, or you could actually draw the parse tree and then traverse it, and then see the number of reductions, and whenever there is a reduction, carry out the production and find out the answer. You can do it in any way. Either ways it is fine. Okay, if you can understand the grammar, it is fine. Let's see one more example. Let's see this grammar, the simple grammar. E derives E hash t or t, t derives t at the ampersand f or f, and f derives number. So this is a simple grammar, and along with that some semantic actions are given, and now this is the SDT. And now the question is, given this SDT and given this input, what is the output generated because of performing this SDT on this input? So one thing is, you could do the same way. You could use the grammar and derive this completely, and then traverse the parse tree and then find out the value. That is one way. Other easier way is just have a look at the grammar, then you will understand what it is actually representing. This grammar is having two operators. One is hash and other is at the rate. Two operators, hash and at the rate, right? And hash is nothing but it is representing multiplication, star. And at the rate is nothing but it is representing addition, plus, right? So if you look at the way they are defined, star is defined closer to E, which means star is having least precedence than plus. So first thing you should observe is, wherever there is ampersand, it means that it is addition, and wherever there is hash, it means that it is multiplication. So you could replace it first. So wherever there is hash, it means that it is multiplication, and wherever there is ampersand, it means that it is addition. Hash is multiplication and ampersand is addition. Okay, so that is the first thing. And second thing you have to note is, plus is defined at a level, star is defined at a level lesser than the plus, which means plus is having higher precedence compared to star. Therefore plus has to be evaluated first and then star. So if I evaluate plus first, it is nothing but 2 into this is nothing 8 into 10, right? And now you have to find out what is the associativity of star. Actually the final answer doesn't depend on associativity of star, because either star is left associative or right associative, the answer is going to be same. So either you can use left associative or right associative, no problem, but then grammar is saying that star is defined as left recursive, therefore it has to be left associative, which means according to the grammar you have to do this one first and then this. So the answer will be 160. So 160 is the answer. If you didn't understand how I did it, then the other way is you can construct the entire parse tree and then if you traverse it and finally you can come to the same answer. Right, it is better that you do it in this way because it is easier and you could answer the question very fast. We shall see one more example. So let's see this SDT. This SDT is used to construct a syntax tree or parse tree. Okay, there is something called as abstract syntax tree and concrete syntax tree. I'll tell you the what it is. See, if I have an expression, let us say 2 plus 3 into 4, and for that if I write like this, e derives, e plus t, t derives, t star f, and then f derives id, t to f, f to id, e to t, t to f, and then f to id. If I write like this, it is called concrete syntax tree, or it is also called as parse tree, right? You know that this is a parse tree and one more name is concrete syntax tree. So instead of representing these many nodes and then finally representing this small sentence, we could even use less number of nodes and we can represent the same sentence. How we can do it is we could do like this. So I could write star is having higher precedence, therefore 3 into 4 will be evaluated here, and then plus is having less precedence, which means 2 plus 3 into 4. This is also the representation of a tree, but then this is abstract, which means it doesn't show you the details about the variables. If I represent only the terminals and still construct a parse tree, this is nothing but a parse tree which is called abstract parse tree, and this is concrete parse tree because it is representing everything. Now this SDT is to build this concrete parse tree, this abstract parse tree. Okay, so why do we need this abstract parse tree is there are various ways in which we could represent intermediate code, and one of the popular intermediate codes is syntax tree. So the output, if I carry out this SDT on any input string, then I am supposed to get ideally the abstract parse tree as output. So let's take the same example and let me explain you this SDT first. You know this grammar. This grammar is expression grammar. E derives e plus t or t derives t star f for f and f derives id. It is nothing but this grammar generates all the strings which contains addition, multiplication and identifiers. Okay. Now let me explain you all the productions and then the semantic action. For this production f derives id, if you look at the semantic action, it is f is having a attribute and the attribute of f is f dot nptr, node pointer. Nptr is nothing but node pointer. It is it is actually assigning some value from this function. Make node is a function. So make node is a function which will create a node with this with 3 attributes. In this node there are 3 attributes: left pointer, right pointer and the value. So value is there, left pointer is there, right pointer is there, which means make node is going to create a node with these values and then return a pointer, and that pointer value will be stored in f dot nptr. And coming to this production t derives f, whenever there is this production, whatever is f's nptr, that will be placed in t's nptr. And coming to this production t derives t star f, here I have written t1. It is actually not t1, it is just t. Just to distinguish that right side t from left side t, I have written t1. And here also it is doing the same. We are going to make a node, and for that the left pointer of the node is whatever is the t1 pointer, and the right pointer of the node is whatever is f dot nptr, and the value is star, and it is going to return some value, and that value will be stored in t dot nptr. So I'll take an example and I'll show you how it is working. Let's take the same example, this one only. Let us say we have the example 2 plus 3 into 4, and we should get this as final output, right? So I have constructed the parse tree, and I'm actually traversing it using a bottom-up parser. Now there is a reduction. What is the reduction? ID is reduced to F, right? So when ID is reduced to F, what is the action associated? F.nptr, which means F will have a value nptr, and into that some value will be written. What will be that value? We are going to create a node, and for that the value of the node will be whatever the lexical value of this is. The lexical value of this ID is 2, this ID is 3, this ID is 4, which means we are going to create a node, okay, and now that node will be containing the value 2, and the left pointer will be null and right pointer will be null, which means left pointer is null and right pointer is null, and the starting address of this node will be returned as the value. Now let us say its address is 100. Just for the assumption, its address need not be 100. I am assuming that its address is 100. Then 100 will be returned, and that 100 will be saved in f.nptr, which means f.nptr will hold 100. Now f is reduced to t. F is reduced to t. Then what is the action? T.nptr equal to f.nptr, which means whatever was f.n node pointer, that value will come into t node pointer. So what is it? 100. And now t is reduced to e. So whenever t is reduced to e, the corresponding action will take place. What is the action? E.nptr equal to t.nptr. What is e.nptr? Whatever was t.nptr, which is 100. And now this is not a reduction, and again next reduction is here. ID is again reduced to F. When ID is reduced to F, again this production will take, this production will be used, and this action has to be carried out. See this, ID is reduced to F. So when I am reducing ID to F, this particular production will be used, and therefore this action will take place. What is the action? We have to create a node, because make node is the function, and its value should be id.value. What is the id.value here? id.name, it is 3. Name is nothing but, let us assume it is lexical value. id is the token and name is the lexical value, okay. And now for this we are going to create a node, and let us say the node value is 3, and left side is null and right side is null. Why? Left pointer is null, right pointer is null, and id.name is 3, okay. And now that, let us say this address of this node is 200, just for the assumption, and now f.nptr equal to 200. Now f is reduced to t. When f is reduced to t, t.nptr should be equal to f.nptr. That is the rule there, which means t.nptr equal to 200. And now this is not a reduction, and again this is a reduction. What is the reduction? ID is reduced to F. Again the same action has to take place, which is nothing but creating a node with 4 as the value, and left pointer is null and right pointer is null. So let us assume that the starting address for this 4, this pointer, this node is 300. That one will be written here, which means this f.nptr will get 300. What is t.nptr? 200. What is f.nptr? 300. Now t star f is reduced to F. T star f is reduced to t. T star f is reduced to t. Then what should be done? Then we should make a pointer. We should make a node. Yes, I am making a node. And what is the value of that node? The value of that node is star. And what is the left pointer of that node? Left pointer of that node is t1.nptr, which is nothing but 200, which means it will be pointing to this, right? And the right pointer is nothing but f.nptr. What is f.nptr? 300, which means this one will be pointing to this. Got it? And next, and now this newly created node, let us assume that its address is 400. Now that 400 will be here, which means t.nptr equal to 400. Now this is reduced, which means E plus T is reduced to E. When E plus T is reduced to E, the production is E plus T is reduced to E, this one. Again we have to make one more node. Yes, I am making one more node. And what is the value of that node? Value of that node is plus, and the left side pointer is E1 dot pointer. What is E1 dot pointer? It is 100, which means this one is pointing to this, and the right side point and the right side node is T dot nptr. What is T dot nptr? 400, which means it is pointing to this. Therefore, if I carry out that SDT on this input, I am supposed to get this entire thing, right? And if you look at this, this is nothing but the data structure of abstract parse tree for this abstract parse tree. The same thing, right? Just verify this. Plus, plus, and left child is 2, left child is 2, star, star, and star is having left child as 3 and right child as 4. Okay, so this is the SDT which is used to create the abstract abstract syntax tree. So what is the abstract syntax tree? It is nothing but a parse tree in which variables are not shown, and parse tree is also called as concrete parse tree. And one more thing is, in the parse tree, whenever you represent all the variables and when you write the values of those variables, these attributes, any parse tree for which the attributes are written along with the values, that is also called as annotated parse tree. Okay, it is the annotated parse tree, and this is abstract syntax tree. It is also called as concrete syntax tree. It is called as abstract syntax tree. Okay, we shall see more examples about this. Let's see this SDT. This is an SDT for type checking. Okay, in order to check the type, we are going to use this SDT. If we have to find out what is the type of an expression, there are three ways. See this, an expression can be either false or true, simply a terminal. If they are just false or true, simply the tokens, then expression type is simply boolean. True or false indicates the type is boolean. If the expression is a number, number means some identifier, right? And then the type of it is integer. If an expression is some other expression closed within a parenthesis, then whatever is the type of this expression inside it, that is going to be the type of the outside expression, which means E dot type equal to E1 dot type. If the expression is E1 is comparison with E2, which means we are checking whether E1 is equal to E2 or not. It is not an assignment, it is comparison, right? If E1 and E2 are compared, first of all, two expressions can be compared only if they are of same type, which means both should be of same type. E1 dot type should be equal to E2 dot type, and either E1, both of them should be either integer or boolean. We can either compare integer values or boolean values. We cannot compare any other values, right? Therefore, both of them should be, coming to this grammar, generally in other grammar we can even compare characters, right? But then coming to this grammar, we have only two types. One is boolean and other is integer. So both should be either boolean or both should be either integer, right? In general programming languages, we might have even other constructs also, but in this grammar we are having only these two constructs. Now first check both of them are equal or not, which means either E1 dot E2 is equal to E1 dot type is equal to E2 dot type. If both the types are equal, then both of them has to be either integer or boolean. Then E dot type equal to boolean, which means if both the types are equal and both the types are either integer or boolean, then the overall expression is going to get a type as boolean, right? Why? It is a comparison. And next one is, when we are adding two expressions, when can we add two expressions according to this grammar is, we cannot add two boolean variables. We can add only two integer numbers, right? So first we should check both are of same type, which means E1 dot type equal to E2 dot type, and then we should be sure that that type is equal to integer. If that is true, which means if the type is integer, then the left side is going to get E dot type as integer, otherwise it is going to be error. So I'll take an example and show you what happens with this. Let us say the example is, I have an expression 2 plus 3 into 8 is equal to 8. So I want to find out whether this is meaningful or not, which means is it, according to the semantics, is it right, can I do it, if so what is the type of this entire expression finally. So always, as I told you, we have to first construct the parse tree and then you could apply these semantic rules, either using the top down parser or bottom up parser. I am just constructing the parse tree for the example. Parse tree for the example is this. Okay, now it is, we are comparing 2 plus 3 whether it is equal to 8 or not, right? 2 plus 3 are in the parenthesis and then we are equating it to 8, so that is why equal to 8, right? So now how to find it out is, first you have to traverse the parse tree top down, left to right, and then we have to assign the types. Now whenever this E is number, then what is the type we get here? See, I'll be going like this. Yes, E equal to number. This is reduction. What is the production? E dot type equal to integer. Therefore, this E got type as integer. And now again, E number is reduced to E. Then what do we get? E dot type equal to integer. Okay. And now this is a reduction. What is the reduction? Expression plus expression is reduced to E. Expression plus expression is reduced to E. In this case, what we should do is check whether both are of same type. Yes, both are of same type and both should be of integer. Yes, both are of integer. Then we are going to say E dot type equal to int. See, here this E1 and E2 are not different variables, they are E only. Just to differentiate between the left side E and then right side E, I have given these numbers, right? Therefore, according to this SDT, the type of this expression is going to be whatever the type of the sum is, which means integer. So here the E is integer. And now again one more reduction. What is the action? Reduction is closed brace E, open brace E, closed brace is reduced to E. Then whatever was the type of E1 dot type, that is going to be for E dot type, which means whatever is the type of this inside E is going to be given to this E. Now what is the type of this inside E? Integer. Therefore this E is going to get type as integer, E dot type as integer, right? This is not a reduction, this is a reduction, right? So then what is the production? Number is reduced to E, then E dot type is equal to integer, right? And again this is a reduction. What is the reduction? E comparison E is reduced to E, which means E equal to E is reduced to E. In this case, what we should do is compare whether E1 dot type equal to E2 dot type, which means these two types should be equal. Yes, they are equal. Both are int, and then we are going to say the left hand side expression is going to get type as boolean. Okay. So overall, the type of this expression is nothing but boolean expression. This is how type checking will work along with SDT. We shall see more examples for SDT. So in this example, I want to do some translations on binary numbers. So you know the binary numbers. It is nothing but all the numbers consisting of zeros and ones, right? So this grammar especially generates binary numbers. So the meaning of this grammar is a number can be a list of bits, okay? And a list of bits can be a list of bits followed by a bit or simply a bit, and a bit can be 0 or 1. See this, a number can be a list of bits can be list of bits followed by a bit or simply a bit, and a bit can be 0 or 1. Now given this grammar, it is going to generate all the possible binary numbers. Now what I wanted to do is, I want to find out the value of a binary number or do some translations like this. So first of all, I want to write some semantic actions where I want to count the number of ones in this produced by this grammar, or given a string, I want to count the number of ones inside this string using some SDT. So this is the grammar. So I'll write like this: whenever bit is 1, then we have seen 1 1, right? Therefore b dot count equal to 1. I am counting number of ones. Whenever the bit is 0, then b dot count equal to 0, which means I have not seen any ones. And if the production is, whenever there is a list, then the number of bits, number of ones in the list depend on number of ones in this bit. If the bit is 1, then we are going to get list, number of ones in list as 1. Therefore L dot count equal to bit dot count. If the bit is 1, then L dot count equal to 1. If the bit is 0, then the L dot count equal to 0. Now there are two L's. So just to differentiate this left side L from the right side L, I am just writing the right side L as L1. It doesn't mean that L is a different variable. Now L dot count, which means number of ones in this list, is equal to number of ones in L1, which means L1 dot count, plus number of ones in this bit, b dot count. Okay, so the total number of ones in the total list is equal to total number of ones in the list followed by total number of ones in the bit. Finally, number of ones in the number dot count is equal to whatever are the number of ones in the C. Now in the same way, if you want to count let us assume that we want to count number of zeros, we want to count only zeros, then what should we do? Everything is going to be same. In place of these two, we have to make modifications, right? So whenever we see 0, the count is 1, and whenever we see 1, the count is 0. So if I use these two semantic actions in place of these two semantic actions and leave the rest of the productions or the actions same, then we are going to get we are going to count number of zeros. In case if I want to count number of bits, I want to count all the number of bits. How can I count all the number of bits is just make b dot count equal to 1 and b dot count equal to 1. Either 1 or 0 we are going to count, then we are going to count everything, all number of bits. It is counting the number of bits. Now given a binary number, I want to find its value in decimal. So I want to convert a binary number to decimal number using this grammar. Okay, so first of all, I'll just give you some examples here. We have to understand some properties about binary numbers or any number system in general. If I have a number, let us say 1 1. So what is its decimal number? Decimal value is 3. If I have a number 101, what is its decimal value? 5. Now one thing you have to note here is, if I have a number 1011, then how do we get the value of it is, take the first number, first digit, its value is 1, right? Yes, 1. And whenever you append one more digit to this, which means 0, you are multiplying this 1 with 0 and then adding 1 with 2 and then adding 0. That is how you get 2, which means 10 is now 2. Whenever you append one more digit which is 1, one more bit which is 1, we have to multiply whatever was the value of previous number and then add 1. Okay, and so total number is going to be 5. And whenever you append one more digit, one more bit, you have to multiply 5 with 2 and then add that. That is why it is going to be 11. Which means, what I mean to say is, if I have a very big number 10110, something like this, if you have to find out the entire number, you need not actually convert the entire number into decimal. You convert the first part into decimal. Let us say 1011. What is its value? Its value is 11, and multiply with base. What is the base? Base is 2, and then add 0. It is going to be 22. Got it? So in case if it is going to be 10111, then you convert the entire number into decimal value. Let us say the decimal value of this is 11, yes, and multiply with 2 and then add 1. It is going to be 23, right? So using this rule, you can easily convert a binary number, especially for this grammar. For this grammar, if you want to convert a binary number to decimal number, following this method is very easy, because the grammar has been written in such a way that it is inherently providing you help for this kind of translation. See this, how can I do it is, if the bit is 0 or 1. You need not, you need not have this count now. So count is not required. You can, without having this count, I just want to convert the binary number into decimal number. See this. So first thing is, if you have this one, then what is it? A bit is either 0 or 1. Then simply that bit's decimal value is either 0, if it is 0, or that bit's decimal value is 1 if it is 1. Okay. And now in this production, what is the value of decimal value of L is whatever is the decimal value of B, which means L dot decimal value is equal to B dot decimal value. And coming to this production, L derives L1 followed by B. L dot decimal value is equal to whatever is L1's decimal value is. We have seen it, right? If I have 10 11 0, then this complete list is L, this is L1 and this is a bit. Therefore whatever is the decimal value of L1, you take it and multiply with 2 and add the decimal value of B, which means L dot decimal value is equal to whatever was the decimal value of L1. So L1 dot decimal value into base. What is base? 2 plus B dot decimal value, right? And finally for this production, N dot decimal value is equal to whatever is L dot decimal value. So using this SDT, we can take a binary string and we can find out the decimal value. I'll just show you with an example. Let us say the string given is 1011 and our question is to find out what is the decimal value of this 1011. Number is going to be a list is going to be list followed by a bit, list is going to be list followed by a bit, list followed by a bit, and a list is bit. So this one is 1 0 1 1. Now we traverse the parse tree like this, and 1 is reduced to bit. Then what is the value associated with this? Bit dot decimal value is equal to 1. And next bit is reduced to L. Then what is the decimal value associated with L? L dot decimal value equal to B dot decimal value, which is nothing but 1. And again there is reduction. 0 is reduced to 1. Then what is it? B dot decimal value equal to 0. And again there is reduction. What is reduction? LB is reduced to L, right? Then what is the value of it? Whatever is L's decimal value, which is 2, 1 multiply with base, which is 2. 1 into 2 plus 0, that is why we get 2, which means till now we have seen 1 0. By this part we have seen 1 0 and its value is written as 2. And again there is a reduction. What is reduction? 0 is reduced to B. Then what is B dot decimal value? B dot decimal value is 0. Now again this is reduced to L. So list comma bit is reduced to a list. Now we already know that, I think this is 1. This is 1. Okay, this is 0 and here this is 1. We already know that this is 1. We already know that the left side list value is 2 and the right side bit value is 1, which means left side bit value list value is 2 and the right side bit value is 1. Now combining these two, we have to take the left side list value and multiply with 2. 2 into 2, which is 4, and then add 1, which is 5. Therefore L dot D value equal to 5. So 101 is nothing but 5. 101 is 5. And again there is a reduction. What is the reduction? 1 is reduced to B. Then what is B dot decimal value? 1, which means left side I have got 5 and the rightmost bit is 1. Therefore what is the value of this list is whatever is left side value multiply with 2 and then add 1. So what is 5 into 2 plus 1? It is 11, which means this entire value is 5 and this entire value is 1. Now adding these two or concatenating these two is going to give me 11. Finally number dot decimal value equal to 11. That is how we got 11. Got it? So this is an SDT where we converted a binary number into a decimal number. Now my question is, what if there is a decimal point for in the binary number, which means if I have something like 11.01, so its value is I think 3.25, right? So what if there is a decimal point inside the binary numbers? If there is a decimal point, then we have to change the grammar and then change the rules in order to find out this value. We shall see that example now. So now let's see one example where the previous one only, the number could even contain decimal point 11.01, like this, something like this. So we know how to find out the value of a binary number into decimal. We have converted it, but then when we have any decimal point, then this is a different case. So there are various ways. So what is the weight of this one? If I have something like .1101, weight of this one is 2 power minus 1, weight of this one is 2 power minus 2, weight of this one is 2 power minus 3, weight of this one is 2 power minus 4, right? And you could multiply and then add them, and we are going to get the final answer. But this method could work in general, but then if you have a grammar and then we are trying to convert it using SDT, it is better to use some other method. Other method is, if I have some value like this 0 1, what is the value of it is, how to get it is, assume that there is no decimal point here. Let us say there is decimal point followed by 0 1. Assume that there is no decimal point here. Then what is the value of this value of this binary number in decimal? Value of this binary number in decimal is simply 1 upon, count the number of bits. How many bits are there? How many bits are there? 2 bits, right? Therefore 2 power 2, which is nothing but 1 upon 4, which is 0.25. So that is one other way to evaluate it. For example, if I have 0.11, what is the value of it is, find out what is the decimal value of this number without using having to assume that there is decimal point. So what is the decimal value of this 11? It is 3 upon 2 by, how many bits are there after dot? There are 2 bits, which means 2 by 2 square, which is nothing but 3 by 4. So that is nothing but 0.75. So we are going to apply this method. What is the method? We are going to count the number of bits after decimal point, and then we are going to evaluate the number as if there is no decimal point, and then we are going to divide the number by decimal value upon 2 power number of digits. Therefore, if I have to generate all the numbers, binary numbers with a decimal point, then the grammar is, there is a slight difference in the grammar. Grammar is going to look like this. A number, decimal number is going to be a list of bits followed by a dot followed by a list of bits. So this is nothing but the decimal point, the radix point, and the number could be 11.01. 11 is first list and 01 is second list. Just to differentiate first list from second list, I am going to write 1 and 2. Both the lists are same, both the L's are same. Just to differentiate it, I am writing it like this. Okay, and the remaining grammar is simple. A list can be either a list followed by a bit or simply a bit, and a bit can be either a 0 or 1. And the grammar is, this is the grammar, and now SDT is going to be straightforward. Let me take the SDT. SDT for this is, first thing is, you have to find out the decimal value as well as the number of bits. You have to count both of them. Therefore, if the production is b derives 1, then what is the decimal value of that b as well as what is the number of bits? So b dot count is used to count the number of bits. There is only 1 bit, therefore count is 1, as well as b dot decimal value. B dot decimal value, if there is only 1, is simply 1. And if b derives 0, in this case also b dot count equal to 0 and b dot decimal value equal to 0. Sorry, b dot count equal to 1. Why? Because there is 1 bit, na? Okay. And this one, if list is simply 1 bit, then list dot count is directly 1 bit. You can write it, or you can either write it as bit dot count. Okay, because anyways bit dot count is going to be 1, and L dot decimal value equal to whatever was the b's decimal value, that we are going to write it here. Okay. And now there are two L's, one L is on the left side and one L is on the right side. Just to differentiate between these two L's, I am going to make this suffix 1, L1. It doesn't mean that L1 is different. Now if I have a list as list followed by a bit, then number of bits in the list is equal to number of bits in the list plus number of bits in that bit. This is the total number of count, as well as now L dot decimal value. What is the decimal value of L is L1 dot decimal value plus B dot decimal value. Okay. And now coming to this number, now the number's value is whatever is L1's decimal value, we have to write that one, and coming to L2's decimal value, you have to take the L2's decimal value and then divide it with L2's count, which means if I have to get the total number of the total value of n, then it is going to be, first thing is you have to find out L1's decimal value. What is L1's decimal value? That is already given, that one we have already derived it till here. So L dot decimal value we have derived it, therefore number dot decimal value is equal to, can write like this, the final decimal value of the number is whatever is the decimal value of L1, which means L1 dot decimal value plus whatever is the decimal value of L2, L2 dot decimal value divided by 2 power L2 dot count. The reason is this number is going to be the fractional part which is equivalent to L2, and this number is going to be the decimal part which is equivalent to L1. That is how we get it. So if you want to see an example, let us say the number is L1 11.01, then we are going to evaluate the decimal value of this, which is nothing but 3, plus we are going to evaluate decimal value of this, which is nothing but 1, divided by 2 power number of bits. What is 2 power number of bits? 2 power 2, which is nothing but 3 plus 1 by 4, which means 0.25, which is 3.25. So that is how this SDT is going to work. So this is an SDT to convert any binary number, including binary numbers containing decimal point, into decimal number. Okay, so we shall see next example. This is an SDT to generate 3 address code. So what is 3 address code is, it is an intermediate representation. For example, if I have something like this, if I have x equal to a plus b into c, this is actually containing 4 addresses. So I want to convert this 4 address code into 3 address code. For that we are going to use something like this SDT. So if you look at this SDT, we have few things here. See, first thing is the grammar is nothing but a statement can be identifier equal to expression, and an expression is expression plus term or term, and a term is term into factor or factor is id. So this is actually supposed to generate all the statements of the form x equal to a plus b into c, right? And now in order to generate it, see this, we are going to use this entire semantic rules. So semantic rules are this: f dot place is an attribute which is used as a placeholder, which means it is going to remember what is the name of that variable. For example, here id can be a, b or c, right? In that case, then it is going to be f dot placeholder equal to a or b or c, something like this, and then t dot place equal to f dot place, and then t dot place equal to new temporary variable, which means sometimes we are going to create a new temporary variable, and then to that temporary variable we are going to generate this code. This gen is nothing but the output. So because of this piece of code, we are going to write output, in the output the 3 address code required. It is better I'll take an example and I'll explain you. See, let us assume that this is the example for which I want to generate 3 address code. Okay, now for that one I am going to construct the tree. A statement can be identifier equal to expression, and the expression can be expression plus term, and term can be term into factor, and a factor can be simply an identifier, and a term can be a factor, term can be a factor, and factor can be an identifier, and expression can be term can be factor can be identifier. Okay, and now this id is nothing but a, and this id is nothing but x equal to a plus b into c. Now let me do bottom up parsing. This is not a reduction, this is not a reduction, this is a reduction. So what is the reduction? id is reduced to f. When id is reduced to f, what is the action associated with this? f dot place equal to id dot name. What is id dot name here? Here id dot name is nothing but a, which means f is going to remember that the variable it has seen is a, and again there is a reduction. So what is the reduction? f is reduced to t. What is the action? t dot place equal to f dot place, which means t dot place equal to whatever was f dot place, which is a. Okay, and now t is reduced to e. Then what is the action? e dot place equal to t dot place, which means e dot place equal to t dot place is nothing but a. This is not a reduction, and again this is a reduction, right? id is reduced to f. Then what is the action? f dot place equal to id dot name, which means f dot place equal to, what is id dot name here? b. And again this is a reduction, f is reduced to t. What is the action? t dot place equal to f dot place, which means t dot place equal to f dot place is nothing but b. This is not a reduction, and again this is a reduction. id is reduced to f. What is the action? f dot place equal to id dot name, which means f dot place here is nothing but c. So all the variable names have been remembered till now. Now this is again a reduction. What is the reduction? t star f is reduced to t. In that case, what is the action? One action is t dot place equal to new temporary variable, which means for the left side t, see, left side t is t and right side t is t1, which means for the left side t we are going to create a new temporary variable. Let us say new temporary variable is t1. So t dot place equal to, I created a new temporary variable t1, and now I am generating the code t dot place equal to t1 dot place into f dot place, which means t dot place, which is nothing but t1, is equal to t1 dot place, which is nothing but b into c. So because of this reduction, output is going to be printed as t1 equal to b into c, which means for this input the output started as t1 equal to b into c, which means this is evaluated first, this part, right? And again there is a reduction. What is the reduction? e plus t is reduced to e. Then what is the action? e dot place equal to new temporary variable, which means for this e we are going to create a new temporary variable. So e dot place equal to new temporary variable, let us say t2, yes, and now generate e dot place equal to e1 dot place plus t dot place, which means e1 dot place t2 equal to e dot place, which is a, plus t dot place, which is t1, which means t2 equal to a plus t1. See, for this one we evaluated it as t1, and now we added these two and we evaluated it as t2, right? And now again there is a reduction. What is the reduction? id equal to expression is reduced to s. id equal to expression is reduced to x. Then what is the action? Action is id dot name is equal to e dot place. Then what is id dot name here? id dot name is nothing but x equal to e dot place. E dot place is nothing but t2. Therefore for this input, which is containing 4 addresses, we have converted into output in which every line is containing maximum of 3 addresses. Therefore this is the SDT which is used to convert any input program into 3 address code which is following this grammar. So in general, if the program is containing if, else and all and other statements, then we have to write the grammar for all the statements possible, and then we have to write the rules for all the statements. Okay, and this is how we converted the input into output. We shall see more examples. Now we have seen many SDTs till now. Now we can classify SDTs into 2 types. One is S attribute SDT and other is L attribute SDT. So before going to classification of SDTs, I want to classify attributes first. So till now we have seen that every variable is having an attribute associated with this, and it is getting some value, right? And there are 2 ways. So one is, if I have a production like this, just for an example, see this, A derives B, C, D, something like this. A can have an attribute which means A dot S. A can have an attribute, and if it is getting the attribute as a function of attribute of B, attribute of C and attribute of D, which means A is taking value from its children. In case if A's attribute is taking value from its children, then such an attribute is called synthesized attribute. Why? Because we are synthesizing the value of the attribute from the children. And other way is, if let us say C is taking attribute from its parent or from its siblings, then such an attribute is called inherited attribute, which means if I have C dot I is an attribute, and if it is taking a value from A dot I, something like this, which means a child is taking a value from parent, then it is called inherited. Or C dot I, if it is taking a value from B dot I, which means a node is taking a value from its sibling, or C dot I is taking a value from D dot I. So if a node takes the value from its parent or from its siblings, then it is called inherited attribute, and if a node takes a value from its children, then it is called synthesized attribute. Therefore attributes are basically of 2 types. One is synthesized and other is inherited. What is synthesized? If a node takes the value from its children, then it is called synthesized, and if a node takes a value from the parent or from its siblings, then it is called inherited. So depending on what are the types of attributes you have in SDT, SDTs can be classified again into 2 types. We shall talk about SDTs first. You know what an SDT is. We have seen it till now. Now in all the SDTs we have seen till now, we are having some attributes and we are trying to evaluate the values of the attributes. So I'll tell you an example. S attribute SDT is nothing but, in an SDT, if there are only synthesized attributes, which means a parent is taking the value from its children. If there are only synthesized attributes, then it is called S attributed definition. And L attributed definition is, it can have both inherited attributes as well as synthesized attributes, but only restriction is we should inherit from the left side. That is why it is also called as L attribute. See this, it is going to have both inherited as well as synthesized, and in case of inheritance, you are not supposed to inherit from your right side, you are supposed to inherit from your left side only. That is why it is called L attributed definition. In this case, see this, A derives x, y, z. In this case, x can take value from A, y can take value from x, but y cannot take value from z. See this, y can take value from A, y it can take it from the left hand side. Yes, this is allowed. And then y can take value from x, y, because it is taking from left hand side, it is allowed, but then y cannot take value from z. The reason is, y can take only from its left hand side, which is A or x, but it cannot take from right hand side. Okay, and moreover, A can take value from x, y, z, because that is nothing but synthesized attribute. So in L attributed definition, we have a combination of S attributed as well as inherited attribute, synthesized as well as inherited, but inheritance should be only from the left hand side. So which one do you think is powerful? S attribute is taking only synthesized, L attribute is taking both synthesized as well as inherited. Therefore this is actually L attributed definition is actually enclosing S attributed definitions also. If a definition is S attributed, then it is definitely L attributed. Why? Because L attributed can allow both synthesized as well as inherited attributes. Now coming to the second rule, the semantic actions are always placed at the right end of the production, which means here if you are going to place some semantic actions, you should place them only in the right side, right hand, at the rightmost. But here, coming to L attributed definition, semantic actions can be placed anywhere in the right hand side, which means you can place it in the beginning or in the middle or in the end, right? Even by this definition, S attributed is more restricted, but L attributed is more free, right? And if you see this, since we are placing the semantic rules only in the right hand side of the production, it is also called as postfix SDT. Postfix means we are going to have the semantic rules at the end. Post means at the end. And next one is attributes are evaluated during bottom-up parsing. So since it is all synthesized attributes, when we come from the bottom, which means let us say like this, since A's values depend on B, C, D, so by doing this bottom-up parsing, by the time I reach A, I will have scanned all the children. That is why it is easier to evaluate during bottom-up. Here attributes are evaluated by traversing the parse tree depth first, left to right. The reason is, see this, if I have something like this, A derives B, C, D, then C could take values from A and from B, but it will not take value from D. Therefore, if I am traversing from top down, left to right, by the time I reach a variable, all the values of the left side are already available. Values at A and B are available, using which I can evaluate the value at C. So understand this. Here values are evaluated in a bottom-up parsing. The reason is, by the time I reach, by doing this bottom-up parsing, by the I could see all the values that A is depending upon first, and then I can come here. And similarly here, attributes are evaluated by traversing the parse tree depth first, left to right. By the time I reach any variable, all the parents have been watched and all the left subtrees have been watched. Therefore, by the time I reach here, all the values that C is depending on are already being evaluated. Okay. So this is the main difference between S attributed and L attributed. I'll take an example and I'll give you, more insight about this. Yeah, see some examples. In this example, I want to show you whether how to find out whether a SDT is L attributed or S attributed. Okay. So first of all, see this first SDT. There are two productions and there are some associated semantic actions with this. Okay, you can have a look at that. Now the question is whether this SDT, both the productions together is called SDT. Okay, both these productions along with these rules is called SDT. Whether this SDT is S attributed, L attributed, both or none. That is what is the question. Now examine each variable, each attribute one by one. Then you can find out. So first one is L dot I equal to F of A dot I. So what does it mean? L is taking value from A. So child is taking a value from parent, which means this L dot I is nothing but inherited attribute. So since it is inherited attribute, this SDT cannot be S attributed. Why? In S attributed SDT, there has to be only synthesized attributes. Therefore, because of this rule, there could be some other rules also which are failing, but then just because of this rule you can stop here and you can say that this is not S attributed definition. Okay, and now let's check whether it is L attributed definition or not. L attributed definition means, see, you have to take only from your left hand side, which means L can take from A, yes, it is fine, and M is taking from L, yes, N can take from L, it is fine, and A is taking from M. A is taking from M. Just check this. How could A take from M? Yes, it could take it. The reason is you are taking a value from your child. It is nothing but synthesized attribute. Therefore, these two rules are according to L attributed definition, right? And now see this. Next one, R is taking from A. R is taking from A. Yes, it could take it. So any variable on right hand side can take anything from left hand side, right? It is inherited, fine. Now Q is taking from R. Q is taking from R. That is what should not happen. You should never take any value from your right side sibling. If it is happening, then it means that it is not L attributed definition, which means because of this it is not L attributed definition. So remember this, if I have any production A derives B, C, D, Now in S attributed definition, A can take from BCD, that is fine. In L attributed definition, A can take from BCD and B can take value from A and C can take value from AB, D can take value from ABC. But then C cannot take value from D or B cannot take value from CD. If you see any such rules, you can say that it is not L. Therefore, because of this rule, this rule, it is not S attributed, and because of this rule it is not L attributed. We can say that it is none, not S attributed or L attributed. Now let's look at the next production. A derives BC. So in this production, the action is, the action given is B dot S equal to A dot S, which means B is taking a value from A. So B is inheriting a value from A. It is an inherited attribute. Yes, inheritance is allowed, right? And moreover, we are taking inheritance from parent, which means left hand side. Therefore, it is not a problem. So this is L attributed. It is not S attributed because it is having inheritance, right? Inherited attributes does not form S attributed definition. And one thing you should even observe is, if an SDT is S attributed, then it is definitely L attributed. The reason is this: in S attributed, see, if a grammar is S attributed, then definitely it is, if an SDT is S attributed, then definitely it is L attributed. The reason is this: the reason is, if a SDT is S attributed, you can understand that there are only synthesized attributes in it, and since there are synthesized attributes, it is definitely L attributed. But if a grammar is L attributed, there could be synthesized as well as inherited attributes. Therefore, if a grammar is L attributed, it may not be S attributed. It may or may not be. Okay. So now this is an example. We shall see one more example, and I will show you the difference between S attributed and L attributed. Let's see this SDT. This is SDT, which is used to store the type information into symbol table. So what is storing the type information into symbol table is, for example, if you have given some input like this, int x comma y comma z, then in the symbol table the information should be saved like this: x is of type integer and y is of type integer, z is of type integer. This is what I wanted to store. Storing the type information into symbol table. So for that, I am going to use this SDT. So how to trace out what the SDT? Okay, before going ahead, let's see what type of SDT it is. In previous videos, I think you might have seen the definition or the difference between two types of SDTs. One is S attributed and other is L attributed. What is S attributed? If all the attributes are synthesized, which means synthesized means we are taking the attributes, parent is taking the attribute from the children, that is synthesized, right? And or other type of attribute is definition is L attributed. L attributed means there are both synthesized as well as inherited attributes, and inheritance is restricted only for the left side, which means you can take the inheritance. See, if you remember it, I think if you are watching a continuation of the videos, you will understand it. Otherwise, I will just explain you what S attributed and L attributed is. So if I have A is having some children B, C, D. If A is taking value from all these children up, then it is called synthesized attribute. If A is taking an attribute and that attribute is taking values from all the attributes of B, C and D, then it is called synthesized. If all the attributes in a SDT are synthesized, then that grammar is called, that SDT is called S attributed. And what is L attributed is, if I have A derives B, C, D, then if C is taking from B or from A, which means, and D is taking from all these left. So you can have inherited as well as synthesized attributes, but inheritance is limited only to the left side. That is called L attributed. So now I hope that you know the difference between L attributed and S attributed. Just look at this example now. Now in this SDT, what are the types of attributes we have? So see this one, L dot in equal to T dot type, which means L is taking a value from T, isn't it? This is nothing but inheritance. So whenever you are taking a value from the sibling, then that is inheritance. And what type of inheritance? As of now, we are taking it from the left side. Therefore, till this point, this is qualified, this SDT is qualified as L attributed SDT as of now, right? But then we shall see if all the other rules are also following this or not. Now t dot type equal to int, which means t is taking the value from the child. What does that mean? It is synthesized, which means t is synthesizing from its children. Therefore it is synthesized attribute, and this is also synthesized attribute because it is taking from its child. And look at this one, L1 dot in equal to L dot in. L1 dot in means this one is taking the value from this one, right? So which is nothing but L attributed. So all the attributes are either left side inheritance, see we are inheriting from the left side, or from the child, which means synthesized. Therefore there are only inherited from the left side as well as only synthesized. Therefore this SDT is actually L attributed definition. L attributed definition, clearly, right? So now what is the purpose of writing this SDT is, I want to find out the output should be like this: x belongs to int, y belongs to int, and z is int, which means the type information. Type information means what is the type of each variable that has to be stored into the symbol table by the end of this SDT, right? So let's now take this example, integer x comma y comma z, and then run that SDT on this example and see what happens. Okay, so first we have to generate this. So declaration, so just understand this grammar also. What is this? A declaration is type followed by list of attributes, which means type can be integer or anything. Type followed by list of attributes, and type in this SDT used is integer and character. In reality there are various types: integer, float, double, character, all this, right? And L is list of attributes. A list of attribute is a list followed by identifier or simply an identifier, which means we can have any big list of identifiers or simply one identifier, right? So just observe this. Now a declaration is type followed by a list, and a list is, here in this case it is simply integer, and a list can be list followed by id, or again list followed by an id, or again id, simply id. We have only 3 identifiers, isn't it? Therefore what is the first id? X, second id y, third id z. Therefore int x, y, z are derived this way. Therefore we have, for this statement, the entire definition is this one. Now how to trace it out? How to evaluate a L attribute definition? Start tracing out top down, left to right, and whenever you come across any inherited attribute, so you evaluate it first time when you visit it, and whenever you come across any synthesized attribute, you evaluate it last time when you visit it, which means in this case start from here and keep on going like this, going like this, going like this. See if t has any inherited attribute. T does not have any inherited attributes. T has only synthesized attributes. So what is the time in which at which we should evaluate this synthesized attribute? The last time when you visit it. This is the last time when I am visiting it. Therefore by this time all the children have already been visited. So t dot type equal to how much? Int. T dot type equal to int, right? And now it is going this way. Now see this, we have visited this one L. So just check if L has any inherited attributes. So D derives TL, D derives TL. This is the production I am there. And see if L has any inherited attributes. Yes, L is having inherited attribute. What is it? L dot in equal to T dot type, which means L is taking the value L dot in equal to T dot type. So whenever there is any inherited attribute in L attribute definition, we are going to evaluate it when we visit it for the first time. Why? By the time I visit any L attribute any inherited attribute in L attribute definition, I am very sure that I would have already evaluated all the attributes of its siblings as well as its parent. Therefore it is better that you evaluate now. So L dot in equal to T dot type. So I got it. And next one is like this. Now again L derives L comma id is the production, and I am at this L. Just check if this L is having any inherited attribute. So what is the production? L derives L comma id. Check this. The production is L derives L comma id, and it is the right side L, right? In L derives L dot id, it is the L of right side. Now check this one. In L derives L dot id, L comma id, In L derives L comma id, this is the right side L. Just see if it is having any inherited attribute. Yes. What is the inherited attribute? L dot L1 dot in equal to L dot in. See, this L1 is used just to mark the place. This L1 is not a new variable. Just there are two variables with name L on both the sides. Just to distinguish left side from right side, I am putting for the right hand side a suffix of 1. Therefore, L1 means it is L only which is present in the right side. Okay, so see this. Now L1 dot in, which means right side in, is equal to L dot in. So whatever value is here, that is coming down here. Therefore, this value is L dot in equal to type here, which is int. And what is L dot in? Here also it is int. And again it is going like this. And again L derives L comma id, which is nothing but the same production. In this L is also having an inherited attribute. What is the inheritance? L dot in is equal to L1 dot in equal to L dot in, which means whatever is the information here, integer, that will come down here. So this also got it, right? And now this is the reduction. So what is the reduction? id is reduced to L. So see this, id is reduced to L. And what is the action associated with this? At this point we are trying to add id comma name, add type id dot name comma L dot in, which means in the symbol table we are trying to add what is the id name, what is the identification name here, x, and what is the type of it? Type of it is actually int, isn't it? The reason is L dot in is int and id dot name is x, therefore x and int are updated there. And again there is a reduction. So what is the reduction? L comma id is reduced to L. L comma id is reduced to L. And what is the action? Add type of id dot name. What is the id dot name here? Here id is y. Y, see this. Now L derives L comma id, which is nothing but L comma id is nothing but y here. Therefore add type of id dot name, which means y is added, comma L1 dot in. L1 dot in is nothing but what is the type of this? L1 dot in, what is the type of this? The type is int. And again there is a reduction. What is the reduction? L comma id is reduced to id. Then the same action. What is the action? Add id dot type, id dot name comma L1 dot type. What is id dot name? Z. And what is type? Int. Therefore z comma int is added. So we have seen that this is how the symbol table is updated using this SGT. Therefore SGT can also be used to update the symbol table, right? And finally t comma this TL is reduced to D. Is there any action associated with this? This action is already over. No more action is pending. Therefore this is all. So this is how this attribute, this definition is used to update the symbol table. So what type of definition is this? L attribute definition. Just see what has happened here. Now what happened in this case is information which is int, type information is int, initially started here and it has moved up. From here it moved up. So whenever the information has to move up, we should use the synthesized attribute. Synthesized attribute means the information will start at the leaves and it move up. That is why this t is having synthesized attribute and its value is int, right? And then afterwards this type information int is moving to the right side from the left side. From here it moved here. If you look at the flow, initially information is here, from here it has moved up and from here it is moving right. Therefore information is moving to the right side. So if the information has to move from left to right, then the right side variable has to inherit from the left side. That is why it is inheritance. And what type of inheritance? L inheritance, right? And now this information is moving from here down. So what does this mean? The information is passing below from parent to the child. If the information has to pass from parent to the child, we should use inherited attribute. That is why it is inherited attribute again. And from here again the information is moving down, right? So if you look at the this movement of information, it started somewhere below and it moved up. For that synthesized attribute is required. And then it started somewhere here and it moved right. For that we needed inheritance. What type of inheritance? L type of inheritance, which means we inherit from the left side to the right side. And then from here it moved down and then it moved down. This is the way it moved. So information is circulating this way, right? So that is why we wanted both the synthesized as well as inherited, right? Now I want to have a definition as this SDT which will do the same work. What is the work? Adding the type information to the symbol table. The definition has to do the same work, but then I don't want to write the L attributed definition. I want to write the S attributed definition. What is S attributed? S attributed means the information should always be flowing above, up. So information has to start at some point and it should always flow up. Then only I can have only inherited synthesized attributes. So I want to write a definition which is not L attributed, which is S attributed, which means I want to change this entire thing so that that is completely S attributed. The problem is, by using the same grammar, by using the same rules, I will not be able to convert an L attributed to S attributed. If you have to convert an L attributed to S attributed, it turns out that first we have to change the rules. First change them and then change these semantic rules. First change the grammar and then change the semantic rules, then everything can be changed. Therefore, I am going to show you by taking a new SDT which is S attributed, how to convert this L attribute to S attribute. Actually, I am not converting, I am rephrasing everything, I am changing everything, and then we shall compare. I am going to leave this diagram as it is here, and we shall compare with the next SDT how the SDT is going to act in coming to the information flow. Okay. Now this is the SDT to do the same work. So what is the work? Adding the type information to the symbol table. Previously also we did it, but using a different SDT. Now it is a different SDT, and in fact this SDT is S attributed. So this one is for the same one S attributed, which means there will be only synthesized attributes. Check this. So this one t dot type equal to int, which means t is taking the information from its child. Therefore it is synthesized, isn't it? And then check any other attributes. Yes, here the attribute is there, d dot type equal to t dot type. So what does that mean? D is taking the value from its child, therefore again it is synthesized. So there are only two attributes, and these two attributes are synthesized. What are they? T dot type and d dot type. These two are taking the value from the children. So definitely this is S attributed. Now if you look at the grammar, this grammar is very much different from the previous grammar, and the grammar had to be changed because in the previous grammar information is not starting from the lowest level. It is starting at some level. See this? In the previous one, information is starting at some level and then going up and then going right. So with this grammar, the problem is I have to circulate the information like this. So when I have to push the information to the right and below down, I don't have any option. I have to use both inherited as well as synthesized. Now if I have to use only synthesized, I have to somehow see that this information is at the lowest level, and only way the information moves is level up, level up, level up. So if I can make it happen by making some modifications, then I could convert the grammar into S attributed grammar. That is why I am going to change the grammar first. Grammar has been changed and appropriately the semantic rules have been added. Now this is a SDT which is S attributed. Let's see for the same example how does this SDT react. Okay. So int x comma y comma z is given. Now how is this one going to generate this? So declaration is actually a tricky one. Declaration is declaration followed by a ID or type followed by a ID. So it is definition is somewhat tricky to understand. Declaration is declaration followed by a ID or simply a type followed by an ID in case if there is only one ID, right? So it is a tricky one to understand. So just see this. In order to define int x comma y comma z, we start with d first. Now d is going to be d comma id, and again this d is going to be d comma id, and again this d is going to be t and id, right? And what is the type of it? Can I go down? What is the type of it? Type is int. So int is the type of it. Okay. So how does this entire thing work out is, I start from see int x, y, z. So this is x, this is y, this is z. Now let's see how this entire thing works. Now I start from here, top down, left to right I am traversing, and since it is inherited attributes only, actions have to be taken only when it is visited for the last time. This is the last time I am going to visit the node t, right? Therefore, see the action. So t dot type equal to int. The action associated with t dot type is equal to int. I got it. And next one is the next reduction is this one. T comma id is reduced to d, isn't it? So what is this? T comma id is reduced to d. Then what is the action associated with this? D dot type equal to t dot type. So what is t dot type here? T dot type equal to id. Therefore d dot type equal to t dot type, whatever is the type here. So what is it? Int. Int will come up, right? And then add type id dot name comma t dot type. So what is id dot name here? So d derives t comma id is the production, d derives t comma id is the production. What is id dot name? X. Therefore add name, which is nothing but add x, add name comma t dot type. What is the t dot type here? Int, right? And again there is one more reduction. So what is the reduction? D comma id is reduced to d. D comma id is reduced to d, right? Then what is the action associated with that? Add type of id dot name comma d dot type. So d1 dot type. So d1 is nothing but the right side d. So this one id dot name is how much? Y comma d1 dot type. D1 dot type is int. Along with this, one more action has to be added here. So the action that has to be added here is the information has to flow from d1 to d. Why? Because the information has to go up. So d dot type equal to d1 dot type. Information is going to flow from d dot type from this one to this one. Therefore it is again synthesized action. So d dot type equal to d1 dot type. d1 means the right side, which means the child. Therefore information int is now passing up. Again the next reduction is d comma id is reduced to d. Then what is the action? Again the same action. Add type of id dot name, which is nothing but id dot name is z comma d1 dot type. What is d1 dot type here? d1 dot type is int. Therefore int is added, isn't it? And d dot type, this one, equal to d1 dot type, which is nothing but integer, right? So anyway the final output is same. Finally we wanted to add this type information into the symbol table. That is what has happened, but then it actually happened in a different way. So look at the difference here. Where did the information start in this diagram? In this one, information has started at the end, at this point, at the end, right? And then it is moving up from here to here, and then it is moving up, and then it is moving up, which means it started at one point and it is continuously moving. That is why using only inherited synthesized attributes it is possible, because information flow is only upwards. Therefore I needed only synthesized attributes. But here if you look at it, information is starting from this point, going up and then going right and then going down and going down. So for this part I cannot do it with synthesized attributes. I wanted inherited as well as synthesized attributes. So in order to convert a L attributed definition into S attributed definition, it is not just enough that you change the semantic rules, you need to change the grammar also. Actually you need to change everything, the grammar as well as syntax rules, right? So this is how for the same action we are converting L attributed to S attributed, right? Now let's see this intermediate code generator. I have already told you that intermediate code generator is used so that the main reason is till some phases, all the phases put together, they will generate intermediate code, and now given that intermediate code, the last phase, the back end, can take that intermediate code and generate the machine code. Therefore having intermediate code is very important if you want to build new compilers for other machines. For example, you might have already designed a compiler for C programming language for Windows machine, right? And now you want to design the C compiler for Linux machine. Then you need not change everything. What you should change is only the phases, the front end, front end, lexical analysis, syntax analysis, semantic analysis, and intermediate code. That entire thing is going to be same, and whatever is coming out of that intermediate code generator, that one is going to be same for all of them. So intermediate code is actually same for all the machines, it doesn't change. And now once you get that, the target code generation and code optimizer, only those two phases have to be changed so that you can write the compiler for a different machine. So intermediate code generator is a very important thing. Maybe even in Java also you might have seen something called as bytecode. Bytecode is intermediate code. You generate the bytecode on one machine and then you send it to some other machine, and on that machine bytecode will execute. So you can generate bytecode on any machine and that bytecode will be executed on any other machine. The reason is every machine will have interpreter which is suitable to the that platform. Similarly, every machine can have only the backend changed, that target code generator and code optimizer. Only these two phases changed, and the intermediate code till intermediate code phase, it has to be same, right? So this phase is very important. And intermediate code means given a code, you have to represent it in some other form. So there are various popular intermediate codes available. So mainly linear form and tree form are very popular. And linear form is postfix notation, 3 address code, syntax tree, and DAG. Therefore, given any program, if you want to convert it to intermediate code, you have these 4 options. Among all these 4 options, the main important or the most popular one is 3 address code. 3 address code is globally accepted and popularly used. So this is the most important 3 address intermediate code which is used in compilers, right? So I'll explain you what about all the intermediate codes with an example. Let us say the example is a plus b plus a plus b plus c. If this is the statement given, then how is this statement represented in various intermediate forms? See this one. In this intermediate form, postfix form, so what we take is we just convert that given input into postfix, right? And now in the 3 address code, the same thing. We take this given input, this a plus b plus c, and we are converting it into 3 address code. What is 3 address code is, at most we should have 3 addresses in every line. So look at this code, how many addresses are there? 1, 2, 3, that is 3 address code. So what does it say? T1 equal to a plus b, which means I evaluated this one first, and then T2 equal to a plus b, I evaluated this one next, and then T3 equal to T2 plus c, which means I evaluated a plus b plus c, and then I multiplied those two results. That is how 3 address code is written. And already we have seen how to generate or how to write a SDT in order to generate a 3 address code. You please go back to the SDT examples. One of the example is, given this input, how I can convert it into 3 address code, that is clearly given there. And now one other representation of intermediate code is syntax tree. So how is syntax tree represented? Watch it. So syntax tree is nothing but it is a kind of parse tree which is condensed, and we have already seen how to generate a syntax tree from a SDT. You please go back to that example and watch it. So an SDT can be used in order to generate the syntax tree. Syntax tree is also a popular intermediate code. So what is the difference between parse tree and syntax tree is, syntax tree is actually condensed, which is modified or a shorter version of parse tree. Without using the variables, we use only terminals to represent a syntax tree, and without with the same meaning will not change here. And now DAG, what is the difference between DAG and syntax tree is, in case if you have any repetitions, DAG will not repeat it. For example, here a plus b is generated 2 times, right? And in DAG, if already one time a plus b is generated, it will not generate it again, it will just refer to it. Therefore, in the second time, watch this one. Second time when a plus b is required, we are not generating it, we are using already what is generated, right? So that is how DAG is used. Even though we have all these intermediate code representations available, the most popular one is 3 address code. Okay. So now we are going to discuss, or in this intermediate code we will mainly focus on 3 address code. What are various 3 address codes available, and given a program, how do you want to convert it to 3 address code, right? Now coming to 3 address code, whatever the high level language program is, when we want to convert it to 3 address code, we have only these 7 types of instructions available. So whatever is given in the high level, you should ultimately convert them to one of these. So just observe this, what they are. X equal to y op z, which is nothing but if you have x equal to a plus b, like that. So x equal to y plus z, it is nothing but binary operator. So if you want to do any binary operation and then assignment, you should always go with this instruction. And what about this x equal to op z? It is unary operation. So like x equal to minus y, like that. And then x equal to y, it is simply an assignment. And this is if x relational operator y, if x relational operator y, then go to L. So it is nothing but go to, which is a conditional go to. If this condition gets satisfied, then we are going to this label, right? And this go to L is unconditional, which means without checking any condition you can jump to some statement. And next one is a of I. This is array indexing, base index. So array indexing, if you want to take any element from array, then you are going to use a of I equal to x or y equal to a of I. And then x equal to star p. Star p means p is a pointer and x is a value pointed by that pointer. Y equal to ampersand, let us say some x. So what does that mean? From a address of a variable is going to be assigned to other variable. So whatever is the high language code, I mean like C, you have to ultimately convert it into 3 address code. So then we are going to use this in order to generate the machine code, right? So we shall see what are various representations, and we shall see all the examples like how while loop is converted, if loop is converted, switch is converted, everything into 3 address code one by one, right? Now let's see what are the various ways in which we can represent a 3 address code. Traditionally people have been using 3 popular representations of 3 address code. See, among all the intermediate code representations, 3 address code is the most popular one. And in 3 address code there are various representations, various ways we can represent the 3 address code only. And now all are equally popular, and it depends on the implementers of what they choose. So depending on their choice, various compilers are having various different representations, but it is all coming to their choice. Nothing is like this one is superior and other one is inferior. Everything is in use. Now see this one. Let us assume that we have the instruction like this. We have a statement. Statement is like this. So for this statement, the 3 address code is written like this. So after writing the 3 address code, we have to convert it to some way you have to store it in the computer, right? So this is the manual code. I mean, we have written it. Now this has to be stored in a computer, therefore it has to have a format, some kind of syntax, right? So what people have come up with, one is quadruples. Quadruples means every instruction can be represented using 4 elements. So see this, operator, operand 1, operand 2, result. For example, in this statement, t1 equal to a plus b, what is operator? Plus, which is addition. And what is operand 1, operand 2? A and b. Therefore, operator is plus, operand 1, operand 2 are a and b, and the result has to be stored in t1. Simple. t1 equal to a plus b is nothing but plus ab and then this. And t2 equal to minus t1 is given. So how is t2 equal to minus t1 written is, minus is the operator and it is having only one operand, and other one, this is null, which means nothing is there for the second operand. Whenever second operand is null, it means that it is a unary operation. Minus is a unary operation and the result is stored in t2. t2 equal to minus t1, right? And t3 equal to c plus d, like that. For every instruction there, we have an instruction here, and it is quadruples. What is the advantage of such representation is, statements can be moved around, which means, if you are waiting for some, let us say the value of a has not yet arrived, then in the pipeline what you could do is, you could move up this third instruction, because third instruction and first instruction both are independent of each other, therefore you can simply execute anything. So it depends, it will increase the efficiency, in the sense you need not wait for some instruction to be for a long time. You can simply swap the instructions or just jumble the instructions and everything will be running on fine. What is the disadvantage of this? Too much of space is wasted. Why is too much of space wasted is, just look at this. Now we are saving the result also in somewhere. So I'll tell you how to save this space. Now instead of these quadruples, if you go for triple, so triple says that plus a b, which means we are only saving operator, operand 1, operand 2, and we are not saving the result. So whoever wants to refer to the result of this, which means if someone wants to use a plus b, they will just use the name number 1. So number 1 indicates the result of this. So whenever, for example, here the result T1 is used in step 2, isn't it? So step 2 is simply minus of 1, which means whatever is the result of the first statement. What is the result of first statement? A plus b. Then negate that. So minus of 1 means negate the result of first one. Now look at this. What does this fourth statement mean? You take the result of second statement and the result of third statement and you just multiply it, isn't it? So just check that. This third statement is multiplication of T2 and T3. So T2 is already there as a result of second statement. T3 is already there as a result of third statement. Therefore, without storing result anywhere, we could have even written that whatever is the result of this line, we are going to use it here. So by using that convention, what happens is we need not store that result anywhere, right? So how is that performed by the compiler? So for example, if they have to execute this, then they will execute 2 and then store the result in the temporary register, and then they will execute 3 and store the register in value in the temporary register, and then find the value of this. Therefore we need not have any temporary variables. Everything can be done in the registers, right? So it all depends on the implementation. Now what is the advantage? Space is not wasted. So the reason is simple. Result, we are not saving it. Only three attributes are enough. And what is the disadvantage of this? Statements cannot be moved around. Why do you think that statements cannot be moved around? Once all the instructions are written and the instruction numbers are used in some other instructions, if you change the order of these instructions, then these instructions themselves have to be changed. Understand this? Once the instructions have been numbered and their numbers have been used in some other instructions, if you change the instruction ordering, then the instructions have to be changed. For example, here you are clearly referring in the fourth statement the address 2 and address 3, isn't it? Now if you somehow change the third line with interchange first line and second line, because they are independent, you can execute first line or third line, anything first. Let us say you have jumbled this one here, you have sent third instruction here and first instruction here. Then what happens is unnecessarily the value that we get here will be changed. Therefore statements cannot be moved around, because if you move the statements, the meaning of some instructions can be changing. That is the disadvantage of this. Space is fine, but then we want the efficiency by moving the statements. It is clearly saying that statements cannot be moved. Therefore either you go with this or this. Both have advantages and disadvantages. Here statements can be moved, here statements cannot be moved. Here you are wasting this space, here you are saving this space. So one quick fix to this is, what they say is, don't directly put the instructions in the program. You put the instructions in the memory and then you put their pointers in the main memory, so that first we look at the pointer to the instruction and then we go to that instruction and fetch it. Understand it? So what they are saying is, we are not directly taking this program and executing. We are saving this program in the memory, and now for those memory elements, for these instructions, we are using pointers, which means indirected triple says that every line is a pointer to an instruction. So the order in which this program executes is this Roman letters. I just use the Roman letters, Roman numbering system, so that they will not get confused with this. So this means that first instruction that has to be executed is represented by pointer 1. This is a pointer and this points to this first instruction here. Okay, and the second instruction that has to be executed is second instruction here. Now what is the advantage of writing like this pointers is, so you can move the statements here and you can just write the numbers there, which means you need not change the order anything here. You can move the statement, which means you can take this statement 3 and put it there, and take this statement 1 and put it here, and you just change the numbers here. So by changing the numbers here, you can move the program here. You can move the statements without doing anything. But the problem with this one is, you are actually having the pointer to an instruction. So in order to execute an instruction, you have to take that pointer one axis and then go to the instruction file and then take that instruction itself, which means 2 accesses are required. So the advantage of this one is statements can be moved. You can move the statements. Here you can move the statements because here the statements are not being moved. Here you can execute third one first and then first one. No problem. Here you can move the statements as long as this order is consistent. Here we are not moving it. Here we are moving it. Therefore statements can be moved. But then disadvantage is 2 memory access are required. One memory access is to get the address of the statement and second memory access is to get the statement itself, right? So everything has their own advantages and disadvantages. So again, what is it? Given this instruction, we are generating the 3 address code. In order to represent the 3 address code, the popular representations are quadruples, which means using 4 elements, triple, which means using 3 elements, indirect triple, which means like this. So what is the advantage of quadruples? The statements can be moved around. Disadvantage, more space. What is the advantage of triple? Space is not wasted. Disadvantage is statements cannot be moved around. What is the advantage of indirect triples? Statements can be moved around. Here you can move the statements as long as order there is consistent, right? As long as you don't change anything here, since the instructions are referring to these numbers, and since you are not changing anything here, nothing is going to be a problem. So you can change the order, move the ordering of the statements here, and then you can execute them in any order, right? So but in the disadvantage of this method is 2 memory access are required. First time you access the address and second time you are going to access the instruction itself, right? Fine. That is all about the representation of 3 address codes. All are popular and all are being used. That depends on the implementer. Okay. Do one thing. I'll just zoom in. You can just copy it. Just pause it for a second and copy it. When the frame contains the entire board, just pause it and copy it. Okay. Now let's see this backpatching technique. If you look at this statement, if A less than B, then T equal to 1, else T equal to 0. Actually, this statement is not there in the 3 address code. If you look at the 3 address code, I have given you in the initial, in few lectures ago, I have given you that there are only 7 3 address codes available. So this statement is definitely one of the 3, is not in the 3 address code. The reason is, this is one statement which contains 1, 2, 3, 4 addresses, right? So we are not going to use such a statement as 3 address code. Then what we have to do is we have to convert it to 3 address code. So the conversion is like this. Now we have to use the statements which are defined in the 3 address code and convert it. So these are the statements which are present in one of the 7 statements, and using only those 7 statements I have written it, right? Now what did I do is I have written all these statements, but then I left some blanks. So this technique is called backpatching. Leaving the blanks, leaving the labels and later filling them is called backpatching. See this? Leaving the labels as empty and filling them later is called backpatching. So I am going to fill them later. Okay. So just understand by the minute. It is very simple. In GATE they have asked this question long back, but I don't think that they will ask it again. The reason is it is very simple and easy to do it. Maybe what other modification they could do is, instead of just giving a blank here, they will entirely give some blank here or blank here. One statement they could miss, or they could just jumble the statement orders and they will ask you to rearrange them. But then asking it directly in this level is very simple for GATE. But anyway, we are not going to risk it. We shall do it. And in case if they jumble the question, you will still be able to answer it. Okay, even though they are not going to ask it the same way. Okay, see this? If A is less than B, it is called value representation, which means if A is less than B, then some value is going to be set, otherwise some other value is going to be set, right? So see this, if A is less than B, what should happen? T should be equal to 1. So where is T equal to 1? The instruction numbers are I plus 1, I plus 2, I plus 3. It is relative numbering. So I am assuming that instruction is going to start, first instruction is starting at some number I, and the next instruction is I plus 1, I plus 2, I plus 3. Now see this, if A is less than B, then go to T equal to 1, which means we have to make this one. Therefore go to I plus 3. In case if A is not less than B, then what happens to T? T is made 0, isn't it? If A is less than B, then go to I plus 3, otherwise t equal to 0, which means if this is true then t equal to 1, otherwise automatically we are not going to this, automatically t equal to 0 is set, and after setting this you should come out of this completely. So how can you come out of this? I plus 4, right? So what is this? If a is less than b, t equal to 1 is set, otherwise t equal to 0 is set, and immediately you should not go to I plus 3, you should come out, therefore I plus 4. It is simple and logical. I don't know how to explain it also, it is so simple. Okay, and now let's look at this statement. There are three relational operations: a is less than b, c is less than d, and e is less than f, and they are connected with and or. There is and here there is or. Now how are we going to generate the 3-address code for that? Obviously this is not a 3-address code, it is not in that format, therefore I have written the entire 3-address code, assuming that it is starting at an address 100. Just fill in the blanks, just see what should be done. Now if you look examine the code, if a is less than b, then t1 is used in order to represent if a is less than b or not. If c is less than d, then t2 is used. If e is less than f, then t3 is used. Therefore t1 is used to represent this one, t2 is used to represent this one, and t3 is used to represent the value of this one. Now check this. If a is less than b, then what should be made 1? t1 should be made 1. Where is t1 1? At 103. Therefore go to 103, right? Otherwise you make t1 equal to 0. Yes, you can make t1 equal to 0, and after making t1 equal to 0 you should not again hit this line. What happens if you hit this line? Then again t1 will be set to 1. Therefore without hitting this line, then you have to jump to 104, right? Then what about the next one? If c is less than d, which means if c is less than d, if it is true, then t2 should be set to 1, which means go to 107. If this is false, which means if c is not less than d, automatically t2 will be set to 0, and after that you are going to 108, right? And 108 is if e is less than f, then you have to set t3 equal to 1. So how can you set t3 equal to 1? 111, t3 equal to 1. If this is false, then t3 is made 0, and after t3 is made 0, you should not again make t3 equal to 1. Therefore jump to 112, right? And just watch this line 112. 112 is doing t4 equal to t1 and t3, which means t4 equal to t1 and t2. So which means these two are ANDed first. The reason is in this and or, and will be having higher priority. So we are going to see this in C programming language, but here understand that or you just assume that the rule is and is having higher priority. That is why and is executed first, t1 and t2, and then whatever is the result of this, that is ORed with t3. Therefore t5 equal to t4 or t3. So that is how the entire program is written. This is called backpatching. Okay, so whenever the statements are not in the 3-address code, we are going to use all the 7 statements, and then for every statement which is not in 3-address code, we are going to generate that all 3-address code statements, and then we are going to leave some blanks and fill them later. It is called as backpatching, right? Now while loop is not there in the 3-address code. If you look at the 7 statements of 3-address code, there clearly while loop is not there, but while loop is present in many of the high level languages like C programming language, Java, whatever. While loop is the most frequently occurring case, right? So whenever in the high level language there is while loop, how are you going to convert it to the 3-level language, the 3-address code? So this is how. See this, while e do s. What is the meaning of it? We are going to test e. If e is true, then we are going to do the statement s. If the after doing statement s, again we are going to go back and check the condition. Otherwise we are going to go to false. Now there are various ways. There is nothing called a single way in which you can implement it. There are various ways you can implement it using the 3-address code. I have given you 2 of them. So for this while loop, you could either use this 3-address code or this 3-address code. You can use anything. So in exam either they will give you this one or this one. No problem, both are right. Now see this, if e equal to 0, which means if the condition is false, then you should not execute s, right? Then where should you go? Without executing s, you should go to L1. That is why go to L1 if condition is false. Otherwise, if e is not equal to 0, which means if condition is true, then we are going to execute yes. After executing yes, then what should we do? Again we go back and check the condition. That is why go to L, right? So what is it? If the condition is false, then we are going out of the while loop. If the condition is true, then we are executing it and again going back and checking the loop, checking by the condition. Now look at this one. The other way of implementing is if e means if e is true, then go to. Where should I go? I should go and execute the condition, that statement. So where is the statement? L1. Therefore go to L1. Otherwise, if this condition is false, which means if e then go to has not happened, then the next choice is we go to the next statement. Now we are at the next statement. Go to. Where should I go? If this is false, then obviously I should not execute yes, I should go to last. So go to last statement, and now after this L1 is there. So L1 is executing yes. After executing yes, what should I do? Again I should go back and check the condition. Therefore go to L, right? So these two, actually I am explaining the back patching, but the main intention of explaining this one is how to convert the while loop into the 3-address code. Now one tricky thing is, once the while loop is over, once the while loop has been converted to 3-address code, you will not be able to identify that there is a loop at all. You don't know whether it is a pure if statement or if there is a loop. That is the worst part of it. So in your initial C program, if you have something like this, while and then some statements, after you convert it to intermediate code, there will be no block at all. Therefore you will not be able to identify the loops very easily. Identifying the loops in 3-address code is very difficult because it looks like a plain text. There is nothing like while and there is nothing like curly braces. Everything has been removed. Now the problem is, how can you identify the loop in the intermediate code? Why should you identify the loop in the intermediate code is, you have to do some optimizations later. Code optimization requires that you should identify the loops, while loops. But now you have converted it. Okay, we shall see it there. For now, just keep it simple. Now understand the next one. This is the statement given, while a less than b, then you execute this one, x equal to y plus z. If this is the case, while a less than b, actually there is a chance that it will fall in infinite loop. The reason is, while a less than b and you are doing this, in this loop actually a or b is not changed. So if you don't change a or b, obviously you will keep on executing this. But then my intention here is not finding out the correctness of the program. It is just for the sake of example how this program, this statement is going to be converted to 3-address code. Obviously this statement is wrong. It falls in infinite loop, or it might not. In case if a is less than b, it will always be less than b as long as you enter the loop, because you are not changing a or b, right? Anyways, let's look at how we are going to implement it in 3-address code. Obviously it is incorrect, but still it is just an example. If a is less than b, then go to some statement. So what has happened initially is, they have checked the condition. If a is less than b, then what should I do? Then this statement has to be executed. Where is this statement? This statement is executed here. So t equal to y plus z, x equal to t. How did I get these two lines from this line? Maybe you should look at the SDT, where there is an example, SDT to generate 3-address code. One of the SDTs is that. So in that example I discussed how to convert this instruction into these two, right? Even though there are trivial steps like this, you could have directly written as x equal to y plus z. Our SDT converts it into two lines. Now say this, if a is less than b, which means if this statement is true, then we are going to execute these two statements. Therefore where should I go? Go to L1. After doing this, which means if I am reaching here, definitely a is not less than b, then I should definitely not execute these statements. I should come out of the while loop. Then what is it? Last. Last means coming out of the while loop. Last is the label which contains the remaining of the program, right? I am assuming that this program with these two lines are present inside a program, which means above it there are lines and below it there are lines. Therefore last is just a pointer to the other lines which are following while loop. And after executing this statement, this entire statement, what should I do? Again I should go back and check this condition. So where is checking the condition? L. Therefore again after executing this, go back and check the condition, right? So this is how while loop is implemented. Since the while loop is not in 3-address code and it is there in the high level language, we are going to convert the high level language while loop into 3 address code, and this is how we are doing it. Now look at one more construct which is there in the high level language and which is not there in the intermediate code, that 3 address code, which is for loop. So if you look at the for construct, generally it will have this format. In every for loop there will be initialization and then condition checking and then finally incrementing, right? So first we initialize and then check the condition and then go into the loop and execute this statement. For example, I have the statement yes, and go into the loop and execute this statement, and after the statement execution is over, I have to come back and increment the condition and again check the condition, increment the variable, check the condition, either increment or decrement or whatever you have written, you are going to do that and then check the condition and again enter into it. So how does it work? So first thing is we are going to make E1, which means we are going to initialize. After initializing E1, then we are going to check the condition, which is E2. If the condition is true, we are going to go and execute this statement, and after executing this statement we are going to go to that increment or decrement condition, that E3, and after that again we check the condition and repeat this everything, right? So that is how the flow is. Now see how a for loop can be represented using 3 address code, using those one of the 7 lines. Now this is the first statement given: for I equal to 0, I less than 10, I plus plus, A equal to B plus C. If this is given, first step is what? Initialize. So what is initializing? I equal to 0. After that, what is the next step? If I is less than 10, then go to. So what is that? We are actually testing the condition. If this condition is true, if I is less than 10, if this condition is true, then we are going to go and execute this statement. So if this condition is true, then go to execute this statement. What is the statement? A equal to B plus C. And for this statement A equal to B plus C, the 3 address code generated is T1 equal to this and A equal to T1. So how do you think that we generated it? We have already seen it previously. It is very, using that SDT, we are going to generate this 3 address code. Now what should be written here? Go to L1. The reason is condition is true, therefore execute this statement, right? After executing these statements, you are supposed to increment or decrement. I plus plus is nothing but I equal to I plus 1. Again for that I plus plus, this is the code generated. For I equal to I plus 1, the code generated is this. How? Again refer to that SDT, which is generating 3 address code. Now after doing this, again you are supposed to go back. See this? After executing this statement, again we are going to increment the, after incrementing, again we are going to go to the condition. So what is the condition? L. So after doing this, go to L. In case if it is false, then you go to the next line, which means you leave the for loop and go out. Therefore in case if it is false, if this is false, then go to last means the remaining part of the program. It is very simple and straightforward, right? So this is how a for loop is converted to 3 address code. Again here also examine that after for loop is converted to 3 address code, there is no hint that this is actually a loop, which means there are no brackets and there are no for statement, and therefore it is very difficult to identify that there has been a loop here. Now we should identify it later. See, high level language is converted to intermediate code, and now inside the intermediate code we have to do code optimization. For doing that, we should identify the loops again. We removed the loops, we didn't remove it, we transformed the loops into some other form. Now it is a difficult task for us to understand that there has been a for loop here. Let's see that later, but this is how for is converted. Now let's see this switch case. Switch is not a loop, it is a, one of the statement has to be taken and we should come out. Actually switch is not in the high level language. Switch is only, switch is there in the high level language, but it is not there in the 3 address code. So we have to convert this high level language construct switch into 3 address code using only those 7 statements which I have given. Now how we could do it is, just understand it. I'm just explaining you. First we should know the value of I plus j. Depending on the value of I plus j, if the value is 1, then we are going to take this. If the value is 2, then we are going to take this. If the value is not 1 or 2, then we are going to take this case, default case. Anyway, after taking any of these cases, you should come out of the switch loop. We should not take 2 cases, right? So how is it implemented? Watch it. Now t equal to I plus j, which means we first find out what is the value of t. then go to dash, right? So we shall see where we should go. Now L1 is nothing but case 1, isn't it? Case 1 is A equal to B plus C. These two are the 3 address code for A equal to B plus C. And after this, go to. So after executing this case, where should I go? I should definitely not go to L2. I should come out of the switch case. Therefore, I should come out of the switch case is nothing but going to last. This is break. After executing this, you break, come out of the switch completely. Now next one is T2 equal to X plus R. This is nothing but case 2. After executing case 2, then also you should come out. Therefore, go to last. And next one is third one, T3 equal to Y plus Z, X equal to T3. So after executing this, you should come out. Therefore, go to last. Right? Now test. It is testing depending on the value of T1. It is testing where to go. So what should be written here? Depending on the value of T. So after computing the value of T, then we should go and test the value of T. If value of T is 1, where should we go? We should go and execute case 1. Therefore, go to L1. If value of T equal to 2, where should we go? We should go and execute second case. Therefore, go to L2. Otherwise, go to, which means if it is not T1 or T is not 1 or 2, then we should go to the default case. What is default case? L3, right? And what is this one? After finding out the value of T, we should go and test the value of it, which means test. So how is this executing? First we find out the value of T, and then depending on the value of T, we take the corresponding case. And after that case is executed, we are going to come out. The reason is there is break after every case, right? So this is how switch is executed. So anyway, after the switch is done, there is nothing called a loop. So we need not find out the loop later in the later phase, optimization phase. It is very straightforward and simple. Okay. Now let's look at this line, x equal to a of y comma z. So yz, it is nothing but they are trying to refer to a two-dimensional array, and a is a two-dimensional array, and we want to access an element which is at a of y comma z. These are the indices given. So before going ahead and see how the 3 address code is going to be generated for this, this is the 3 address code which is going to be generated for this line. Very big, isn't it? So before going ahead and seeing about it, let's see how the two-dimensional arrays are actually stored in the memory. So once you know how these are stored in the memory, that will give you a better understanding about how to solve this one. Let us assume that there is a two-dimensional array A of 4 rows and 4 columns. Then how will the elements be in the array? So assume that we have starting indices starting from 0. Generally we start the indices from 0 and we go till n minus 1. So the first element is 0 0, second element is 0 1, third element is 0 2, and fourth element is 0 3, and next element is 1 0, 1 1, 1 2, 1 3, 2 0, 2 1, 2 2, 2 3, 3 0, 3 1, 3 2, 3 3, right? So if this is the array, all the elements are there. Now whenever you have this array at your hand, the two-dimensional array, and when you want to store it in the memory, inside the memory it is a, memory is a kind of single dimensional array. You can think of memory as a one-dimensional array with all the elements in a sequential form. We don't have any pattern to actually lift it and store it as it is inside the memory. So what are the various ways generally we follow is, people, they follow these two ways. They will take the row one by one and then put it in the memory, which means they will take the first row and put it, and this row will be following the first row, which means that is called row major order. Row major order. Row major order means I'll be taking each row and then I'll arranging them in the array, which means this entire array will be like this: 0 0, 0 1, 0 2, 0 3, and then 1 0, 1 1, 1 2, 1 3, 2 0, 2 1, 2 2, 2 3, 3 0, 3 1, 3 2, 3 3. So all the elements will be placed in the array like this, like a single dimensional array. all the elements of the two-dimensional array. So when I take each row and place it, and after that second row, after that third row, after that fourth row, this is called as row major ordering. It is very popular, and this is the default. By default, everyone is going to use this. And the other one is it is not very popular, but it is still in existence. So other way to arrange this array is column major ordering, which means I will take the column and then place it over. First column will be kept, which means 1 0 1 1 0 0 0 1 0 2 0 3 0, which means I am putting the first column and then I will put the second column. What is second column? 0 1 1 1 2 1 3 1, and next is third column, which is 0 2 1 2 2 2 3 2, and next is fourth column, 0 3 1 3 2 3 3 3. So like this. So this is called, first one is called row major order, in which I am putting the rows one after the other. Second one is called column major order, in which I am putting the columns one after the other. So anyway, what I mean to say is the array which is double dimensional, two dimensional, or multi-dimensional, it could be either three dimensional, we don't have any such representation in the memory. Memory is a contiguous array. You can think of memory as one dimensional array. So you have to store it in a different way. Then when you are storing it in a different way, user doesn't know it. At high level language, user thinks that in his imagination array is this, but at low level language, the implementation, you are going to store it like this. Then whenever he asks for an element, now it is your responsibility to fetch the element from the memory in such a way that user will still think that he is actually in a two-dimensional array, which means he will give a line like this. He wants to refer to a of I comma j, something like this. So let us say he wants to refer to element 2 3, a 2 3. He wants element refer the element 2 3. Now he thinks that it is in the second row, third column. In case if we use the row major order, so actual implementation says that it is in a single dimensional array somewhere here 2 3, isn't it? But then according to him, the element is in a double dimensional array somewhere here, right? So now let's see how to fetch this element in case if we are used row major order. The first one is row major order, second one is column major order. Everyone is going to use row major order by default. C is going to use row major order, all the C implementations. I mean, it depends on you actually, the compiler implementer, but most of the people, they have chosen row major order only. So I am assuming that we are talking about row major order, and I will just tell you how to fetch this element a of 2 comma 3. Now if this is the row major order, in order to reach this element, what does 2 say? 2 says that you have to cross 2 rows. In order to reach this element, you have to cross this complete first row and then second row. That is what the first index 2 says. And what does 3 say? 3 says that you have to cross 3 elements in the next row, which means the first index says if I have a of ij, it says that in order to reach this element a of ij, you have to cross the first I rows, and after crossing the I rows and reaching the exact row that you need, you have to cross j elements, which means in case if you are going for a of 2 3, you have to cross the first 2 rows, and then after reaching the third row you have to cross the 3 elements, right? So that is how it works. Now for example, if you look at this element, if you have to reach 3 2, how many rows you should cross? You should cross 3 rows, which means first row, second row, third row, and in the next row how many elements should you cross? 2 elements, 1 2, right? So what does crossing a row mean? Crossing a row means crossing those many elements which are present in the row, and how many elements will be present in each row? That will be equal to the number of columns. So in this case, see this, if I have to reach 2 3, then how many elements should I cross? I should cross actually 2 rows, which means 2 rows I should cross, and each row will have how many elements? 4 elements. Why? Because number of columns is 4. Therefore first you have to cross 8 elements, and after crossing 8 elements, now it is 2 3, right? So 2 3, which means after reaching the exact row you have to cross 3 elements, therefore plus 3. The total number of elements you have to cross is 2 into 4 plus 3, which is nothing but 11 elements. After crossing 11 elements, you will be reaching the exact element in the array, right? In the one dimensional array. See this, 1 2 3 4 5 6 7 8 9 10 11. After crossing 11 elements, the next element is here. Got it? So in any two-dimensional array, whenever a of ij is asked, you cross I rows. How can you cross a row? By crossing those many elements which is equal to number of columns. And after crossing those many rows, then you cross the number of elements. How can you cross? That j will give you the number of elements, right? That have to be crossed. Now these many elements have to be crossed, but then in a memory, a element can take more than one byte, and we want the base location of this, which means the starting byte of this. If every element has been stored in 1 byte, you need not do anything further. But then let us assume that every element is going to take 4 bytes. Then how many memory bytes or how many addresses I should cross is these many elements multiplied with 4. In case if every element is going to take 4 bytes, then how many total bytes I should cross? Total number of elements I should be crossing multiplied with size of each element. If each element size is 4 bytes, then you multiply with that, right? So now let's get back to that problem, this problem. Now they are saying that A is an array which is having dimensions 10 by 20, which means 10 rows are there and 20 columns are there. Since 20 columns are there, crossing one row is nothing but crossing 20 elements, right? So if they want to find the element yz, which is having index yz, then how to reach that element? First you have to cross all the rows. How many rows should you cross? Y rows. And how many elements will be there in y rows? Every row has 20 elements, right? Y number of columns is equal to number of elements in each row. Therefore y into 20, you should cross this, and after crossing this, after going into that particular row in which the element is present, you have to cross some more elements. How many elements? Z elements, which is nothing but the number of elements before that element. So you have to cross Z elements. These are the total number of elements you should be crossing. But then along with this, I want to find out the address. So if every element is going to take a size of 4 bytes, then how many bytes I should be crossing? Into 4. This is the final one. So this is what I want to find out. This will give me what is the offset of the desired element starting from the base of the array, which means starting from the starting location, how many bytes I should be crossing in order to reach this element, right? Once you find out that offset, then you take the base address and you add the offset, then you can find the element, which means if you have found out that I need to cross how many 11 elements, 11 elements have to be crossed, and each element is going to take 4 bytes, therefore 44 bytes I have to cross. And if the starting address of the array is, let us say 100, then the required element will be at a position 100 plus 44, which is 144. That is called base offset. So in order to calculate the offset, I should be crossing those many rows, and in a row I should be crossing those many elements, and then multiply with the size of the every element, each element, and you are going to get the offset starting from the beginning of the array. Now you take the offset and then you add the base, and then you add the desired offset, then you are going to get the location of the element. Then you can directly go there and fetch it. Even though the array is 2-dimensional, we are going to save it as if it is 1-dimensional, right? And fetching is important. While fetching it, I am converting that 2-dimensional address into 1-dimensional address. Now just look at this. What they are trying to do is t1 equal to y into 20. So y into 20 means this one. They are trying to cross y rows. In order to cross every row, how many elements should be crossed? 20 elements. If there are y rows, y into 20. Yes, I crossed it. And then t2 equal to t1 plus z, which means they are crossing z elements in the row. So for this one, this is the statement. So now the total elements have been crossed. Next, what should we do? If we assume that every element is 4 bytes, this is an assumption. It need not be 4 bytes all the time. Here I am assuming that every element is 4 bytes. And what is the size of integer? It is not 2 bytes or 4 bytes or 8 bytes. It depends on the implementation. It changes from compiler to compiler. Whatever you decide, you can have it. It is not a hard and fixed rule that it should always be 4 bytes. Here I am assuming that it is 4 bytes. Then the offset is all the elements, number of elements multiplied with the size of each element. This is the offset. Now once you get the offset, already you know the base. What is base? Base address of A. So that is nothing but where the address A has been started its memory, which means inside the memory from which point are you actually storing A, that is called base of A. Now you know the starting point and now you know how many bytes to cross. Therefore it is simply your required element X is take the base and you add the offset. It is called base offset addressing. It is nothing but take the base and add the offset, then you are going to get the address in which X is present. X equal to so and so means get that element from that address and store it. That is how this two-dimensional array is going to be stored. It can be extended to 3 dimensions, 4 dimensions, any dimensions, but whatever it is, ultimately it has to come down to one-dimensional array when you are saving it in the memory, right? And while retrieving, this entire procedure has to be done. It looks tedious, but then giving this illusion that you are having a two-dimensional array will help the user in many ways. So all these things will actually simplify the programming at user level, but then they are complicating the compiler design, right? Because you have to design the compiler in such a way that it should be it should be transparent. User should not know that it is a single dimensional array, right? So this is all about how to convert a two-dimensional array into single dimensional array, how to retrieve it. Okay. Now look at runtime environments. Runtime environment means when you run the program, what is the support that you want from the operating system. So runtime environment is how a program should be loaded in the operating system and what is the support that your program needs. So before going ahead and talking about this theory, what I would like to do is I'll just take an example and I'll show you how the this runtime environment is currently implemented at the right now, and then we shall see what has happened in the evolution, which means before we are now at some position at some point where we are using some strategies. Before, when we have actually come to this before coming to this strategy, there is a evolution procedure. Then how we evolve, what are the various strategies they applied initially, and what is the advantage and disadvantage of each strategies. I'll just show you current position, which means currently what are the strategies we are applying. Later we shall see how we have reached that point. So now when you try to run a program, when you try to execute a program, that is called a process, right? And the process is managed by operating system, that is called operating system process management, right? So in operating system, whenever you try to run a program, when you give the program to the operating system, and before running it, the operating system will create the process for that program. So in order to tell you in the simple words, let us say you have taken a C program and you compiled it and you got the output file some .exe or a.out in Linux. And when you try to execute that .exe file, then operating system will create something like this for that .exe file. So what it will do is that will take the .exe file and it will place it here, which means .exe file will be here, which is nothing but machine code. Machine code is here, right? And above this machine code, if your program is having any static variables or global variables, in C programming language there is something called as a static. There is a function, there is a keyword static. So what does static means that variable is created and that variable will live throughout the lifetime of the program. So we shall talk about these variables and what are the various types of variables later in C programming language, but for now just understand that there is a concept called as static variables. If you declare any variable to be static, that variable is going to be forever, which means from the beginning to the ending you can refer to that variable anytime and any number of times. It is going to be having a permanent storage. So above this there is something called as static memory, static or global, which means all the global variables as well as static variables are going to be saved here. So for example, if you want to declare a array is a static type by default. So array has to be declared in this. Therefore, before doing anything, when you are going for some static variables or static kind of arrays in C, You should even specify what is the size of each one. You cannot specify an array without giving this size. The reason is it has to be allocated in this memory, therefore you should know exactly how much memory should be allocated to that array before running the program. Therefore at the compile time itself, while the compilation is going on, you should specify the size of the array. Therefore operating system will be very clear about how much memory is required for the static part. And after the static part, we have heap. So heap is used for dynamic memory allocation. So whenever in your C program, whenever you write malloc means memory allocation function, malloc, calloc, right? So whenever you use such functions, what happens is a new variable or data structure is going to be created in the heap memory, and heap grows like this. Heap grows upwards. It will start from this point and will keep on growing upwards. There is no hard and strict boundary. It will keep on growing as and when required. And other thing is stack. So stack is required for function calling. Whenever you call any function, there is something called as recursion stack. In that stack, activation records will be pushed. Therefore stack will be growing downwards. So stack will be growing downwards and heap will be growing upwards. Why do you think that both are not going in one direction? Is actually you could have had a boundary here and you could have reserved some part for heap and some part for stack. Why is no strict boundary here and why are they both growing in opposite directions? It is like this. You can imagine this concept as you have a book, one notebook, and from one side you are writing TOC and from other side you are writing compiler design. Then what happens? Why do you want to do that? Why don't you start writing TOC from one side and exactly in the middle you start writing compiler design, so that half of the book will be given to TOC and half of the book will be given to compiler design. But no one is really doing it. What we generally do is from one side we start writing TOC and from the other end, which means we turn the book around and from the last page we start the compiler design as if it is the first page for the compiler design. That is the general strategy you use. Why do you think that we have been using it? The reason is from one side TOC grows and from other side compiler design grows, and we don't know which one is going to take more space. Sometimes TOC can take more space and sometimes compiler design can take more space. If you exactly divide into half, then there will be wastage of that pages. The reason is sometimes TOC will use up the entire half of the book which is allocated for it and it might need more pages, but compiler has not used half of the book. Then some pages are remaining there, but those pages will not be used by TOC because it has to be contiguous. Similarly here also, a program can use lot of heap space or lot of stack space, and we don't know exactly which space it is going to use. Sometimes it will use lot of heap space and sometimes it will use lot of stack space. We don't know which one it requires. Therefore it is better that you leave it to them. So if heap requires more, then heap will take up more space. If stack requires more, stack will take up more space. In case if this entire space is over, you are going to get a error, that memory error, segmentation error or something. There will be some error printed according to your operating system. So whenever you get if this space is not enough, so generally this space depends on the operating system. Every operating system has a fixed amount of space reserved for every process. It is called process, and these are the runtime environments which are provided by operating system to the process these days, which means presently every operating system is going to provide you with three types of storage techniques. One storage technique is static, another storage technique is heap, other one is stack. Now we are using all these three, but during the evolution, which means initially people didn't use all these three. They have used one each, which means either they were using static or heap or stack initially, and later they found out that using all the three is not just not efficient, it is necessary nowadays for the functions. Now let us assume if we have used only one of them, either static or heap or stack, what would really happen to such a program? Which means if we don't have all the facilities provided to a program, then if we have used only this particular one of them, then what would happen to such a program? So let's see this. Now runtime environment means that is what is the support that the program will be given. So first show this one. Now storage allocation strategies. Now we are talking about what are all the storage allocation strategies. There are basically three. One is static, other is stack, other is heap. Now let's talk about static. if I have static allocation, which means like this, static allocation. Now allocation is done at compile time, so everything that has to be done, which means every element has to be specified at compile time itself, and binding do not change at runtime. So once you bind some variable to some address, which means once you decide that a variable is going to sit in some address, that variable can never be moved out of that address, which means there is nothing like malloc and free. So it has to be there always. That is about the static, and that is a disadvantage as well as disadvantage. Advantage is that element is going to be there forever till the end of the program. Disadvantage is if you don't need it in the middle, you cannot free it up, right? And only one activation record per procedure. So at compile time you cannot decide, or you cannot actually think of how many times a function has to be called. Therefore the best thing is, if you have 10 functions, you allocate 10 activation records, thinking that every function will be called only once at any time. So if you want to call a function, then that particular region which is allocated for that function, in that region that particular program will be allocated, which means, see this once, show this one. What do I mean by one activation record per procedure? Means, let us say you have a program, and in your program you have f1, f2, f3, so on, f10 functions, right? Then if you have static memory, there is no choice, you don't have any choice, you have to allocate one stack element, which means one activation record for each function. If it is f1, this element, this record is given for f1, and this record is given for f2, and this record is given for f3, right? Like that, one element has to be, or one record is going to be allocated for one function f4. Now whenever you want to call f1, you should always use this space allocated for f1, and in case while one activation of f1 is active, if you want to call one more f1, it is not possible, because you have no more space in order to run f1. Every function will be given only some set of space, and you are supposed to use only that space. And if already a function is sitting in that space, you cannot call the same function again. That is why recursion is a function calling itself is not possible here, right? So one activation record is allocated per procedure. There is no option, because you cannot guess at compile time how many times a function has to be called. Let us say you have guessed it, and maybe you have allocated 2 activation records for a function. Then what happens? You can call the function 2 times. When one function is active, you can call one more function. What if you need 3 times? It is not possible, right? Therefore, what are the disadvantages? Recursion is not supported. The recursion needs many times calling the same function, but according to your settings, you can call it only once. And size of data objects must be known at compile time, which means since every object has to be allocated during the compile time, their size has to be specified initially. So you have to, before running the program, their size has to be known. You cannot say that I'll declare the size of array later. It has to be declared initially only. And then data structures cannot be created dynamically. So there is no support of heap. So while the program is running, if you want to create one more variable, there is no space. The reason is your operating system has allocated exactly the amount of space which is required by you, which you specified at the compile time. For example, you have specified that I need 10 functions and 10 variables. Then exactly for those 10 functions, space will be allocated, and 10 variables, space will be. And if you want one more variable, even in that case, even if you want one more variable, you will not get any space. The reason is the entire space has been already given away. Now you cannot go out of your space allocated and do anything. Therefore, you have to be content with whatever space you set before. So the problem, obviously, it is a lot of disadvantages are there. Only one advantage is there. What is it? If you use a static memory, the variable can be alive throughout the program. So it is not very advantageous for many functions. So static is not very popular. Next one is stack. So just watch this stack. Whenever an activation begins, activation record is pushed onto the stack, which means whenever you call any function, a record will be pushed onto the stack. So if you have stack, you can use it, grow it and then shrink it, and whenever you want to call a function, a new activation is created. Therefore you can call a function once and again you can call it second time, then again one more activation record will be pushed. Therefore recursion is possible. And what is activation record? I'll talk about it after this topic. I'll talk about it in detail, what is activation record is. But now understand that for every function call, a new space will be created in the stack. Therefore what happens is, even if one function call is active, even if you call the same function call again, then one more space will be created. Therefore recursion will be permitted. And whenever activation record ends, whenever activation ends, activation record is popped off. So in case if your function is over, then you are going to pop off the activation record. Local variables are bound to fresh storage. It is important. Local variables are bound to fresh storage means whenever you try to, you have local variables, and whenever you call the function, that local variable will be created again and again. So if you have int x in a function f, now that integer x will be created as many times as you call the function f, and each time it will be created in a different space in the stack, and everything will have different values, right? And anyways, we are going to talk about recursion in detail in data structures. Again, I'll teach you about it in detail. Now, disadvantages. Local variables cannot retain values once the activation ends. Once your program is over, then that function call is over, that entire stack record will be popped off, and once it is popped off, the values which are present in this will be gone. Maybe you could, as an exercise, you might have seen this. If you want to try to find out the number of times a function is called, which means, let us say there is a function called as show here. Let us say there is a function by name f. Now inside that function I am having a count. Initially you made int count equal to 0 and then count plus plus. You did something like this. Now the purpose why you have written it is you wanted to count the number of times f is called, and then finally you want to print f count in main function or somewhere you want to print the count. Then the problem with this kind of setting is you are trying to count the number of times f is called by writing a variable which is local inside f itself. The problem with such a setting is simple. Now whenever you call it for the first time, one fresh count will be created. Whenever you call f, inside the activation record, one fresh variable count will be created and it will be 0 and it will be incremented, which is 1. And if you call f again, one more fresh variable will be counted, and this variable will be completely independent of the first variable. They are completely independent variables, and it doesn't have any clue that there is someone whose value is 1. No clue at all. Therefore it will again start with 0 and make 1, and again if you call f one more time, again it will do the same thing, count equal to 0 and it will be made to 1. So it will keep on happening. Therefore every function is going to have its own local variable. So local variables are bound to fresh storage. Every time you create the function, a new local variable is created, and there is no relation between the old variable and the new variable, right? What is the disadvantage? Local variables cannot be retained once activation ends, which means whenever whenever the function call is over, this will be popped off. You cannot even find out what is the value of count here. So that is the disadvantage of this function, right, of this stack. So if you go only for pure stack, finally your local variables will not contain anything. That is the disadvantage. But then what is the advantage? Recursion is supported, right? And now coming to the heap, in heaps allocation and reallocation can be done in any order, which means when the program is running on, you could call malloc and allocate it, and then you can call free and then deallocate it, and you can do it in any order. But here, coming to stack, you cannot allocate or deallocate. Coming to static, you cannot allocate or deallocate. They are all bound by some rules. But here nothing, you are free to do anything. What is the disadvantage of this? Heap management is overhead. So why is it a disadvantage is, let us say in your process you have been allocated some memory for the heap. In your process you have been allocated some memory for heap. Now what happens is, you will create a variable now, or you will create a data structure which will take up some space, and then you will create a data structure which will take up some space, and then you create one more data structure which will take up some space. Let us say this is a program, right? And now you free up something, you free up the second data structure which is created, then it leads to forming a hole in the memory. Inside the memory there is a hole. So because of this hole, the management is going to be difficult. So how is this managed is, even we are going to see this in the memory management of operating system. In C, the technique used here, there is the first fit. So there are techniques like first fit, best fit, worst fit. We shall discuss about it after operating system, but just remember that in C we are following the first fit because it is faster. Just make a note of it. In C programming language we follow first fit. Okay. So anyways, we are going to look at it later. And now look at the summary. Summary is, activations can have, activations means this function calls and all. Activations can have one, permanent lifetime in case of static allocation, which means if you use static allocation, a variable or a function will have permanent lifetime, they will be alive forever. And second thing is nested lifetime in case of stack allocation. If you are using a stack, then they have nested lifetime. So why nested lifetime is, the reason is simple. So whenever any function is up, whenever any function is on the top of the stack, whatever variables are present, they will get the lifetime. And later, whenever this function is pushed up, or any other function is pushed up on top of it, the lifetime of these will be nested by this, will be overwritten by this. And again this one, if you push one more thing, the lifetime will be like this. So it will be like this. Initial variables for this function, this entire thing will be lifetime, and as and when you push the second one, the lifetime will decrease like this, and as and when you push the third one, the third variables will be like this, and again when you pop it off, again the lifetime will be like this. This one will be active, and when you pop it off, this one will be active. Therefore lifetime is kind of nested. So anyways, we are going to talk about this one again in principles of programming languages. So just understand that initially these three ways have been used separately, but right now we are having a hybrid, which means we are making use of all these three. The reason is, every strategy has got its own advantages and disadvantages, right? This is all about the runtime environments. I hope that you have taken the notes, and please memorize the points. There could be some theory questions asked in GATE. In GATE they didn't ask anything as of now, exactly from these points. They have touched one or two theory questions. In case if they ask you, it is very easy to answer also, right? But anyway, please make a note of it, right? Please make the note of the entire theory. Okay, fine. Let's look at the code optimization. It is the phase after intermediate code generation. If you look at all the phases, after intermediate code generation, you will see the optimization phase. The main intention of this phase is, code optimization phase is, reducing the number of lines in the program. If you have 100 lines, maybe if you could reduce it to 80 lines, that is the main intention of this. And in any program, if you take any program, a majority of the time is spent by every program. It is statistically analyzed that majority of the time which is spent in every program is actually inside the loops. So every program you take, 99% of the programs will have loops, and most of the time will be spent inside the loops, in case if it is an iterative program. Otherwise, if it is not an iterative program, then you could have had this recursive program. Anyways, a block will be there, and majority of the time will be spent on the block, and mainly that block will be iterative block in most of the programs. Therefore, reducing the number of lines in the loop will actually reduce the overall time of the program. Even if you could reduce one line inside a loop, that is actually reducing thousands of lines, or how many ever lines, the number of times the loop is going to be executed. Let us say a loop is going to be executed 1 million times, and if you have reduced only one line inside the loop, effectively you have reduced 1 million lines, isn't it? Therefore, most of the optimization is actually focused on eliminating the redundancies inside a loop or decreasing number of lines inside the loop. Outside the loop, even if you decrease one line, that is not going to be of huge help by any compiler, right? So if you look at it, optimizations are of two types. One is machine independent and other is machine dependent. Machine independent means you need not worry about what is the type of machine the compiler is working on. You can directly do it on every machine. Machine dependent means depending on the features available for a machine, we could apply these optimizations. For example, some machines will have better features, better instruction set. Some instructions will be like this. If you want to increment a variable, most of the machines, they will have 3 lines: fetch the variable, increment the value, and then store it back. And some of the architectures, they have just one instruction: increment inc that variable. With just one instruction, it is going to be done. Therefore, depending on the capacities of the machine, we could do some optimizations, and some optimizations are applied for all the machines. For example, see this. Machine independent means loop optimizations. Every program is going to have a loop, and in that loop optimizations we can do in that loop we can do some optimizations, that is loop optimizations. And there are various types of loop optimizations like chord motion or frequency reduction. I'll take example and explain you each one of them. And then loop unrolling, loop jamming, and folding or constant propagation. It is not loop optimization, it is a normal optimization which is machine independent. And redundancy elimination, strength reduction. I'll take an example and I'll explain you each of this. And coming to this machine dependent optimizations, there is the register allocation. So this register allocation is again a topic which will be discussed in CO as well. So I am going to defer this topic to CO. In computer organization, we are going to use some graph coloring techniques and register allocation, and we are going to combine these two concepts, and we are going to see how register allocation is going to work. Okay, that I am going to show you at CO, not here. And next one is use of addressing modes. So addressing modes are very specific to the architecture. It is not that a particular addressing mode is going to be present in all the computers or all the platforms. And then peephole optimizations, so redundant load and store. So better I'll take an example and explain you all this. So what you could do is you can make a note of it. I'll just read it out for you. Redundant load and store, flow of control options, and flow of control optimizations, not options. Strength reduction, use of machine code. So what I would like you to do is just copy this table, then I'll get into each one by one, and then we shall discuss about all this. Okay, please copy it. Just zoom in and copy it. You can pause the video, copy it. Okay, fine. Now let's look at the first type of optimization, which is machine independent optimization. And in this, the first type is loop optimization. So what I would like to say is, see, I'll give you a bigger picture about what we are doing, and then I'll get into the inner details. But then I would like you to take these notes. This is going to be important and useful later if you want to understand what is happening. Okay, so I'll explain you each one point by point. You please pause the video, make a note of it, and we can continue, and later I'll get into the details. Now whatever I'm going to give you is a bigger picture, how the optimization is going to work. So loop optimization. To apply loop optimization, we must first detect the loops. So what does this step mean? So if you remember, I told you that at high level language we have loops like for loop, while loop, and all this, right? So when this high level language is converted to a intermediate code, and in fact optimization works after intermediate code, which means, see, initially high level language, in high level language we have for loop, assume that, and it is very easy to identify it. Now when it is converted to intermediate code, generator is going to convert it to 3 address code, which means there will be if statements and then go to statements and all, right? So like this. Now there will be no for visible at all. Therefore after this you are going to apply code optimization. So even though in the high level language we have for loop, it is not visible at the intermediate code generator. You might say that by looking at goto, it is a for loop, but it is not always guaranteed. Remember, we have, even in switch case also we have goto statements, and even in if condition also we have goto statements. Therefore every goto need not actually mean a loop. Therefore there is no way you can directly look at the statements inside it and say that it is a loop. For that we need to analyze it. So first step is to apply optimizations. We must first detect the loops, right? So what does it mean? In order to apply the optimization, we should first detect the loops. That is the first thing that you should be doing. And now for detecting the loops, we use control flow analysis using program flow graph. So if you have to detect the loops, see, in order to apply optimization, you should first find out the loops. In order to find out the loops, we should do control flow analysis on program flow graph. And now to find the program flow graph, we need to find basic blocks, which means in order to find this, we need to find the basic blocks first. What is a basic block is? It is a collection of, read this one. A basic block is a sequence of 3 address statements where the control enters at the beginning and leaves only at the end without any halts or jumps, which means basic block is generally a sequence of 3 address code, and if you enter the basic block here, there will be no gotos or no jumps. It will directly come out from here, which means it is a continuous block of lines from which there is no other exit point. Only we enter here and exit here. That is called a basic block. So what is that you understood now? First point says that in order to apply the optimizations, we should first detect the loops. And if we have to detect the loops, you should find out control flow analysis, or you should do control flow analysis on program flow graph. And in order to do program flow, in order to find out the program flow graph, you should find out basic blocks. And now basic block is nothing but a sequence of 3 address code. So it is actually a chain reaction kind of it. So one thing needs other thing needs other. Now where did we stop? If we have to do optimization, finally we have stopped at the point where we wanted basic blocks. Now how is basic block going to help us in identifying the loops? That is the main question. So let's see with a diagram. Now how does this basic blocks help us is, given a program, let us say this is a program. Now you have to find out the basic blocks. Let us say I found out the basic blocks, and I found out that inside this program I have 4 basic blocks: B1, B2, B3, B4. I have got 4 basic blocks. Now this is called program flow graph. So now after finding this program flow graph, then I am going to do control flow analysis. Control flow analysis means how the control is entering into each block and how it is leaving to some other block. For example, if the control enters here at this point, then it has to leave here, and if it enters here, it has to leave here, and after this it could either go to this B3, or let us say there is a if condition, and using which it can either go to B4, and let us say after B4, after B3 it is again going to B2, something like this. Okay, so after finding out basic blocks and drawing the program flow graph, in this program flow graph every block is nothing but a node, and I am writing the control flow, how the control is flowing. And now in the control flow analysis, if I find out any cycle like this cycle indicates a loop. If I find out any cycle will indicate a loop. That is the concept, right? So once you find out the loops, then we can apply the loop optimizations. Okay, so where are we again? See this, in order to apply the loop optimizations, first thing is we have to detect the loops, right? So first we detect it. Why should we detect it? Because in higher level languages we have for loop and while loop, but code optimization is after intermediate code generator. By the time you reach this phase, there is nothing called while loop and for loop. They are all converted to 3 address code. Therefore, by looking at the 3 address code, you should find out whether there is a loop or not. That is called detection. So in order to detect the loops, what do you need? Control flow analysis on program flow graph. In order to construct the program flow graph, we need to find out the basic blocks. What is a basic block? it is a 3 address code sequence of 3 address line statements, and if the control enters in the beginning, it should only leave at the end. This is called a basic block. Okay, now once you find out basic blocks, now the program will look like this. The program is a collection of basic blocks, that is called program flow graph. In this, every block is a node. Then on that one, we are going to do control flow analysis, how the control is entering and how the control is leaving. So if I do that control flow analysis, assume that I got this. Then if you look into this, there is a loop, right? So every loop in the graph is actually a cycle. That is how you find is actually a loop. That is how you found out the loops, right? So everything boiled down to small point. If you have to apply the loop optimization, find the loops. In order to find the loops, now you have to find the basic blocks. Now let's see how to find the basic blocks. I think you now understand why am I talking about basic blocks. Without basic blocks, I cannot find out loops. Without loops, I cannot do optimization. Therefore, now let's see how to find out the basic blocks. Okay, fine. Now let's talk about how to find out the basic blocks. So why are we finding out basic blocks? This entire thing, you already know that. Now in order to find the basic blocks, this is the procedure. Okay, so you please take a notes of it so that it will be useful at the end. Now I'll just explain you point by point what is happening here. So in order to find out the basic block, we have to find the leaders in the program. So what our leader is, then once we find out the leaders in the program, a leader is nothing but a statement, some statement, a special statement. Now once we identify the leaders, then a basic block will start from one leader and it will go till the next leader, but not including the next leader, which means if you find out that line number 1 is a leader and line number 10 is a leader, then the lines from 1 to 9 is a basic block. That is the meaning of it, which means first we have to find the leaders in the program, then a basic block will start from one leader, which means line number 1 if it is a leader, and then it will go on till the next leader. Next leader is what? Line number 10, just for an example. Now it will go on till 10 but not including the 10 next leader. That is the meaning of it. Now how do you identify leaders in a basic block? So what is the procedure now? See this, now we are here. In order to find the optimization or apply the optimization, we have to find the loops. In order to find the loops, we have to find the program flow graph. Program flow graph is nothing but this. Now in order to find this, we have to find the basic blocks. Now entire thing has boiled down to, in order to find the basic blocks, we have to find the leaders. This is the final thing, right? Now this is the algorithm to find out the leaders, or the procedure to find out the leaders. Identifying the leaders in a basic block. First statement is always a leader. That is the first statement, which means if your program is having 100 lines, line number 100 is always a leader. And the second one is statement that is target of a conditional or unconditional statement is a leader. What is the meaning of that? If you have if go to, right, then go to 100, then that is 100 is a leader, or go to 200 is a leader. So the second statement means statement that is target of a conditional or unconditional statement, which means if you have anything like this, if some condition, then go to 200, then line number 200 is a leader, or directly unconditional means go to 300, then 300 is a leader. So whatever it is, you can directly either it is conditional or unconditional. If there is go to, then the target of the conditional or unconditional statement is always a leader. That is the meaning of it. And next one is statement that follows immediately a conditional or unconditional statement is a leader, which means after this statement, if go to, whatever is following it, let us say it is line number 10 and there is line number 11, so line number 11 is going to be a leader. Anyway, I am going to take an example and I am going to explain you everything, but just have the bigger picture in the mind. Why are we doing all this? In order to find the optimization, apply optimization, we need the loops. For finding the loops, we need PFA. For finding PFA, we need basic blocks, and for finding the basic blocks, now we need the leaders, and this is the algorithm to find out the leaders. Now I'll take a program, and in that program let's find out leaders first, and then let's find out basic blocks, and then let's do control flow analysis, using which we can find out the loops. Okay, So now I'll show you with an example everything. Now let's see an example using which I will demonstrate how to find out the leaders in a program, and from the leaders we can find out the basic blocks, and from the basic blocks we can find out the PFG, that program flow graph, and then finally we can do find out the loops. So how does this entire thing works is, everything boils down to finding out the leaders. So let us assume that this is the program. This program is finding out the factorial of x. So what is x factorial? You take the numbers from 2 to x and you multiply all of them. That is nothing but the x factorial. You need not multiply 1 anyway. That is why I am starting from 2. So the factorial function is int factorial equal to 1. Initially, if that factorial value is supposed to be 1, we are assuming that it is 1. And then for I equal to 2, I less than or equal to x, I plus plus. From 2 to x, I'm going to find I'm going to take every value and I'm going to multiply with f. Then finally I'm returning the value of the factorial, right? So here what does this, how does this program, this is the actual program in high level language which contains the for loop. Now I'm converting this program into 3 address code. After converting the program into 3 address code, you will not see any for loop. That is the problem here. So now we don't have any for loop shown, and we have to find out that in this 3 address code we have to know that there is a loop, right? So that is the problem here. Now how do we find out? First let's see how this program is converted. First step is f equal to 1. The first line is written as it is, f equal to 1, and next step is I equal to 2, that is initialization, isn't it? And now next thing is you have to compare, you have to find out this, you have to do the comparison, right? You have to test the condition. So we are testing it. If I greater than x, we are actually testing it in a reverse way, which means if this condition failed, if I greater than x, then go to 9. 9 is nothing but go to the calling function. Calling function is returning. Go to the calling function is nothing but returning. So if this condition fails, don't execute the for loop, directly go to the calling function. That is what it says. And now t1 equal to f into I. So what does it mean? We are doing this statement. This statement, when I convert it into 3 address code, then I get these two statements, right? So t1 equal to like this and like this. Even though these are redundant, later after optimization these two will be eliminated and these two will be combined. But then as of now, when I generate the 3 address code, as we have seen the STT, I'll get these 2 lines. And after evaluating this statement, we have to do the incrementation. Do you remember that how we converted a for loop into the 3 address code in one example? Same way it is being done. So after testing the condition, you are going to execute these statements, and after statements are executed, you have to you have to go to this increment or decrement loop, and after that again you should repeat the same. So I am just incrementing the value of I. So t2 equal to I plus 1, I equal to t2, which is nothing but incrementing the value of I. And after this, which means after doing this statement and incrementing it, I have to again check the condition. Where is the condition checked? At 3. Therefore go to 3. And in case everything is over, we are going to go back to the calling function. Now for this program, this is the 3 address code. Once we have 3 address code, this is the output of the intermediate code generator, isn't it? So all the phases are over, syntax analysis, semantic analysis, everything is over, and finally we are here after intermediate code generator, right? Now we are taking this intermediate code generator, and now the code optimization we have to apply. In order to apply that, we have to find out the loops. So for finding the loops, leaders, see this first statement is a leader. So what is the first statement here? 1. Therefore this statement is a leader. I am just putting the stars. Star means a leader. And next one is statement that is target of conditional or unconditional statement is a leader. So see this statement that is a target of conditional or unconditional. If some condition go to, it is nothing but conditional, right? Conditional statement, conditional. So whenever you have a conditional go to, what is it saying? Go to 9. Therefore 9 is a leader. And then go to 3. It is an unconditional statement. So 3 is a leader. So 1, 3, 9 are leaders. And next statement is statement that follows immediately a conditional or unconditional statement is again a leader. So see this statement 4 is following immediately a conditional statement, right? So actually it is a conditional or unconditional, you have to write go to, not just the statement. Conditional or unconditional go tos, right, or jumps. Now anyways, you understood the meaning, right? So now statement that is following this conditional unconditional go to, which is nothing but this is following the conditional go to, therefore it is a leader. And unconditional, this is the statement following this, it is a leader, right? And one more thing, yeah, so the statement following this one is leader. So how many leaders you got? You got totally 4 leaders. What are they? 1, 3, 4, and then statement number 9, the last statement. So we got totally four leaders using this algorithm. So after that, what is the definition of a basic block? If you remember it, the basic block starts from one leader and it goes on till the next leader without including it. See this? Basic block is nothing but a basic block will start from one leader and goes on till the next leader but not including the next leader, which means it will start from one leader. One leader is 1 from here till the next leader but not including it. Therefore this is a basic block. Let's call it basic block B1. And again next statement will start from the next leader without including the next leader. It starts from 3 without including the next leader. I am going to take it. And the next basic block starts from next leader and it will go on without including the next leader. Therefore this is the basic block. Let's call it B. This one is B2, B3, and the last one is only one statement is remaining. Therefore that is obviously one basic block, B4. Therefore how many basic blocks we got? 4 basic blocks, isn't it? So in case if you have 4 leaders, how many basic blocks do you get? 4. In case if you have n leaders, how many basic blocks you get? N. Why? Every basic block has to definitely start with a leader. Then the number of basic blocks will depend on the number of leaders. Since 4 basic leaders are there, basic blocks are supposed to be 4, right? So what are they? B1, B2, B3, B4. Now let's construct the program flow graph. So what will it contain? Basic block B1, basic block B2, basic block B3, and basic block B4, right? And now let's see how to analyze the control flow analysis, how the control is flowing. If the control enters B1, there is no other option. After B1 it has to enter B2 only. So after B1 there is no other option, we are entering B2. And now if you are at B1, then depending on the condition, if you are in B2, depending on the condition, if this condition is right, then we are going to 9, which means 9 is nothing but B4. So one option is you can go to B4, or if this condition is false. In case if this condition is false, ultimately we will enter the next block. So that is why we are going to B3, right? And now coming to B3, see this, there is no condition at all. We are directly going to third statement. Third statement is nothing but B2. Therefore this is B2. Now check this. In this control flow graph, after the analysis, we found out a cycle. So this cycle is nothing but the loop, right? So what are all these statements which are present in the loop? All these statements which will be in B2 and B3. So this B2 and B3 is nothing but a loop. In fact, this is the for loop. If you can look at it, this is nothing but the for loop. See this. For loop, I equal to 2 need not be in the loop, it is just outside. That is why it came outside. And what will be executed over and again? This condition will be checked, and then this statement will be executed. Yes, this statement will be executed, and then I will be incremented. Therefore, this statement, all of them have come into the loop. Now we are able to identify that this B2 and B3 combinedly is forming the loop, and all these statements inside the loop are this. So this is how we can identify the loops. Once we identify the loops, now we can apply the loop optimizations, right? So what did we do? In order to find out the loop optimizations, we have to find the loops. In order to find the loops, we have to find the program flow graph. In order to find the program flow graph, basic block. For basic block, leaders. So it is a very big picture. Maybe without that chain, you will not understand what I am doing and why am I doing all this. I think now it is clear, right? So now let's see how to apply the loop optimizations on the loops. Okay. Now after finding out the loops, what we want to do is loop optimizations. So loop optimization means, one thing is we want to decrease the number of lines present in a loop. That is first thing. By doing that, we could significantly reduce the number of lines totally executed. Or we want to reduce the number of loops themselves. Sometimes we want to eliminate a loop completely, or we want to decrease the number of times a loop is executed. So just understand it. Either reduce the number of lines which are present inside the loop. By doing that, we are effectively reducing the number of lines executed. First thing. Second thing is reduce the number of loops themselves. Sometimes some loop can be completely eliminated. And third thing is reduce the number of times a loop will be executing. From 1000 to 500, if you reduce it, then it is fine, like that. So we could do this, we could do this in loop optimizations. So before coming to this loop optimizations, we have already found out the loops, right? And after finding out the loops in the 3 address code, now we are going to apply this. Now see this. Even though I am showing you all the programs in high level language statements examples, but actually it is happening, it could be appropriately converted to 3 address code, and we can apply it, but that will be confusing for you to understand it. Okay, just look at the examples now. First thing is frequency reduction. Frequency reduction means moving the code from high frequency region to a low frequency region is called code motion. What is high frequency region? The region which is called many times is called high frequency region. For example, see this. See, even though I am giving you the program in high level language using while, so don't worry, we can convert this into intermediate code, that 3 address code, and then we can apply the same optimizations in 3 address code. But then explaining it is a bit difficult for me. That is why I have taken this. So I want to explain the concept, not actual procedure. The concept works like this. Initially assume that I equal to let us say 0, and I is incremented, here, right? So which means this loop is executed nearly 5000 times, and every time we are entering into it and we are trying to assign something to a in such a way that a equal to sin x by cos x. So this, if you look at this value of sin x and cos x, they are not changing, and if you look at sin x by cos x, that is also not changing. Therefore, we need not execute this sin x by cos x 5000 times. Since it is present in a high frequency region, it is getting executed this many times. So what is the better thing we could do is, we could move out this sin x by cos x outside the loop. So which means we could place it outside, and inside the loop we can place only one statement. So compute this sin x by cos x once and use that value inside a equal to t into I. So that is how this loop optimization is going to work. Simple. So what is it? The concept is, you just compute the whatever is present in the high frequency region, you just take it out, compute it once and put the result there. Therefore we are not executing this statement 5000 times. Effectively we have reduced the number of divisions that have to be performed, right? And this is called frequency reduction or code motion. Now next one is loop unrolling. Loop unrolling means we could reduce the number of times we enter into the loop, or we could reduce the number of times we do a comparison. See this. Now this code is working like this. While I is less than 10, x of I equal to 0, I plus plus. It is a very frequent code, initializing an array to all zeros, right? So what is that we are doing is, we are comparing, entering, assigning, coming out, and for every assignment we are doing one comparison, isn't it? So if there are 10 elements which have to be assigned some value 0, then we are effectively doing 10 comparisons. We could have done something better. Do one comparison, enter into the loop, and after entering, assign 2 elements to zeros, which means here what we are doing is, we are making x of 0 to 0. See, x of 0 once, x of 1, x of 2, 3, 4, 5, 6, 7, 8, 9. Let us say we have all these elements, and now we want to assign all these elements to 0. In this one, we are actually trying to assign one by one, which means we are taking each number and then we are doing it, right? But what we could have done is, instead of taking each number one by one, we could have taken 2 numbers together and we could have assigned both the numbers 0 at once, which means once we enter the while loop, instead of doing one number each time, 1, 2, 3, 4, 5, 6, 7, 8, 9. We could have entered the loop, and once we enter, we could make two values to be zeros, and next time when you enter, make two values to be zeros, next time when you enter, make two values, next time when you enter, make two values, which means I'm effectively taking a window of 2. But see that whenever you are taking such kind of window, it should not by mistake include the next numbers which you are not included in the original code, which means you cannot take 3. So if you try to make 3 elements to be zeros by checking this condition, what happens is you might start out with this. See, here 2 is working fine, but then what happens if you try to do the same thing with 3 at a time is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then you take the 3 first, and then again next 3, and then again next 3, and next time you will by mistake include 10 and 11 also. They are not in the program, therefore you have to be careful when you are doing this. So don't take any random number, which means here 2 works I think, and then 4 doesn't work, and then 5 works. So if it is from 0 to 9, 2 works and then 5 works, which means enter the loop once, and either you do one element 0 or 2 elements as 0 like this or this, or 5 elements as 0, but then don't go for beyond any other number, because that will not that will sometimes get into picture some other numbers also, right? So just be careful there. And next one is loop jamming. Loop jamming is here we have, what has happened by loop unrolling is we have effectively reduced the number of comparisons, isn't it? So how many times this while loop has been executed is 10 times initially, but because of this only 5 times. So in this loop unrolling, we are reducing the number of times a loop is getting executed. Now let's look at loop jamming. Loop jamming is combining two loops together or decreasing the number of loops, that is loop jamming. Now example is, see this, for example, if I equal to 1 to 10 I plus plus, j equal to 0 to 10 j plus plus, and this loop is simply making all the elements of two-dimensional array x as 0, and the next loop is simply making all the diagonal elements to be 0. So what we could have done is we could have included this statement here itself, that is nothing but loop jamming. Eliminate this loop completely and join these statements into some other loop without the changing of meaning. So this is how it is. So I'm taking this statement and I'm putting it in the first loop itself, right? So using this, number of loops can be eliminated. Here number of statements are reduced, number of operations, number of times a particular operation is done is reduced, and here number of times a while loop is executed is reduced, and here number of loops are reduced. So anyway, these are all called loop optimizations, which have to be performed only after finding out the loops. Even though I have taken the high level language as example, it is all happening at 3 address code. So I told you how to find out the loop in a 3 address code. This is all about loop optimizations. Some other optimizations which are machine independent and which doesn't depend on loops are, one is folding. Folding is if I have an expression like this, see 2 plus 3 is there, it can be evaluated at the compile time. So either you do 2 plus 3 equal to 5 at the compile time or leave it to the runtime, then it is going to be same. Therefore compiler can do the addition and put the number there, right? So replacing an expression that can be computed at compile time by its values, which means whenever you want to, whenever you have some expression which you could compute it at the compile time itself, don't leave it till the runtime. At runtime it is going to be a burden. The reason is, who knows, this statement might go and fall in a loop, then it is going to be executed many times. Therefore whenever you find any such statement, then you execute it at the compile time. Next one is redundancy elimination. So redundancy elimination is you might have heard of, you must be remembering that topic, DAG, directed acyclic graph. So in which I told you that if an expression is already evaluated and next time when you call for the same expression, then DAG is going to return you the this particular pointer which is the expression which has already been evaluated. For example, if you have already evaluated the expression b plus 3, b plus c, which is a, then you need not actually evaluate it second time. So you can put it there. If it is already evaluated, DAG will say that this expression is already evaluated, and therefore next time when you try to add this b plus c, you can get it. And in fact this 2 plus 3 will also be folded to 5 by using folding and then this. So redundancy elimination is, if expression is already evaluated, we are not going to evaluate it second time. And next one is strength reduction. Strength reduction is replacing a costly operation by a cheaper one. So costly operations means generally multiplication and divisions are costly. So if you take such a statement, a equal to a into 2, in place of this multiplication, here you could have done left shift. Left shift is cheaper. So because shifting is done on registers, it is just very fast operation compared to the multiplier. Therefore multiplying with 2 a number is nothing but left shifting the number by 1. So multiplying by 2 is easy. Left shifting is easy. And next one is algebraic simplification. Algebraic simplification means sometimes you have some statements like this: a equal to a plus 0, x equal to x into 1. Such statements are trivial. You can eliminate such statements. That is nothing but algebraic simplification. So this is all about the optimizations which are machine independent. One is loop optimizations, which we have seen, and then the remaining are this, right? Now let's see machine dependent optimizations. These optimizations are done depending on the machines, right? So it is not possible that we can do this optimization on all the machines, because depending on the architecture, the platform, we have some facilities already provided by that platform. So depending on that, we are going to do this. Okay. So first one is register allocation, local allocation and global allocation. So register allocation, that depends on how many registers you have, and depending accordingly the number of registers, we can do the allocation. So it is purely dependent on the architecture. If you have 4 registers, then lot of moving in and moving out has to be done, because we cannot save a variable in 4 registers. We can only save only 4 variables in the 4 registers. Therefore this one is purely dependent on the machine. Anyways, we are going to see this register allocation in CO topic, and we need the graph coloring algorithm also. Okay. And next one is use of addressing modes. So addressing modes also I'll discuss in CO. And next one is peephole optimization, redundant load and store elimination, which means sometimes what we do is we load something and immediately we store it back, right? That is simply a redundant thing. Then what we do is in such cases what we do is, so I'll just take an example and explain you. Let us say this expression x equal to y plus z, this statement is generating 3 codes, 3 statements. First thing is move y into r0 and then add z to r0, which means it is nothing but y plus z is added, and then move r0 to z, which is nothing but y plus z is now moved to x. R0 to x means y plus z is now moved to x, right? And if you look at these 3 statements, and if I have these 2 statements, a equal to b plus c, d equal to a plus c. Now for each statement, if I am writing 3 statements like this independently, individually, then what does this mean? I am moving b into r0, and then I am adding c to r0, and finally the result b plus c is in r0, and I am moving the result b plus c into a, right? And similarly I am doing the same thing for this one. I am moving a to r0, and then I am adding e to r0. Now the result r0 contains a plus e. Now I am going to move that r0 into d, which means a plus e is assigned to d. Now if they are independently executed, you don't see anything, but when I combine them, then there is some redundancy here. This is a load store problem, isn't it? What we are doing is we are trying to store it back, which means the value into a, and again we are trying to load it. So loading and storing is there, so this one has to be eliminated, right? This is optimization. Now look at this flow of control optimization, which means sometimes the control flow will be in such a way that it is redundant. For example, jumps on jumps. See this? Now L1 is saying that jump to L2. Now if you jump to L2, L2 is saying that jump to L3. Now if you go to L3, it is saying that jump to L4. So unnecessarily you are jumping these many times. Actually this should have been written as simply jump to L4. That would have been sufficient, which means directly going to L4 is what is needed, but you are going these many times. And next one is eliminate dead code. So hash define x as 0. So if I define x as 0, and if dead code is eliminated this way, see this, already if x is 0, now if x, then some code is there. This entire code is called dead code, because this 0 is never going to become 1, because it is already a constant. This x is a constant, nowhere we are going to change the program. Therefore, instead of compiling this code, you could have easily left it out. So compiler need not compile it and generate the code unnecessarily, because that will never get executed, right? And now use of machine idioms. Machine idioms means, now let us assume that we want to increment the value of I by 1. Then what we generally do is, we load the value of I into R0 and then add 1 to R0 and then again store that value back into I. So these three instructions are generally carried out in most of the processors. But if your processor is rich in the sense, if you have a rich instruction set, if you have special instructions like increment I, then you need not go with these three instructions. Instead of that, you could have gone with only one instruction. So these are all the optimizations which you could do on machine. I mean, these are all depending on the machine. Okay.
Hi, let's look at the liveness analysis of a variable. So the main purpose of doing this liveness analysis is, one is for register allocation, okay, and the second is dead code elimination. Register allocation and dead code elimination. Okay, now what do I mean by register allocation is, let us assume that we have a program. Okay, let us say we have many statements in a program. See, these are not the basic blocks. We'll do the basic block analysis also later. For now, I'm thinking that these are just the statements. Okay, statements in a program, right? And say we are executing this particular statement, this one, right? And this particular statement is assume that this particular statement is saying that x equal to y plus 1. Okay, so before you execute this particular statement, the value of the variable y has to be fetched from the memory into the registers. Whenever we execute a program, we try to store the variables in the registers, both for reading purpose as well as writing purpose. Okay, now we have to get the variable y from the memory and store it in the registers. Okay, there lies the problem. In any computer, the number of registers are generally limited, but in a program, the number of variables can be any number. So if you compare the number of variables that are used in a program to the number of registers that are available in a computer, you can see that the number of registers are very less compared to the number of variables available in the program. So we can't put all the variables in the registers. I'll just take an example and I'll show you. Assume that we have 4 registers, R1, R2, R3, R4. Okay, and by the time we reach this particular statement in the program, let us assume that already R1 is allotted to variable A, and R2 is allotted to variable B, R3 is allotted to variable C, and R4 is allotted to variable D. Okay, and now suddenly we want a variable y, and the variable y is in the memory and it has to be now kept in the register. Okay, now the problem is, which of these registers are you going to spill? So spill means take the variable and store it back in the register, and then you are going to get the variable y from the memory into the register, right? So how are you going to decide which register is going to be allotted to y? Okay, and it is very important, because depending on your decision, in future more number of reads and writes will happen. Now here liveness analysis is going to be helpful. Now let us say we have done the liveness analysis and we found out that variable A, B and C are live at this point. Try to observe it carefully. It is somewhat a difficult concept. I'll try to simplify as much as possible, but you have to be very careful here. Okay, so I'm saying that at this point A, B and C are found to be alive or live. How did I find it? By doing liveness analysis. Now what does this mean is that A, B and C may be used in the statement, or somewhere in future these values may be required. That is the concept of liveness of a variable. Again, so if I say A, B and C are live at this point, it means that A, B and C may be required while executing this particular statement, or it may be required in future somewhere in the program. Got it? In that case, what we should do is we should try to preserve this. We should try to keep them in the registers as long as possible. Now A, B and C are already allotted registers R1, R2 and R3, and D, we found out that D is not in the live list, which means D is dead. Therefore we take the that particular dead variable and we spill it, which means we will write it back to the register, to the memory, if it is required at a future point. Otherwise, if it is not required at all in the future, that is what the live is saying, right? It is saying that it is not at all required in the future. In that case, you need not save the value in the memory also. You can just let it go. What does it mean? The value of D is computed, but it is not required anywhere in the program. Therefore, you can simply overwrite on the register without saving the value to the memory. Got it? In that case, we are going to allot register R4 to Y. Then for this particular statement, the code generated by the compiler will be move Y to R4 and then add 1 to Y and then store that particular value to X. That is how the code will be generated. Got it? So once the registers are decided, then the code will be generated depending on the register which is allotted, right? This is one case. Now luckily we found out that one variable is dead, and that is how we are able to use that variable, that particular register, right? Let us say if all the variables A, B, C and D are live, and also Y is live because Y is needed here. Okay, that part we will see later. For now, assume that Y is required. Then what we should do is see all the variables are required in future, and we definitely have to allot one variable, one register to Y right now, because this is the current need. Okay, it is on demand. Okay, now in that case, what happens is we randomly pick one of these. Randomly means there can be any algorithm for picking. You randomly pick one of these registers and we do spilling. Spilling means, let us say this register is now allotted to Y. Then we have to save A value to the memory, let us say main memory or RAM, whatever, and Y value has to be stored here. A value is thrown out and Y is being fetched. This is called as spilling. Okay, so we have thrown out the A and we got Y back, and Y will be here. Got it? And now for now this statement will be executed, but we have seen that definitely A is live, which means in future it will definitely be asked somewhere. So which means, let us say something is like this in future. Now when we reach here, this statement, again at this statement we do live variable analysis, which means at every statement we do live variable analysis, and then we will find out what are all the variables that are live at that point, and then we will see which variable to allot to that particular variable, which register to allot to that particular variable. Now I assume that at this point Y, B, C, D are there in the registers, and Y, B, C are found to be alive at this point. Now what does it mean? We need A, we need to allot a register to A, and D is dead, right? At that point you can overwrite D with Y. Got it? So that is why live variable analysis is helpful in register allocation. Got it? So liveness of a variable. So now if you observe it, when is a variable live is at a statement, let us say n, a variable is live if it is used in that particular statement, or if it is used somewhere down the lane and there are no definitions for it during that line. Okay, I'll just give you the definition and again we come back to the example. Okay, so in this diagram, in this example, you might have understood 50% of it. I'll again come back with more examples. There you will understand the remaining things. Okay, there are a lot of things to be discussed. Here it is just an overview. Okay, now let's see the definition of liveness of a variable, and then we'll get back with the examples and we'll analyze, then you'll understand it. Okay, fine. Now let's look at the formal definition of the liveness of a variable. We say that a variable v is live at a statement n if there exists a path. Okay, so what is a path? If you look at the control flow graph, generally the flow is nothing but the path. Okay, if there exists a path in the control flow graph from this statement to a statement m such that v is used in m, and for each line k from n to m it is not defined. Okay, so I'll explain it with an example. Okay, so what it means is, if you have a variable, if you are standing at a line n, okay, at that particular line n, a variable is said to be live if from that particular line, if you are able to reach a line, another line where it is used, and in between there should not be any definitions. Okay, I'll tell you that with an example. Okay, next thing is, or a variable is live at a statement if it is used at that statement. Okay, let's take an example and let's see that. Okay, what that definitions actually mean. So assume that we have few lines in a program like this. They're all lines. Okay, I'll write some variables inside these lines and assume that the control flow is like this. After this particular statement, this one is executed, and then this one, and then this one, and then this one. Okay, now we are standing at this point. Okay, at this point, whatever variables are used, they are all live. For example, if you have a equal to b plus c, got it, then both b and c are used here, their values are used, so b comma c are live. Got it? Now in this program there can be any number of variables. Got it? Assume that in this program all the variables we have are a, b, c, d, e, right? So a, b and c are live at this point in this statement because they are used. Now what about a? Is it live? Whenever there is a definition and if there is no use in this statement, it is dead. Okay, so a is dead here. Okay, this is the only exception that you might have to remember in the entire analysis. Wherever you see a definition, that particular variable is dead. Why? Because whatever value a was having earlier is not useful now from this point. That is why it is dead, which means the earlier value of a is not useful in this statement, therefore a is dead. Now even though you have only a, b and c, only these three variables in this statement, you should not do only 3 variable analysis. Okay, you should do all the variable analysis. I am not able to make it clear. What I mean to say is, at every point you have to do the liveness analysis for all the variables, not just for the variables which are present in that particular line. Okay, some people think that if a variable is not defined at that point, why are we analyzing that particular variable? We should be only sticking to that particular variable. No, because the other variables may be defined somewhere else in the program, and that value may be used somewhere else in the program, and in this flow you might have to save these variables. You might have to save, okay, these values, keeping the future in mind. In this line these may be useless, but if they are used somewhere else down the lane, then the registers allotted should be kept intact. What I mean to say is, at this point D and E are not used. Okay, assume that at some other point a line is like this, D plus 1 is like this. Okay, now that first definition says that even though D is not used here, there is a path from this statement to this statement where it is used, and let us say D is not defined here or here, which means we don't have any statements like this, D equal to. Okay, in that case, since D is being used, right, we can say that D is also live. Are you getting this? Now let us assume that some line is there, like E equal to is here. Okay, or E is not used anywhere from here till here, then in that case E is dead. Got it? So to simplify it, whenever a particular variable is used in a statement, that particular variable is live. What do I mean by use? It should be on the right hand side, not on the left hand side. Okay, if variables are on the right hand side, we say they are used. If the variable is in the left hand side, we say it is defined. Okay, so from this statement we can directly say B and C are live, and from this statement we can directly say that D is live here. Okay, D is live at this point. It is also live at this point. It is also live at this point. It is also live at this point. Therefore all these 4 points put together is life of D. Getting this? So let us assume that the control flow is such a way that from here there may be a if statement or some other statement which is taking the control flow to here. Okay, and let us say from somewhere this is also being used. Okay, now if you observe it, D is being used, but at this point, from this point we can't reach D, therefore D is dead. We can't say that D is live there. Are you getting it? So there should be a use somewhere in the program, and we should be reaching that particular point. Okay, so let us say this is like this. There should be use somewhere in the program, and we should be able to reach from this statement to that statement, and also on the way there should not be definitions for D. Let us say a statement is like this, D equal to, then what happens? Now from this statement, before we reach the use, it is again defined. Therefore this particular new value will be used here, and old value whatever is available here will not be used there. So D is dead. Okay, so blindly remember it as a rule, whenever there is a definition, it is going to kill the variable. Okay, the variable will be dead there, right? See, now D is dead here at this point, D is dead here, and D is dead here, because even if you have a definition, then we consider it as dead. Got it? And again D is live here. At this point D is live, right? So this is how you should analyze the liveness of a variable. But there is a problem here. Now whatever examples I have taken so far are all programs, and we are doing liveness analysis at every statement in the program, right? And therefore we are able to say at a particular statement whether a variable is live or dead. But this kind of analysis will not be done in the compilers. Okay? Why? Because in a compiler, if you have to analyze the liveness at every statement, it is going to take hell a lot of time. Then what will compiler do is, it is going to divide the entire program into basic blocks. Okay? Basic blocks. Let us say basic block number 1, right? And then basic block number 2. And then basic block number 3, right? And it is going to, compiler is going to analyze, before entering this basic block, what are all the variables that are live, and after leaving the basic block, what are all the variables that are live. And it does not care about exactly what are all the variables that are live inside the block. Okay, so this is why it is confusing. The reason is, for theoretical explanation purpose, we are going to use a program and we are going to analyze line by line. Therefore, you follow this method whenever the question is asked in GATE by giving the lines in the program. Got it? But in a compiler, it can't do line by line analysis because there might be millions of lines, and so it will do block by block analysis, where it will compute before this block what are all the variables that are live. That is also called as live in. Okay? And it will also compute after the basic block what are all the variables that are live. So this is also called as live out. Okay? So in GATE, they might give you questions like this, and they might ask you which variable is live at this statement. Got it? And you can directly do it. We'll solve some examples. You will be very confident. You will be very comfortable in this method. Okay? And the second kind of questions that might come is, they might give you basic blocks, and in a basic block they can't ask you a question like what are all the variables that are live inside this particular basic block. They can't ask you that, because in a basic block itself, for few lines a variable may be live, and for few lines a variable may be dead. It can both be live as well as dead in the same basic block, right? That is why they will ask you what are all the variables that are live coming into the basic block. What are the variables that are live going out of the basic block, right? And what will compiler do is, it will compute all this, and before executing the basic block, it will see what are all the variables required, and it will try to allot the registers to all those variables. Got it? So this kind of questions, you need not have any algorithm or anything, you can directly answer. For this kind of questions, we have to follow an algorithm which is used in compilers, and then you have to compute in and out. So that is a small algorithm. It is not very difficult. If you practice well, you will be able to answer these questions also in 2 to 3 minutes. Okay? So I don't think that such kind of questions will be asked in GATE, but I don't want to take any chance. So what I'll do is, I'll try to explain you the algorithm which is being used in this method, and then I'll tell you how to compute in and out using a table, and we'll solve 1 or 2 examples on that, few examples, then you will be comfortable with this. Okay? And now we'll first stick to this particular program, because most probably this kind of questions will be asked, okay, where every line is taken as a basic block, which means a basic block may contain only one line. That is what I mean to say, okay. So in this you need not use any algorithm, you can use the definitions and you can directly answer the questions, okay. Fine, now let's see some examples of solving the question where each basic block is going to contain only one line, and in this question we'll be able to find out what are all the variables that are live at a line, at a statement. But here you cannot say what are all the variables live at a basic block, because in the same basic block there can be lines, and because of those many lines a variable may be live and dead and live and dead, and it might happen many times, okay. So let's see some examples on this, okay. Hi, let's see the algorithm here. So what algorithm is mainly for is, if there is a basic block, see, we are not going to do the analysis for every line about the liveness of a variable. Instead we are going to do, V means compiler. Compiler will not do analysis at every line because it is going to be very time consuming thing, okay, and compiler needs to be fast, and for that reason compilers do analysis on the basic block, okay. So now we are going to discuss an algorithm which is going to say, let us say this is a basic block. Now the algorithm, the purpose of the algorithm is to find out what are all the variables that are live before the basic block, okay, and we represent it using in, and some people also call it as live in, which means what are all the variables before the basic block, okay. And then what are all the variables that are live after the basic block, we call it out, and some people call it live out also, okay. So these are the two sets. So what is in and out? Basically set of variables, right. So ultimately the purpose of the algorithm is to find out inset and outset of variables, okay. Let us say if the inset is a comma b, if we compute it by using the algorithm, I mean whatever I am going to discuss, and let us say outset is c comma d, okay, just an example. They can be same also, they can be different, okay, or there can be intersections, anything is possible here. It means that a and b are alive before the basic block, and it means that C and D are alive after the basic block. Now what will compiler use in general is inset. Outset is not of any use, we compute it, because whatever is out here is going to be in for the next basic block, that is why we compute out also. But compiler will generally use this information in of a basic block. Why? Because it says that before this basic block A and B are alive, therefore they might be used in the basic block, and so try to save them in the registers if possible. So in the register allocation, these can be useful, okay. So that is the main purpose of this algorithm. Now before going to algorithm, we have to use, the entire algorithm is based on basically two things. One is def of the basic block, which means defined, okay, and then use of the basic block, which means used, okay. So what does def of a basic block mean is, so these two are going to be inputs for the algorithm, okay. Algorithm is going to take these two, definitions and use, and it is going to compute in and out, okay. So these two are basically the building blocks on top of which the algorithm is going to run. Now what is def of B is, def of B is nothing but the set of variables that are defined inside B. That is the meaning of it simply. So assume that we have a basic block like this, P equal to R plus S, R equal to P plus Q, and then let us say Q equal to A plus B, something like this, okay. Now In this basic block, let us assume that this basic block is basic block number 1. Okay. Now, what is def of basic block 1? It is nothing but set of all variables which are defined in the basic block. Now you can clearly see that P, R and Q are defined inside the basic block, right? Therefore, def of basic block 1 is nothing but P, R, Q. That is how you do it. Okay. So for every basic block, we are going to find out what is the def and what is the use. You understood the def, right? So in def there is no complications. So directly when you see any variable on the left hand side, then you can take it into def. There is no confusion at all in this. But in use there is a little confusion. You have to be very careful in this definition. Okay. So use of a basic block is nothing but set of variables whose values may be used in B prior to any definition of the variable. Okay. So what it is saying is, if you see a variable to the right hand side of a expression, you can say that it is used, but then you are not going to put it in the use set if it is defined before its use. Okay, you might not understand by this. I'll take an example and I'll explain you. Okay. Now assume that we have a basic block like this. P equal to Q plus R, Q equal to S plus T, and let's say T equal to P plus Q. Okay. Now, in general, if you directly go by the definition that whichever variables are used are going to be in the use of the basic block, then what will you do normally, right? Normally you will say that Q is used on the right hand side. Therefore, use of this particular basic block, let us say basic block number 1, is going to be Q because it is on the right hand side, R because it is on the right hand side, S right hand side, T right hand side, and you will also include P. Okay. But if you see the definition of use of a basic block, it says that, see, use of a basic block is nothing but set of all variables whose values may be used in B prior to any definition. That is the important thing. Okay. Prior to any definition of the variable. What does it mean? Now if you observe it, P is definitely used, right? But it is not used prior to the definition of P, which means after the definition of P you are using P. Therefore it cannot be included. Even if common sense, by common sense if you think about it, if a variable P is defined here and if a variable P is used here, it means that this P value is nothing but whatever this P value is, right? And so whatever the value of this particular P is before the basic block is not used. Therefore you should not say P is live before it. Are you getting this? See, what I am trying to say is, even though P is used here, it is defined in the basic block before its usage. Therefore before the basic block, even though it is live, this is going to kill that particular P. Got it? So that is why P has to be removed. Just be careful with that. Okay. Got it? Now coming to Q, in this basic block there is no definition of Q before its use, but there is a definition of Q after its use. That is why it is still in the use. Coming to R, see, again R is used and there is no definition of R before it. That is why you are going to use it. And coming to S, there is no definition of S before it, right? That is why S is also in the use. And the same thing with T. Even though T definition is there, T is defined after the uses of T. Therefore, whatever the value of T is outside the basic block, that will be used here. That is why it is included. Got it? Now, let's assume that here we have a definition like this. something like t equal to a plus b. Then what happens? As t is defined here and t is used here, the definition is before the usage, therefore should not be included in the use, so t will be removed. Can a and b be in the use? Yes, because they are not defined. So this is the only thing that you have to remember in this algorithm, and the rest of the algorithm is straightforward. It is very simple, you will understand it. Okay, so again let me recap it. So first thing is, definition of a basic block is nothing but set of all variables which are defined in the basic block, which means if the variables are in the left side, then you are directly going to use them. And use of a basic block is nothing but set of all variables which are used prior to any definition. That is what you have to remember. Okay, so in exam, if they give you single lines in basic block, and if they are asking you about in and out, then you need not worry about it. If there is only one line, then what happens? It will either be used or it will either be defined. Okay, only thing that you have to be careful is with this statement. Let us say this statement is like this: t equal to a plus b, right? So if they are giving, if they are saying that in every basic block I want to have only one line, it is straightforward. Use is nothing but whatever is on the right hand side, and defined is nothing but whatever is on the left hand side, right? But you might have to be careful with this statement: t equal to t plus s, something like this, right? Now what do you say about it? T is used as well as t is defined. Which one is happening prior? In order to assign a value to t, the t value is used first. So how will compiler look at it is, first it will compute t plus s, therefore t is used before the definition. That is why t and s will come in the use set and t will come in the definition. Okay, so mostly I am expecting that mostly such lines will not be given. Okay, and also I am expecting that basic block containing only single lines will be given and not many lines. Okay, but then we are discussing the algorithm keeping in mind that even if there are many lines in a basic block, you should be able to do that. Okay, now let's look at the algorithm here. Right, so algorithm assumes that in of exit is phi. What does that mean? What is exit is, even though you don't write any exit in a program, let us say you have a program like this. Okay, at the end of the program, the last block is assumed to be exit. This is how. And if it is simply exit, you don't need any variables, right? And there are no variables used or defined or going anywhere. Therefore the first step is in of exit is phi, which means we assume that the variables which are live before the exit block is phi. That is the meaning of it. Okay, why? Because this is the basic step. Based on this we are going to do the analysis, and also while analyzing performing this algorithm, while doing the analysis, we do the analysis backward, because base condition is here. You cannot start the analysis from the first block, because we don't have any information to work with. But you can start your algorithm from the last block, because we have something to work with. On top of this we keep on building. Got it? So this algorithm is going to take, for every basic block you are supposed to find out initially what is the use and what is the definition. Use, definition, use, definition. Okay, now after computing this, using these values, in and out will be computed. Now what is the step is, what are the steps is, first we know this is a simple step. Okay, and the second step is, for each block other than exit, in of b equal to 5, which means initially we don't know anything about in or out, so both in and out will be 5. From there we start building. Now while changes to in occur, so what it means is we are going to build the solution iteratively, and how many times should you iterate, that depends on where the data stabilizes. Okay, stabilizes means, let us say in iteration 10 you got some values, and in iteration 11 also if you get the same values you are going to stop. Got it? That is the meaning of this line. While changes to any in occur, which means as long as data is changing, data means in and out, in fact you can only focus on in. As long as this in is changing, you are going to do these steps, right? What are these steps? For each basic block b other than exit, so exit you need not analyze, other than exit you are going to do this. Out of a basic block is nothing but union of all the ins of the successors. Okay, simple step, just try to understand this. Here what it is trying to say is, let us say we have basic blocks like this. Okay, basic block 1 2 3 4. Let us say the control flow is like this. Okay, now it is saying that out of a basic block is nothing but union of all the ins of the successors. For example, if you look at this particular basic block 2, out of this 2, which 2 will be union of in of 3 and in of 4. It is logical, right? Whatever values are here are going to be here. Got it? Therefore, if a node is having 2 successors, out of that particular node is nothing but union of in of all the successors, right? For example, out of 1 is nothing but in of 2. That is the meaning of it. Okay, why simply in of 2? Because there is only one successor, right? When you have 2 successors you have to use union. Got it? Fine. And then in of a basic block is equal to use of the basic block union out of a basic block minus def. So what it means is, if you have a basic block, then what are the variables that are alive before the basic block is whatever are the variables that are used in the basic block, as well as whatever are the variables that are alive after the basic block minus whatever are the variables that are defined here, right? So if you have, you can just use your common sense. What it means is, what are the variables that are alive here is nothing but whatever are the variables that are used in this, definitely they are alive, right? And whatever are the variables that are alive after it minus whatever are the variables that are defined in it. So why we are doing this minus is because we want to kill those variables. Why? Because they are defined. Once we come across a definition, that particular variable is going to be killed. That is why it is used, right? So overall, what you should remember is about the use, how to find out use of a basic block. And after that, you have to just remember these 2 lines. The summary in crisp is, if you have to run this algorithm on a program, on a control flow graph, just these 2, you have to remember these 2, out and in. If you remember these 2 equations, everything will be done. So you might not understand this algorithm, I am very sure. Okay, if you understood it, fine. If you have not understood this, with an example you will be able to understand it. Okay, we will do few examples, then you will be able to understand everything. Okay, so just remember this part, what is use. Okay, and you need not by heart the algorithm. No one is going to ask you algorithm in the exam. They will just give you a question and you have to answer it based on the algorithm. Okay, just remember those 2 lines, out and in, and then we are going to do analysis based on that. Okay, let's take an example, you'll understand it better.